Hello, I'm Professor Steven Sekula, and I'd like to welcome you to Modern Physics at SMU. Modern Physics is the first course past the two-semester introductory sequence, where we begin to get closer to the physical principles that are at play in the modern technological and scientific world. Now, like all good sciences, physics builds on the past discoveries that have driven the field forward to continue to move through the frontier of human knowledge. And modern physics is going to challenge you to step beyond the comfortable confines of introductory physics and into the modern view of the universe, particularly space, time, energy, and matter, which are the four subjects at the heart of the science known as physics. Now, introductory physics tends to leave off at the end of electricity and magnetism, and that period coincides with the end of the 19th century, the late 1800s, which was a feverish time of experimentation. The foundations of space and time had been laid in the centuries before by people like Isaac Newton. And the laws of electricity and magnetism, which were relatively the new kids on the block as regards scientific law, had been established firmly in the mid-1800s. It was believed at the time that for the most part, everything that needed to be known about the universe had been established. And all that was really left was to sort out some lingering puzzles that hadn't quite yet been fit into the framework of Newton's mechanics and the laws of electricity and magnetism. Now, one of those phenomena is light. It's fairly straightforward to make a light source in the modern world. All we have to do, for instance, is take a sealed tube filled with gas, for instance, and expose it to a strong electric field, a large electric potential. And we can coax it into emitting light. Now, light is, of course, all around us. It's what's literally illuminating the scene here. But what light was only thinly established by the end of the 1800s. We'll look at the foundations of light in electricity and magnetism and mechanics in this video. But one of the puzzles that was left over at the end of the 19th century was why certain elements emitted certain kinds of light, but not others. So for instance, this sealed tube here is containing hydrogen gas. And you'll notice that it gives off a fairly strong reddish color. On the other hand, if I place it with another tube of gas, this one of mercury vapor, mercury being a metal, the only elemental metal that's liquid at room temperature, in this case sealed as a vapor in the tube, you'll notice that in this case we get a very strong blue light from this particular element. If you study the fingerprints of these light emissions very closely, you'll observe that they have strong colors in some places, but not in others, in what is known as their atomic spectrum. Why was that? The mystery of atomic spectra would only be fully understood in the early part of the 20th century, with the advent of what we now call modern physics, specifically quantum physics. Now, another interesting phenomenon that had been observed in the 1800s, but which was not fully understood, had to do with electric currents. So what I'm going to do here is using the triboelectric effect, using friction to build up an electric charge on a piece of plastic, and then placing that plastic in contact with a conductor so that it can soak up that excess charge. You'll see that I've now caused a net electric charge to sit on this mylar material attached to this aluminum soda can. Now, nothing dramatic here so far. The charges can freely move on the conductor, and in this case they don't like to be near each other because they're electrons and they all have the same electric charge, and so they rush as far apart as they can get while remaining on the conductor. So they're trapped on this conductor, they can't escape, but they've done everything in their power to get away from each other, and in the process they've exerted an electric force that mechanically causes the mylar to spread out in space. Now, while I've been talking, the light in this room, which comes from something like a dozen light fixtures in the ceiling, has been blasting this metal. And yet, while there's a breeze in the room that moves the mylar sheets around, nothing's really draining the charge off of this. We don't see these sheets appreciably falling down. So we have many watts of natural light coming in from light sources here, nothing happens. But it was observed in the 1800s that if you expose certain metals to certain colors of light, or even colors of light that are beyond human perception, like ultraviolet, they'll begin to allow an electric current to flow. This is the so-called photoelectric effect. And it was unexplainable by Newton's mechanics and the laws of electricity and magnetism as they were established in the 1800s. So all I have to do, according to the photoelectric effect idea, is take something that emits ultraviolet radiation, in this case a sanitizing wand for a sink or a counter or a toilet or something like that. Just go ahead and switch it on, and it will begin to emit ultraviolet C radiation, or light, down toward the surface of the table. And if I move it over the aluminum can, it will begin to almost instantaneously drain the electric charge off the mylar. And if I sit here long enough, it will eventually pull almost all of that electric charge off the mylar, leaving it hanging back down in a more vertical position. This is 4 watts of UV light, compared with tens of watts of natural light coming from the light fixtures in the ceiling. Why? Why does the color of the light matter to this effect more than the intensity of the light? That was a mystery left over at the end of the 1800s. Now, another mystery, which would ultimately combine to lead to a firmer understanding of matter, energy, space, and time, had to do with heat energy. Now, heat energy is something that we will explore in this class. If I light this burner on fire so that it emits a nice blue flame, I can take a bimetallic strip. This is a strip of 2 metals bonded together back to back, and I can place it in the flame. Now, we'll take a look at some of mechanically what's going on here later in the course when we establish the foundations of heat energy in about a month or so. But if I leave this metal in the flame, not only because does it begin to bend, but after enough time it will also begin to glow on its own. Originally it had a silvery color at room temperature, but as I continue to expose it to the source of heat energy, this open flame, and heat energy is transferred into the metal, eventually the metal begins to glow of its own accord with its own light. Now, this wasn't such a mystery to physicists and chemists of the 1800s, but what was a mystery had to do with the degree of absorption of energy and the degree of re-emission of energy at other frequencies and wavelengths, other kinds of light that you can see with your eye. And the exact relationship between heat energy and temperature and the kinds of radiation that should be emitted from a heated body proved a real challenge to mechanics, electricity and magnetism, and the laws of heat energy transfer, or thermodynamics, that were also established in the 1800s. So modern physics is your gateway into a world that's more consistent with the kind of world we live in today. Not the world of the 17 and 1800s, but the world of the 1900s, the 20th century, and now the 21st century. The foundations that we will establish in this course will lay the groundwork for a variety of important technological revolutions. Non-invasive imaging of the human body, the harnessing of the energy at the heart of every atom, the construction of semiconductor devices which revolutionized our ability to do computations quickly and efficiently, and a host of other advancements whose roots were all laid down in a revolutionary period in the transition between the 1800s and the 1900s that led into the era of modern physics. Welcome to this course. For the rest of the video, we'll do a foundations review of introductory physics to refresh your memory about the most salient things from the past 2 semesters of material, and then we'll move on to the foundations of modern physics. In this lecture, we'll re-explore the foundations of introductory physics, the basic concepts that should have been communicated to you in the first 2 semesters of introductory physics. Physics builds on the past. Like all sciences, the discoveries of an earlier era influence our understanding
of new discoveries and how to adapt our mathematical descriptions of nature in order to describe what we know from the past, but include new observations that don't quite fit into the original framework that we had developed. The big picture that I want you to take away from this Foundations lecture can be broken into 4 large parts. First of all, a foundation of the physics that you have learned so far is Newton's mechanics. These are laws of motion. They link forces that act on objects to changes in the states of motion of those objects. And a state of motion is characterized by the velocity of an object. The laws of mechanics were first established by Isaac Newton in his foundational publication, Philosophiae Naturalis Principia Mathematica, or the Principia, published in 1687. This set of laws illuminates how velocity, the state of motion of an object, can be influenced by external forces, and codifies mathematically using geometry, algebra, and the newly invented calculus, the way in which you can describe the interaction of these things in order to understand the natural world. What would also be developed over the following centuries were a series of what we now call conservation laws. These are principles that establish that certain quantities appear to be conserved, that is, left unchanged, even by complex phenomena in nature. These include things like the total energy of a system, including internal forms of energy like chemical energy, the total linear momentum of a system, and the total angular momentum of a system. And for closed and isolated systems, where no external forces, especially of the non-conservative variety, those that can't store and release energy in some kind of potential, in those systems, conservation laws will absolutely hold. And they were established through careful chemical and physical work up through the 1700s. And they continued to be built on in work on heat energy in the 1800s. Heat energy and the laws that govern its transfer from the mechanical form to the thermal form will be revisited in later lectures, the second part of the foundations of modern physics. The third key idea is Newton's law of gravitation. That is the law that relates the distance between material bodies and the force between them, a force that requires no actual physical contact, no medium to be present between two things in order for them to exert a force on each other. And this was also established in Newton's Principia. And finally, the last set of laws of physics that we have to accept as a foundation for what's going to happen in this course are the laws of electromagnetism. These are the rules of electricity and magnetism, describing them as forces in the same way that gravity is a force, that can induce changes in states of motion, again without physical contact between material bodies. Electric forces and magnetic forces can operate even if there's no medium between the two bodies that are interacting with each other via these forces. They were established in the 1700s to 1800s, and they were finally codified formally in 4 equations known as Maxwell's equations in 1862. One of the mathematical foundations of describing nature in physics is a kind of number known as a vector. These are essential to describing any multidimensional quantity, and they have a well-defined algebra which you should have exercised in previous physics courses. You probably have also exercised these in a dedicated math or engineering or both course. Vectors are numbers that can be built from scalars. Scalars are numbers that have no directional information. So, for instance, a good example of a scalar would be if you asked for directions to somebody's house and they told you, go 10 miles. Well, that might eventually, by going 10 miles, get you to their house, but without some crucial directional information, how far east, south, north, or west should I go to add up to those 10 miles, you're probably not going to make the journey successfully. Scalars, however, can be assembled using, for instance, component notation into a vector. So here, for instance, is demonstrated a vector denoted A with a little arrow over its head, and it's broken into components. It has a component that lies entirely along the x-coordinate axis in a Cartesian coordinate system, with length a with a subscript x, and similarly it has a component along the y-axis in a Cartesian coordinate system, a with a subscript y. And these little vectors here, I with a little triangular hat over it, j with a little triangular hat over it, we'll come back to those in a moment, but they are essential in indicating a dedicated direction, either only along the x or y or z axis. Vectors, even though they carry both length information and direction information, can be summarized as having a singular length that characterizes the full straight line distance that you would have to go to get from the beginning of the vector to the end of the vector, and this is known as its length or its magnitude. This can be denoted in one of several ways, either just drawing the vector with no arrow over it, so a in this case, or putting absolute value signs around the vector. That's another common notation for length or magnitude of a vector. And this can be computed using the sums of the squares of the components, and then you take the square root of that total sum. In 2 dimensions, this will recall the familiar Pythagorean theorem, which, given the lengths of the sides of a right triangle, will tell you the length of the hypotenuse. Then there are unit vectors. This is a subspecies of vector, and they're special because they are vectors whose length is always exactly 1 in whatever unit system you choose to use. Unit vectors are denoted with that little triangular hat symbol. So for instance, I hat, j hat, and k hat, as they would be denoted in spoken terms, are special, and they're unit vectors that point only along the x, y, and z axes, respectively, of a Cartesian coordinate system. This also means that because the angles between the x and y and z and x axes are 90 degrees, the angles between these unit vectors are also always 90 degrees for any pair. You can add vectors. So for instance, if I have a vector A and a vector B, and I want to know what the resulting vector, for instance, C with a little vector arrow over its head looks like, all I have to do is take the x components and add them together, noting that they point along the I hat direction. Take the y components and add them together, noting that they point along the y direction, etc. And this will give you the resulting sum of 2 vectors. You can replace the sum with a minus sign to get the difference of 2 vectors, but the math is the same. There are 2 kinds of multiplicative products of vectors, the dot product, which gives you a number, and the cross product, which returns a vector. The dot product is given by the following notation. C can be represented as the dot product of 2 vectors, A and B, with a little dot between them, and it's a number, it's a pure scalar, whose size is the magnitude of A times the magnitude of B times the cosine of the angle between A and B. In component notation, you can calculate this by taking the x components and multiplying them together, taking the y components and multiplying them together, etc., and then adding all of those products together. And again, this yields a pure scalar, a pure number with no direction. On the other hand, the cross product, the other multiplicative operation between 2 vectors, yields a vector. So in this case, the cross product of 2 vectors A and B would yield a 3rd vector, C. The cross product is denoted by putting a cross multiplicative sign in between the 2 vectors A and B. This one's a little bit more complicated, and you have to be a bit more careful with this. I like component notation because you can essentially distribute the multiplication algebraically between the 2 vectors A and B, and you wind up with terms that look like the x component of A and the y component of B with this cross product of unit vectors next to it, and then the y component of A and the x component of B with the reverse cross product of I and j hat next to it, and then a bunch of other terms that look similar to this depending on how many dimensions this thing has. And in the end, this yields a pure vector with a length given by the magnitude of A times the magnitude of B times the sine of the angle between the 2 vectors A and B. Also, the vector C will always point at exactly a right angle to both A vector and B vector. That's one of the natural consequences of the cross product. Now, the cross products of coordinate axis unit vectors like I hat, j hat, and k hat obey the following rules. The cross product of any unit vector with itself is 0, because there is no vector that's perpendicular at the same time to both I and itself. There's an infinite number of those vectors, and the cross product yields a result of 0 for this. Similarly with j cross j and k cross k. Now, the rule of thumb for computing all of the other cross products is that I cross j is k, and then if you kind of conveyor belt k to the beginning of this operation, move I to where j is and move j to where k is, you get one of the other cross products. K cross I is j. And then similarly doing this conveyor belt permutation one more time, so-called cyclic permutation, you get j cross k is I. Now, what about j cross I cross k, or k cross j? Well, if you swap the order on the left side of these equations, then the right side changes by a minus sign. So j cross I would be negative k hat, I cross k would be negative j hat, and so forth. Vectors are an essential building block of everything that happens in mechanics. But the real laws of nature that we encounter in a course on introductory mechanics are Newton's famous 3 laws of motion. The first law states that the state of motion, that is, the velocity of an object, remains constant unless the object is acted upon by an external force. Absent external influences, the natural state of an object is to maintain whatever velocity it presently has. This can be summarized in an equation as follows. The sum of all forces with subscript I, and there can be from 1, 2, 3, all the way up to capital N forces acting on an object, if all of those add up and cancel each other out so that there is 0 net force acting on an object, then the resulting acceleration, that is the change of velocity with respect to time, or the change of the state of motion with respect to time, given by the second derivative of a position vector of the object, is 0. No net force, no change in state of motion. The more general form of this equation is given by Newton's second law, which relates the net unbalanced force acting on an object to any resulting acceleration or change in the state of motion of that object. The change in Newton's second law is proportional to something. Force and acceleration can be related to each other by a simple equation, and the constant of proportionality between force, F, and acceleration, A, is given by m, the so-called inertial mass of an object. Because you can write the acceleration as the second derivative with respect to time of the position vector of an object, I've put here the calculus notation for the acceleration in 3 dimensions, where r vector is a position vector x, y, and z that not only can change with time, but whose change with time can be further altered by having an external force act on it. That is an acceleration. And then finally there's Newton's third law, that in every interaction of 2 material objects, let's call them A and B, 2 forces are in action. The direction of the force exerted by object A on object B is the opposite of the force of object B on object A, but they are otherwise equal in magnitude. So if I take my hand and push on the surface of a table, the table pushes back against my hand with an equal magnitude but opposite direction force. That's why my hand doesn't go through the table. Now, usually after learning about Newton's laws of motion, we then learn about quantities that are associated with motion. These are known as energy and momentum. What is common between these quantities is that they vary in some proportion to the degree of motion. So, for example, the quantity of energy associated with a moving object, so-called kinetic energy, is proportional to mass and to the square of the velocity of an object. It is a scalar. Because you square the velocity, you lose all directional information about it. And the exact equation for kinetic energy is determined to be 1/2 times the mass times the velocity squared, or the speed squared, of an object. There is a direction full quantity of motion, and that is known as linear momentum. it is proportional to mass and directly to the velocity of a body. At least in this classical physics and this introductory mechanics we learn about, this is observed to be the thing that appears to also be conserved in nature like energy. Linear momentum is denoted by the letter P with a vector hat over it, and it's the product of inertial mass and the velocity of the object. We can write this in calculus notation as the mass times the first derivative of the position vector with respect to time. Now there's another momentum quantity that's associated with a body that can rotate as well. So the degree of its rotation around some axis imparts some angular momentum to the system, and we also learn that in closed and isolated systems this quantity can be conserved. It's proportional not to the mass of the body, but to the distribution of mass around the axis of rotation, the so-called moment of inertia, and to the rotational velocity of that body. All points on a rigid body that can rotate about an axis will have the same rotational velocity regardless of their distance from the axis of rotation. And the moment of inertia describes using an integral, which is shown here. I is the integral of r squared dm, where r is the distance from the axis of rotation for the little bit of dm mass that you're considering at the time. The product of these two things yields the angular momentum, and this is observed to be conserved in systems that are closed and isolated. Now, if an external conservative force acts, one where the work done by the force in moving an object from point A to point B is the negative of the work moving from point B to point A by any path that you can take, then there is an associated potential energy as well, which we denote U. This is another kind of energy. So there's kinetic energy, and then for conservative forces, where those things like gravity, for instance, can act on a system, you have an associated potential energy. You can lose kinetic energy and store it in potential energy, and you can lose potential energy and gain it in kinetic energy. There's an interplay in these kinds of energy in systems, and the total energy can be conserved. On the other hand, for external non-conservative forces, such as friction or air drag, there is no associated potential energy. But other forms of energy, such as heat, which is the motion of atoms in a material object, can result from losses of kinetic energy through the action of those forces. Now, as I've hinted at before, energy and momentum can be conserved. And for a system that is acted upon only by conservative forces, which have an associated potential energy, and is otherwise closed to and isolated from all other kinds of forces, in that specific case, what is known as mechanical energy is completely conserved. Mechanical energy is the sum of all kinetic and all potential energy in the system at any moment. So for instance, there might be some initial moment of time where there's a total kinetic energy Ki and a total potential energy Ui. And if the system obeys the constraints I've listed above, then I can look at any other time, say some time final later, denoted with an F, and I can see that although kinetic and potential energies may have morphed one into the other, the sum of these two things across all objects in the system is the same sum as I had at the earlier time. Now, for a non-closed and non-isolated system, and especially where non-conservative forces can act, total energy will be conserved, but not just mechanical energy. And total energy is the sum of kinetic, potential, and all other forms of internal energy like heat due to friction or drag, or even chemical energy. If, for instance, mechanical energy has been converted into stored chemical energy through some chemical and mechanical and electrical process, then you can retain the energy in that form, and you may be able to get it back later in the form of either potential or kinetic energy, depending on what kinds of non-conservative forces are acting in the system. But if you can figure out all the energy buckets where energy can go in a system, even one where non-conservative forces can act, then you can still see that the total energy in all of those buckets, added up, remains constant over time, even if you can't recover mechanical energy when it's lost into forms like heat or chemical energy. And for a closed and isolated system of objects, total momentum, both kinds, linear and angular, is conserved. So if I sum up all the linear and all the angular momentum at one time initial, ti, I will find later on that the sum of all momentum and all angular momentum, all linear momentum and all angular momentum is the same, even if it's been interchanged between objects, maybe they've collided with each other, things like that. Now, if only elastic collisions of these objects are possible, that is, the number and mass of the objects never changes, then the total momentum and kinetic energy are conserved in that case. But if inelastic collisions are possible, where objects can stick together for appreciable periods of time, or if they can lose mass or gain mass, then only momentum will be conserved. But again, you have to be very careful with how closed and isolated the system is. Now, another law that we encounter in introductory physics, which seems a strange beast compared to the other kinds of mechanical phenomena that we encounter in these courses, is the law of gravitation, which governs the gravitational force between any two bodies with mass. It acts without physical contact, and it does so even across empty space. And I've illustrated that here by showing you the planet Jupiter, which is the heaviest planet in our solar system, and 4 of its moons, the ones that were first spotted by Galileo when he turned his telescope to the night sky to see what he could see. These are the so-called Galilean moons. They're the biggest moons of Jupiter. Jupiter has many more moons than this, but these are the 4 most visible, the most easily visible, even with a modest aid to the eye. And those are Io, Europa, Ganymede, and Callisto. And these 4 moons do an orbital dance around Jupiter. They don't orbit the Earth, they orbit this planet. And this was a remarkable observation in the days of Galileo, that you had objects in the night sky that didn't go around the Earth. And they do this under the influence of gravity, the same force that holds our moon in orbit around our planet, and our planet and all the other planets of the solar system in orbit around the central star, our sun. It's gravity. Gravity explains all of this stuff. Now, the gravitational force that an object A exerts on an object B is proportional to the masses of both objects and inversely proportional to the square of the distance between them. And this is codified in the law of gravitation. That is, the gravitational force between any two bodies, so for instance the force on A that's exerted by B, is proportional to the product of their masses divided by the distance squared between them. The constant of proportionality, G, I'll get to in a moment, but the force points from the object that's acted upon, A, toward the object that's doing the acting, B. So it's an attractive force. Now, again, this is the force that A experiences exerted by B. Now, G is this universal constant of proportionality. It must be determined by experimental methods, and it's currently known to be about 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. Not a very big number. Gravity may seem like a strong force, but that's because we're being pulled on, for instance, by all the atoms of the planet Earth, and that's why when we try to jump off the surface of the planet Earth, we get pulled back down to the surface. So all the atoms of the Earth below us are pulling back on us as we attempt to accelerate away, and it re-accelerates us back toward the center of the Earth. But of course, we don't go through the surface of the Earth when we hit it. Why is that? That's because another set of forces, electromagnetism, governs the interactions between atoms. And atoms tend to repel each other because they have clouds of electrons around them, and the electrons have the same electric charge, and in the laws of electromagnetism, this causes a repulsive force to occur. And so while gravity may seem strong, the truth is, because we don't get pulled through the surface of the Earth and down to the core of the planet, is because of the strength of electromagnetism, which overcomes an entire planet's worth of atoms pulling on you. Now what's worse, gravity seems like a strong force, but it's not. And also, this force law doesn't really tell us its origin. It has something to do with mass, and it weakens or strengthens depending on your distance squared between two objects. It tells you what direction it points. But it doesn't explain what the origin of gravity actually is. What is this force? Where does it come from? So one of the unsatisfying things about the law of gravitation is that it's very descriptive, but it is by no means explanatory. And this was something that even Isaac Newton recognized, and because he could provide no evidence to explain the origin of the force known as gravity, he preferred not to speculate on it and left it open for the people that would come after him to try to figure out. But it was certainly one of those puzzles he never managed to resolve in his lifetime, and its resolution would be left until the modern era of physics. Now, speaking of the laws of electricity and magnetism, let's take a look at those. And I'm going to do so in a form that may not be very familiar to you, but it will be beneficial to you later, even if you don't completely understand the notation. Now, electric and magnetic forces have something in common with gravitation. They can act without physical contact across stretches of empty space. However, it's pretty much right about there that they part ways from gravity. Their strength is proportional to a completely different physical property of nature, electric charge, which various bits of matter, like the electron, for instance, appear to carry as a fundamental property. Now, like gravity, the strength of, say, the electric or magnetic force appears to vary inversely with the square distance between charges or flows of charges, and depending on the situation we're talking about here, but I can wave my hands, sort of make that rough approximation. A density of electric charge, however, is the source of the electric field of force. Mass has nothing to do with the electric field of force. It has something to do with the gravitational field of force, but again, this is roughly where gravity and electricity and magnetism all part ways. Now, an electric current density, that is a flow of electric charge, is the source of a magnetic field of force. So a static electric charge just sitting there in space will exert an electric force on another charge somewhere nearby. But in order to get a magnetic interaction to occur, one of those charges has to be moving relative to the other. Now, I'm going to define a symbol. It's this funny triangular symbol known as nabla, because it resembles an ancient harp of the same name. It's got a little vector sign over it, which immediately tells you that whatever this thing is, it has directional information. And it's funny because it's not made of numbers, it's made of derivatives. And specifically, it's made with either the full or partial derivatives with respect to space. So, for instance, the derivative of something with respect to x, the derivative of something with respect to y, and the derivative of something with respect to z. This exposed triplet of derivatives is known as an operator. It doesn't itself return a number, but when used on another thing, like another vector, it can return a number. So you can think of it as a function that when finally given something on the right-hand side to act on, will give you some information back. But on its own, it doesn't really give you information. It's just prepared to tell you how something changes in space. Now, you may not have seen this symbol before, and that's okay. But by defining it, it allows me to write the laws of electricity and magnetism, so-called Maxwell's equations, in 4 compact mathematical lines. Now, the laws governing these electric and magnetic fields are 4 in number. The first one is known as Gauss's law for electric fields. And believe it or not, from this compact little equation here, you can, under special conditions, derive Coulomb's law, which is probably what you really learned was the law of the electric force in introductory physics. There is a simple exercise one can go through to show that this reduces to Coulomb's law. But this is the most preferred and general form of this particular law of electricity and magnetism. And in English, what it tells me is it tells me that a charge density, that is, a charge per unit volume, rho, is the source of an electric field on the left-hand side. We have this operator I defined above, which is just a triplet of space derivatives acting on an electric field via the action of the dot product. So this thing returns a number, and that number is equal to the charge density divided by epsilon naught, which is a constant of nature. The second law is Gauss's law for magnetic fields. And this one is probably the simplest of the 4. it's that same operator action, the nabla symbol with a dot product with the magnetic field. But on the right-hand side, you get 0. And what this equation tells you is that so far as we know, there are no such thing as a magnetic charge. In order to create a magnetic field, you have to have moving electric charge. And so far as we know, and many experiments have tried and many experiments have failed, there is no such thing as a magnetic charge. That's what this equation codifies. Then there's the Faraday-Maxwell law. The Faraday-Maxwell law tells me that if I have a time-changing magnetic field, this can generate an electric field. Now, I have a different vector operation on the left-hand side. I have this nabla symbol, the vector, cross product with the electric field, which returns a vector. And indeed, I have a vector on the right-hand side as well. The time derivative of a vector field is also a vector. And then finally, there's the Ampere-Maxwell law. And this tells me something a little bit similar to the Faraday-Maxwell law. And that is that if there's a time-changing electric field, or if there's a current density of electric charge, a flow of electric charge, or both, then this results in a magnetic field. So the left-hand side tells me that there's a magnetic field that exists. The right-hand side tells me where those magnetic fields might come from, either from a charge current density or from a time-varying electric field. And mu naught here is another fundamental constant of nature. Epsilon naught and mu naught you should have encountered in introductory physics, and you can go ahead and look up their values. Now, what's amazing about the laws of electricity and magnetism, Maxwell's equations, is that when you consider them in a particular situation, it finally clarifies what the heck the nature of light is. Light is an amazing phenomenon. It carries information from one place to another, and it does so at a seemingly immense speed. And it turns out that by solving Maxwell's equations in a certain regime, you find out what light is. It's a very rewarding exercise, one that you would presumably go through in a more advanced course than this one, but I'll tease it here. So, for instance, if you consider empty space where there are no electric charges, no rho, no charge densities, and where there are no electric currents, no J's with the vector hat over the top of it, nonetheless, Maxwell's equations are not just simply all zero. So let's take a look at those equations under those conditions. I've rewritten the four equations with no electric charges and no current densities. So I have this nabla dot E vector is 0, nabla dot B vector is 0. I have nabla cross E vector is just negative dB dt, and nabla cross B is something proportional to the time derivative of E. So there is a trivial solution to this. E and B can be 0. That works out just fine. But there's another solution to this that isn't the so-called trivial solution. And the non-trivial solutions are vector functions of space and time. And this is what they look like. The electric field and the magnetic field as a function of space and time that also satisfy these four equations are these time and space varying functions over here. They're cosinusoidal, and they can all be written in terms of the electric field. They describe some kind of oscillatory phenomenon. Oscillatory phenomena, like waves, are things you should have learned about in an introductory mechanics class. K hat here simply indicates a unit vector that's in the direction of travel of the phenomenon. And this number, c with a 0 subscript, that turns out to be the speed of the phenomenon in empty space, because that's the kind of space we're considering here. Empty, no matter, no charges, no currents. And it turns out that you can solve for that speed, and you find out that it's equal to 1 over the square root of those fundamental constants of nature, mu naught times epsilon naught. And if you plug those numbers in, you get an amazing fact out of this, that whatever this phenomenon is, it travels at 2.998 times 10 to the 8th meters per second. And for the astute among you, this is the speed of light. So what Maxwell's equations in empty space tell us is that when solved, they describe a phenomenon that can travel from point A to point B seemingly through empty space, and it does so at precisely the speed at which light was known to travel in the days when this was solved. So light is what is known as an electromagnetic wave. And like a mechanical wave, which was the only analogy that physicists had at the time, it was originally assumed that it must travel in a medium. Sound travels in air. Water waves travel in water. They are distortions of a medium. And so it was presumed that light must too be some kind of mechanical wave. And that means that seemingly empty space couldn't really be empty. Something's got to be there that distorts to allow this wave to travel. That was the assumption based on mechanics. Now, finally, I want to go into the subject of relativity, which would have been introduced to you probably under the phrase relative motion. In introductory physics, you get some exposure to relative motion. That is, a person standing on a train, the train is moving relative to somebody on the ground, the person on the train throws a ball up in the air, what does the person on the ground see? That's usually the way in which this is couched. The person on the train, for instance, who throws the ball straight up in the air, will see it go up, gravity will accelerate it, and eventually it will come straight back down into their hand. So it just goes up, slows to a stop, and then accelerates down back to their hand, all along a straight vertical line. That's what the person on the train sees. A person on the ground watching this sees the ball follow a parabolic trajectory, because the ball and the person have a horizontal velocity because they're standing on the train. So the ball goes up and comes down, yes, but it doesn't land at the same coordinate along the horizontal that it started at. It appears to follow a parabola. And so the two observers will disagree on the motion of the ball. The person on the train says, no, it goes straight up and then comes back down to my hand. And the person on the ground says, well, no, it didn't go straight up. It followed a parabolic trajectory, but your hand moved too, and so it was there to catch it when it came back down. And it's possible to use mathematics to relate these differing observations of space and time. And to do this, you assume that time passes the same for all observers. The person on the train and the person on the ground all experience time the same way. And when you make that assumption, you get out of this something known as the Galilean transformation that allows you to relate spatial coordinates and velocities of objects from a frame you consider to be at rest to a frame that you consider to be moving. So in our case, you might consider the platform or the ground next to the train to be the rest frame. You might consider the train to be the moving frame. And these equations shown down here will relate coordinates, velocities, and times in the moving frame with the primes next to them to things in the rest frame, the numbers without the primes attached to them. Okay, so that's not so bad. It's actually one of the more complicated things that most students encounter in introductory physics because it forces you to think in two different frames of reference, and this is not always as straightforward as it seems. But the math itself is not that bad. It's more the conceptual issues that go along with this that pose a particular challenge for most people who see this the first time. So that is basically a summary of what we now call classical physics, introductory mechanics, and the laws of electricity and magnetism, or semester 1 and semester 2 physics. And even though classical physics is challenging, there are many difficult things that you have to do. There's new math you haven't seen before. You're often learning calculus at the same time you're expected to use calculus in introductory physics. Nonetheless, at the end of the day, if you stop and look at all of this stuff, you'll often say, okay, the mathematical or some conceptual difficulties aside, all of this stuff feels to me very intuitive. I can throw a ball up in the air, I can catch it. I can watch somebody do that in a train and see it moves in a parabolic arc. Okay, yeah, we disagree on what's happening, but we can explain to each other why we see what we see. It's all very, normal day-to-day human scale stuff. Really, this is intuitive. It just had to be described by mathematics, and that often is the difficult part. But you have to be very careful about intuition. Intuition is largely based on experience with events that involve the following things. Speeds that turn out to be very close to zero. Driving at 70 miles an hour may seem really fast to you as a human being, or getting on a rocket ship that goes into Earth orbit might seem really extreme, and they are for human beings. But compared to the fastest known phenomenon in the universe, which is light, 2.998 times 10 to the 8th meters per second, 70 miles an hour seems pretty pathetically slow, and in fact is so close to zero that from the perspective of light, it might as well be nearly at rest. Not very impressive to light. So you have to be careful, one, because the speeds that you're used to encountering are really close to, it turns out, zero, and so your intuition is built on a very narrow spectrum of experience in the universe. The other thing that you may take for granted is that the sizes of things that we usually think about in classical physics, with the exception of electrons and protons and electricity and magnetism, the sizes of those things tend to be very large by comparison to what are known to be the building blocks of the material universe. And for the stuff around us, that's mostly going to be atoms. That's the day-to-day stuff that we are interacting with. But when you interact with a table, that table has like Avogadro's number worth of atoms in it. That is a huge number of atoms, and the scale of the structure built from those atoms is vast by comparison to the atoms themselves. And so as a result, as we begin to encounter phenomena, and this was true of physicists at the end of the 1800s, as you begin to encounter phenomena that are very fast or very small, so objects moving very close to the speed of light, or objects that are really more at the atomic or even the subatomic scale, the things that make up the atoms, you begin to find that classical physics needs to be modified to describe the universe more completely. It works for slow things at large scales, like human scales, or planet-size scales, or even bigger. But it breaks down in regimes where it was never designed to operate, the very fast and the very small. So, as a result, you're often going to find as you go into modern physics that what you think to be true about the universe is based on intuition from a limited set of experiences in the cosmos. And as a result, your intuition is actually fundamentally wrong. But the good news is that this only means that you are finally experiencing the breadth of the universe, all it has to offer at all of its scales and speed and size, rather than that limited scale of phenomena closer to human experience. So let's use classical physics and let's make some predictions to set ourselves up for where people started to go really wrong with these ideas in roughly the late 1800s. Now, the tenets of classical physics, which I can summarize based on the earlier part of this lecture, are encoded largely in Newton's laws and Maxwell's equations. And they should, if this is all there is to the universe, apply to all phenomena in the natural world. After all, if this was really the complete set of all the laws of nature that had been discovered in the 16 and 1700s, then it must be true that they describe everything. Otherwise, they're not a complete set of laws. So let's take a look at light. What would the framework of classical physics then insist be true about light? Well, from Maxwell's equations, we know that light is some kind of oscillatory phenomenon, like a wave. And so our experience with waves in the 1800s was that they must be mechanical in nature. They must represent the distortion of a medium. So they gave it a name. They named it before they ever discovered it, and they called it the ether. And it was believed to be the thing that actually fills empty space. Empty space isn't empty. It's made of this substance called the ether that we normally can't experience, but light experiences it, and the distortion of the ether is what we call light. That was the hypothesis based on the mechanical understanding of wave phenomena. So the speed of light in so-called empty space, the number that we got from Maxwell's equations, that isn't really the speed of light in empty space. It's the speed of light measured relative to an observer at rest with respect to the ether. The ether is the universal reference frame for light. And if you can be at rest with respect to the ether, then you will observe that light moves at 2.998 times 10 to the 8th meters per second. It's a big number, okay? But this would then make ether the universal rest frame. That is the frame that you could define to always and absolutely be at rest, and then everything else is in motion relative to it. That would be awesome. The Galilean relativistic and Newtonian mechanical view of the universe would have allowed something like this to exist. Now, the problem was that sort of the new kid on the block, Maxwell's equations, which really only emerged in the second half of the 19th century, they were silent on the topic of the ether. They described no substance that required this electromagnetic wave called light to propagate. So it was assumed that they must be incomplete. They're the new kid on the block. They're probably not complete. They need to be completed, and the ether would complete them. So it was assumed that Newton's mechanical view of the universe, the laws of motion and all that stuff, that was correct, but that Maxwell's equations was just incomplete and needed to be completed with this mechanical substance, the ether. So if we then apply this thinking to a problem involving light and travel and time, what would we predict? Let's put ourselves in the role of sort of late 19th century physicists. We've learned all this stuff. It's been solid for 200 years. So what are we going to predict?
So let's do a thought experiment. A thought experiment is a kind of experiment that you can carry out entirely inside of your head. What you do is you imagine a scenario, you analyze the scenario using the understood principles of nature or laws of physics, and you look to see if the conclusions of running this imaginary experiment would in any way violate logical or physical consistency. And if you determine that that's the case, you may have hit upon a useful inconsistency in our understanding of nature that could then be used to figure out what the correct description of nature might be. So to do our thought experiment, let's imagine that we are in a space that is filled with ether, the medium in which light traveling as a wave disturbs the medium and propagates at 2.998 times 10 to the 8th meters per second. Now imagine into this volume of ether we place two cars, one car at the left, one car at the right. And the car at the right has its headlights aimed at the car on the left, so that an observer in the car on the left could look back out the window, and if the headlights of the car behind them were on, they should be able to see the light. But let's put a 30-kilometer gap between the front of the right car and the back of the left car, so that light, if it wants to go from the car on the right to the car on the left, has to cross this gap of 30 kilometers. Okay, fine. So we've placed the cars in the ether. The cars are at rest with respect to the ether, so they're in the frame of reference of the ether. And the car on the right switches on its headlights. How long does it take for an observer in the car on the left, the second car, to see the light reach them? Well, this seems pretty straightforward, right? You know the distance. It's 30 kilometers from where the light leaves the right-hand car and arrives at the left-hand car. And Maxwell's equations tells us that light travels at a fixed speed. It doesn't say anything about the ether, but we've invented the ether to help us to have electromagnetic waves comport with all prior knowledge of mechanical waves. So it's a medium with mechanical properties that can stretch and squash, and those stretchings and squashings are electromagnetic waves. And in that medium, light travels at 2.998 times 10 to the 8th meters per second. Okay, everything's at rest with respect to the ether. Light travels at the speed of light in ether, so we just run the numbers. We take the distance, we divide by the speed, and we get the time that is required to make this journey. And we find that that time comes out to be about 0.1 milliseconds, 1 times 10 to the minus 4 seconds. Okay, nothing hugely revelatory here, but let's take our thought experiment one more level forward. Now let's imagine that both cars have been plopped into this ether volume, and they accelerate at the same time up to a constant velocity of half the speed of light. That's a speed of 1.5 times 10 to the 8th meters per second. And let's imagine that the cars are both moving together at the same velocity from right to left. So they're traveling from the right to the left in the ether. At all times, they maintain a fixed distance between the front end of the right car and the observer at the back end of the left car of exactly 30 kilometers. The car on the right turns on its headlights. Now how long does it take the light to reach the observer in the other car? Well, let's review what we think we know about light speed and this so-called ether that distorts to allow electromagnetic waves to
propagate. Light travels at c, the number given by Maxwell's equations, 2.998 times 10 to the 8th meters per second, in the rest frame of the ether. But now, from the perspective of the cars, the ether is a wind that's rushing past them. Still air on a calm day leaves no sensation on your body. But if you were to start running forward, you would perceive a wind hitting you in the face. And that's sort of the equivalent situation here. Both of these cars are now traveling through the ether. They're doing so at half the speed of light. And so from their perspective, the ether is rushing past them as a wind, and its speed is also half the speed of light. It's as if they perceive themselves to be at rest, and the ether to be rushing past them at half the speed of light. So the velocity of this wind is the negative of their velocity with respect to the ether. Now, Galilean relativity and Newtonian mechanics demand that, from the perspective of observers in the car, that the light that leaves the car on the right, while it's traveling at 2.998 times 10 to the 8th meters per second in the rest frame of the ether, is encountering this wind of ether that has the apparent effect of slowing it down. This is sort of like sound waves or water waves in their respective media. If the medium is moving, then the medium's speed can add or subtract from the velocity of the wave in that medium. And so Galilean relativity and Newtonian mechanics are going to demand that the observed speed of light in the frame of the cars is the speed of light in the rest frame of the ether minus the velocity of the cars. And so you would actually see the light leaving from the right-hand car and traveling the gap between the right-hand car and the left-hand car at what seems like a slowed speed, as if it's encountering resistance as it moves forward. It's not moving at 2.998 meters per second anymore. It's moving at about half that. And so you would answer that, well, the distance between the cars is still the same. It's 30 kilometers. And the speed of light has been reduced by the ether wind. And so you would predict, based on all knowledge at this stage, that the time it takes for the light to get to the other car is greater than it was before. It's about 0.2 milliseconds now, twice the time that was required when the cars were at rest with respect to the ether. Now, that's a prediction, and it comports with all prior experience in the pre-20th century world. It comports with ideas about how velocities add in relative motion. It comports with the idea that waves can only travel because they're distortions in some kind of medium, a mechanical explanation for waves. That's consistent with Newton's mechanics. All of this seems to be perfectly acceptable from the perspective of the bare-bones introductory physics to which you would have been exposed. But a fair question to ask is, this is the outcome of a thought experiment. What would be observed in a real experiment in the real world? And we'll take a look at that. So let's review the basic ideas that are the foundations for modern physics. The groundwork for modern physics are Newton's mechanics, the concepts of energy and momentum, quantities associated with motion that can be conserved under certain conditions, the law of gravitation, and the laws of electromagnetism. However, these were largely built to describe phenomena that comport with typical human experiences, phenomena at our size scales, or slightly larger or smaller, essentially within our ability to see the world around us, including with a microscope or a telescope. That would all be within the human scale. The exception, however, is Maxwell's equations. They were developed by studying electric charges, which are very small, and they are really beyond the scale of everyday experience, except in their large-scale macroscopic effects, like electric and magnetic forces, electric currents, lightning strikes, refrigerator magnets, things like that. They have these big macroscopic effects that feel familiar to us, but at the individual level of an electron, let's say, things are not typical compared to the human world. By the end of the 1800s, chemists and physicists were beginning to directly interact with scales that really were beyond human experience. So, for example, the electron is discovered in 1897, and it turns out to be the first subatomic particle, although that really wouldn't be fully understood for several more decades. In addition, an invisible radiation, like, for instance, what we now call X-rays, this was discovered at the end of the 1800s and 1895 in the case of X-rays. And these phenomena and other phenomena at the same scale, even atoms themselves or other general forms of light, they turn out to be way beyond human experience. And so trying to adapt our intuition in the form of Newton's mechanics, for instance, to these phenomena would lead to spectacular fails. Now, not only were such new phenomena small, they also turned out to be capable of moving extremely fast. X-rays move at the speed of light. Electrons, with minimal effort, can be compelled to move at almost the speed of light. Such speeds are also very much beyond human day-to-day experience, although you might lead yourself foolishly to think that you understand them really well. So this concludes a foundational lecture, a review of the material you should have been exposed to already in Semester 1 and Semester 2 physics. I know that I've couched this in some ways that are unfamiliar, but I'm trying to rattle you out of any complacency you might be in after having had a couple of introductory semesters of physics. And we're going to begin to explore the consequences of these classical physics predictions on phenomena like light in class. And then we will build on what we conclude from those explorations into the first steps of modern physics. In this lecture, we will learn the transition in thinking that led from Galilean relativity to the special theory of relativity in 1905. We will learn the postulates of special relativity, which are the basis of the mathematics of the framework. And we will look at some of the consequences of those postulates even before we delve into the mathematical framework itself. In class, we looked at the lessons of the Michelson-Morley experiment, which can be summarized as follows. First, light travels at a fixed and constant speed in any medium, regardless of the relative velocity of the light source and the light observer. This is unlike any other phenomenon described in mechanics, and it implies that Newton's mechanics is actually the incomplete theory of nature. No medium is actually required for that light to propagate. Unlike a mechanical oscillatory phenomenon, a wave, to exist, light requires no medium to be distorted. It is not mechanical in origin. And this implies that Maxwell's equations are complete, or at least sufficiently complete to understand light. These lessons, however, would not be fully absorbed until about 1905, when Albert Einstein, one of the most famous physicists in history, published the definitive papers explaining how to reconcile mechanics, electricity and magnetism, and the results of the Michelson-Morley experiment. Now, interestingly, the mathematics that Einstein would come to rely on for encoding the relationship between space and time measurements in one frame and space and time measurements in another frame were actually laid down much earlier by Hendrik Lorentz in a famous paper on the compression of bodies in the ether. The mathematics that would later become a replacement for the Galilean relativity equations would actually be kind of sketched out, but for a completely different purpose than they would ultimately be used for. Lorentz was considering the effects of the ether on bodies that are moving through it. Now, these bodies are held together by chemical bonds. They're made of atoms, and those atoms are chemically bonded to each other. But chemical bonds are just electromagnetism in action. And so, based on this, he arrived at a few hypotheses, should the ether exist. First, that mechanical bodies would compress along the direction of motion in the ether, and this has a precise mathematical description for the process. And second, in transforming observations from the ether frame to other frames of reference, he would conceive of an alteration of time that also had a very firm mathematical description. Now, Lorentz conceived of this during a period when the ether was still very much believed to exist. The results of the Michelson-Morley experiment were not fully digested during this period. The ether's existence would ultimately be disproven, or at least shown not to be necessary to explain anything that was then known about nature, in the decades that would follow this work. But the mathematics laid down by Lorentz during this period would still prove extremely useful, and today we know this as the Lorentz transformation, the replacement of the Galilean transformation from frame to frame. We'll come back to that in a later lecture. Let's talk about Albert Einstein and his miracle year of 1905. So Albert Einstein in 1905 was a young PhD physicist who was laboring doing physics as sort of side work in what was otherwise supposed to be his regular work at the Swiss Patent Office in Bern, Switzerland. He had this job because he was unable to secure, for instance, a faculty job after completing his PhD. And in part, this was because Einstein really couldn't get any recommendations out of any of the professors that had supervised his education, because he had so irritated them with his behavior during what we would consider graduate school, including skipping out entirely on classes, in particular, for instance, math classes for mathematics he didn't consider to be physically useful, and also for challenging his professors, challenging their authority, thinking of them as idiots, and so forth. Now, Einstein was a very bright young man, but he was also a bit arrogant and temperamental, and this didn't do him any favors when he was trying to get a job. Now, ultimately, it was the thinking that culminated at the end of his PhD work and then into the years leading up to 1905 that would lead to a change in the way that the community of physicists thought about the supremacy of the assumptions made in Newton's mechanics versus what the laws of electromagnetism, that is Maxwell's equations, had to say about light and space and time. And in 1905, he published the work that had resulted from his PhD research in a series of about 4 papers. And this was his so-called miracle year. This is a highly productive year for a young and relatively unknown physicist in this day. In doing so, he reframed assumptions about space and time and what is not invariant to all observers and all frames of reference. Recall that in the Newtonian and Galilean view of space and time is experienced the same way by all observers, regardless of their relative states of motion. Time would be referred to then as an invariant. But what Einstein proposed challenged thinking about what was and what was not invariant in space and time. Now, in short, here's what Einstein did. He accepted the conclusion of the Michelson-Morley experiments that light has a fixed speed regardless of the motion of the source relative to the observer of the light from the source. This then implied that there's no ether as well. Using a simple thought experiment, like the one that we did in the Foundations lecture involving car headlights and the ether, he explained also why time is not absolute even in Newton's mechanics. Time itself is not an invariant concept, and he did a quick thought experiment that showed that it wasn't even true under Newton's way of thinking. And so he was free to abandon time as the constant thing in transformations from one frame to another frame. Instead, he chose to preserve overall the forms of the laws of physics and the speed of light, which the Michelson-Morley experiment implied was constant regardless of your state of motion. This then led to the foundation of 2 postulates that allowed him to then define all the mathematics that would follow. The first postulate is what I hinted at a moment ago. The forms of the laws of physics, that is, F equals ma, for instance, or Maxwell's equations, will be the same for all observers, regardless of their state of relative motion, that is, their frame of reference. The second postulate is that the speed of light is the same for all observers, regardless of their frame of reference, their state of relative motion. Now, let's begin by breaking down the concepts that we need to dig into so that we can really understand where all of this is headed. We need to take these postulates and parse them into some phrases and words, define those things, and then go forward from there. This will allow us to build back up to a more complete understanding of the math that we'll eventually need in order to understand relativity and relative motion going forward in modern physics. First off, there's the word event. You might think you know what this is, but in physics it is given a very precise definition so that we can always try to define the concept mathematically so that everyone can agree on what an event is and what an event is not. Another phrase that's deceptive and may seem to have a common definition for you, but where we have to be careful about this in physics, is the phrase frame of reference. We need to define it. It comes up a lot in our discussions, and because descriptions of events can depend on the frame of reference in which the observation is made, we have to carefully define this concept. Simultaneity is another word, probably the one that causes the most consternation among people who are making the transition from introductory mechanics and electricity and magnetism into modern physics. Because simultaneity has probably been implied in a lot of things in the past, but we have to put it on some firm footing conceptually here so that we can use it and explore it going forward. It turns out that the concept of simultaneity is actually essential to many things you take for granted all the time. You've just never been forced to think about it before. This concept turns out to be a subset of the discussion of events, and it's going to play a very important role. So we're going to have to define this. And then finally, you might think you're comfortable with this idea, but the phrase speed of light would benefit from some context and some description. We should really try to understand the number that is behind this phrase. It's a ridiculously large number compared to most things on the day-to-day human scale. But it actually turns out that this speed is only impressive on the scale of things that are roughly the size of planets. I'll even allow solar systems, and maybe smaller, depending on how you define a solar system. But it turns out the speed of light is not as fast as we would like it to be, and certainly on the scale of things like the entirety of the universe, it is pathetically slow. So, let's get started in the next few slides trying to define each of these things very carefully. First of all, let's talk about the concept of an event. An event is, quite simply, anything with a location in space and time. So let's practice this concept. I will show you an event, and I want you to try to describe it with words and numbers. Go ahead and pause the video while you're doing this when prompted. See if you can come up with a short sentence that describes the event using the definition that an event is anything with a location in space and time. This is excellent practice for defining events in any new situation that you will encounter as an exercise in setting up a problem for eventual solving. I've given you a one-dimensional axis, so an x-axis, and let's say that the numbers here have units of meters. That'll make it easy for us to very precisely describe an event. I've also given you a timer. The timer is capable of ticking out about 12 seconds, and the units on each of these tick marks, 1, 2, 3, and so forth, are seconds. Okay, so you have a spatial reference, and you have a time reference. Given that information, let's go ahead and proceed with looking at an event and attempting to describe it. I want you to describe the event depicted above on the x-axis. Go ahead and pause the video, come up with a short sentence that uses the definition of an event to describe it, and then resume the video when you're ready to compare to my answer. You should have come up with something like the following. The dot is at position x equals 0 meters at time t equals 0 seconds. That's an example of describing an event in physics. The dot is at a spatial location that is defined at a time that is also defined. X and t, space and time locations. If you didn't feel comfortable doing this, now that you've seen me go through it once, let's try another event. You try to describe it, and let's see what you come up with. Describe the event depicted above now on the x-axis. Go ahead and pause the video. Write down a short sentence that uses the definition of an event to describe this event, and then resume the video when you're ready to see what I came up with. So what I decided to do was to describe this as follows. The dot is at position x equals 2 meters at time t equals 2 seconds. Make sure to check your space reference and your time reference when presented with an event, so that you correctly mark in, say, x and t, or x, y, z, and t, the coordinates of an event. An event is something that has well-defined coordinates in space and time, a location in space and time. Let's now talk about a frame of reference. A frame of reference is any object or system, all of whose parts move at the same velocity with respect to an agreed-upon reference point in space. That's quite a mouthful. Let's go ahead and illustrate this with an example. I want you to consider the three objects shown below, labeled black, a black dot, blue, a blue dot, and red, a red dot. Now, one of them, the black dot, is agreed upon by the others, the red and blue dots, as the common reference point for all measurements. Now, as I've depicted them here, blue and red have an associated velocity vector, shown here, and as depicted, red and blue are in the same frame of reference because they have the same velocities. Let's check that. If I roughly eyeball the length of this vector, it seems to be pretty similar to the length of this vector. So from this I could conclude that very likely blue and red have the same speed with respect to black. But velocity is not just speed, it's not just the magnitude, it's also the direction. And here I see that the directions align. They point parallel to each other, and so I conclude from this that they have the same velocities. Therefore, although blue and red are both moving, they are moving in the same way, with the same velocity. They have the same state of motion, and therefore they are in the same frame of reference. Now take a look at this one. I've changed something here. Does this change alter the conclusion about blue and red? Do the red dot and the blue dot share the same or different frames of reference? Pause the video here, look carefully at the image, and then resume the video when you're ready to hear the answer. The answer is that they do not. Although their speeds are the same, the lengths of those two arrows look pretty much identical, the direction of the motion of the red dot relative to the blue dot, and all measured with respect to the black dot, has changed. This means that they have different velocities, and different velocities means different states of motion, and therefore different frames of reference have now emerged here. The blue frame of reference is no longer the same as the red frame of reference. Now I want you to consider the objects in this picture, blue, red, and now a purple dot. All of their velocities are measured with respect to the black dot as the reference point. That hasn't changed. I want you to practice a little bit more, and I want you to think about how many unique frames of reference you can identify in the above picture. Go ahead and pause the video here. I'm not going to provide the answer here because I really want you to try to step out on a limb on this one. But feel free to talk to me as the instructor outside of class or in class if you're not confident in how to determine the answer to this question. Now let's visit the concept of simultaneity. Simultaneity is a subset of events in which two events or more are said to be simultaneous, that is, to possess of this quality, simultaneity, if they are observed to occur at the same moment in time. This seemingly straightforward definition of the concept should not fool you. You have to think really hard about whether events are actually simultaneous, and if there are multiple observers in different frames of reference, for whom are those events simultaneous? Finally, let's look at the speed of light. And let me be clear about the speed of light. It is the number of meters that light can travel once it's been emitted by some kind of source in a certain amount of time. That's just the old definition of speed. But light is special. It's special because the Michelson-Morley experiment tells us that no matter the state of motion of the observer or the emitter of the light, all parties will agree that when they measure the speed of that phenomenon in any frame of reference, it always comes out to be the same number, 2.998 times 10 to the 8th meters per second, at least in empty space. Now, the history of the speed of light is interesting, and it can be cherry-picked through to take a look at what people try to do to measure the speed of this phenomenon, because it is ridiculously fast. Now, Galileo Galilei famously claims to have attempted to measure the speed of light by uncovering a lantern, having an assistant on a distant hill who, in response to seeing the light from Galileo's lantern, then uncovers one of their own, and then Galileo, upon seeing the assistant's lantern light, records the time for the round trip, taking into account human reaction time. It turns out, of course, that light moves way too fast for this to work with 17th century technology, even if Galileo used the most precise clocks of his day, which he had invented, water clocks. There's no way that, even given 40, 50, or 60 miles of distance between him and his assistant, that technology would have been sufficient, especially with really slow human reaction times, to, in fact, measure the speed of light. So this was kind of a lost cause, but a clever technique nonetheless, and one which can successfully be used to measure the speed of sound. Another important person in the story of the measurement of the speed of light is Ole Romer. Now, he would go on to use the period, that is, the time it takes to complete one cycle, of Jupiter's moon Io, which had been discovered by Galileo using the telescope. And by looking at its cycle of eclipses by Jupiter, to then make the first reasonable determination that light travels in finite time. He did this in about 1676. Revisiting his data in a modern context suggests he shouldn't have been as accurate as he was in measuring the speed of light, but he actually got fairly close to the currently accepted value, certainly impressive for its time, impressively close to the currently accepted value of the speed of light. But one could definitively conclude from his work that light does not travel instantaneously from place to place. Rather, it takes a finite amount of time to cross space, even if it does so very quickly. Now, by the time of Albert Einstein's publications, the speed of light had been established by multiple experimental methods to be within about 50 kilometers per second of the precision of today's methods. And that is remarkable for such a large number, representing such an incredibly high speed. So let's then take a look at the modern speed of light and the number that is the currently accepted calibrated value of this speed today. And I say that because the definition of things like the meter are based on the distance that light travels in a certain amount of time. So based on the current definition of the meter and the second, the speed of light is defined to be exactly 299,792,458 meters per second, or about 2.998 times 10 to the 8th meters per second. A good rule of thumb, something that will aid you whether you're thinking about how long signals will take to propagate in electronics, or if you're thinking about how long it will take for a light signal to propagate across some space for a communications system or something like that. A good rule of thumb is that light travels roughly 1 foot in 1 billionth of a second. That is, it goes 1 foot per nanosecond. That's a handy little thing to remember for engineering purposes going forward. Now, let's begin to look at the consequences of the postulates of special relativity. And I say special because there's a more general theory of relativity, a more general theory of space and time that Einstein would spend another decade working out after 1905. What makes the early theory of space and time that he developed special is that it focused on what are called inertial frames of reference, those in which there are no net unbalanced forces. Now, that doesn't mean that accelerations can't be present, but it is a special case of a more general theory of reference frames, space, and time. Now, under this special condition, an object in motion will appear to all observers in all frames to have a constant velocity, even if observers in different frames disagree on the magnitude and direction of the vector. So let's recall his postulates again in light of this special condition for the frames of reference that we're talking about here. Postulate 1 is that the forms of the laws of physics are the same for all observers, regardless of their state of relative motion. That is, regardless of the frame of reference in which they find themselves. And we've looked at the definition of the terminology frame of reference. The second postulate is that the speed of light is the same for all observers, regardless of their frame of reference. All observers, no matter their relative state of motion, when they measure the propagation speed of light signals, will always find, and this is based on experimental observation, that light travels at the same speed in every frame of reference, even if that frame of reference is moving with respect to the source of the light. This is taken to be the thing that is invariant from one frame of reference to another frame of reference. Not time, the speed of light. Now, let's look at some of the consequences from these postulates, starting with the first postulate. So the consequences of the first postulate are both straightforward and a little surprising. So one of the conclusions you can draw from the first postulate, assuming that it's true, is that all physical laws, like Newton's laws or Maxwell's equations, will all have the same observed form in all inertial reference frames. Now, this is pretty helpful, actually, because what it means is that regardless of our relative states of motion, the basic laws of physics that we can uncover by doing experiments, observations of the natural world, are not dependent on your current state of motion. The moon goes around the Earth, so from our perspective, the moon appears to be moving. But the law of gravity has been tested on the moon by dropping objects there. We see no difference between the law of gravity on the moon and the law of gravity on the Earth, despite the fact that we are definitely in relative motion to one another. This has been tested more precisely than just dropping things on the moon, but the basic conclusion is that this postulate holds, and as a consequence of that, basic laws of physics can be determined regardless of what your state of motion actually is. But this consequence has a flip side. It's impossible, based on determining the laws of physics by making observations in your frame of reference, to determine whether or not you are actually in motion. The analogy I like to make for this one is being a little sleepy on a train. If you've ever been on a light rail car or a real passenger train, you've been a little tired, you're sitting on the car waiting at the station for the train to leave, and another train is parked next to you, you might doze off for a moment while sitting there looking at the other train. And then you might wake up, and during the time when you were slightly unconscious, your train began to move. With ever so slight an acceleration, you started to gain some velocity. And so when you wake up, you've missed the fact that there was an acceleration in your frame of reference that caused you to start moving. And you might look out the window and see the train next to you moving past you and draw the conclusion that the other train is pulling out of the station. You conclude, therefore, that you're in the rest frame with respect to the Earth. Your train is standing still because you feel no forces, and the train next to you is moving. But then suddenly you reach the end of the train next to you, and you realize that your train is the one moving with respect to the ground, and that other train was sitting still the whole time. You had no way of knowing that you were actually the frame in motion with respect to the Earth, because there were no cues. And there's no experiment you could have done in that 30 seconds while you're passing the other train that would have definitively told you you were moving and the other train was not, or that the other train was moving and you were not. And that's one of the consequences of the first postulate. There's no way to measure even the most fundamental statements about nature, the laws of nature, and figure out that you are moving and not something else. So as a result of this postulate, it has to be concluded that there is no such thing as an absolute state of rest or an absolute state of motion. All motion is relative. All motion in nature is relative to a reference point. You have to pick what that reference point is, and depending which one you pick, may change the degree of your state of motion or the state of motion of the other frame of reference. All motion is relative as a consequence of this postulate. There is no experiment that could be done if this postulate holds forever that would tell you that you were moving and something else wasn't, or vice versa. Now let's look at the consequences of the second postulate. The speed of light is the same for all observers regardless of their frame of reference. Now, the consequences of the second postulate are typically more surprising to a general audience of individuals who start really thinking about this for the first time on their own. And these conclusions tend to put most people well outside the comfort zone of typical human experience. So let's take a look at these. So all observers agree that light moves at a fixed speed. This is a singular invariant independent of states of relative motion. Now that's already a bit freaky in the sense that you could be driving in a car at 70 miles an hour and switch on your headlights, and somebody on the side of the road, standing still with respect to the earth, measures the speed with which the light from your headlights passes them. And they measure 2.998 times 10 to the 8th meters per second. Exactly. Not 70 miles per hour faster. Exactly the speed that it would travel in empty space if it were emitted from rest. And you, in your frame of reference, could get out on your hood and do some very careful experiment to measure how fast light is moving when it's emitted from your headlamps. And you would draw the same conclusion, that the speed of the light is exactly that number from a few slides ago. Even though the person on the ground sees you and the source of your light as moving, they still measure the same speed of light you measure. That is freaky, that somehow light is immune to a state of motion of the emitting source, but that is an observational fact. It may be freaky, but it's also reality, and that means you need to rethink the universe at a fundamental level, particularly rethink space and rethink time. And so as a consequence of this observational fact of nature, the belief that humans typically hold that, say, time or space or both are experienced in the same way by observers in different states of motion has to be completely abandoned. If we are to hold the speed of light constant in all frames of reference, you have to abandon the absolute nature of, for instance, time. Time passing will be experienced differently by observers in different frames of reference. So as a result of this postulate, there's just no such thing as an absolute measure of time or an absolute measure of space. I mean, we already have to abandon the notion of an absolute frame of reference in space from the first postulate. But in the second postulate, we also find that we can't hold on to this seemingly intuitive belief that time passes at the same rate for all people regardless of their state of motion. Measurements in one frame of reference regarding space and time distances need not agree with measurements in a different frame of reference. But all observers will agree that light signals travel at a specific and fixed speed, independent of the relative states of motion. So really, special relativity is not so much a theory of what is relative. It's a theory of what is invariant between observers in different frames of reference. And it allows us to define a mathematical framework to figure out how to relate our observations. So let's take a look at the relative nature of time briefly, using a variation on Einstein's thought experiment, or as he called them, Gedanken experiments. Gedanken from the German for thoughtful or mindful. What freed Einstein to write down the postulates, ultimately, of what we now call special relativity was his ability to be able to abandon Newton's old idea of absolute time. That is, time that passes the same way for all observers, regardless of their state of motion. It was this thing that was really a key moment for Einstein of insight, a moment when he he relates that the dam kind of broke at that moment in his mind, and he was freed to draw the conclusions that ultimately led down the correct path to the correct description of nature. So let's take a look at a variation on the Gedanken experiment that he felt liberated him from the sort of tyranny of absolute time that had been passed down through the generations as an assumption that turned out not to be true. So while riding on a streetcar in Bern, Switzerland, where he worked as a patent clerk, Einstein began to think more carefully about what it meant to know the time by observing the clock tower. So shown here on the right-hand side of the slide is a picture of the Bern clock tower. And here you can see the tram lines in the street that likely carried the streetcar on which he was riding at the time when he finally had one of his moments of insight into this question. What does it mean to know the time by observing the clock tower? Well, we're going to do a modern version of his thought experiment because analog clocks are not as common as they were in his day. Time is the measure of distance, if you want to think about it that way, between events that occur, for example, at the same spatial coordinates. So imagine not an analog clock on the face of this clock tower, but rather a large blinking light. And when the light is on, that marks a moment of time. It's an event. It has a location in space and a location in time. And then the light goes out, and then it comes back on later in the same position in space. The gap between the two blinks is what we refer to as a duration of time. And we could use that gap between these regular blinks of the light to define a standard unit of time, whatever we choose that to be, the second, for instance. Now, Einstein realized that the way you know that time is passing is you see these two events. But to see these two events, you need to receive light from the blinking light. And light has to travel through space. So if you're on the streetcar and the streetcar is moving away from the clock tower, the light from the clock tower has to travel from the tower to your eyes. So you see the blink after it's actually occurred, but in your frame of reference, in the streetcar, it's the arrival of the light that tells you that a moment in time, an event, has occurred. And then you wait for the next blink to occur. But by then the streetcar's moved a little further away, so the light has to travel a little bit further, and that takes a little bit longer. And so in your frame of reference in the streetcar, time appears to be slowing down. And this is just using a Newtonian view of the universe. I haven't even invoked the postulates of special relativity here. This is just the simple fact that light has to travel across a distance, and it does so in finite time. And the time intervals are stretched by moving away from the clock tower, because light has to catch up to you. So even in Newton's view of the universe, time measurements cannot be absolute as a result of this. So imagine two observers that are using a blinking light to measure time. They agree that the blinking of this light is how they will define their standard time units. Now, one of the observers is at rest on the ground with respect to the source of the light, maybe standing right next to the blinking light. And the other is on a super train that's racing away from the light source, and it's doing so at a ridiculous speed, half the speed of light. So the two observers agree to count how many blinks occur while the super train makes a journey of 2 million miles. Now, I chose that because this is about how far light can travel in 10 seconds. Now, on the ground, the observer at rest with respect to the blinking light counts 10 blinks during the journey, each blink being 1 second apart. But for the observer in motion, not all of those 10 blinks will have had time to reach the super train by the time it arrives at its agreed upon destination. It will have marked off fewer observed blinks from the light. And thus, an observer on the train would rightly claim that less time was required than the 10 blinks that the person on the ground saw to make the journey. Two observers disagree on how much time has passed using a common reference point. So even in Newton's view of space and time, the notion of an absolute time measurement is just not correct. Now, this thought experiment is essentially based on an optical effect. You could even say it's based on an optical illusion, the transit time of light through space. But nonetheless, because it already, using a Newtonian view of the universe, disproves that there is such a thing as a notion of an absolute unit of time that passes the same way for everybody, this completely then frees a thinker from abandoning the concept of absolute time as a necessary tenet of reality. So, the speed of light is the same for all observers regardless of their frame of reference. And since space and time displacements are not experienced the same in frames with different relative states of motion, even based on this optical illusion-based thought experiment, observers at rest, looking at an object in a frame of reference that's moving with respect to them, will observe that that object is contracted in length along the direction of motion. Now, we will firmly see that when we explore the lorentz transformation for relating observations in one frame to observations in another frame. But already you could have concluded that since it's the speed of light that remains fixed, not time or something else, that you're going to have to give something in this process. And what you find out from all of this is that objects in motion, from the perspective of people who are in the frame that's agreed upon as being the rest frame, will be observed to shorten along their direction of motion. This is known as length contraction. So hang on to that phrase because it will come up over and over and over again. It refers to this phenomenon of spatial measurements from the perspective of observers at rest looking at the moving frame, getting contracted in the moving frame. Now, observers in motion relative to other observers will also experience a slower passage of time. It's not an optical illusion that you need to use to explain this. It's a physical change in the experience of time itself. No optics required to explain the phenomenon. It simply is a behavior of time that for objects in motion relative to other observers, if they stop moving and then compare their clocks to people on the ground, they'll find out that they have experienced less passage of time than their colleagues who remained in what was agreed upon to be the original rest frame. This is known as time dilation, that time slows down in a moving reference frame relative to a frame that's at rest. Now, it will be a lot easier to appreciate the degree of these consequences as we actually explore the postulates of relativity in class, and then in the next section of this class, look directly at the Lorentz transformation, which is the correct way to relate observations between frames of reference. So I want you to get these notions of terminology down. You don't necessarily have to agree that this is what happens right now, because I have done no math to prove to you that this is possible, and I've certainly shown you no experimental results to tell you that this is what happens. But for now, look at the terminology and understand what a length contraction or a time dilation is, so that we can carry that terminology forward with us. So to review what we have done in this lecture, we have learned about the following things. We've learned about the transition in thinking that led from Galilean relativity to the special theory of relativity in 1905. We've learned about the postulates of special relativity, which are the basis of the mathematics of the framework. And further, we've started looking at the consequences of those postulates, from the fact that it's impossible to tell from looking at the laws of physics in different reference frames that a given frame is in motion relative to any other. All motion is therefore relative. And also that different observers in different frames of reference, while they'll all agree that light moves at the same fixed speed regardless of their relative states of motion, they will disagree on the lengths of objects and the durations of time that are passing in different frames. These consequences will carry forward into the next section of the course, a discussion of the Lorentz transformation, and preview the conclusions that we'll draw from the correct mathematics that relates observations from one frame of reference to another frame of reference. In this lecture, we will learn to appreciate the Galilean transformation and its built-in assumptions. a decent understanding of the past will help us to set the stage for the present. We'll learn a way to derive the form of the correct transformation between frames of reference, respecting the postulates of special relativity. And we'll learn how to begin applying this transformation and see that it is in fact consistent with the postulates of special relativity. It does end up being entirely self-consistent, and it gives us a basis for making predictions about the natural world, predictions that can be tested. The Galilean transformation was predicated on two assumptions, and these assumptions may not have been made very clear when you originally learned about this transformation. For observers in inertial frames of reference, that is, frames of reference in which all observers agree that objects in motion are moving at constant velocities, time is assumed to pass in the same way for all observers regardless of their state of motion, and all observers agree that objects in each other's frames are in states of constant motion. And I've drawn down here an example graphic of a representation of an object in motion with some velocity vector illustrated here that I'll use in a lot of the images going forward that will help us to think about these transformations. Now let's define two frames of reference that we can use as the archetypes for thinking about transformations of space and time information from one frame to another. Let's denote one of these as frame S, and we will always take frame S to be the thing that we call the rest frame. Now, this is an arbitrary assignment. You can choose one thing to be at rest and not another, or vice versa, but once you make that choice, you need to stick with your choice. You need to see that through to the bitter end. So, for the purposes of illustrating the process of thinking about transformations of space and time information from frame to frame, we'll always take S to be the frame that is not in motion. Now, in this frame of reference S, we will imagine that they carry along with them a coordinate system, like a framework of three lines that are at right angles to each other, that they'll use as reference markers for all spatial measurements. And the coordinates from their Cartesian coordinate system will be denoted x, y, and z. When they describe object velocities, they'll notate them as using the letter u. The letter v for velocity, as you'll see in a moment, has a special place in relativity calculations, and so to avoid confusing us as to what velocities we're talking about, we will use u to denote object velocities. Now, we will define a second frame, s with a little prime symbol next to it, or s prime, that is moving relative to frame S at a velocity v. So everything in that frame is moving all at once in the same direction at the same speed, relative to S. And in that frame, they too have a little framework, a little Cartesian coordinate system framework of x, y, and z. But they label their coordinates x prime, y prime, and z prime. And when they measure object velocities, they denote them as u prime, to be consistent with the notation of their coordinate system. Now, we will do the following to simplify our thought process going forward. It doesn't have to be this way, but we can set the problem up this way to make it easier for ourselves. We will assume that they have arranged their coordinate axes so that they are always parallel to each other. X is always parallel to x prime, even if x prime is moving relative to x. Y is parallel to y prime, z is parallel to z prime. This makes it easier for us mathematically to relate things between the frames. We can't allow chaos to reign in all of this. And we're going to further simplify, for the purposes of our discussion here, that frame S prime has a velocity v that is entirely and only along either x or x prime. It's entirely parallel to x and x prime and has no component along y, y prime, z, or z prime. Now, in the Galilean picture of things, in all frames, time is absolute, so that t is equal to t prime. The time measured in one frame, frame S, is equal to the time measured in another frame, frame S prime, always. That is the definition of absolute time. Now, I've recovered the picture of our two little frames of reference here and our blue object in motion, viewed from the perspective perhaps of one or the other frame with its velocity u or u prime. Now, this picture, built from the postulates of the Galilean or Newtonian approach to space and time, then allows us to define the equations transforming observations in one frame to observations in another frame. For instance, if we measure x prime and t prime and u prime in frame s prime, these equations will allow us to figure out what the people in frame s would see. And here are the equations. You've probably seen them in this form or a similar form in introductory physics. Because the motion of frame s prime is entirely and only parallel to x and x prime, there's a transformation between the x and x prime coordinate system that is given by the first equation. Measurements in y are equal to measurements in y prime, and measurements in z are equal to measurements in z prime. And of course, because of absolute time, t is equal to t prime. Now, object velocities are related between the frames using the velocity transformation equation, which, if you use calculus, and I would invite you to do this as a simple exercise, you can prove from the first of the equations up here, x equals x prime plus vt. You can prove that this equation is the addition of velocities derivable from the coordinate transforms using a little bit of calculus and a few minutes of work on paper. But basically, the velocity observed for an object in frame S is equal to its velocity in frame S prime plus v, the velocity of frame S prime with respect to S. Now, there's a problem here. We know that the postulates of special relativity are more compatible with reality than the assumptions that were made to define the Galilean transformation in the first place. And if you play around with a Galilean transformation, you can pretty quickly find out that it violates the postulates of special relativity. So, for example, and this can be left as an exercise for the student, especially because Maxwell's equations are not something you get rigorous training on in introductory physics, you can show that Maxwell's equations, their forms, are not invariant under a Galilean transformation. That would violate the first postulate of special relativity. Because if Maxwell's equations have different forms that can be determined by experiment in different frames of reference, that implies that it's then possible to know whether or not you're in the absolute rest frame, for instance, in the mechanical view of the universe, in the frame of the ether. It's a bit easier to see how the second postulate is violated by using a simple example. You can imagine that the object in motion on the previous slides is a beam of light, and it's been emitted in the ether frame, which we'll take to be frame S, the absolute rest frame. And what you'll find then is that that beam of light will have a very different speed in all other frames moving with respect to the ether frame, the absolute rest frame, or frame S in our notation here. That violates the second postulate, that the speed of light must be observed to be the same by all observers, regardless of their relative states of motion. So already the Galilean transformation is immediately shown to be at odds with the postulates of special relativity, which again are based on observational evidence. So here's our picture again of these two inertial reference frames with a blue object being studied by both of the observers in each of the reference frames, S and S prime. And we want to find a transformation of X and X prime, Y and Y prime, V, U and U prime, and T prime between these frames that gets something that's compatible with the postulates of special relativity. And we don't have to change this picture to build up the correct transformation. We just have to apply the postulates of special relativity in constructing the transformation from one frame to the other. And these new postulates, the postulates of special relativity, will enable us to arrive at a mathematics that's consistent with observation. So our goal is to figure out what is the correct transformation. And we will continue to work with frames of reference wherein object velocities are observed to be constant. That is, inertial frames of reference. That puts the special in special relativity. Now, it must be true that in two inertial reference frames, S and S prime, as depicted in the cartoon above, that because the object in motion will be observed in either frame to have a constant velocity, maybe a different magnitude, but both frames of reference will agree, yes, we have each observed a constant velocity for the object that we're studying. It must therefore be true that x in the frame S is equal to the object velocity times time if it's moving entirely along the x direction. And in the moving frame S prime, it must be true that x prime is related to t prime by the observed velocity of the object in that frame, u prime. In order to further satisfy the first postulate of special relativity, it must also be true that the transformation equations represent a linear transformation between the frames. Otherwise, it can't be true that all frames observe object velocities to be constant. And let me demonstrate this. It's important, I think, to start exercising your calculus a little bit at this stage in the class so that you get a bit more comfortable with using calculus as a means to make predictions about the natural world. So let's begin by assuming an extremely generic form for the transformation between spatial coordinates in frame S and space and time coordinates in frame S prime. I've assumed that x is given by some unknown transformation with a spatial term and a temporal term. Each of these has coefficients, I'll talk about those more in a moment, and each of the coordinates in the moving frame is raised to some unknown power. For space it's n, and for time it's m. And similarly, the time coordinate in frame S is related to the space and time coordinates in frame S prime. In the same way, there's some new coefficients, c and d, that enter in here, but again, I've raised x prime and t prime to various powers. They could be 2, could be 10, could be 20, we don't know. Now, let me comment on these coefficients. A, b, c, and d are constants here. We could always absorb some non-constant behavior in the coefficients into the function of x prime or t prime that we're using here. Now, I've used a simple function just raising the space and time coordinates to a single power, but you can draw the conclusion more generally that an arbitrary polynomial of x prime and t prime also won't work to satisfy the requirement that all observers agree that the object's moving at a constant velocity regardless of their frame of reference in inertial reference frames. So here's my generic pair of transformation equations. I don't know what a, b, c, and d are, and I don't know what n and m are. But what I can do is I can recall that any velocity, any object velocity, like, the object velocity along the x direction in frame S, ux, or the object velocity along the x prime axis in frame S prime, so u prime x, is defined by a derivative with respect to time. That is, ux is dx dt, or u prime x is dx prime dt prime. That's the definition of a velocity from its most foundational aspects. So what I would like to do to motivate that this has to be a linear transformation between the frames is to simply take the above equations and turn them into statements about differentials of x and x prime and t, rather than just statements about the coordinates themselves. So this is where you can dust off your calculus and see if you can arrive at the same answer that I get here. But the bottom line is that the differential of x is related to differentials in x prime and t prime by this equation. So the coefficients a and b remain unscathed. But you wind up with this new power of x prime and t prime due to transforming this into a statement about differentials in space and time rather than just about space and time themselves. And then similarly, you get an equation that looks very much like that for dt, differentials in time in the frame S as well. Okay, so let's hold those equations here for a moment and consider them. So what I would like to do now is use these equations to relate the observed velocities in each frame of reference. And so to do that, I'm just going to take the ratio of the above two equations. Why? Because when I do that, I get dx divided by dt, which on the left side is just the definition of the velocity of the object in frame S, ux. And on the right side, I get something that's a fair bit nastier than that, but we will simplify it into something that looks a bit more familiar in a moment. So notice that I have dx prime and dt prime both in the numerator and in the denominator of this ratio. So what I can do next is I can divide the top and the bottom of the right-hand side by dt prime. Doing so eliminates dt prime from the right-hand terms in each part of the ratio and creates a dx prime dt prime in the left term of each part of the ratio. And that should look very familiar because dx prime dt prime is, by definition, the velocity of the object in the prime frame, in the s prime frame. And so we arrive at this final relationship that relates the observed velocity of the object in frame s prime to the observed velocity in frame s. But there's a problem here. Unless n equals m equals 1, the above equation will always leave a lingering space and time functional dependence on the right-hand side, which violates the first postulate of special relativity. The speed observed in frame s, even if the speed in frame s prime is constant, will not be observed to be constant because it will depend on where in frame s prime the object is at any given moment. It will have a space and time dependence that is rather nonlinear. And so we're forced to conclude that in order to be compatible with the basic idea that we're looking at inertial reference frames and relating object velocities in inertial frames of reference where there are no net forces that can cause changes in the state of motion of the object, we're really forced to choose a linear transformation from frame to frame. Now, that's what we had in the Galilean transformation, but we are still stuck with it even here in special relativity. That's a good thing because it vastly simplifies the mathematics. Okay, so we're going to now begin to build up the mathematics of the transformation. Now that we've accepted that we need a linear transformation from frame s prime to frame s, for example, we get a very simplified pair of equations. X equals ax prime plus bt prime, and t equals cx prime plus dt prime. But we don't know what these coefficients are. They may be trivial, they may be zeros or ones, but we need to figure it out. So now that we've established the linearity of the transformation, we need to nail down A, B, C, and D. So we need to think of some special limiting cases of this picture where we can isolate these constants, maybe one at a time or in small batches, and in doing so figure out what they are in order to be compatible with the postulates of special relativity. Now, this is a standard trick in algebra. We have 4 unknowns and 2 equations. We're going to need 4 special cases to solve for all the unknowns, and the postulates give us the framework to define those special cases. So let's pick special case number 1, where we take the moving object, the blue ball, and we pin it to the origin of the coordinate system of frame s prime. So in frame s prime, the object will always be located at 0, 0, 0 in the x prime, y prime, z prime coordinate system. It's moving along at the same speed as the frame itself, and so it's observed to be at rest in frame s prime. In frame s, however, what we see is we see the blue ball pinned to the coordinate system of this frame, and they're all moving together at a velocity v to the right along the x-axis. So in frame s, it's observed that the object is moving at v. So u equals v in frame s. Now, when we do this, we have a simplifying situation for x prime. X prime will always be 0 because this thing is pinned to the origin of frame s prime. And so we can simplify the above equations to the following. We have now that x is just equal to bt prime in this special case. T is just equal to dt prime in this special case. And then the velocities, x equal ut and 0 equal u prime t prime, are the resulting equations from this special case. So let's take the first 2 equations, the one for x and the one for t, and divide them. And then let's use the third equation, x equals ut, as a substitution to eliminate one of the unknowns. So when we do this, we wind up with x divided by t is equal to b over d. Go ahead and check this yourself. And then from the velocity equation, we get that x over t is equal to u. But in this special case, the object speed is also the frame speed, v. So we wind up with x over t equals v. And as a consequence of that, we get the first constraint on our coefficients. Whatever b and d are, their ratio is equal to v, the velocity of frame s prime. Now let's choose a second special case. And you might have guessed that this would be the next thing that we would do. We pin the blue object to the origin of the rest frame coordinate system. We put it at 0, 0, 0 in frame S. So x, y, and z are 0, 0, and 0. And now we observe that blue object from frame S prime. Now from the perspective of frame S prime, which is moving to the right at speed v, the blue object appears to be falling further and further behind their frame. Its velocity appears to be negative v from the perspective of an observer in frame S prime, the moving frame. So with that in mind, and fixing x to 0 in the general equations up here on the right, we can simplify the equation set to the following. 0 equals ax prime plus bt prime. The t equation doesn't get affected by any of these choices. We wind up with 0 equals ut, and x prime equals negative vt prime, substituting in for u prime with negative v. Now, let's employ the first and third equations, namely this simplified first equation for the coordinate x, and this x prime equals negative vt equation, to further get the constraint on coefficients. So if we do that, we wind up with the first equation telling us that negative ax prime equals bt prime. That's the consequence of the first equation. From the third equation, we get that x prime is negative vt prime. And if we combine these two things together, we find out that avt prime equals bt prime. Now, t prime entirely drops out of both sides using the substitution, and we find out that v equals b over a. Go ahead and try this yourself. I'm going through this a little bit fast, but of course you can pause this at any time and work through the algebra on your own. And so we arrive at our next batch of constraints. Now, we already knew from the first special case that v equals b over d. From the second special case, we also find out that v equals b over a. And if these two constraints are simultaneously true, then it must be true that a equals d. So now we have really constrained ourselves down. So here's the third case we'll look at. What if the object is a beam of light? Now, this is the first time that we will definitively deploy one of the postulates of special relativity, specifically the second postulate. Because if the object that's observed to be moving in both frames of reference is a beam of light, then by the second postulate of special relativity, observers in both frames must observe the velocity of the object to be exactly c, 2.998 times 10 to the 8th meters per second, regardless of their relative motion. So what happens to our equations as a result of this fact that, according to observations and encoded in the second postulate, all observers observe that the beam of light moves at the same speed regardless of their state of relative motion? The equations simplify as follows. The first two don't really change at all, but because the last two are statements about velocity and their relationship to space and time measurements, it must be true that x equals ct, but also x prime equals ct prime when the object in motion is a beam of light. So let's combine the first two equations, the x and t equations, and substitute using the information from the third equation at the bottom. And when we do that, this one gets a little nasty at first. We wind up with x divided by t equals this horrible ratio over here, not looking very promising so far, but x over t is just c by the third equation. And if we divide the top and bottom of the ratio on the right-hand side by t prime, we wind up with x prime over t prime in both the numerator and the denominator. And x prime divided by t prime is just c, the speed of light. So we wind up with the speed of light here, the speed of light here, and the speed of light here. And now what we can further do is take the previous constraints relating b and d and a, we can substitute those in and go through a simplification process. And when we do that, we find out that c is equal to b over the speed of light squared. And we finally arrive at c equals a times the velocity of frame s prime relative to s over the speed of light squared. So all of our constraints allow us to eliminate b, eliminate c, and eliminate d from the equations up here in the top right of the screen. b is equal to av, c is equal to a times v over the speed of light squared, and d is just equal to a itself. So what we have done now with special case 1, 2, and 3 is we've eliminated 3 of the unknown coefficients in favor of the fourth, a. And all we have to do is come up with one more constraint that allows us to figure out what a is. Well, here's our last case. And the last case is a basic assumption about the transformations. First of all, we chose that the transformation of x and t to x prime and t prime from the perspective of observations in frame s prime being mapped onto observations in frame s have a certain form. But because it shouldn't matter which frame we pick to be the one that's at rest and the one that's in motion, we should get the same transformation equations if we had started with frame s prime being at rest and having frame s be the one that was in motion. And the only thing that should change between observations in frame s and observations in frame s prime is that the relative velocity of the two frames changes sign. That's the only thing that should change when you alter the perspective of which one is at rest and which one is in motion. And so as a consequence of that, we should be able to eliminate the unknown a and figure out what it actually is. So let's start by writing down x and t in terms of the coefficient a and all the other things we've already sorted out. So I've effectively just copied these two equations down here. Next, let's rearrange and rewrite these equations not as solutions for x and t, but solutions for x prime and t prime, as if we were trying to figure out what the person in frame s prime would have seen if frame s was chosen to be the frame that was in motion. Now, a lot of algebra is involved in this, and I will leave it as an exercise to the viewer to try this out, to practice their chops at algebraic manipulation in order to get what we want. But the bottom line is that if you work this through, you will find out that x prime is given by this nasty function of x and t prime is given by this equally nasty function of x and t. Now, these equations tell us what should have been observed in frame s prime, given observations in frame s, treating frame s as if it had been the frame in motion, and frame s prime as if it had been the frame at rest. But all that should change when switching perspectives on the problem like this is you should get the same equation, differing only by a minus sign on any term with v in it. Then we're forced to say that a is equal to 1 over a times the quantity 1 minus v squared over c squared to the minus 1. And if you rearrange now and solve for a, you find out that a must be equal to 1 over the square root of 1 minus v squared over c squared, this quantity shown here. Now this may not look pretty, but this strange thing, 1 over the square root of 1 minus v squared over c squared, shows up all over the place in special relativity calculations. And so it's given a special name. We don't leave this as coefficient a. It gets the symbol gamma, the lowercase Greek letter gamma, shown here in the lower right. Gamma is defined to be this strange beast here, 1 over the square root of 1 minus v squared over c squared. So let's take a look at the final form of the Lorentz transformation, the mathematical transformation that obeys all the postulates of special relativity. If we are making observations in frame s prime and relating them to frame s, which is taken to be at rest, then these equations here tell us what we want to know. We measure things in frame s prime and we get x prime and t prime, and then we combine them using these equations to get x and t, the observations that should be made in frame s. If, on the other hand, we're making observations in frame s and want to convert them to observations in frame s prime, we flip the sign of v and change all the coordinates around, and we get basically equations that look the same up to a minus sign on terms that just have v in front of them. This number, gamma, always lurks out in front of everything. And we see here another interesting thing that's going on. We see that in transforming space and time from one frame to another, the space and time measurements in one frame get tangled up to compose the space and time measurements in the other frame. In a sense, space and time in special relativity are not separate entities. We treat them as separate in introductory physics, But the lesson of special relativity is that we should have been thinking of this all as one framework, space-time, not separate frameworks of space and time, this entire time. Now, this multiplicative factor gamma depends on the relative velocity of the two frames. And as you'll see, it's effectively a measure of the degree of the relativistic effects, how much you need to take into account special relativity to solve a problem correctly between two frames of reference. And again, it's given by this funny combination of velocity of the frames relative to each other and the speed of light, 1 over the square root of the quantity 1 minus v squared over c squared. So let's build a little bit of intuition about the meaning of the gamma factor. It appears everywhere in relativity calculations, at least in special relativity. It gets absorbed into other things in what is known as general relativity, the general theory of space and time, which we will only cover in the most shallow way in this course. It's largely unavoidable for all of the physics calculations you're going to do going forward. So let's try to understand it a little bit better. And to do that, I think we can build some intuition by playing around with the quantity gamma at various limits of its observable nature. So for instance, what is gamma for a frame S prime that's at rest with respect to frame S? Well, we would expect to find that the two frames are the same, since they are then in the same state of motion. Well, we already know that if frame S prime has a velocity of 0 with respect to frame S, that the terms with vt in front of them will vanish. But what happens to gamma? Well, if you plug in 0 for v in the function gamma, you find out that indeed for v equals 0, we observe that gamma is 1. In other words, the multiplicative factor in front of either the space or the time coordinates when relating those to space and time coordinates in frame S all become coefficients of 1. In other words, you're in the same frame, so you should get the same space and time measurements. That's good. That's what we would hope would happen. Now, on the other hand, what is gamma for a frame S prime that achieves a velocity of exactly c, the speed of light, relative to S? So this would be like imagining a frame of reference that's pinned to a beam of light moving at the speed of light. And it's another very weird special case. And it's weird because what happens is that the gamma function takes on its biggest possible value, infinity. You wind up with 1 over the square root of the quantity 1 minus c squared over c squared. Well, c squared over c squared is just 1. So you wind up with 1 over the square root of 1 minus 1, which is 1 over 0, which is infinity. 0 goes into 1 an infinite number of times. So that's the upper limit for gamma. So far as we know, it's impossible to travel faster than the speed of light. There's no observational evidence that anything does travel faster than the speed of light. And so we are led to believe, and special relativity encodes this, that the fastest speed in the universe is that of light. And so gamma takes this special value of infinity at that speed. So as we can see, gamma is a frame velocity dependent number, and it has a well-defined range. At the low end, its smallest value it can take is 1, and at the high end, the largest value it can take is infinity. And it can take all numbers in between that depending on what v is. I think it's useful to graph this, albeit perhaps in a way that's not terribly familiar to you. This is a plot of the value of gamma, so the so-called gamma factor, on the y-axis, as a function of the frame relative velocity v on the x-axis. And so you can see here that I have chopped off the low end of the x-axis at about 10% the speed of light. Why? Because gamma has a value that's so close to 1 that, generally speaking, you don't have to worry about it being different from 1. Now, that's not true in all cases, and we'll look at some of those cases going forward in the class. But generally speaking, if you are at about 10% or less the speed of light, you do not expect to really observe what are called relativistic effects. That is, effects that distinguish an observation from what you expected from Galilean or Newtonian relativity. Above 10% of the speed of light, however, gamma can begin to take values that are appreciably distinct from 1. And you can see here that when you get to values that are about half the speed of light, which occurs roughly here on this graph, this is 1 times 10 to the 8th, this is 2 times 10 to the 8th, so this is about 1.5 times 10 to the 8th right here. And as a result of that, you can see we've now appreciably started getting gamma factors that are above 1 by about 20% or so. When we get to about 2/3 the speed of light, 2 times 10 to the 8th meters per second, we've achieved gamma factors that are about 50% bigger than 1, so 1.5. And as we begin to approach closer and closer and closer to the speed of light, we see that the gamma function takes on increasingly larger and larger and larger and larger values, spiking up to infinity at exactly the speed of light. This plot will help you to understand why it is that we just didn't notice these deviations from the Galilean or Newtonian view of the universe for most of the history of science and humanity. And that is because the laboratory experiments that we were effectively conducting as a species were all done at speeds that were far less than that of light. And so we really never would have noticed these effects to begin with. It was only when we began playing around with light and things that can move very close to the speed of light, like subatomic particles, that we began to get ourselves into trouble with the intuition we had built up on human experience prior to that. But we see now that the postulates of special relativity predict that we should have expected deviations from that Newtonian or Galilean view of time, where time is the constant between all observers. It's not. It's the speed of light. And we can see this effect encoded in the gamma function.
Now, as has been teased in the previous lecture on the basics of special relativity, that is, the postulates and their consequences, this theory of space and time has some consequences that can feel surprising to the average human being. For instance, objects in motion relative to what we consider to be a rest frame, that is, the frame we denote S, will appear contracted along the direction of travel. We can actually show this as a prediction of the Lorentz transformation. Now, that said, to appreciate this particular effect, even from the Lorentz transformation, really requires you to think extremely carefully about what it has ever meant to measure the length of something. I feel that discussion is best saved for class time, as in class time we can get very hands-on with the concept before we start plunging into calculations where the language you would use to describe the recipe for attacking this particular question may not feel very natural, because you haven't really thought about what it means to measure the length of something, especially the length of something that's moving relative to you. So instead, in this lecture, let me concentrate on frames in motion relative to the rest frame S, which will also observe a passage of time that, relative to S, seems slowed. This effect I labeled time dilation, and we're going to formally calculate it now. And finally, I'll also look at events that are simultaneous in one frame and show that that simultaneity is not guaranteed at all in another frame that's moving relative to the first. Let's explore time and simultaneity in this lecture.
So how does one consider the passage of time in different frames of reference? Well, to measure time, we have to define a clock of some kind, a regular pattern of events that all happen, for instance, at the same reference point in a frame. So consider a clock that's at rest in frame S prime, and it provides regular information. So, for instance, pulses of light at different times, T1 prime, T2 prime, T3 prime, and so forth, always with regular intervals between them. But that clock is always pulsing at the same position, x prime. So x1 prime equals x2 prime equals x3 prime whenever the time measurements are established. And what we want to know is, what's the time between the pulses observed in the rest frame? So that clock is in a frame that's moving with respect to a frame that we agree is at rest. We call it to be the rest frame. What does an observer in the rest frame observe the time to do in the moving frame? Well, again, you want to relate time observations between the two frames, but to do that you need to use the Lorentz transformation, which takes space and time information from the moving frame and translates it into time information in the rest frame. So we want to take the pulse at T2 and transform its time into what the person in the rest frame measures, their so-called T2. And we want to take the pulse at T1 and transform that into the rest frame's T1. And to do that, we have to use this equation. This comes from the Lorentz transformation. Now, we have a simplifying fact here, and that is that the clock in frame S prime is always pulsing away at the same location. x1 prime equals x2 prime. So if we were to combine these two equations to calculate the duration of time between t2 and t1, we might do the following. We might take t2 minus t1 and try to figure out what that is in terms of t2 prime minus t1 prime. Well, because the clock pulses at the same location in frame S prime, x2 prime and x1 prime terms cancel out. And we're left with this equation, which relates the durations in time observed in the two frames by a gamma factor. And so I can write the two time durations, delta t in frame S, the rest frame, and delta t prime, the time duration in the moving frame, and I can relate them. And they're related, again, by a gamma factor. And I find that if I take the ratio of the time duration observed in the rest frame and the time duration observed in the moving frame, that they will differ. They will not be a ratio of 1, and the ratio, however, will be given by the gamma factor, which takes a value of 1, but only in the special case that the two frames are at rest with respect to each other. At any relative speed greater than that, gamma takes a value that's greater than 1. Now, until you get to very high speeds, it's not appreciably greater than 1, but nonetheless, it's not exactly 1 unless you're at rest with respect to each other. And so that we see now that in a frame that's moving relative to another, durations of time will always observe to be shorter than in the rest frame. The duration of time observed in the rest frame is greater than the duration of time that's observed in the moving frame for the same pair of events. And the degree of dilation of time depends again on the ratio of v over c, specifically through the gamma factor. Time in the moving frame will appear to the rest frame to pass more slowly. Now, another expected effect due to special relativity is that events that are simultaneous in one frame of reference may not necessarily be simultaneous in another. Now, we already explored that a little bit, even under classical velocity situations, but we can revisit that idea here under the Lorentz transformation. So, for instance, consider two events, like pulses of light, which are observed to be simultaneous in frame S prime, the moving frame. The events have coordinates x1 prime t prime and x2 prime t prime. So what is the time between the events observed in the rest frame? Does the rest frame observe that they are also simultaneous, that is, also at exactly the same time? Well, we can start by relating the times in the rest frame to the space and time measurements in the moving frame for t2 and t1. Again, we're just writing down the Lorentz transformation here between observations in frame S prime and the observations we want to establish in frame S. Now, since the events are simultaneous in frame S prime, t1 prime will be equal to t2 prime. So if I now calculate the duration of time that passes in frame S, t2 minus t1, I find a very interesting fact that it's not equal to 0. It's equal to this thing on the right-hand side here, which depends on the velocity of the frames relative to one another, v, quite directly in this case, not just through the gamma factor, but gamma multiplied by v. And what's particularly interesting about this is this question, whether two events are simultaneous in one frame and simultaneous in another frame of reference that's in motion relative to it, really picks at this interesting thing I mentioned earlier, which is that space and time have to be treated as one framework, space-time, and they can get tangled up in each other. And what we see here is that because the events in frame S prime are simultaneous, but not necessarily at the same location in space in frame S prime, this creates a displacement in time between the two events in the rest frame. In other words, delta t in the rest frame is not necessarily equal to 0. It's equal to gamma v over c squared times the spatial displacement of the two events in the moving frame, delta x prime. So we see that in the rest frame, events cannot be observed to be simultaneous, even when they are simultaneous in the moving frame, unless those events happen at exactly the same position in space. That is, x2 prime equals x1 prime. That's a special case. Or unless the two frames are not in relative motion to each other. That is, v equals 0. In that case, of course, the two frames become indistinguishable and the whole discussion was moot to begin with. But if the two frames are not the same frame of reference, if the events occur at different locations in space in one frame but are otherwise simultaneous there, they will not be viewed to be simultaneous in the other frame. Simultaneity of events could have been guaranteed in Galilean relativity, even if they were at different locations in space, because of the absolute passage of time. But since time is not absolute, and special relativity doesn't accept that as one of its postulates, you find out that except under these very special conditions, simultaneity cannot be guaranteed in another frame. And again, this is a really good example of how space and time are not inseparable from one another in special relativity. In transforming observations in space in one frame, you wind up with observations in time in another frame. Space and time get kind of tangled up in each other and going from frame to frame. A spatial separation in S prime becomes a temporal separation in frame S. And I find this to be one of the more remarkable features of space and time as viewed through the lens of special relativity. Now, one last question we can visit in all of this is whether or not it's possible to recover classical physics from this view of the universe. In other words, are the Galilean-Newton view of space and time and relative motion totally gone? Were they totally wrong this whole time? It turns out the answer is not really. After all, the Galilean transformation did work in real computation for centuries before special relativity was needed, right? I mean, people were able to relate observations in different frames of reference at relatively modest speed compared to those of light. So one of the things that should become evident from all of this, and this is a general feature of a good theory of nature, a good predictive description of nature that can be tested and even falsified. A good theory of nature describes all new phenomena, but also it accounts for the existing confirmed observations, the old phenomena that we had all that experience with, from which we built intuition. What generally seems to happen is that when you find out that your current understanding of nature is wrong, you find out eventually through enough observation and experiment and mathematical work the correct description of nature, and you find out that your old observations were correct, but in a more limited regime of nature. In this case, for instance, low velocities. So to recover the Galilean or Newtonian view, we need only slow nature down from speeds close to that of light. Now, for example, we can consider the special case of speeds between the frames of reference that are much less than the speed of light, so that v over c, for instance, becomes a very tiny number, approaching 0. So let's look at what happens to the gamma factor using something called the binomial expansion. Now, I'm going to illustrate the binomial expansion for this specific function here. But in general, there is a general form for the binomial expansion, and you can use a math reference on the web or a paper book to explore the binomial expansion more on your own free time. So let's begin by looking at the gamma function. The gamma function was defined as 1 over the square root of 1 minus the quantity v squared over c squared. So what we have here is we have a function of a number, v squared over c squared, that's bounded between 0 and 1. V over c can either be 0 for v equals 0 or 1 for v equals c. And as a result of that, gamma takes values between 1 and infinity. But this parameter, v over c, that depends on the relative frame speed, that thing is bounded between 0 and 1. Now, one of the things that we can do is we can rewrite this gamma function as a more basic generic-looking function by replacing v over c with a number alpha. Or in other words, rewriting this in terms of alpha squared, which is v squared over c squared, and note that alpha squared is a number that is less than or equal to 1, and its lowest value it can take is 0. So we wind up with this more generic-looking function, 1 minus alpha squared, all raised to the negative 1/2 power. In other words, 1 over the square root of 1 minus alpha squared. Now, if we apply the binomial expansion to this more generic-looking function with this condition on alpha that it's bounded between 0 and 1, then we find that we can rewrite this function as a series expansion. The first term in the series is just the number 1. The second term in the series depends on alpha, and it's plus 1/2 alpha squared. Now, the binomial expansion allows you to keep adding terms that have higher and higher powers of alpha in them. The next one will have a power of alpha to the fourth, the one after that alpha to the sixth, and so forth, with different coefficients in front of them. Now, because alpha is a number that cannot be greater than 1, as a result of that, for the special case that alpha is much, much, much less than 1, in other words, as alpha tends towards 0, we see that indeed we recover the behavior that as these terms with alpha squared, alpha to the fourth, alpha to the sixth, as they approach 0, the only term left that really dominates in the sum is the leading term, 1. And we see that gamma is approximately equal to 1 as alpha gets closer and closer and closer to 0. And when alpha equals 0, we get gamma equals 1, which we know is the limiting case of gamma for velocities of 0 speed. So that makes sense. It's approaching the limiting case when v equals 0. That's what it means for alpha to go to 0. It means v is going to 0 too. So what happens to the Lorentz transformation equations when we replace gamma in it with this binomially expanded version of gamma? So let's start with x equals gamma times the quantity x prime plus vt prime. Let's substitute in the binomial expansion in terms of v over c being equal to alpha. All right, so now we replace gamma with this thing. 1 plus 1/2 alpha squared plus all terms with alpha to the fourth and higher in them. And in the limiting case that v is much, much less than c, that is, as alpha approaches 0, these terms with alpha squared, alpha to the fourth, alpha to the sixth, they contribute less and less and less and less to the sum until we're left with just 1 in front of the sum x prime plus vt prime. So in the special case that the velocity we're considering for the relative motion of the frames is much less than that of the speed of light, we find that we recover x equals x prime plus vt prime, which is the old Galilean relationship between x and x prime and t prime. Now similarly, I can take the equation relating x prime and t prime to time in the rest frame, and I can substitute for the gamma factor using this binomial expansion. I can also notice that there's a v over c lurking here in front of the x prime coordinate. That's another alpha that sits in front of x prime. So if I write that all out, here's the binomial expansion of gamma. Here's that alpha that I've substituted in for the v over c that was lurking in front of x prime. And what you'll notice is if I distribute this gamma to both the terms inside of this sum, that the space term, the x prime term, always has an alpha somewhere in front of it multiplying it. You can't escape it. You don't just get a bare number like 1 multiplying the x prime coordinate. Whereas for the t prime coordinate, there is a term in the expansion that just goes as 1 times t prime. And so in the limit that the velocity is much, much less than the speed of light, all terms with alpha in front of them vanish to 0, and we're left just with t prime. In other words, in the low velocity limit, t is equal to t prime. And we see that we have completely recovered the Galilean transformation, and we've reconciled with classical physics in the limit of low velocities. This is why time appeared to be absolute in the original formulation of mechanics. It's because when the velocities are much lower than the speed of light between two frames of reference, you have a very hard time seeing these extremely subtle effects between clock measurements between the two frames. But that is laid bare as a false perception of nature as you approach the speed of light in relative velocities between two frames of reference. But we see that we can reconcile the old picture of space and time with this modern and correct picture, at least correct as regards observation of the natural world, simply by considering the limit of small velocities compared to that of the speed of light, and we completely recover the old view. The old view is nested inside the modern view as a limiting case. So to review, in this lecture we have learned the following things. We've learned to appreciate the Galilean transformation and the assumptions upon which it's built. We've learned a way to derive the form of the correct transformation between frames of reference, the so-called Lorentz transformation that is the modern way of relating observations in one frame to observations in another frame of reference. And we've begun to see how you start to apply this transformation by asking questions like, what are the events, and in what frame are they defined? And is anything the same for those events? Are space measurements the same? Are time measurements the same? in a given frame of reference to simplify the questions that we're trying to answer and then get the answers out of the Lorentz transformation. And we see that we have arrived not only at a transformation that's consistent with the postulates of special relativity, but which gives us a mathematical formulation for the intuition that we built off of the postulates that distance and time measurements are not going to be the same in different frames of reference, even if all observers agree on the speed of light as a constant of nature. So while we see that all observers must agree that light moves at the same speed regardless of their relative motion, nonetheless observers in different frames of reference will disagree on lengths of objects, the durations of time that pass, and the simultaneity of events. Events simultaneous in one frame will not necessarily be simultaneous in another frame of reference except under very particular conditions. We've also seen how to recover classical physics from special relativity by allowing the velocity of the relative motion of the two frames of reference to drop far below the speed of light so that these corrections from the original Galilean transformation all vanish and leave behind the Galilean transformation with its assumption of absolute time laid bare. And we've seen how in that limit the Lorentz transformation exactly reproduces what were the original assumed relationships between space and time and velocities as encoded in the Galilean transformation. We've recovered the past from the present, and we can continue to use the present to build a foundation for making future predictions. And that is precisely what we're going to do in the next section of the course. In this lecture, we will learn the following things. We will learn what is a muon. We will learn how to use the muon as a laboratory for making predictions with a Lorentz transformation. And finally, we will learn how the muon was the first direct test of the validity of special relativity. Let's begin by reminding ourselves one more time about the Lorentz transformation. If we make observations in a frame S' that we consider to be moving, and we want to convert them into observations in a frame S we consider to be at rest, then the equations in the top left of the slide will do just fine. If, on the other hand, we have observations that are made in the rest frame S and we want to convert them into observations in the moving frame, then all we have to do is change x to x prime, t to t prime, and v to negative v in the upper left equations, and we get the necessary equations in the upper right. This function, gamma, that appears in all of these equations is a function that depends on the relative speed between the two frames, v, and it has the form of 1 over the square root of 1 minus v squared over c squared, where c is the speed of light. This can be expanded into a series representation of this function using the binomial expansion. We've looked at this before, and so we get an expansion that looks like 1 plus a half v squared over c squared plus terms that are higher order in v, like v to the fourth, v to the sixth, and so forth. And for sufficiently low velocities, less than a few percent the speed of light, we can usually neglect some or all of these higher order terms in the series expansion and get a simpler representation of the gamma function at low velocity. Now, we've looked at some consequences of the Lorentz transformation in special relativity. We've looked at length measurements and we've seen how they depend on frame of reference. We've looked at time measurements and seen how they depend on the frame of reference. And we've looked at the simultaneity of events in one frame and see that they are not necessarily guaranteed to be simultaneous in any other frame that's moving with respect to the one in which they are simultaneous. But is the relativity of time a real thing? Ideally, what we would want to do is take two twins, put one in a spaceship that can accelerate very quickly up to speeds well in excess of half the speed of light. That's where the gamma function begins to take on values that are very much in excess of 1. And then we would let the twin travel out on a journey of maybe 10 or 20 years, and then bring them back. That's going to take another 10 or 20 years. And when the twin gets back from the journey at high speed, we would compare the two twins and see how they have aged from the perspective of observers on Earth. That would be a great experiment, except that it is really not easy to construct a vessel not only that can hold humans for long-duration space flights, but also that can accelerate up to speeds that are appreciably close to that of light. This is an engineering challenge that we as human beings have never really mastered. Instead, what we need to do to test the claims of special relativity is to identify a laboratory where such speeds can be readily achieved, but also one where there's a natural clock of some kind, a regular sequence of events whose time can be well predicted, so that we can compare those things when they're at rest to when they are in motion. Now, tiny particles would be a great potential laboratory. Tiny particles have very small masses, they're very easy to accelerate, and so it's possible that something like the electron, with a mass of 9.11 times 10 to the minus 31 kilograms, could be ideal for investigating fast-moving objects and maybe even the relativity of time. Now, for example, the ground state energy of the hydrogen atom, the lowest energy state that an electron can have when orbiting a single proton, is 13.6 electron volts. You can look back at the conversion factor for the electron volt, look it up on the web, whatever you want to do, but you'll find that this comes out to be about 2.19 times 10 to the minus 18 joules of energy. Now, if you translate that into a corresponding kinetic energy for the electron in that state of hydrogen, what you'll find is that you can calculate the speed of the electron that is represented if you pretend that the electron is orbiting like a little planet around the proton under the influence of the Coulomb force. So let's do that. Let's imagine that the electron is orbiting the proton at the center of the hydrogen atom, and let's use the energy of this state to estimate the kinetic energy and therefore the velocity of this electron. And if we do this using the classical kinetic energy, 1/2 mv squared, and rearranging it to solve for the speed of the electron, we find that it should come out to be about 2.2 times 10 to the 6th meters per second, or thereabouts. That's already pretty fast on its own. That's about 1% of the speed of light, without having to do anything exotic except maybe study the electron in a hydrogen atom. Now, of course, we'd like to get the electron up to faster speeds than that, but if that's how fast it's already going in a hydrogen atom, then you can imagine it's probably not too hard to get it going faster. In fact, J.J. Thomson, who's credited with the discovery of the electron, isolated them by ripping them off of parent metal atoms using the Coulomb force, using a strong electric field and a large electric potential. This has the effect of accelerating the electrons up to rather high kinetic energies for the tabletop experiments of his day, representing tens of thousands of electron volts of energy in the electrons. And that would equate to speeds roughly of the scale of 10 to the 8th meters per second. Perfect! Those are the speeds we want to investigate phenomena at. So a particle like the electron would be easy to accelerate, but there's a problem. The electron doesn't do anything. It's an extremely stable particle. In fact, left on its own, an electron will simply be for the rest of the history of the universe, so far as we know. So it doesn't have any regular, characterizable phenomena associated with it once you've isolated an electron. It lacks a kind of clock that it carries along with it that we could use to see whether or not the passage of time is affected by the motion of the electron. Well, are there any such clock-like phenomena in nature that are associated with very small particles? The answer is yes. Radioactive decay of atomic nuclei is exactly an example of a natural clock that ticks all the time in nature, whether we're there to observe it or not, and if we do observe it, we can use it to measure the passage of time in a system. So, for example, among her many discoveries, two-time Nobel Prize winner Marie Curie isolated the element polonium. It is highly unstable, and the natural isotope of polonium, polonium-210, transforms spontaneously into a stable lead atom, lead-206, after emitting energy in the form of radiation. Specifically, what it does is it spontaneously ejects 2 protons and 2 neutrons from the polonium nucleus. These 2 protons and 2 neutrons are bonded into the nucleus of a helium atom, and this thing is known as an alpha particle. We'll return to alpha particles later in the course. The bottom line is there's some spontaneous phenomenon that happens with regular time intervals that we can use to actually track time in nature. Now, polonium-210 has what is known as a half-life of 138 days. But what does that phrase, half-life, mean? It means that if I were to isolate 100 atoms of polonium-210 in a sealed container and have some way of looking at those atoms and counting them every hour of every day, if I were to wait 138 days from the time I seal the container and then look in the container, on average I will find that after 138 days, about 50 atoms of polonium-210 will remain in the container. The container will also now be home to 50 lead-206 atoms. They resulted from the spontaneous decay of the missing polonium-210. Now, if I further wait another 138 days from that moment and look in the container again, on average I will find that I now have 25 polonium-210 atoms left, half of the sample I had 138 days ago. And correspondingly, I'll find 75 lead-206 atoms in the container. A half-life is a regular interval of time, and if you had some kind of equipment that could be used to establish the amount of a certain isotope present in a sample, you will find that after one half-life, after every half-life passes, you'll lose half of what was there the last time you looked. So unstable radioactive elements have a reliable built-in clock, a regular process that occurs at the same place, that is the nucleus, at regular time intervals. However, there's a problem, and in the historical context, what I'm talking about here is a problem in the early 1900s. Polonium and other radioactive elements were pretty hard to come by in the days when they were discovered, and even in the decades after that. And even if you could isolate an appreciable sample of them, how would you know precisely how to count the numbers of those things, whether they're at rest or whether they're in motion? And not only that, you got to put them in motion, which means you need to accelerate them. And they are thousands or tens of thousands or hundreds of thousands of times heavier than electrons. Particle accelerators that are capable of bringing ions up to speeds approaching that of light of any decent quality and control were decades away in the early 1900s. They wouldn't emerge until the 1930s, 40s, and 50s. So it's nice that we have these regular clocks like radioactive isotopes, but you can't actually do practical experiments of the variety we're thinking about trying to do. That is, attempting to see whether their clocks slow as they are put into a state of motion relative to the observing frame. If only we had a tiny particle that combined the lightness, abundance, and ease of acceleration of the electron with the regular instability of radioactive atoms. And it's into this part of our story enters the mu meson, or for short, the muon. Now, the mathematical description of unstable nuclear behavior and of the strong binding of things in the nucleus took decades to work out. But around the 1930s, with some experience now with other forces in nature, like electromagnetism, it was hypothesized that the forces inside the nucleus that both bind it together so tightly, but also occasionally allow it to catastrophically break apart, that these forces were maybe of two different kinds, and that they had particles like the particles of light that transmit electromagnetism that acted as intermediaries in the nucleus and transmitted these forces within the nucleus. And so these intermediaries were given a generic class of name, mesons, from the Greek word mesos, meaning intermediary. And by the 1930s, or certainly the 1940s, the hunt was on to find them. Now, shown at the left here on this slide is an image that was taken by two physicists, Anderson and Nettermeyer, and published in 1936. A previously unobserved electrically charged particle punches through the slab of lead that runs through the center of the photograph. These are two different views taken from different angles of the same particle interactions at the same moment in time. And the interactions are taking place in a lead target that runs through the center of the picture, roughly here in the picture. Now, as this previously unidentified particle passes through the lead, it knocks apart nuclei, but in this process it barely loses any energy. This was a really strange beast in its day. It would come to be dubbed the mu meson, or muon for short, as the physicists of that day mistakenly thought that this has to be one of the sought-after nuclear force intermediaries. I mean, what else could it be? This turned out to be a bit of a lack of imagination and experience on the part of physicists with the broader picture of nature, a good lesson for all of us, of course. And this assumption turned out to be wrong. The particle was real, but its role in nature was not as originally assigned. And that wouldn't be fully understood until the 1940s and 1950s. Its electric charge, however, was pretty well determined from careful experimentation, and it was found to be identical to that of the electron, negative 1.609 times 10 to the minus 19 coulombs. So it carries with it the same elementary charge that the electron possesses. Its mass, however, was very unlike the electron. It weighed in at 207 times the mass of the electron, too light to be a proton, too heavy to be an electron. And crucially, unlike the proton and unlike the electron, it is also unstable. If you trap a muon nearly at rest, and there are some fairly straightforward ways to do this, on average you will find that it only lives about 2.2 microseconds, or 2.2 times 10 to the minus 6 seconds. Now, let me make an important aside while we're on the topic of unstable particles about unstable particles, half-lives, and the characteristic lifetime of an unstable particle. The mathematics of unstable particles was developed in response to the discovery of radioactive decay of atomic nuclei, and it's a fairly straightforward application of algebra and calculus, and I find it's instructive to run through it here. Consider the kinds of systems we've been talking about so far. So for instance, let's imagine you have a system of n0 unstable objects, like 100 nuclei or particles, like the muon. And you observe them to have that number at time t. And then you wait a little bit, and we consider some change in time, t plus delta t, at which point we then discover that the number of objects has decreased by negative dn. Now here, dt and dn are differential units of time and number, respectively. And you find that the number of objects remaining after a time has passed, dt since the original time measurement, is the original number n0 minus dn. But if you double the number of objects, so if you start with 200 unstable objects, for instance, and wait the same amount of time, you don't find that the dn is the same size as it was before. It gets bigger. And if you triple the objects to 300 or quadruple them to 400, you again find that dn after the same dt is proportionally larger, and it's larger in proportion to the size of the starting sample. There is some proportionality between the change of number of objects, the change in time, and the original number of objects. And so we can express this observational relationship in a simple equation. Negative dn, the change or decrease in the number of objects, is equal to a constant, which we have yet to determine. We'll denote that with the Greek letter lambda, lowercase lambda, times the original number of objects, n, times dt, the time that passed during which the time the number changed. Now you'll notice that this is set up to look like an equation of differentials, and so one could actually integrate both sides of this equation. You can put all the n's and dn's on one side and all the constants in dt on the other side. And then you could integrate the side with the number stuff on it from the original number n0 to the final number n after waiting a time t. Now you'll notice that on the left-hand side we have the integral of negative 1 over n dn, or 1 over x dx, if that sounds more familiar to you. And so you should know from some experience with second semester calculus that the natural log of the argument, n in this case, will wind up being the answer to this integral. On the right-hand side, we have a much simpler integral. We're just integrating a constant times dt from time 0 to time t whenever we observe the system later. And that's a very simple integral. You just wind up getting the time t back times lambda, and then you just evaluate it at the endpoints. So if you do that, you should find that you get the following equation. The natural log of the original number of objects minus the natural log of the final number of objects at time t is equal to lambda times t minus 0. 0 is the original time at which you observe the system, and see that it has objects n0 in it. Well, if you rearrange now and try to isolate the number of objects n at the later time t on the left side, you wind up with this equation, moving the logs and constants and signs around. And so finally you can solve for n as a function of time, and you find out that it's exponential in nature. If you start with a number of objects n0, the number of objects left after a time t is given by e to the minus lambda t, times the original number of objects, n0. Now, let's talk about this constant of proportionality, which we've been calling lambda. So, in order to satisfy the requirement that the total argument of the exponential function be dimensionless, it must be true that lambda has units of inverse time, 1 over time, or 1 over seconds, per second, hertz, in the units of oscillatory phenomena. It's convenient to therefore define lambda as 1 over some characteristic time, which I'll denote with the lowercase Greek letter tau, where tau is known as the time constant of the phenomenon. Well, what does it actually mean for t to reach tau, the time constant? Well, if you allow enough time to pass that one time constant's worth of time goes by, you find that 63.2% of the original number of objects are gone. For unstable particles, this characteristic time is what is known as the lifetime of the particle, and you can actually show, using some math we'll develop later in the course, that mathematically tau is also equal to the average time that an unstable particle exists. So it has two meanings. One, it's the time after which 63.2% of the original n0 objects have disappeared from the system. And two, it's the average time that any randomly picked unstable particle will exist. Now, where does the half-life come into all this? Well, you can show that the half-life of an unstable particle, which we could denote as t with a subscript 1/2, is directly related to the time constant tau by the following simple equation. The half-life is equal to the time constant times the natural log of 2. So when we say, quote, the muon has a lifetime of 2.2 microseconds, unquote, we're referring to the time at which there is a 63.2% chance that any single muon has decayed, vanished, gone away from the original sample of muons. Now, let's talk about muons and observing them and their origins in the world around us. Muons are not naturally occurring in the same sense that atoms are naturally occurring. Atoms are, generally speaking, stable, they stick around for a long time, and they form large structures because they have a chance to bind to each other through chemical means, which is just electromagnetism in action. Muons, on the other hand, are a bit stranger. You have to make them, and because they don't live very long, you have a very limited opportunity to study them once they come into existence. Now, thankfully, nature does make them all the time, and it does so because the Earth is constantly bombarded by particles from outer space that are smashing into the atmosphere at very high speed, very high kinetic energy, and these things are known as cosmic rays. And when cosmic rays slam into the Earth's atmosphere, they result in a whole bunch of particle interactions that ultimately spray muons down onto the Earth, among other things. So they do this by smashing into nitrogen or oxygen nuclei, having all kinds of nuclear reactions in the process that produce a whole bunch of other particles, and I'm not going to worry about what those are right now, but ultimately muons can result from this, and the symbol mu with a minus sign next to it denotes the muon with its natural negative electric charge. There are also positively charged muons, and that's a subject we'll come to later in the course. Now, Anderson and Nettermeyer, who originally discovered the muon, did so using showers of particles from cosmic rays, so-called cosmic ray showers. And they did so by putting detectors at different altitudes in the Earth's atmosphere. So, for instance, they did a bunch of experiments with a detector located on top of Pikes Peak, which is 4.3 kilometers above sea level. And they did a bunch of experiments at home base at Caltech in Pasadena, California, which is roughly at sea level. And it turns out, in the decades we've been studying cosmic ray interactions and muon production, we've learned that most of the muons that are produced by cosmic rays are made roughly at a height of 15 kilometers above the Earth's surface. That's not the top of the atmosphere, but it does correspond to the place where the density of the atmosphere gets big enough that these interactions of cosmic rays and nitrogen and oxygen molecules or nuclei get very high in probability. And so we get a lot of muons that get produced at that part of the atmosphere. Now, based on the known instability of the muon, one might expect that if one counts a certain number of muons at a high altitude, say counting a number n1, then by the math of unstable particle decay and using the known lifetime of the muon when it's nearly at rest, that is, tau for the mu is roughly 2.2 microseconds, one could accurately predict the number of muons you should expect to see at a lower altitude, n2. Now, at that lower altitude, because particle decays had a chance to happen, we expect fewer total muons to be found. If we make 100 muons or 1,000 muons at 15 kilometers above the Earth's atmosphere, and we go down a bunch of kilometers, we don't expect to find the same number of muons. We expect to find typically fewer.
All right, now this is very interesting here. Let me show you this. So here in the basement of Fondren Science, the physics department has a small experiment set up that allows us to capture muons created in cosmic ray showers above the Earth, trap them by trapping them in atoms in a material in this device over here on the left. And then after trapping them, we can wait and see how long they stick around until they decay. So all of this equipment is designed to establish the time at which a muon is trapped, and then the time at which it then subsequently decays, because it doesn't live forever. And if we take a look at the data here, what we find is that when we trap these muons and hold them nearly at rest in our reference frame, indeed we see an exponential fall off in the number of muons that survive after a certain amount of time, as predicted by the theory of particle decay. And we can see that after about 2.2 microseconds, that there's a roughly 60 to 70% chance that any single muon will have already decayed, exactly as previous experiments have determined. So this is our own little way of caging muons using atoms to trap them, then waiting to see them decay, and measuring the time between those two events in a frame that's essentially at rest with respect to the muon. And indeed, this is how we figure out, for instance, that the muon lifetime is about 2.2 microseconds. This experiment alone here in the time it's been operating, which looks to be about 2,300 hours or so, has trapped and observed the decay of about 1.6 million muons. So just think about the sheer number of muons that must be raining down on the surface of the Earth all the time. We're capturing just a tiny slice of all of those. And they're a fantastic laboratory for looking at the little clocks that fundamental particles carry around with them so that we can study time using the tiniest building blocks of the universe.
Now, the muon's short lifetime should radically cut down its numbers as we go lower and lower into the atmosphere, and in fact, the effect is quite stunning. So, let's imagine we give the muon the best possible chance of making it to a low atmospheric height, so close to the surface of the Earth. Now, to do that, we're going to crank its velocity up to the fastest that anything that we know of can travel, and that's the speed of light. So we're going to set the speed of a muon that's just been produced at 15 kilometers above the surface of the Earth. We're going to set its velocity aimed straight at the surface of the Earth to the maximum it can be, 2.998 times 10 to the 8th meters per second. So if you crunch the numbers, you'll find out that in one lifetime, a muon can travel just 0.66 kilometers, not even a kilometer. It doesn't even go 1/15 of the way down closer to the surface of the Earth. But at this point, it's already had a 63.2% chance of decaying. There's a 63.2% chance that that muon won't exist anymore by this point. But let's imagine it survives, and it makes it 2 lifetimes. after 2 lifetimes at the speed of light, it could have gone 1.3 kilometers, doubling the distance it's traveled into the Earth's atmosphere, and now having made it a little more than 1/15 of the way into the Earth's atmosphere. But by this point, it pays the immense penalty of having a probability of 86.4% of having already decayed. 10 lifetimes will only bring a muon 6.6 kilometers into the atmosphere. That still leaves it about 8 kilometers above the surface of the Earth. But by then, it has had a 99.995% chance of decaying. There's really very little chance that muon really makes it this far. And if you take it twice as far, 20 lifetimes, the probability is even smaller. So the bottom line is that we don't really expect, if we produce 1,000 muons at 15 kilometers, to find really any of them down at sea level. So what actually is observed? Well, shown at the right is some data. It's real data taken from an experiment that really can count muons at different altitudes. And the graph shows the number of counts per minute versus the altitude where the measurements were taken. And these measurements were taken by high school teachers who were involved in a program called QuarkNet. This program engages teachers in K through 12, typically high school teachers, in real physics research environments, and this data is actually taken from an experiment they did that was reported in the article that's listed in the footnote on this slide. Now, what they found was that if the experiment was run 3.5 kilometers above the surface of the Earth, above sea level, they found about 300 counts per minute of muons at that height. Now, let's use the Galilean and Newtonian assumption of time, that time passes at the same rate for all observers. That is, whether the muon is moving or not, its clock and clocks on the ground tick at the same rate. Now, that's a total violation of the assumptions of special relativity and, of course, the conclusions that one would then draw from the Lorentz transformation. But we can make a prediction using the Newtonian or Galilean idea. And so we can basically estimate how many counts per minute we expect at half a kilometer, which is roughly the lowest height where the teachers took data. Now, what you observe is that at 3.5 kilometers, the number of counts is about 300 per minute, 300 muons per minute passing through the detector. And if we give the best case chance of all those muons making it down to half a kilometer above the surface of the Earth, we find out that we should expect the yield to go as e to the minus y over c times tau, where c is the speed of light and tau is the lifetime. And so after a height change of just 3 kilometers, going from 3.5 kilometers to half a kilometer here, we expect to find at most about 3.2 counts per minute from muons that are produced at this altitude of 3.5 kilometers. Is that what we actually observe? And the answer is heck no. In fact, the teachers observed not 3 counts per minute, but 100 counts per minute at both sea level and about half a kilometer above the surface of the Earth. It's pretty hard to tell the difference between those two sets of data. So why would that be? Why would it be that the Galilean and Newtonian prediction, or at least its assumption that time is the same for all observers regardless of the state of motion, would not get this experiment right? It seems so simple. We know the lifetime of the muon when it's at rest. You know the height difference between where you make the first and second measurements. You just do some counting. Should be easy, right? And you don't even get close to the right answer. So why would that be? Well, I think we already know the answer. The answer is time dilation. Special relativity, with its Lorentz transformation that's supposed to be valid for all speeds up to that of light, will help us to understand this. So let's relate what's going on in the muon's reference frame, which we'll call S prime, and what's going on in the Earth's reference frame, which we'll call S. So we choose the Earth and the atmosphere to be at rest. We choose the muon to be moving. So it's viewed as a moving object with respect to the Earth, and so we can call that the moving frame. Now, in the reference frame of the muon, where it thinks it's at rest, its lifetime is 2.2 microseconds. Recall that this is the lifetime as observed when the muon is nearly or exactly at rest, and that would be its proper lifetime when it's exactly at rest. The proper lifetime is measured in the frame where all events happen at the same location in space. For the muon, coming into existence and going out of existence all happen at the same place itself. And so that's the frame in which proper lifetime is defined. That's also how we measure the lifetime of the muon, is we stop it and we let it decay, and we see how long that takes, typically. And so that's the 2.2 microseconds associated with how long the muon lives. Now, the Lorentz transformation would predict that the time measured by an observer on the Earth, the time that's passing in the muon's frame of reference, will be different from a person who would measure the time but ride along with the muon, thinking the muon is the thing at rest the whole time. So we can take observations in the frame of the Earth, observations of, say, the clock ticks in the muon's frame at T2 and T1, and take the difference, the delta T between those ticks, and we can relate those to the spatial coordinates where all the events happen and the time measurements as observed in the frame of the muon, the S prime frame. We're just using the Lorentz transformation one more time here. Now, all the events in the muon's frame of reference being created in the upper atmosphere, decaying later at a time T2 where the Earth is closer to the muon, they all happen in the same place in the muon's reference frame. In other words, x2 prime is equal to x1 prime. Therefore, this equation simplifies, and the time difference in the Earth rest frame is relatable to the time difference in the muon's frame of reference by a factor of gamma times the time difference in the muon's frame of reference. Now, the lifetime of the muon in its frame of reference is 2.2 microseconds. So delta t prime, or t2 prime minus t1 prime, is 2.2 microseconds. So special relativity would predict that from the perspective of an observer on the ground, the muon would appear to live longer than would be expected if it were at rest as well. This is completely in accordance with the observational evidence. More muons, many more muons, are observed to survive to a lower altitude than would be expected from classical physics and its assumption of the absolute passage of time for all observers. So the data told us that of the, say, 300 muons per minute observed at 3.5 kilometers, roughly speaking, 100 per minute of those survive around half a kilometer above the Earth's surface. In the reference frame of the Earth, we can relate these numbers to the observed decay time of the muons in their rest frame, that is, tau, the proper time, and also the lifetime of the particle, and the distance that they travel from the perspective of the Earth and atmosphere rest frame, y, as well as the typical speed of muons. So what we find is that taking the decay equation, n equals n0 times e to the minus t over gamma tau, then tells us that we can solve for the velocity and the gamma factor of the muons using the data. We know n and we know n0 from the data. We know y because we know the height difference that the teachers made the measurements at. We can solve for this quantity gamma v, which is related, of course, ultimately to the speed of the muons in the atmosphere relative to the Earth. So if we do the algebra here and solve for gamma v, we get the following equation. Now, I'm going to leave it as an exercise to the viewer. We want to solve ultimately for either gamma or v, but since they're each a function of the other, we have to do some algebra to isolate one or the other. And to help you along with this, recall that the gamma factor is defined as the 1 over the square root of 1 minus v squared over c squared, and that means that the velocity, if you solve for that, is equal to c times the square root of 1 minus 1 over gamma squared. And from this, you can take gamma times v, and you can get a nice expression for that. So gamma v can actually be written entirely in terms of gamma, which is interesting. And if you use that trick, you can get to isolated expressions for either gamma or v from this equation here on the right-hand side. So go ahead and try that yourself as an exercise, but you should find the following things. You should find that the gamma factor for these muons, assuming that all the 300 that are created at or appear at an altitude of 3.5 kilometers then could be counted or not at 0.5 kilometers above the Earth's surface. And you then, based on that assumption, estimate that the gamma factor is around 4.3. And if you solve for the velocity of these muons, they are radically close to the speed of light. They are 2.91 times 10 to the 8th meters per second in speed relative to the Earth and the atmosphere. Now, from the person on the ground's perspective, that journey from 3.5 kilometers to half a kilometer above the surface of the Earth takes about 10.3 microseconds, which is way longer than one lifetime of a muon. So it's no wonder muons make a fantastic and early laboratory for tests of special relativity. Nature is readily making lots of them per second in the upper atmosphere. They can be measured using technology that was available in the early 1900s, at least the first half of the 1900s. They can be observed and to see when they decay and how often they decay and so forth. And all of that together can be used to assess the validity or not of special relativity. And of course, what we find is that special relativity wins the day. It is the correct description of space and time for inertial reference frames. And it's remarkable how well it actually works. Now, of course, the atmosphere is complicated. The production of muons in the atmosphere is complicated. If you really wanted to do a super thorough job of this, you would have to do a detailed simulation of the interactions of cosmic rays in the Earth's atmosphere, producing muons at various heights, and then see how many you count at various heights with and without special relativity. If you do that, we find that with special relativity, we can exactly produce the atmospheric data. Without special relativity, we utterly fail to reproduce the atmospheric data. It really is true that special relativity is the correct description of space and time and motion. Now, I find it's instructive to quickly take a look at this same situation, but from the muon's perspective. That is, if you could ride along with the muon at its ridiculous speed, what would you observe? Of course, in the muon's frame of reference, it's at rest, and the Earth and the atmosphere are rushing toward it, or, in the case of the atmosphere, past it. So, you and the muon come into existence very suddenly, 3 kilometers above the final Earth observation place. Now, that's in the perspective, that 3-kilometer statement, that's made in the frame of an observer on the Earth. We'll get to the distances in a second in the muon frame. What you can say for sure is you come into existence, the Earth is far from you, it's racing toward you at a speed of v, and it's getting closer to you all the time. And at some point you'll go out of existence. And the question is, how far is the Earth and atmosphere going to move in the time between those two events, coming into existence and going out of existence? So the perspective of the Earth observers on the left in this cartoon, and the perspective of the muon observer is shown on the right in this cartoon. We don't know the distance between the surface of the Earth and the muon in this picture. We only know it from the original experiment in the Earth rest frame. But here we are confident that the Earth is rushing toward us at the opposite velocity that's measured in the Earth frame for the muon heading toward the Earth. Now, from the muon's perspective, of course, it's standing still. And all events coming into existence and decaying, they happen at the same location in its frame of reference. Therefore, the time it typically is going to stick around is going to be 2.2 microseconds in its frame of reference. It sees the Earth below it when it comes into existence, and it sees that surface of the Earth rushing toward it at a velocity of negative v. So how far does the muon have to go to make it to its destination, from its perspective and its reference frame? Now, time is ticking away at whatever rate it goes at for the muon, and ultimately it can measure time using its own lifetime, which is about 2.2 microseconds. Nothing funny with time in its rest frame. But of course, the distance where the muon was created above the surface of the Earth is 3 kilometers in the rest frame of the Earth. That's the frame where the Earth and its atmosphere appear to be at rest, and that makes that distance, 3 kilometers, the proper length or proper height above the surface of the Earth. That is the longest distance that any reference frame would measure between where the muon is created and, say, the surface of the Earth. The muon, on the other hand, will see the Earth-atmosphere system as moving, and therefore distances in that system contracted along the direction of flight. And the length or height above the surface of the Earth that it will measure will be the proper length, 3 kilometers, divided by gamma. And this comes out to be about 23.3% of the proper length, or 0.699 kilometers, 699 meters. That's the distance that the muon perceives between where it comes into existence and that final measuring point, which was 3 kilometers away in the frame of the Earth and the atmosphere. So, from the muon's perspective, we conclude that it observes that the distance it will travel is contracted compared to what observers on the Earth are seeing, and that contraction factor is 1 over gamma. From the muon's perspective, the distance between the place in the atmosphere where it came into existence and where it ultimately decays is greatly shortened, requiring only a time of delta t prime of about 2.4 microseconds to make the trip, because the Earth atmosphere system is contracted and moving relative to it. And so, given that it lives about 2.2 microseconds in its reference frame, it's absolutely plausible that it could make it that full distance that people on Earth said it went. It's just that the people on Earth are confused because the distance is shorter than they claim from the muon's perspective. So while observers on Earth and an observer moving with the muon would disagree on the reason for the muon reaching the lower measurement point, they all agree that it's very likely to happen. The Earth observer argues that the reason it makes it is because time in the muon's frame is passing more slowly than they claim, because the muon is moving. And so that takes longer to decay as a result of that. It's able to cross the 3-kilometer gap, even though it should have only lived 2.2 microseconds because time has slowed down for it while it's in motion. The muon observer says, no, our clocks are working just fine. What's going on is that because the Earth and atmosphere are rushing toward us, they're in motion, and so they seem contracted along the direction of motion. And as a result of that, we don't have to go that far to make it to, say, the surface of the Earth. And we're definitely going to make it in about 2.2 microseconds or so. That's why we made it so far. Now, they're both right. Even if they have different reasons for what happens, they both observe the same outcome. The muon makes it to the surface of the Earth. But they disagree on the space and time reasons for that. And that's okay, because the Lorentz transformation allows them to relate their perspectives and put their measurements into the other person's frame to see what's going on, and resolves the paradox in that sense. So to review, in this lecture we have learned, first of all, what is a muon? It's a subatomic particle. It's about 200 times heavier than the electron. It's about 5 times lighter than the proton, and it has the same elementary charge as the electron. So it's its own thing, and it would take decades after it was originally discovered to finally fit it into the sort of final picture of nature that we've reached today. The muon, regardless of what it really is an outstanding laboratory for testing predictions that are made using the Lorentz transformation, specifically about whether or not muons, given their very short lifetimes, should be able to travel the vast distances from where they're created in the Earth's atmosphere to where they can be measured down on the surface of the Earth. And in fact, we find that muons, in vast numbers, make it from where they're produced in the upper atmosphere to the ground. But they're not supposed to if time passes at the same rate for all observers in all frames of reference. So it may seem weird that time doesn't pass at the same rate when you're moving, but it's the truth. We have direct tests of this not only with muons, but with many other systems as well. And in many ways, the muon wound up being the very first direct test of the validity of special relativity, and it held up against that test beautifully to live another day and make more predictions, which is what makes it such a spectacular theory of space and time. In this lecture, we will learn the following things. We'll begin by learning what is the classical Doppler effect on an oscillatory phenomenon like a wave. We'll also learn about the effect of the motion of a light source on the characteristics of the light other than its speed. And finally, we will learn how to compute the so-called special relativistic Doppler effect on light and interpret the effect on observations of the world around us. Let's begin by recalling oscillatory phenomena from introductory physics. Specifically, let's look back at something called simple harmonic motion. This is a kind of repetitious motion that has a time and space structure that allows itself to be described using sine or cosine functions of space and time. So for example, depicted in the graph at the bottom of the slide, we have the vertical position of some object as a function of the horizontal position of the object. And we see that the vertical position varies gently upward, then downward, then upward again, and then repeats with the horizontal position. And this motion of the y-coordinate with respect to the x-coordinate lends itself to a direct description, in this case, using a sine function. Now, a wave phenomenon, such as a water wave or a sound wave, can similarly be described using exactly this kind of mathematics. A sound wave is a region of high compressed air, followed by low compressed air, followed by high compressed air, and so forth. It's a so-called density wave in air. A water wave is similarly an increase in the number of water molecules in one region of water and a decrease in the number of water molecules in another, a rising and a falling of the surface of the water. These wave phenomena are oscillatory in nature and can be exactly described using the same kind of sine or cosine function approach that we apply on simple harmonic motion. Now, the wave phenomena, just like oscillatory phenomena, have characteristic numbers that describe their spatial distribution. There's no one place where a wave is and where it is not. For instance, you could say that there's more of the wave in this region of y and less of the wave in this region of y. The wave is a structure that's spread out in space, and it has both a spatial structure and, because it can move in time, it has a time structure as well. We have to use certain quantities to characterize the overall macroscopic shape of an oscillatory phenomenon or a wave. And the wavelength, denoted by the lowercase Greek letter lambda, is one such number. For instance, the wavelength of a wave, like the one depicted here, could be taken as the distance between crests of the wave, the locations of the maxima, the maximum displacement from zero in the y direction. Or it could be taken as the zero displacements of the phenomena. Really picking any two similar points on the wave and drawing a line between those points horizontally will give you the wavelength. Now, if we were to observe this phenomenon passing us by picking a reference point in space and just watching it go by that point, the time between maxima or minima passing the same spatial reference point is known as the period, capital T, of the wave. This is the time between the same thing happening over and over and over again in the wave phenomenon. Now, the inverse of the period, 1 over t, is the rate at which, for instance, maxima pass that point, and it's known as the frequency. And it can be denoted in one of a couple of ways. For instance, the lowercase letter f for frequency, which equals 1 over t, or it can be denoted using the Greek letter nu, which looks like a little curved v. That's also used often to describe the frequency of a wave, and again, that's just equal to 1 over the period, or 1 over t. Frequency have units of per second, or hertz, H-E-R-T-Z, the unit of frequency. Now, the speed with which waves move in space during some unit of time is actually given by a very simple product of frequency and wavelength. If you want to know the speed of a wave, you just take the wavelength lambda and you multiply it times the frequency f. And of course, for a light wave, the speed with which all light waves move is known to be c, the speed of light. And so this will just be, again, the product of the wavelength of the light wave and the frequency of the light wave. But that product will always yield c, 2.998 times 10 to the 8th meters per second, regardless of whether an observer is in motion relative to the source of the light or not. We know that already as one of the postulates of special relativity. Now, summarizing again the gross properties of waves, it's helpful to pick a characteristic point on a wave and think about the repetition of those characteristic points as representative of the spatial or temporal distribution of the wave phenomenon. So for instance, we can think of waves of sound or waves of light as merely being represented by lines or planes. So for instance, the location of a line in 2 dimensions or a plane in 3 dimensions could indicate a location in space of a maximum of the traveling wave. Using this picture at the right, you might imagine that each of the locations in space marked by one of these red planes is a place where you would find a maximum of the wave, having been sliced through by the plane. This is a very common way to quickly and simply sketch a wave without having to draw the sine or cosine function. The distance between lines or planes is the wavelength. That's the sort of cartoonish way you represent that particular feature of a wave in the image. Now, such a line or plane would be referred to as a wave front, and wave fronts can be used to characterize the location in space of a particular point on a wave and all of the repetitions of that point. The frequency of such a phenomenon can be thought of as how many fronts per second are emitted by the source. So if you think about one plane and then another plane and then a third plane being emitted by the source, the distance in time between those planar emissions would be the period of the wave, and 1 over that would be the frequency, the rate at which it emits wavefronts. Now, this brings us to the so-called classical Doppler effect. And I'm going to use sound waves to motivate this because most of you have probably at one point in your life or another actually experienced the Doppler effect with sound waves. The Doppler effect occurs when the source emitting a wave is itself moving relative to an observer. So if we're talking about a sound wave here, we're talking about a listener, someone who can receive the pressure changes in their ears. And when that observer is moving relative to the source, the Doppler effect can occur. And this is actually illustrated in this cartoonish animation below. A car starts emitting sound, perhaps by the driver laying on the horn, and the wavefronts are represented by those red circles. So everywhere you can locate a point on a red circle would be a wavefront of the sound waves, and they're emitted at rest uniformly in all directions. But as the car accelerates forward, the wavefronts in front of the car begin to pile up. The sound waves get closer together, the wavelength shrinks, and behind the car, we see the wavefronts spread out. The wavelength gets bigger. So in this example using sound waves, we have the effect that in the direction of motion of the emitter, the car honking its horn for instance, and ahead of the source, the wavefronts are pressed together more densely, shrinking the wavelength and thus increasing the frequency with which waves will strike our ears. If we were to be standing on the backside of this moving object while it's moving away from us, sort of against its direction of motion, the wavefronts are more widely spread apart than they would normally be. And this increases the wavelength and thus decreases the frequency with which these waves reach our ears. So to human ears, it's the frequency of waves that determines what we call pitch. High-pitched sounds are also high-frequency sounds. The wavefronts are striking our ears more frequently. And vice versa. Low-pitched sounds are low-frequency sounds. The time between wavefronts hitting our ears is longer. Now, let's think about the Doppler effect on light waves. There is a classical Doppler effect on light waves, but because time and space measurements are also relative to the frame in which you're making the measurement, there's a relativistic component that gets added to this kind of pitch shift, even for light waves. So it's true that while all observers may agree on the speed of light, we know that special relativity leads to the conclusion that space and time measurements may differ between observers in different reference frames. Now, wavelength is a space measurement, and frequency is a time measurement. So, couched in that language, it should come as no surprise then that while observers in relative motion all agree that a wave of light travels at c, 2.998 times 10 to the 8th meters per second, regardless of what frame of reference they're in, observers in different frames will disagree on the wavelength and frequency of that light wave. Now, to measure wavelength, for example, is to be able to simultaneously locate maxima on a wave. Think back to our discussion of measurement and how one measures distances on a moving object. There are different ways you can do it, but one of those ways is to simultaneously co-locate points on the object. In this case, one maximum and then the next maximum. But we know that simultaneity is a frame-dependent statement. And in moving frames of reference, we know that the objects pinned to those frames appear contracted along the direction of motion from observers that are not in that frame and are, for instance, at rest with respect to that frame. Similarly, to measure frequency is to be able to measure the time displacement between two events at the same location in space. How often or how much time happens between wavefronts going by a single point. And we know that from the perspective of a frame that's at rest, the time in the moving frame passes more slowly, and these two frames would disagree on the amount of time between two wavefronts. So the combination of the classical piling up of wavefronts or stretching out of wavefronts due to the motion of the source, with these time or space effects that come from the special relativity postulates and the Lorentz transformation, come together in what is known as the special relativistic Doppler effect. And we will derive it here using the Lorentz transformation applied on top of the classical Doppler effect calculation. And we will discuss the implications of this phenomenon for observing the universe. It has some extremely deep impacts on our ability to understand nature, even distant parts of the universe where we have no physical access to moving objects. So to motivate the derivation of the relativistic Doppler effect, I'm going to start by talking about just the sort of classical Doppler effect. And to do this, what I want to do is have you imagine a light-emitting device, illustrated here as a blue ball, that is sending out wave fronts to the left along this coordinate axis, and it's doing so at regular intervals in its rest frame. So for instance, we might have a moment in time, t1 prime in the frame of the source, where it emits its first wavefront. Its first maximum is emitted from a point, say, for instance, 14 along this coordinate axis. And then at a later time, t2 prime, it emits the second front. So in the time between emitting the first front and the second front, of course, the first front has moved at the speed of light to the left, and it's now at point 13 on the x-axis, at the moment t2 prime that the second front is emitted by the source. And if these fronts are emitted regularly, as would be true in a simple harmonic oscillatory or wave phenomenon, then there will be a third front emitted at t3 prime and a fourth front emitted at t4 prime, and the distance in time between these successive emissions of fronts will all be the same, corresponding to the period of the source, capital T prime, in the frame of the emitting source. So t2 prime minus t1 prime will be the same as t3 prime minus t2 prime. All of those intervals between neighboring wavefront emissions will be the period of the source as observed in the frame of the source. This defines the period of the light wave. Thus, we have a regular frequency in the source frame. We can write that frequency in the source frame as f prime equals 1 over t prime. Now, that was done with the source sitting at rest along this coordinate axis. And so in that picture, an observer sitting at 0 on the coordinate axis would agree that the wave fronts all arrive with a time between them equal to what the source said it would be, because the source and the observer were at rest with respect to each other. But now let's imagine that the light-emitting device that's sending out those wavefronts at regular intervals in its own reference frame is moving with respect to the observer at 0 in the above coordinate axis. So let the velocity of the source be plus v, that is, it's moving away from the origin to the right and entirely along the x-axis. Treat the observer as being at rest, we'll call that frame S, and the source as being in motion, we'll call that frame S prime. Let's think about what will be the distance between wavefronts arriving at the observer from the perspective of the source. So we're doing all of this from inside the source frame S prime. We will transform to the rest frame of the observer later. So here is our source. It's at location 12 along the x-axis, and it emits its first front, front 1, at time t1 prime. And the wavefront moves toward the 0 point on the x-axis at the speed of light, c. Now the next time that the source emits a wavefront it has itself moved to the right from point 12 to point 13. In the meantime, the light wave front that it emitted, the first front, front 1, has moved at the speed of light to the left, and in this particular example it winds up being at point 10 on the coordinate axis. So in the frame of reference of the source, the distance between the wavefronts would have been lambda prime, the wavelength. And that's depicted here on this cartoon, showing where the original unstretched wavelength of this phenomenon would have been if the source had been at rest. The source had been at point 12 when it emitted front 1. Front 1 is now at point 10. And so the distance between those two would be lambda prime, the wavelength of the phenomenon in the frame of the source. But the source is now moved, and so it's at this location 13 that it emits its second front. So by the time it emits the second wavefront at time t2 prime, the first wavefront is a distance of c times t2 prime minus t1 prime, or c times the period in the frame of the source. And that's just equal to lambda prime. That's the distance from where it was emitted. But the source is now farther from the observer by an amount of v times t2 prime minus t1 prime, or v times the period, when it emits the second wavefront. And again, that's depicted up here. So this is the distance from the point of emission that front 1 has traveled, which technically would have been one wavelength of the original emission. But the source has moved back further along the x-axis by a distance vt prime, v times the period. And so the source will argue that as a result of this, an observer who is looking at these wavefronts coming at them, sitting at point 0, should see the combined distance of lambda prime plus vt prime between the two wavefronts. And this will actually be the observed wavelength of the phenomenon, according to the person riding with the source. That will be what the observer sitting at 0 should see. So this is all illustrated above. We take lambda prime and we add vt prime, and that's going to give us the observed wavelength in the frame of the source. So this is all illustrated, and we can write the equation down, adding these two together. And then we can rewrite this in terms of frequencies by remembering, first of all, that period is equal to 1 over frequency, or frequency is equal to 1 over period, and that the speed of light is equal to the product of wavelength and frequency. Similarly, the wavelength, for instance, in the frame of the source, will be the speed of light divided by the frequency in the frame of the source. And the wavelength, according to the observer, from the perspective of frame S prime, will be equal to the speed of light divided by the frequency, according to the observer in that frame. So we then find, again, all of this from the perspective of frame S prime, that the observed period at 0 should be 1 plus v over c, all divided by the frequency of emission f prime. So maybe pause here and try to work all this out for yourself, but again, keep in mind that we have not yet transformed this observation into the rest frame. That is the frame in which the observer is at rest. Right now we're calculating the observed wavelength or period according to what the observer should see if their time measurements were absolutely in agreement with the moving source. This is the classical Doppler effect, the stretching or compressing of wavelength with the motion of the source. We haven't yet included, for instance, time dilation or length contraction in all of this. Now we're going to take that last step. And to aid us in notation here, we're going to begin by defining a very convenient symbol, and that is the lowercase Greek letter beta, which is rather regularly used to represent the ratio of the speed of the frame, for instance, divided by the speed of light. Because speeds v never exceed the speed of light c, and because speeds can never be any less than 0, beta is a number that goes from 0 to 1. 0 for things that are at rest, 1 for things that are moving exactly at the speed of light, and can take all values in between. In terms of beta, the claimed period of the phenomenon, as observed by the observer in frame S prime, should be 1 plus beta divided by the frequency of emission. But again, so far all of this is in the S prime frame. This is what a person in S prime following along with the source would argue is what the observer should see. The original frequency of emission from the perspective of the source, F prime, which we can just call F with the subscript source, and it includes the relative speed of the source and the observer, V, and the period and frequency with which a person in the source frame would expect the observer to receive the wavefronts, T prime observed, or correspondingly the observed frequency. However, if we now do the special relativity and use the Lorentz transformation and transform this stuff into the actual frame of reference of the observer, we know that there's going to be another effect here. And for instance, we could summarize that by saying that it will be the relativity of time. Time in the source frame, where all emissions happen at the same location, is proper time. The source always says that wavefronts are being emitted from its location in space. And as a result of that, that's the frame where proper time will be observed. But in any other frame moving relative to the source, time dilation will be what is observed. That is, the passage of time on the moving object will appear to be slower than the observers on the moving object would claim. And it's given simply by taking the proper time and multiplying it by gamma. So the time, the period observed in the rest frame of the observer will be gamma times the period that the source claims the observer should have seen according to the classical Doppler effect. So we then finally arrive at an expression for the period of the phenomenon of the light wave as observed in the rest frame. So we start by just saying that the period observed in the rest frame will be equal to gamma times the period that should have been observed from the perspective of the moving frame, T prime with the subscript OBS. We can substitute in with 1 plus beta over the source frequency, F prime. And we can do some algebraic gymnastics to sort of rewrite this in a more pleasant looking form. We've got gamma and we've got beta. Of course, gamma depends on beta. Gamma has V over C all squared inside of it. That's beta squared. So it's nice to try to rewrite this all either in terms of just beta or just gamma. And so with a little algebraic gymnastics, starting with writing gamma as 1 over the square root of 1 minus beta squared, you can then do a little work and show that a final neat-looking expression for this is that the period observed in the rest frame is equal to the square root of the ratio of 1 plus beta over 1 minus beta, all times 1 over the source frequency, the frequency of emission from the perspective of the source itself in its rest frame. So we can transform this into an observation, of course, of the frequency in the rest frame by simply doing 1 over t observed. And that just flips the stuff in the square root upside down, and you wind up with this neat little relationship that the frequency of the light observed in the frame that's not moving will see the frequency as emitted in the source frame where the source is at rest, shifted by an amount given by the square root of 1 minus beta over 1 plus beta. So we've solved the problem now. We've derived the special relativistic Doppler effect, the shifting of the frequency due to relative motion between the source of emission and the observer of the light, by considering the situation where the source is moving away from the observer. Now, this special relativistic Doppler effect is a combination of two effects. The classical Doppler effect of just the effect of the moving source that adds extra space between the wavefronts. But in addition to that, the dilation of time due to relative motion of the source and the observer. Proper time, and therefore proper frequency, would be in the frame of the source. This is modified by a gamma factor to go into any other reference frame. So the special relativistic Doppler effect is a combination of the classical Doppler effect with the relativity of space and time measurements. And you actually would expect from just Newtonian and Galilean relativity that there's a Doppler effect on frequency and wavelength of light. But the special relativistic addition to that actually makes the effect even more extreme than expected from Newtonian and Galilean mechanics. And in fact, what we see in the universe is what is predicted by special relativity and not just the old mechanical Galilean and Newtonian approach to motion. Now, for a source that's moving toward an observer, that is, approaching the observer while emitting wave fronts, the sign of the velocity is all that needs to be changed. We go from having beta, the velocity moving away, to negative beta, the velocity now moving toward the observer. And in fact, you can do the work yourself, but this formula up here for the source moving away from the observer can be transformed into the case for the source moving toward the observer by flipping the sign of beta. So taking beta and turning it into negative beta. And all that does is it takes the stuff under the square root and flips it upside down. So now we have the square root of 1 plus beta divided by 1 minus beta, that whole thing times the frequency of emission in the source rest frame. So I would recommend you practice this calculation by checking for yourself that this second equation for an approaching source is correct. But once you've convinced yourself of that, the shortcut is a really easy thing to remember. If you can remember one of these two formulas, you can get the other one simply by changing the sign of beta. Not too bad. So let's talk about some expectations from the special relativistic Doppler shift. For example, if a light source is moving away from us or toward us, what do we expect to happen to the frequency of its light? So for a source that's moving away from us at speed beta along our line of sight, we expect to scale the source frequency by the following quantity, the square root of the ratio of 1 minus beta over 1 plus beta. Now, if you play around with this a little bit, you'll notice that this thing is always less than or equal to 1. It's exactly 1 when beta is 0, and if beta is anything other than 0, its value decreases from 1. The frequency, therefore, that we should observe should always be lower than in the source's frame of reference, owing to the stretching of its wavefronts combined with the dilation of time. Now, because, as I said, beta is a number that's inclusively bounded between 0 and 1, we are taking the ratio of a number less than 1 and a number greater than 1 for beta that's anything other than 0. Now, if instead the source and observer are moving toward each other, then we scale the source frequency by this quantity, the square root of 1 plus beta divided by 1 minus beta. And again, if you play around with this, you'll find out that this is either always equal to 1 or greater than 1. This means that the observed frequency is always greater than what is observed in the frame of the source, since we're dividing a number greater than or equal to 1 by a number that's less than or equal to 1. So to summarize all of this, for a source that's moving away from the observer of the light, the frequency that the observer sees will be lower than the frequency that's observed in the rest frame of the source itself. And similarly, for a source that's moving toward an observer, the observer will always see that the frequency is increased over the frequency as observed in the rest frame of the source of the light emissions. These equations are all for frequency, but we can very quickly derive the equations for wavelength using the fact that the speed of light is equal to wavelength times frequency. So if we go through the brief algebraic gymnastics for this, we find that we get the following equations for the observed wavelength, depending on whether the source is moving away from the observer or if the source is moving toward an observer. So as expected, when a receding source is present, this gives us a lower frequency and a longer or greater wavelength. So the frequency has gone down, therefore the wavefronts are farther apart from each other because the wave is still traveling at the same speed, c. On the other hand, when the source is approaching us, we get the higher frequency, which means the wavefronts are coming at us more often, and that means a shorter wavelength will be observed for the phenomenon. So let's talk about the perception of light color due to the full relativistic Doppler shift. So I've rewritten here the equations for the wavelength that an observer sees depending on whether the source is moving away from the observer, in which case the wavelength is stretched by the motion, or if the source is moving toward an observer, in which case the wavelength is compressed by the motion. Receding sources of light are said to redshift compared to when they are at rest. And that's because longer wavelengths correspond to redder light than shorter wavelengths, which correspond to bluer light. I've illustrated this over here on the right using a spectrum, and specifically I've isolated the visible or color spectrum of the electromagnetic frequency spectrum. So for instance, red light, near the edge of where the human eye can detect the color red, has a length of about 700 nanometers, or 700 billionths of a meter. Blue light, or violet light, which is at the other end of our ability to see, comes in at around 400 nanometers, or 400 billionths of a meter in length. Blue light has a shorter wavelength and thus a higher frequency than red light. So if a source is moving away from us, the wavefronts get stretched out, and that would take something that's bluer and shift it more toward the red end of the light spectrum. And conversely, an approaching source is said to be blue shifted because this results in shorter wavelengths, which corresponds to the bluer end of the color spectrum. Now, of course, it's possible that if you have an object that's already, say, violet in color, and it's moving toward you very rapidly at a significant fraction of the speed of light, the shifting effect can be such that it actually shifts so blue that it goes outside the visible spectrum. And then you'd have to look for it in ultraviolet or X-rays or other similar very short wavelength electromagnetic phenomena. Similarly, if an object is already very red and on the edge of the ability of the human eye to see it, and the source of the light is moving away from you appreciably quickly, this can result in a redshift that puts it into the infrared or even microwave or radio, depending on the speed of the object that's emitting that light. You can imagine, therefore, that this has some strong implications for measuring our place in the whole cosmos. For example, without making physical contact with distant stars or galaxies, which are collections of billions or trillions of stars, it's possible to actually determine whether or not those objects are receding away from Earth or approaching toward Earth based on the degree of the color shift of their atomic spectra. Let's take a look at an example of this. Through long centuries of observation of distant objects by astronomers, and especially by breaking down the light from distant objects into their component colors, the so-called color spectrum or atomic spectrum, astronomers have determined that the stuff that makes up everything out there is the same stuff that makes up everything down here on Earth. And that is, at least for the luminous stuff, the stuff that emits light or absorbs light, that stuff is atoms. And the atoms that are out there appear to be the same as the atoms that are down here on Earth. Iron has the same atomic spectrum, whether it's found on Earth or in the heart of a star. So as a result of that, we can look at the light coming from distant objects, figure out what atoms it's made from, and knowing the pattern of light each atom gives off, determine whether or not, first of all, it's composed of certain atoms, and second of all, whether it's moving relative to us. So here's how you figure out the motion. The spectrum on the left over here on the slide is actually from our own star, the sun. The sun is not appreciably getting closer or farther away from us over the course of a day or a year. We're going around the sun, and our distance is changing slightly as we orbit the sun every year. But it's not happening so fast that you get an appreciably different shift, at least to the eye, in the color of the sun. So we can consider the sun to be an atomic spectrum that represents a star at rest. On the other hand, on the right-hand side, is an atomic spectrum from a very distant so-called supercluster of galaxies. That's a cluster of galaxies of stars, which are themselves clusters of stars. And it's named BAS 11. It's not so important what it's called. But if you stare at this for a few moments, you'll notice that there's an interesting similarity in the pattern of the light between our sun and the light that's coming from all the stars that make up this distant supercluster of galaxies. There's a missing color line here in our sun, and then there's a gap where there's lots of colors, and then there's another missing line. And then there's another gap, and then there's a missing line, and then there's a small gap, and there are two missing lines. And if you look over on the right at the light from the supercluster, you see that, oh, look, there's a line in the red that's missing, and then there's that same gap, and then there's a line in the yellow that's missing, and then there's that same gap, and then there's a line in the green that's missing. And then there's that same small gap, and then the two dark lines that are next to each other. It's as if somebody took the pattern in our sun and shifted it toward the red end of the spectrum. And this is exactly what we would expect from special relativistic Doppler effect if the supercluster is moving away from us, thus stretching its emitted wavelengths of light longer from our perspective. So these black gaps, so-called absorption lines in the spectrum, have the same pattern, but in a slightly shifted location in the sun compared to this supercluster of galaxies. And the fact that those missing colors are redshifted means the galaxy supercluster is moving away from us. That's the conclusion from the special relativistic Doppler effect. And you can actually then use measurement differences of the wavelengths between where the missing wavelengths are present in the sun and where they're present in the galaxy supercluster. And using some astronomy, you can actually estimate the relative velocity, beta equals v over c, with which the supercluster is receding from us. This is incredible. This allows us to measure velocities without having physical access to a material object. All we have to do is look at the pattern of light that comes from its atoms, and knowing that those patterns are the same patterns that should be found here in the atoms on Earth, look at the shifting of those patterns to determine the relative velocity of us to the distant object. This kind of measurement is actually how we know that the universe as a whole is expanding. So far as we've been able to determine, all distant objects appear to be receding away from the Earth, as if carried along on the momentum of an initial explosion that set the whole universe in motion, with all points expanding outward from every other point. This implies the universe as a whole, and on the largest distance scale, is expanding with time. So let's review what we have learned in this lecture. We've looked at the classical Doppler effect, both in a cartoonish way and using the example of a moving source emitting wavefronts along a horizontal axis. We've then considered the effect of the motion of a light source, where observers all agree that the light waves are moving at the same speed. We've looked at the effect of the motion on characteristics of light other than that speed, which isn't changing, the wavelength and the frequency of that light. And by combining the classical Doppler shift with time dilation, we've seen how to compute the special relativistic Doppler effect on light, and we've even looked at ways that you can interpret that effect on observations and take observations of the natural world and use those to infer relative velocities on the grandest scales of the cosmos. Third party, another object from the perspective of those two frames, and thinking about the velocity of that object as perceived in the two frames. We'll also learn how to properly add velocities of objects to frame velocities in special relativity. Let's use a concrete example to motivate a kind of basic problem we can use going forward to think about the question of object velocities relative to moving frames of reference. So the example I will pick for this is a non-copyright violating Space Wars. Recently, in a globular cluster fairly nearby, two ships were engaged in a chase. The The lead ship is moving away from the pursuing ship at a velocity given by the vector v. The pursuing ship fires a projectile straight at the lead ship along the line of motion and at a velocity vector u relative to the firing ship. With what velocity does the lead ship observe the projectile to move? Now, I've illustrated this with a little graphic cartoon right here. We have the pursuing ship on the left, the projectile it's fired, with the velocity of the projectile from its perspective drawn here in red, the ship it's pursuing over here on the right, and the velocity of that ship being pursued relative to the pursuing ship, given by the vector v. Now, in the Galilean or Newtonian view of space and time, the answer to the question, with what velocity does the lead ship observe the projectile to move, is rather straightforward. The observed velocity in its frame of reference, u vector prime, would be equal to the velocity of that ship with respect to the pursuing ship minus the velocity of the projectile with respect to the pursuing ship. That would also turn out to be completely wrong when the velocities in this question approach velocities near that of light. So, for instance, if the projectile is actually a beam of light, imagine a laser beam, a laser cannon mounted on the front of the pursuing ship. It turns on the cannon, the beam is emitted, this is a beam of pure light, it should move at the speed of light. If we plug that into this calculation, we get all kinds of wrong answers here. The lead ship doesn't see the laser beam approaching at the speed of light, and we know that's just not consistent with observation as encoded in the postulates of special relativity. So, what then is the correct addition of velocities in a problem like this? And that's the question we want to figure out in this lecture. We can begin by writing down the Lorentz transformation equations, treating the pursuing ship as the rest frame, the lead ship as the moving frame, and the projectile as an object to be located or studied in either frame. The space-time coordinates of that object in each frame are given as follows. For example, if we have the space-time coordinates x and t in the rest frame, we can get the space-time coordinates in the moving frame, the s prime frame, using this version of the Lorentz transformation equations, yielding x prime and t prime, the location and the time at which the location is observed for the projectile in the perspective of the lead ship. Now, we can write differentials of space and time using calculus, dx prime and dt prime, and this will allow us to work toward obtaining equations with velocities. So for instance, u prime is the first derivative of x prime with respect to t prime. After all, that would be the velocity of the object as observed in the lead ship or moving frame. U would be the first derivative of x with respect to t. That's the perspective of the projectile's velocity from the rest frame or the pursuing ship. Now, if this particular step feels weirdly familiar to you, in an earlier lecture, I walked you through a brief example as to why the Lorentz transformation needs to be a linear transformation between moving frame coordinates and rest frame coordinates. And we came dangerously close in that lecture to deriving the velocity transform, albeit I was doing that for arbitrary powers x to the n and t to the m, for instance. Here, of course, it's purely linear because it's based on the Lorentz transformation, and so if some of this feels awkwardly familiar, you may flip back to the earlier lecture on the Lorentz transformation and have a look and see where the roots of this were planted. So the differential of space in the moving frame, dx prime, is going to be equal to gamma times the quantity dx minus v dt. And the differential of time in the moving frame is going to be equal to gamma times the quantity negative v over c squared dx plus dt. Now, we can take the ratio of dx prime over dt prime, and this allows us to get the velocity u prime of the projectile as observed in the moving frame, or the frame of the lead ship. Substituting in with our differentials for dx prime and dt prime, we arrive at this rather unpleasant-looking equation. But one of the nice things about this is that the leading gamma factors, the 1 over square root of 1 minus v squared over c squared terms, they cancel out in both the numerator and the denominator. And this leaves us with an equation that looks like this, just in terms of the remaining differentials of dx and dt. Now, if we divide the top and the bottom by dt, the little unit of time that we're considering, then we wind up with terms that go like dx over dt, which is just u, the velocity of the projectile, in this case entirely along the x-axis. And so this equation takes the following form, which at the end of things doesn't look horrible. The velocity of the projectile as observed in the moving frame, the frame of the lead ship, is simply given by the velocity of the projectile as launched from the perspective of the rest frame, the pursuing ship, minus the velocity of the frame, so the velocity difference between the lead ship and the pursuing ship, divided by a quantity that goes like the motion 1 minus uv over c squared. So we have arrived at a formula for combining the velocities of the moving frame with the velocity of the projectile as observed in the rest frame to allow us to compute the observed velocity of the projectile in the moving frame. This equation is a substitution for the old Galilean transformation addition of velocities equation and is correct from the perspective of special relativity. So let's plug in some numbers and see what we learn about projectile motion in the case where objects are also in relative motion to each other and observing that projectile as it moves. And let's begin by picking a low velocity situation where the ships are not really moving apart from each other all that fast. I've decided to pick the lead ship having a velocity of just 1% the speed of light, or 0.01 c. And I've picked a projectile velocity that's just 3 times bigger than that, or 3% the speed of light, 0.03 c, from the perspective of the firing ship, the pursuing ship. Now, from the above equation, we learn that the lead ship observes the projectile approaching it at a speed of 0.02 c. Now, if you stare at this for a moment and recall the Galilean velocity transformation, you'll note that this is exactly what we would have expected from the low speed case, where all the velocities of objects in the problem are not really a large fraction of the speed of light, although I've allowed them in this case to go up to a few percent the speed of light. We actually get back exactly what would have been told to us by the velocity transformation in Newtonian/Galilean relativity, that is that u prime equals u minus v. Now, that doesn't mean that this is exactly true at every decimal place. There's some decimal place where the Newtonian Galilean approximation to space and time and motion breaks down compared to the more accurate special relativistic calculation. So let's instead pick some bigger velocities. Let's now assume that the lead ship is racing away from the pursuing ship at half the speed of light. And then from the perspective of the pursuing ship, it fires this projectile at 8/10 the speed of light, 0.8 c. Plugging those numbers in, we find out that the lead ship observes the projectile to approach it at 1/2 the speed of light. And if you stare at that again for a moment, play around with the numbers on your own, you'll very quickly realize that this is definitely not what would have been predicted by the Newtonian or Galilean approach. It's not simply u minus v in this case. Now, interestingly, we can look at the case of when the lead ship is flying toward the pursuer. So now we turn the lead ship around and we aim it back at the pursuing ship and flip its velocity vector so that it's moving at negative 0.5 c compared to its original direction of motion. In that case, we see that the lead ship that's now racing toward the projectile that's been fired at it doesn't observe that projectile to be moving in excess of the speed of light. Rather, it observes it to be moving at 93% the speed of light. And that's, again, a distinction from what the Newtonian or Galilean approach would have yielded. The old relativistic approach from Galilean relativity would have predicted that the lead ship observes the projectile to be approaching at a speed that is far in excess of the speed of light. But we also know from the postulates of special relativity that one consequence is that nothing can move faster than the speed of light. And so we see that that's preserved here in the velocity transformation. Although the velocity of the ship is now aimed back at its pursuer, and although the naive addition of velocities would give you something in excess of the speed of light, the naive addition is not consistent with observations of space and time and the speed of light. And using the special relativistic transformation, we see that while it's true that the velocity of the projectile does appear to be larger than when the lead ship was racing away from it, it does not exceed the speed of light, but comes in at a pretty fair fraction of the speed of light. So let's summarize what we've learned about adding velocities in special relativity, keeping in mind that the cases that I've built these equations from all involved an object velocity that was parallel or anti-parallel to the velocity of the frames. If you have the velocity of the object in the rest frame and want to determine it in the moving frame, then the left equation is what you want. If, on the other hand, you have the object velocity in the moving frame and you want to determine it in the rest frame, all that should change between the left equation and its corresponding equation on the right should be that you swap u and u prime, and you flip the sign of all terms that involve v or v cubed or something like that. You take v and send it to negative v. And in fact, that's the equation that's written here on the right. You can always derive these directly from the Lorentz transformation, or you can memorize one of them and remember how to transform it into the other by swapping the object velocities and flipping the sign of the frame velocities. I'll leave it up to you as to what your best possible learning strategy is for this, but know that if you memorize one of these, you can figure out the other from context and knowing how to trade the mathematics around. Now, what if the object, instead of having its velocity aligned parallel or anti-parallel to the frame velocities, is moving in a direction that isn't solely parallel or anti-parallel to v? So you might be tempted to assume that the object velocity in, for instance, the y direction, assuming that the frames are moving only along the x and x prime axes, you might be tempted to assume that the object velocity along the y direction and the z direction, as observed in either frame, is the same. Since in the Lorentz transformation, coordinates y and y prime, z and z prime are equal to each other if all the motion is along x and x prime. And you'd be wrong. You need to be very careful with these things. Why? Well, think about it a second. Object velocity necessarily involves the time derivative of a coordinate. Is time absolute between two different frames of reference? Well, we should feel pretty confident at this point that the answer is that it does not. T does not equal t prime in special relativity. Because a time derivative is involved, there's going to be a dy dt, and there's going to be a dy prime dt prime. And while y may be equal to y prime, t is not equal to t prime. So let's go through this. I'm going to consider motion component along the y-axis. The frames are moving entirely along x, so v in this is still directed entirely along the x and x prime axes. But I'm going to allow the velocity of the object to develop a component, uy, or uy prime, along the y and y prime axes, respectively. So let's look at what the transformation of u prime to u would be for the case of this component along the y-axis and y prime axis. So we know that in the rest frame, u subscript y is just dy dt. It's the change in the y-coordinate with respect to time, as observed in the rest frame. Now, it's true that in the Lorentz transformation, if the motion is entirely along x and x prime, that y does equal y prime. So we can replace dy with dy prime, and no harm, no foul. That's mathematically allowed. But if we're going to substitute for dt with dt prime, we have to use the full glory of the differential form of the time equation in the Lorentz transformation. And that means replacing dt with the quantity I show here in the denominator of this fraction. Now, of course, I can divide the top and the bottom by dt so that I get a uy prime in the numerator and the denominator. Gammas don't cancel out in this case, though, between the numerator and the denominator, because y equals y prime. Y and y prime don't depend on a gamma factor to correct between them. And as a result, it's actually an easier derivation, I feel, than for the case of the object motion component along the direction of travel of the frame relative to the rest frame. But it's not perhaps quite as memorable looking. Now, similarly, if we have uy prime and want uy, all we have to do is swap uy prime and uy in these equations and replace v with minus v. And so the corresponding equation that tells us what the velocity component in the moving frame looks like, given the velocity component in the rest frame, will be the one I show here. And by the way, if there's a component of motion along z and z prime, you can obtain a similar equation. It has pretty much exactly the same form as the one shown here, with uy replaced by uz and uy prime replaced by uz prime. You can very quickly write that equation down. But I just want to go through this because it's important to recognize that while it's true that y equals y prime and z equals z prime when the motion is entirely along x and x prime, it is not true that uy is naively equal to uy prime. And that's because a time derivative is involved. And time does not pass the same way in the two frames when one is moving relative to the other. Finally, let's take a look at one last special case. And that is if the pursuing ship shoots a laser beam at the lead ship. So what I've done is I've replaced the red projectile with a red squiggly line to represent an electromagnetic wave, light, being fired at the lead ship. Now the lead ship is still moving at a velocity v vector with respect to the pursuing ship. I've put everything along the horizontal axis here. But now the velocity of the projectile is c, because this is a beam of light. And so it will always and forever move at exactly the speed of light. So the speed of this projectile is now exactly 2.998 times 10 to the 8th meters per second, as viewed from all frames. So if the pursuing ship had fired a weapon like this, a laser beam, a beam of light, well, we know that the second postulate of special relativity demands that all observers must see light moving at c, regardless of their state of motion. So does this velocity addition relationship capture that postulate in all of its full glory? Well, let's find out. Let's assume that the relative velocity of the lead ship to the pursuing ship is 1/2 c, and that the projectile speed, as viewed in the rest frame of the pursuing ship, is c, the speed of light. Well, plugging these numbers in, we can start from the equation where we have the relative velocity of the two frames and the speed of the projectile in the rest frame, and we can get the speed of the projectile as observed in the moving frame. So all I've done is I've replaced u in this equation with c, because the projectile is a beam of light that's moving at the speed of light. If you do some algebra, you can simplify this equation to c minus v all over the quantity 1 minus v over c. And if you do a little bit more algebra, you'll find out that this is just equal to c minus v over the quantity 1 over c times c minus v. And if you play with this one step further, you find out that this is just equal to c, the speed of light. So in fact, we see that v entirely drops out of this equation once the projectile is a light beam. The value of v doesn't matter at all. The relative velocity between these two vessels can be any number, and it won't affect the outcome of the calculation. V could have been a 1/2 c, or negative a 1/2 c, or 0.8 c, or 0.99999 c. Basically, once u equals c, v drops entirely out of the equation, and we always recover that u prime equals c as well. The second postulate of special relativity is fully obeyed by this velocity transformation equation. So, to review, in this lecture, we have learned how to think about object velocities in different frames of reference, and how to go from the coordinates of an object that's in motion to its velocity in different frames. We've then used that information to figure out how to properly add velocities of objects to frame velocities in special relativity. We've looked at a couple of case studies of this and seen that everything seems to comport with the postulates of special relativity, which themselves comport with observations of the natural world. In this lecture, we will learn the following things. We will learn how to define kinetic energy and momentum while incorporating special relativity. We will learn about the nature of mass and the concept of intrinsic mass. And we will learn about the relationship between energy, momentum, and mass. Now, let's take a look back at Newton's second law from the perspective of classical physics, and in particular have a look at momentum or classical momentum in the context of this discussion. So in introductory physics, you are introduced to the concept of momentum roughly as follows. Historically, it was observed that there appeared to be a conserved directional quantity associated with motion. This quantity, which we call momentum, is well defined in the classical domain of physics, that is, low velocities or large scales, by the product of the mass of an object, m, and the velocity of the object, u vector. So we arrive at the definition, the so-called classical definition of momentum, by taking the product of these two things, m times u, and that gives us p, the momentum or linear momentum of that object. Now, in a closed and isolated system, perhaps with a whole bunch of different objects, I equals 1 to n, it is observed that this quantity overall is conserved. That is, the sum of all momenta of all objects in a closed and isolated system can be written as a singular number, the total momentum, and that total momentum remains constant no matter what happens inside that closed and isolated system. Now, when a system is not closed and isolated, for instance, subject to some net external force F, then the full beauty of Newton's second law is observed to be obeyed by the system. That is, that the net force acting on the constituents of the system is just given by the change in momentum of that system divided by the change in time, or dp dt. So Newton's second law, F equals ma, can actually be rewritten in terms of momentum concepts as just F equals dp dt. Now, of course, we need to bridge from classical physics to modern physics. And to do that, I want you to start thinking a little bit about the laws of physics and their invariance under transformations from one inertial frame of reference to another. Recall that one of the postulates of special relativity is that the laws of physics should not depend on what frame of reference you are measuring them in. They should be the same for all frames of reference. And the consequence of that, of course, is that you can't tell if you're in an absolute state of motion. But the benefit of that is that it preserves the forms of the laws of physics for all observers, regardless of whether or not they're moving. So if one subjects the classical momentum concept to consideration moving from one frame of reference to another, imagine a second frame of reference observing an object moving at speed u prime, and that second frame of reference, s prime, is moving at relative velocity v to the original frame s. Now, imagine that this is all closed and isolated, and in the rest frame, the velocity of the object is u, and in the moving frame, it's u prime, and the conservation of momentum will hold. And so, for instance, if we take the momentum observed in the rest frame for this object, so p equals m times u, and we use the Galilean transformation from classical physics to move to what we observe in the moving frame, we find that, of course, the moving frame will observe p prime equals m times u prime. And we can relate the momentum in the moving frame and the momentum in the rest frame using a Galilean velocity transformation, changing u prime to u minus v, and then distributing that inside the definition here. So when we do that, we find out that the momentum observed in the moving frame is related to the difference between the momentum observed in the rest frame and sort of the frame momentum itself, m times the velocity of the moving frame. Now, if we then consider changes in momentum in the moving frame with respect to universal and absolute time, so dt prime or dt, it doesn't matter which in the classical view of physics, we just wind up taking the time derivative of momentum in the moving frame, and if we distribute that time derivative to the two terms on the right-hand side above, we find that we have du dt and dv dt. Now, since the moving frame is moving at a constant velocity relative to the rest frame, dv dt is 0. That is, the moving frame is not accelerating with respect to the rest frame. It's moving at a constant velocity with respect to the rest frame. So this second term is 0. And we see that we recover exactly dp dt in the rest frame. In other words, dp dt in the moving frame is the same as dp dt in the rest frame. This is Newton's second law, and so we find that this transformation in classical physics leaves the form of Newton's second law invariant, at least under Galilean transformations, assuming that's the correct transformation of space and time and velocity. Now, this should all work in domains where the speeds are low compared to that of light. But we know that the original definition of momentum was predicated on experiments and observations that were all done in that low velocity, large scale regime of investigation. That is sort of the human scale of speeds and sizes. And we also know that that wasn't quite correct. The Lorentz transformation, not the Galilean transformation, gives the correct way to define relationships between frames. Great, well, let's just take the classical definition of momentum and apply the Lorentz transformation, the correct transformation between frames. So when we do this, of course, we find that the momentum is equal to mass times velocity. And we want to view this in the moving frame, where the momentum in the moving frame should be mass times the velocity in the moving frame. Well, if we insert into this the relativistic transformation of velocities in special relativity, we wind up with this nasty thing over here, the mass times u minus v over the quantity 1 minus uv over c squared. That's the thing we have to insert that contains the velocity of the object as observed in the rest frame, and of course the relative velocity of the two frames. All right, well, fine. So let's then transform this into a statement about differentials. So if I try to write the differential of p prime in terms of the differential of p, the momentum in the rest frame, if I do the calculus on this, I wind up with this horrible looking thing here. And then, of course, if I do dp prime dt prime, which would be the change in momentum with respect to time in the moving frame, that's related to the change in momentum with respect to time in the rest frame by this horribly velocity-dependent thing here. This is bad. Why is this bad? It's bad because it totally violates the first postulate of special relativity. The forms of the laws of physics must be invariant across all inertial reference frames. But here we see that one frame has that force is just equal to dp dt. But in the other frame, that very same law is horribly velocity dependent. This is not good. And rather than throwing the whole concept of momentum out the window, what we should do is stop and ask ourselves, did we really define momentum, the conserved quantity associated with degree of motion? Did we do that assignment correctly in the classical regime of physics? Did we just get the wrong definition? Is m times u too naive a definition of momentum, given now what we know about space and time and invariance in special relativity? Now, in order to come up with a more appropriate and physically correct definition of momentum, that is, relativistic momentum, there are many, many alternative approaches to finding the correct definition of momentum. Textbooks gloss over this because in many cases the framework for coming up with the exact form of this is not really approachable to students at the level of a student taking this course. So I had to cherry pick a methodology to motivate where the definition of relativistic momentum might come from. And I prefer the method that comes from my colleague Darren Acosta. So let's assume that the problem in the original definition of momentum was that of the definition of time used in the time derivative of space. Momentum was defined as mass times velocity of an object u. Velocity is the derivative of space with respect to time. So perhaps it's that time definition that's the flaw in the original definition of momentum. After all, that definition of time did not regard changes from frame to frame as having any appreciable effect on time. dt was not necessarily invariant from frame to frame, and in fact could have been the root cause of the problem we saw on the previous slide. However, there is in fact a time unit that all observers, regardless of their states of relative motion, can agree on. They can agree it exists and it can be measured the same way in a specific frame every time. And that is proper time, denoted with the letter tau. So if two events occur, and those events are observed by all observers in all frames of reference, all observers agree that proper time will be observed in a frame where the two events happen at the same spatial location. That is the definition of the proper time. It is the shortest time duration measured in any frame by any method of measuring time durations using two events. Now, it's always possible to find such a frame. If you're not in the frame where proper time is defined, you could always accelerate yourself in such a way until you enter the frame where the regularly occurring events that will be used to define passage of time occur at the same place. The time in any other frame is going to be given by the relationship between time in that frame and the proper time. So in any other frame, the time t for a frame moving at velocity v with respect to the proper time frame is simply given by gamma, the gamma factor associated with the motion of that frame relative to the proper time frame, times the proper time duration tau. Now, we're talking about inertial frames of reference, moving in relative constant velocities with respect to one another. And so as a result of that, the gamma factors involved here will not be time dependent. They are defined using constant velocities of objects or constant velocities of frames relative to one another, or both. So consider an object moving at velocity u with respect to the proper time frame. That, in and of itself, that object would be a frame of reference that's in relative motion to the frame in which proper time can be observed. So let's trade the old time derivative in the definition of momentum, that is, momentum equals mass times the first derivative of space with respect to time, for the derivative with respect to proper time. That is, momentum will now be defined as mass times the first derivative of space with respect to proper time. Now we want to convert that into any other frame, specifically into the frame where the momentum is being measured, which may not be the proper time frame. And to do that, we just substitute for d tau with the relationship between it and dt. And if you do that, you'll find that you now have mass times the first derivative of space with respect to time times a factor of gamma. So if this is a better definition of momentum, one that preserves the second law from Isaac Newton under transformations from frame to frame, then we should be able to show that. And the definition that we get from this exercise using proper time derivative instead of just the plain old time derivative is that the momentum of an object viewed from a reference frame is given by the gamma factor of that object relative to that frame times its mass times its velocity as observed in that frame. Now again, I want to be careful here because the gamma factor that appears here is very specific. It has to do with the gamma factor associated with the velocity of that object viewed in the frame of reference. The object itself could be viewed as a reference frame, of course, but because we're going to start talking about transforming object velocities into other frames moving at speed v relative to the one where we measured it, it's extremely important to realize that there are suddenly going to become multiple gamma factors in your equations. Some of those gamma factors will relate to the observation of the object and the passage of time relative to its frame of reference, And some of the gamma factors will be related to the relative motion of other frames of reference relative to the one in which you're defining momentum. And if that all seems confusing, it is, and the only way to get better at this is to practice, practice, practice. So the gamma factor here I've denoted especially with a subscript u to indicate that it is not the velocity of another reference frame, v, that appears in here, but rather the velocity of the object itself, u. And so this gamma factor is defined as 1 over the square root of 1 minus u squared over c squared. That's what gamma with a subscript u is going to refer to. Now, this redefinition of momentum can be demonstrated with a lot of algebraic pain to leave Newton's second law invariant. And in fact, this is accepted to be now the correct definition of momentum. I leave it to the viewer to go through the exercise sketched out on a previous slide to transform the momentum of an object observed in one frame into another frame moving at velocity v with respect to that first observing frame, and show that the form of Newton's second law, dp dt, remains invariant from frame to frame. Now, any good definition of momentum will hopefully respect the observations of the past, that at low velocities, the classical definition of momentum seemed to be good enough. If special relativity is the more correct general framework for describing space and time, then in some appropriate limit, in this case, low velocity of the object, we should be able to recover the classical definition of momentum. So let's give this a try. And I'm going to begin by writing the gamma factor for the moving object, gamma with a subscript u, as a binomial expansion. And I've used this before in an earlier lecture, so hopefully the rhythm of this will begin to look familiar. The binomial expansion is very useful for carefully step-by-step exploring what happens when you send a parameter of the theory, in this case the velocity of an object relative to that of light, closer and closer to one of its limits. So we'll start by writing down gamma subscript u with its traditional definition of 1 over the square root of 1 minus u squared over c squared, and then we can use the binomial expansion approach to write it instead as a series of terms of increasing powers of the velocity over c. So the first term is just 1, the second term is 1/2 u squared over c squared, etc. After that you have terms of order u to the fourth over c to the fourth, u to the sixth over c to the sixth, and so forth. Those terms matter when u over c is very close to 1. But when u over c is very close to 0, those higher order terms really don't matter so much compared to the lower order or leading terms in the expansion. So now let's write relativistic momentum using this series expansion of the gamma factor. So I have momentum is equal to gamma subscript u times mu, which is now this series expansion times m times u. And you'll notice now that I have an extra u to multiply into the series expansion. If I take m times u and distribute it to every term in the series expansion, I'll wind up with something that looks like this. The leading order term now has a dependence on velocity, but the subleading term has a dependence on velocity cubed over c squared. And then the terms after that are velocity to the fifth over c to the fourth, or velocity to the seventh over c to the sixth, etc. And as u approaches 0, that is, as the velocity of the object gets much lower than the speed of light, essentially as its velocity is sent towards 0, any terms that depend on u cubed over c squared or higher in this expansion are going to vanish. They're going to approach 0 much faster than that leading term of mu. The leading term will dominate the series expansion as u over c gets very small. So I can start from this expanded version of momentum using the binomial expansion, and in the limit that the velocity is much less than the speed of light, only the first term in the series will survive the one that's largest compared to the others as u over c goes to 0, and that's just m times u. We have recovered the classical definition of momentum in the limit of velocities that are small compared to the velocity of light. So we can proceed similarly now, having had some measure of success with looking at momentum as the quantity, the directional quantity of motion, thinking about kinetic energy, which is the scalar or directionless quantity associated with motion that can also be conserved. So let's begin to think about kinetic energy in special relativity. Did we really have the right definition in the old days? 1/2 mv squared, is that the relativistically correct definition of kinetic energy? Well, we can start by looking at the relationship between external forces, changes in states of motion, work, and kinetic energy. When an external force acts on an object and displaces it over some, for instance, straight line distance s vector, the action of accelerating this object under the influence of an external force represents itself a unit of energy being imparted to the object, and that energy is known as work. Work done by an external force changes the kinetic energy of the object. It was in a state of some kinetic energy, maybe 0, and then a force acted on it and accelerated it, and now it's in a different state of kinetic energy because its velocity has changed. That means that the work done by the force has had some action in changing the kinetic energy of the object, and according to the work kinetic energy theorem, the change in the kinetic energy of an object is directly proportional to the work done by the external force. Now, the work done by the force on the object, displacing it over, for instance, a linear distance s vector, can be written as the dot product of that external force and that displacement. Now, I'm taking some shortcuts here with the form of the work equation. This is for a constant magnitude force displacing an object over a straight line distance. That's not the general form of the work equation, and I will use the general form of the work equation in a moment. So let's assume a constant force acts on an object from the perspective of an observer in frame S. And of course, the form of that force and its relationship to the momentum of that object and the changes in momentum of that object will be given by Newton's second law. The force is equal to the change in relativistic momentum with respect to time. This is now the correct definition of momentum in that frame, and used in any other frame preserves the form of Newton's second law, which is F equals ma, or F equals dp dt. Now, let's say the force acts over a small displacement, a differential of a path, ds vector. And at any moment, it's related to the velocity of the object and the time over which the displacement occurs via the fact that the object velocity is the change in the path position divided by the change in time in that frame. In other words, u vector is ds vector dt. We can write the differential of work, the little bit of work done by that constant force over that little bit of displacement, by thinking about the definition of work itself in a more general form. That is, the little bit of work done in displacing the particle over a little bit of path, ds vector, by a constant force F, is given by the dot product of F and ds vector. Now, by Newton's second law, this has to be equal to the first derivative of the relativistic momentum with respect to time. That is what the force should be equal to. And again, that thing is dotted into ds vector, the little bit of displacement. But we can replace ds vector with its relationship to the instantaneous velocity of a particle under the action of this external force. ds is just going to be equal to u dt. Now, to simplify this dot product, I'd like to assume that the change in momentum is in the same direction as the force that's applied on the object. So the force is entirely directed in the direction of the displacement, or the change in momentum, or the change in velocity. And as a result of that, the dot product trivially becomes the product of the magnitudes of the two vectors. To find the total work done by the force, which is to be related to the total change in kinetic energy, if I can find the total work being done by this force, I can absolutely relate that to delta K, the change in kinetic energy, and perhaps arrive at the form for the kinetic energy. What we're going to do is we're going to integrate both sides. So by the work kinetic energy theorem, the change in the kinetic energy of the object, whatever equation that is given by the work done by the force on the object. And that is going to be the integral of this equation here. The sum of all the little bits of work should add up to the total work. And so that equates to taking the sum of all these little bits here. And if I pull out all the constants in all of this, I'm going to wind up with the mass times the integral of u times the quantity d gamma u. The dt's have canceled out here in this dot product, leaving us with just a differential of the gamma u times u. Well, that doesn't look like a very pleasant integral, but there is a way that we can get this into a more pleasing form, one that's more easily solved. I'm going to start by rewriting this relationship. Delta k equals w equals m times the integral of the speed times the differential of gamma u times speed. To get this into an easier to solve form, we're going to integrate by parts to get a final form for the integral. This is using the trick that the, for instance, integral of u dv is equal to uv minus the integral of v du. So let's make some identities between this more general form of the equation and the specific stuff that appears in the integral up here. I'm going to identify u as being equal to u. That's straightforward. I'm going to identify v as being equal to gamma times u. When I do that, I can then write u times v, which I need here, as gamma u times u squared. And then I need v times du. Well, v times du is just going to be equal to gamma sub u times du. That's pretty straightforward. Try this on your own. This will help you dust off your integration by parts. But you'll find that the integral becomes the following. The change in kinetic energy is given now by substituting in, using the integration by parts trick, as m times gamma u times u squared, evaluated at the endpoints of velocity, the initial velocity ui and the final velocity uf, minus the mass times the integral of gamma u du, again evaluated between the initial and final velocities. And if you work through all this, you'll get an equation that looks something like this. You have this first term, m gamma u times u squared, plus this second term, which looks a bit nastier, mc squared times the square root of 1 minus u squared over c squared. And we are to evaluate this at the endpoints of the motion. So let's do ourselves some favors here and assume that the initial speed of the object is 0. That means that the initial kinetic energy must also be 0. Whatever the equation for kinetic energy is, that's got to be true. The final speed we'll just set to be u, some final speed u that we achieve. And at that point, the kinetic energy is k. So substituting all this in, we find out that the kinetic energy is equal to m times gamma u times u squared plus mc squared times the inverse of gamma u minus mc squared. And rewriting this, doing some algebraic gymnastics with the gamma factors and mc squared, you'll find that this can be simplified to this lovely little equation here. The kinetic energy of a particle is simply given by the quantity of its gamma factor minus 1 times mc squared. Now, I'm going to let you show that last step on your own. It's good practice for the gamma factor gymnastics that you'll often have to do in these problems. We find that the relativistic kinetic energy is just gamma u minus 1 all times mc squared. M is just the mass of the object, c is just the speed of light, and gamma u is its gamma factor relative to the frame in which the object is being observed. You can use the binomial expansion trick once again, and I encourage you to try this on your own, in the limit that the velocity is much, much less than the speed of light, and you'll find that the expression reduces to 1/2 mu squared, the classical definition of kinetic energy. These quantities for momentum and kinetic energy have all the right behaviors. They don't look like what they looked like in their assumed classical forms, they reduce to their classical forms in the appropriate limit, and they leave laws of physics invariant where they can be applied. Now, we've looked at momentum, and we've looked at kinetic energy. But what about the total energy of an object in special relativity? In classical physics, the total energy of an object was just its kinetic energy, and if it wasn't moving, it was said to have no energy. Now, that's not entirely true. If that object was being acted on by an external conservative force, it's possible that that object could have some potential energy associated with it. For instance, if you raise a ball up in a gravitational field, it has some now stored potential energy. If you let the ball go, it will be released and turned into kinetic energy. But for a force-free situation, an object at rest really had no defined energy in classical physics. Is that still true? Well, we can start by just simply noting that, as before, the total energy of a body in any system is composed of at least two parts: a kinetic part describing the energy associated with its motion, and a potential part describing any energy that is stored internally in the system and that could be released by some means. Now, the total energy then is the sum of these two pieces. So I will use capital E to denote total energy, K to denote kinetic energy, and U to denote potential energy or stored energy. We see that kinetic energy in special relativity is the difference of two pieces. K is equal to gamma mc squared minus mc squared. So if we rearrange the above total energy equation and then plug in this expression for kinetic energy, we arrive at an interesting preliminary conclusion. So if I take K and solve for that using the above equation, I find that K is equal to the total energy minus the stored energy. And if I substitute in with this equation, I find that K is also equal to gamma umc squared minus mc squared. And by identifying and relating terms in these two equations for K, I can draw the conclusion that the total energy of an object is given by gamma u mc squared. And the stored energy of an object, even one that's at rest, is mc squared, its mass times the speed of light squared. So by this identity, the total energy of an object in special relativity is given by gamma umc squared, and in the limit that the object is at rest, we see that the total energy becomes not zero, but mc squared, mass times the speed of light squared. And we note that this same quantity, mc squared, has been identified in the above exercise as a kind of energy stored somewhere in the object. What's particularly remarkable about this exercise is that, by our own means, we arrive at a conclusion that Albert Einstein too arrived at in his miracle year in 1905. It's one of the most profound conclusions drawn from special relativity, that mass is itself a form of stored energy, and even when a body is not moving, its total energy is not zero, but rather decreases to a minimum given by E equals mc squared. And this latter equation is one of the most famous in the history of science. It is an equation that would lead to the development of nuclear weapons, nuclear power plants, the PET scan, a non-invasive medical invention, the particle collider, and many other technologies taken for granted, feared, or loved in the modern world. For an indivisible, fundamental particle, for instance, the electron is a pretty good example of this. We've never seen that the electron is made of anything else. One has to conclude that when it's at rest, its energy is the result of some kind of intrinsic mass, a fundamental property of matter, just like electric charge appears to be a fundamental property associated with matter. Now, it's interesting to ask yourself, well, how much energy, if I could find a way to convert it into some other form, is contained in the mass of an object? Well, consider the fact that a typical-ish human being has a mass somewhere in the realm of 60 kilograms. And if by some means all of that could be converted to another form of energy, like kinetic energy or chemical energy or radiation, then the above equation tells us the energy in joules that this represents. E equals m times c squared, which is 60 kilograms, times something that's about 9 times 10 to the 16 meters squared per second squared. And this yields a total energy in joules, stored in your body in the form of mass energy, is 5.4 times 10 to the 18 joules. Now, for comparison, the energy, the little sliver of energy that reaches the Earth from the sun every second a tiny bit of the total energy that the sun can emit, and yet the same energy that keeps our planet warm and hospitable to life as we know it. That energy is 10 to the 17 joules. The stored energy in the form of mass energy in your body is a factor of 10 more than that. And if even a fraction of it could be converted into some other form of energy, it represents a terrifying amount of potential. So let's do an example of this sort of hidden energy of matter by considering the mass that's lost by a uranium nucleus during fission, the process of breaking that nucleus into pieces. Nuclear fission was itself first discovered by physicists and chemists Otto Hahn and Fritz Strassmann, and this was done in Germany in December 1938. If you know anything about your history, this was the period of Nazi rule of Germany. Now, the observation of nuclear fission, especially the fact that the uranium nucleus was observed to split into nearly 2 equally massed parts, was a bit of a mystery, and it was explained very quickly thereafter by physicist Lise Meitner and her nephew Otto Frisch. The physics community came to understand that what was going on here, just in breaking up the nucleus of a uranium atom, was the potential of a vast power that lays in the hearts of all unstable atoms to be unleashed on humankind. So consider the process shown at the left. This little blue ball is supposed to represent a neutron, one of the components of a nucleus. They can be freed from the nucleus and fired at other nuclei. A neutron striking a U-235 nucleus will set off a chain of events that results sometimes in it breaking up into roughly equal mass pieces. A nucleus of the element krypton, krypton-92, and a nucleus of the element barium, barium-141. Now, the mass of the unsplit U-235 nucleus is given in atomic mass units using this number, and I'm keeping the precision on purpose because small differences when it comes to mass energy matter a lot. Now, the masses of the daughter nuclei, krypton-92 and barium-141, are 83.798 atomic units and 137.327 atomic units, respectively. Now, I should note that for purposes of conversion, one atomic mass unit is given roughly as the mass of a proton, 1.6605402 times 10 to the minus 27 kilograms. Now, if you check, the daughter masses do not add up to the parent mass. Mass is not conserved in this process. It's lost in the fission process, and the amount of mass that is lost is roughly 14 atomic units. Even accounting for the fact that 3 neutrons get produced in the fission process, that only adds up to roughly 3 atomic mass units. That's still 10 atomic mass units or so of energy left over that could be converted into forms like kinetic energy or heat. Now, since we've checked that the daughter masses don't add up to the parent mass, we recognize that there's missing mass energy here. And that mass energy that's missing is about 2.1 times 10 to the minus 9 joules, about a billionth of a joule. Now that doesn't sound like much, but consider what's going on in this cartoon at the left. 3 neutrons have also been produced in this process. 3 neutrons that are bullets that can be fired at other U-235 nuclei that might be lingering nearby. For instance, if you highly enrich uranium to greater than 90% pure U-235, it's possible to set off a reaction of events that cannot be stopped and has catastrophic consequences. This process can initiate what is known as a chain reaction, as you multiply the fission process over and over and over again using these neutron bullets that get produced from the first fission process. So for instance, the first split makes 3 to the 1 neutrons. The second generation of splits makes 3 to the 2 neutrons, because each of these neutrons goes on to split a uranium nucleus that produces 3 neutrons. So that gives you 9. The third generation gives you 3 to the 3, or 27. A typical chain reaction in purified U-235 can go something like at least 40 to 50 generations before this device will blow itself to pieces. That's a multiplicative factor of about 3 to the 45, or 3 times 10 to the 21. So you're taking the energy left over from one split, and you're multiplying it by about 10 to the 21. Now, those neutrons won't all go on to split uranium nuclei. Some of them will be thermalized and will result in dumping thermal energy into the body of the material or into the surrounding air around it. If the energy of those neutrons is converted to heat from collisions, you'll find that this level of multiplication is sufficient to explain the explosive yield of the very first uranium atomic weapon, codenamed Little Boy, which was equivalent to about 13 to 18,000 tons of trinitrotoluene, or TNT, being dropped on a single city. That's 54 to 75 trillion joules of energy. That weapon devastated the Japanese city of Hiroshima at the end of World War II. So we can see that a little bit of mass energy goes a long way, and it can have positive applications in society, it can have negative applications in society. But all of this stems from the revelation that energy and mass are not distinct from each other. Now, in classical or Newtonian Galilean physics, there is a relationship between momentum and kinetic energy. We know that. It's K equals P squared over 2m. Go ahead and try it yourself if you've never seen this before. Convince yourself that this is true in classical physics. P equals mv, K equals 1/2 mv squared. Do the substitution. There's a relationship between kinetic energy and momentum. Now, in the more correct description of space and time given by the special theory of relativity, we have kinetic energy, mass energy, and momentum. What is the correct relationship between these things? Let's begin with the momentum equation. That is, momentum is equal to gamma u times m times u. Let's then insert a sort of clever multiplicative 1. Multiply this equation by c over c, which has the effect of just multiplying the equation by 1, but allows us to distribute the c in a useful way. We can take the denominator, 1 over c, and move it to the left and associate it with the velocity of the object u. So we wind up with a term of u over c in this equation. Now, we know that the equation for total energy has c squared and gamma u in it, and gamma u depends on u squared over c squared. They're related to each other. So I recommend you try squaring this above equation. Square p, which then squares this thing on the right-hand side, gamma u times m times u over c times c. And when you do that, you get this equation here. Now, if you then use the fact that u squared over c squared can be related to gamma by 1 minus 1 over gamma squared, you can then insert that, and you find that p squared is equal to m squared c squared times the quantity gamma u squared minus 1. Now, if you stare at this for a moment, you'll notice that this equation has a piece in it that's awkwardly close to E squared. E squared, the total energy, would be given by gamma squared m squared c to the 4th. So multiply both sides of this equation by c squared. We wind up with p squared c squared on the left. This is going to be equal to m squared c to the 4th times the quantity gamma squared minus 1. If we then distribute the m squared c to the 4th into the parentheses, we wind up with this equation. And we can identify the first piece here as e squared, and the second piece here as m squared c to the 4th, or the square of mass energy. So, putting it all together, we find that energy and mass and momentum have a relationship to each other. And it's an elegant relationship between an object's total energy, its momentum, and its mass energy in special relativity. And that relationship is given by this quadratic equation. E squared equals p squared c squared plus m squared c to the 4th. Now, this equation allows us to think about some cases of certain kinds of particles. And one very interesting special case is to look at particles that have no intrinsic mass. Now, the electron is a particle with intrinsic mass. The muon is another example of a particle with intrinsic mass, albeit 207 times that of the mass of the electron. But we can ask ourselves, what if there is a particle out there in nature that has no intrinsic mass? Can it exist? And if it did exist, what would its properties be? Well, let's take a look at that. We can use these relationships to study this very special case. Now, it will turn out that photons, which are the particles involved in light, have never been observed to have an intrinsic mass. They behave as if they have no mass at all. So let's go ahead and take that exact limiting case of m equals 0. And if we plug that into the energy, momentum, and mass energy relationship, we find that we're left with E squared equals P squared C squared. That is, we can take the square root of this and say that the total energy of a massless particle is given by its momentum times the speed of light. The total energy of a massless particle is entirely energy of motion. In other words, if such a particle could be stopped from moving, you would have to interpret it as them ceasing to exist. Their total energy would suddenly become 0. But of course that violates the conservation of energy. You can't just make energy go away without consequence. So this implies that such particles can actually only be stopped when they're removed from the natural world by being absorbed into another process. Now, you might then feel emboldened by this and say, aha, well, this is great. I'm going to go ahead and figure out what E and P are for massless particles. But then you very quickly run into a problem. And that is that E depends directly on m, and P depends directly on m, as defined in special relativity. And so you get no useful information from these equations from special relativity. Special relativity can't give you otherwise useful information about what the total energy actually comes from and what the momentum actually comes from for such particles. So what is it that defines energy and momentum of a common particle like a photon, which so far as we know has no intrinsic mass, no mass energy? Well, to answer that question, we're going to have to wait a little bit longer and see as we enter the next phase of this course. So to conclude this lecture, let's look at what we have learned. We have learned how to define kinetic energy and momentum while incorporating the principles of special relativity. And in doing so, we've learned something deep about the nature of mass, and we've learned to appreciate that there is intrinsic mass in nature, and that mass in general is associated with a kind of internal energy of all objects. An object at rest does not have zero energy. It has internal energy given by mc squared. We've also learned about the relationship between energy, momentum, and mass. We've looked at some applications of the relativistic concept of energy, momentum, and mass, and we've left ourselves with some questions that we can hopefully resolve by delving deeper into nature in the next phase of the course.
Before we get started on this lecture, on the first glimpses into the general theory of relativity, I want to kind of put a little cautionary warning label at the beginning of this video. In any textbook at the level of a course like this, and certainly in this lecture video, I don't want you to walk away with a feeling of full confidence that you have completely understood the generalization of the theory of space and time that Einstein set in motion in 1905 with what we call the special theory of relativity. Relativity is an extremely rich subject. You can quite literally fill volumes on this particular bit of material, and in fact I'm holding one of them in my hands now that I'll show you later. The general theory of relativity is fundamentally built on a rich and complex set of mathematics that students at the level of a course like this simply have never seen and cannot be expected to master in a week or a month or even 3 months without really first having had the full breadth of undergraduate mathematics. Now that said, there are nuggets of ideas and mathematics that one can draw out of the general theory of relativity and use to motivate, in the context of special relativity, the implications of the grander theory of space and time. Since 1916, when Einstein first established the calculational framework, the reliable calculational framework that set the stage for the general theory of relativity and all the work that would be done with it, students have struggled with this material because it challenges many preconceived notions, many concepts that we walk into any standard science class cherishing. So I want you to be a little bit forewarned, first of all, that the nuggets that we will draw out of the general theory of relativity and analyze in the context of special relativity can have some stunning implications that either will challenge things you already believe to be true, or which open your eyes to the grander scale of the cosmos that we inhabit. Now, I mentioned this book earlier. This book is one of the seminal works in the field of physics on the whole of the general theory of space and time. And it's entitled Gravitation. Its three co-authors are Charles Misner, Kip Thorne, and John Archibald Wheeler. Now, all three of these individuals, each in their own way, are considered some of the brightest lights of 20th and 21st century theoretical physics. And this book is expansive in its treatment of the subject. I mean, look first of all at how thick this book is, and if you flip through this, you will quickly see that most of us would be out of our depth in the level of mathematical rigor and notation and variety and subject matter that is minimally expected in order to follow along with a text like this, certainly to its bitter end. All of this is to simply point out that the general theory of relativity is complex and rich, and mathematically far beyond the scope of a course at this level. Now, that said, we can draw nuggets of ideas out of the general theory of relativity, and we can put them in context in our own course experience for a course at a level like this one in modern physics. Now, some of the names on here may seem familiar to you. Kip Thorne, for instance, has become recently famous not only for winning the Nobel Prize in Physics for one of his key bits of work on space and time, energy and matter, and the theory that links them together in general relativity, but also because he has served as an advisor to film and TV, including things like the movie Interstellar from 2014, which had some of the most advanced visualizations of physics based on the general theory of relativity in any movie that came before it or since then. John Wheeler is another bright light in the field of theoretical physics. He will feature briefly later on in this lecture in the context of an individual who could not only deal with the mathematics of this subject, but elegantly communicate to an audience, even at the level of our course, the grandest sweeping summary of the general theory of relativity and its implications for energy, matter, space, and time. So, with all of those caveats in mind, let's pluck some interesting nuggets of ideas out of the general theory of relativity, place them in a local context in special relativity where we feel more comfortable with the mathematics, albeit with the caveat that the mathematics required to really do this treatment is far beyond our grasp at this stage in a physics course at the university level, without the full breadth of undergraduate mathematics behind us quite yet. Let's see what those nuggets tell us should be revealed about energy, matter, space, and time. And then let's look at how those ideas have implications for the whole structure of the cosmos in which you and I live. So, with all of those things in mind, let's start digging into some of the basic ideas that motivated the general theory of relativity and take a look at some of those nuggets of ideas that we can couch in the picture of special relativity that we're a bit more comfortable with at this stage of our engagement in physics. In this lecture, we will learn the following things. we will learn about the transition in thinking from the special to the general theory of relativity. This will by no means be comprehensive, but merely a taste of some of the basic ideas that led Albert Einstein ultimately to construct this theory of space and time. We'll look at some implications of the general theory of relativity on specific physical phenomena, and we'll look at some of the large-scale implications for space and time. Let's talk a little bit about the transition from special to general relativity. Experiments on the speed of light in the first and second decades of the 1900s continued to yield no disconfirming evidence for the postulates of special relativity. Now, Einstein's physics work in 1904 and 1905 and beyond earned him the faculty position that he had so richly sought after his PhD, and he was able to escape the job as a patent clerk in Bern, Switzerland, and finally take on the mantle of the academic position that he had hoped for after earning his PhD. He was sure that the special theory itself could be generalized to a complete theory of space and time, including, he hoped, an explanation of the nature of gravity itself, the very prize that had eluded Isaac Newton. All that Isaac Newton could establish was that his law of gravitation correctly described the behavior of gravity on all scales that could be observed at the time. Einstein ambitiously pursued the elusive prize that Newton could not grasp, and that was to finally unmask the nature of gravity itself. Now, this work would take another decade of struggle. Einstein would fail many times, and in fact, if you look at the record of Einstein's work in the decade that followed his miracle year, there were some serious missteps in papers that he had published based on his work beyond the special theory of relativity. And had anyone been able to mount an experimental test of the claims of the general theory of relativity prior to 1916, Einstein might have been laughed off the scene of physics. But it took more than 10 years to be able to make an observational test of one of the key predictions of the general theory of relativity. And that ultimately saved Einstein, buying him the time he needed to fully develop the mathematics behind the general theory, put on firm ground, theoretically speaking, the predictions of the theory of general relativity, and to finally publish key papers in 1915 and 1916 that are considered the first accurate and fairly complete treatment of the subject from Einstein himself. Now, interestingly, in order to lay the groundwork for the general theory of relativity, Einstein required much of the advanced math that he had eschewed during his time in graduate school, one of the things that offended many of the faculty that had him in his classes. He was forced then to go and actually relearn subjects that he had actively avoided in some cases during his PhD education. He benefited from a close network of friends who were outstanding physicists and mathematicians in their own right, and through his network of friends he was able to build his own foundation strong enough to eventually lead to his key insights and firm mathematical grounding of the general theory of space and time. In this lecture, we will explore some of the very basic ideas and tease the larger implications of the general theory. It's very difficult at this level, as I have warned you before, to give you the full treatment, but I will do my best with the aid of the textbook that we use in class to attempt to communicate some of the key nuggets and frame them in the language of special relativity, which we've developed more carefully over the last few weeks. Let's begin with a tale of two masses. We take for granted in introductory physics that mass appears in a large number of equations. But if you really boil it down,
mass as a concept appears in two distinct equations in introductory physics. The rest of the equations that we use that involve mass can be found to stem from these two laws of nature. Now, what's interesting, and what may not have been pointed out in introductory physics, was that the two equations do not necessarily have anything specific to do with one another as regards mass itself. The two equations in question are Newton's second law of motion, F equals ma, where mass appears as the multiplicative scalar factor in front of acceleration, the constant of proportionality between what an external force of a general nature exerts on a body and the responding change in the state of motion, the acceleration of the body. But mass also appears in an equation that describes the nature of a very specific fundamental force, gravity. The law of gravity states that the force of gravity between two bodies, which we might label 1 and 2, is proportional to the product of their masses divided by the square of the distance between them. Now, the m for mass that appears in Newton's second law has to do with inertia, the tendency of a body to resist changes in the state of motion. And so it's more honest to say that Newton's second law is concerned with a mass concept we might label inertial mass, the mass of a body that resists changes in state of motion. But the m that appears in Newton's law of gravitation has to do with the primary cause of the gravitational force between two bodies that have mass. This doesn't necessarily have anything to do with their tendency to resist changes in the state of motion. It has all to do with the degree of the gravitational attraction between the two bodies. This is more honestly referred to as gravitational mass, potentially distinguishing it from inertial mass. There is nothing in these two laws that says that these two quantities, these two kinds of mass, have to be fundamentally the same. And yet, their equivalence, the equivalence of inertial mass and gravitational mass, has been tested to a remarkable precision. Inertial mass and gravitational mass appear to be one in the same. Let's take a look at this by briefly stepping through some mathematics, now couched in the language of inertial mass as potentially distinct from gravitational mass, and revisit some conclusions we drew in introductory physics. So, a consequence of their equivalence is often taken for granted. What if they weren't equivalent? Well, if they weren't equivalent, then we would rightly state that two bodies that are acting on one another through the gravitational force can have their degree of acceleration explained by Newton's second law, but without necessarily equating inertial mass and gravitational mass. For example, if we consider the Earth to be pulling on a body, say you jump off the surface of a table in an attempt to accelerate down to the floor and land on the ground. The Earth is attracting you down toward its center. We can figure out the local degree of acceleration due to the gravitational force by taking the product of Newton's gravitational constant g, the mass of the Earth, and dividing by the distance between you and the center of the Earth squared. Now, we multiply that acceleration, which we often denote little g for gravitational acceleration, times your gravitational mass. And we set that equal to your inertial mass times your total acceleration. Now, if we then solve for the acceleration due to gravity, we find that this would be equal to this gravitational acceleration, little g, or big G times the mass of the Earth divided by the distance between you and the center of the Earth squared, times the ratio of the gravitational mass and the inertial mass.
And if we were to substitute for little g, 9.81 meters per second squared here, we would conclude that if gravitational mass and inertial mass are not the same, if, for instance, the gravitational mass were 10% of the inertial mass, that only 10% of your inertial mass has anything to do with causing the force of gravity, well, then we might conclude that your acceleration might be very different than a body that has more mass. But we don't observe that. When two objects of different masses fall in a uniform gravitational field, a field of uniform gravitational acceleration, if you will, all bodies, even though they possess of different masses, appear to fall at the same rate. And so by eye, you can already draw the inference that gravitational and inertial mass are, if not equal to each other, very close to one another. And as far as the limits of our ability to test this have taken us, we've never seen a difference between gravitational and inertial mass. They really seem to be one and the same within the limits of experimental methodology. This leads us into one of the key insights that Albert Einstein had early on in the process of trying to generalize the ideas of space and time to include gravity. This is summarized by the phrase the equivalence principle. Now, I've pointed out that observationally there seems to be an equivalence of gravitational and inertial mass. And this can lead you down the path, as it did along with some thought experiments for Albert Einstein, to a larger consequence. And that is the principle of the equivalence of a system accelerated by a constant force, or alternatively experiencing a constant gravitational field. The principle of equivalence, in the language of relativity and space and time, is about the equivalence of two different situations. One in which a system is experiencing an external force of some kind that causes it to change its state of motion, like a rocket or something pushing on something else. The equivalence of that system and a system that's experiencing a gravitational acceleration that pins objects to a low point in the system. And I will illustrate this. Einstein observed early on in his thought process about all of this that due to the equivalence of these two kinds of mass, inertial mass and gravitational mass, there's really then no difference between being under the influence of a uniform and constant gravitational field, or source of gravitational acceleration, or instead being placed in a non-inertial reference frame, one where there is an observed net force acting on all the parts of the system by the action of some other kind of external force. This picture illustrates the idea in a rather cartoonish but elegant way. The scenario I like to have that goes along with these set of pictures is the following. Imagine you wake up and you find yourself in a room with no doors and no windows. There's no way to see past the walls of the room at all. As I like to joke with people, this is like the premise of the opening scene of some kind of cheap horror movie. You push yourself up from the ground, you feel gravity pulling you down, and you have to work against gravity to raise yourself up. That's what it feels like to you. Now on the floor next to you was a red ball. You lean down and you lift up the red ball, and you hold it out roughly at arm's length and level with your shoulder, and you let the ball go. And indeed, you observe that the ball falls down to the floor of the room. You then check your watch. Think about the average height of a human being, measure roughly how long it takes that ball to make that drop from shoulder height to the ground, and you're relieved to find out that you seem to still at least be on Earth, albeit you have no other external information to tell you where you are, because the ball appears to fall at a rate of acceleration consistent with g at the surface of the Earth, 9.81 meters per second squared. But in reality, in this opening scene of this cheap horror movie, the camera zooms out and gets a view from outside of the enclosure in which you have woken up, and reveals that you're not on Earth, but rather far from all planets and stars in empty outer space. being accelerated upward from your perspective by a rocket that you can't hear through the soundproof and vibration-proof walls of your little prison. And that rocket is accelerating you upward at 9.81 meters per second squared. So from your perspective in the sealed room, you think that objects are falling down in a gravitational field, or that you have to work against a gravitational field to lift yourself off the floor. But in reality, what's going on is the entire system is being pushed by an external force, experiencing an acceleration in one direction of 9.81 meters per second squared, which gives you the illusion inside the room that you're in a gravitational field, even though you're not. How would you be able to tell the difference between these two situations? A soundproof, vibration-proof, windowless, doorless room with no external reference information to tell you that you're moving or not in outer space. And a gravitational field on Earth under the same conditions, where, yes, you're on the surface of a planet, but you have no external information that tells you that. A ball dropped in either of those two environments will look and behave the same way. And it was this insight, or a variation on it, that led Einstein to realize that a constant acceleration due to gravity is no different from taking a reference frame and accelerating it at a constant rate.
As a visual test of the equivalence principle, let's see if you can tell the difference between the following two situations: a zero-gravity environment and an environment that's in free fall in a gravitational field. Take a look at the video on the left and the video on the right. Which one do you think is shot in a zero-gravity environment? Which one do you think is shot in a free fall environment where a gravitational field is present? The answer is that neither of these is in a zero gravitational field environment. This may surprise you. Maybe you recognized somebody in one of the videos and said, aha, that person's an astronaut. Therefore, this video must have been shot in zero gravity. But in fact, both of these videos are depicting life in a locally inertial reference frame in free fall in a gravitational field. The video on the right is shot in something known as a reduced gravity flight, an airplane that makes a parabolic arc through the sky and briefly enters free fall in the Earth's gravitational field, close to the ground. The video on the left is shot in the International Space Station. The International Space Station may be far above the surface of the Earth, but the acceleration due to gravity is actually quite strong in its orbital position. However, the International Space Station is orbiting the Earth every 90 minutes, and as a result of this circular motion, it's actually in free fall constantly. It's just missing the Earth because it's moving to the side every time it falls down a little bit. It's almost impossible to the human eye to tell the difference between life in a free fall frame of reference in a gravitational field and life in a zero gravity environment. That's no accident. That's the equivalence principle in action.
Einstein then defined the concept of a locally inertial frame by imagining not this situation I've described here, but a system in which a person, for instance, is in free fall in an external gravitational field. The concept of a locally inertial frame of reference is one in which all parts of the system are experiencing a constant acceleration due to gravity, but because all parts are accelerated the same way, it's as if the system is entirely free of any external forces. It's as if everything is in an inertial reference frame with no external forces, because all of you are accelerating at the same rate at the same time. This is an incredible insight. It may not seem that impressive, but it frees you very suddenly from thinking of gravity and acceleration of an entire reference frame of things as different things. And it was this insight that freed Einstein to think about gravity in a completely new way, as another aspect of space and time. The key idea here is that without external information in any of the situations I've just described, being in free fall above the surface of the Earth, or being inside a sealed room with no windows and no doors that's vibration resistant and sound resistant, without external information, there's absolutely no experiment you could do in any of those situations that will tell you that the system is either away from a gravitational source or simply in free fall in a gravitational field. These all seem like inertial reference frames as a result of that. Now, since there is no difference between gravitational acceleration and the act of changing a whole reference frame into a non-inertial reference frame, you can analyze phenomena in a situation, for instance, where an inertial frame of reference is considered instantaneously inertial. That is, although it experiences overall some acceleration, like taking a whole room, strapping a rocket to the bottom of it, and accelerating the entire room and all its contents up at 9.81 meters per second squared, you're doing that equally and fairly to all parts of the system. And so at any moment in time, all elements of the frame will have the same velocity. Now, of course, if you take an object off the wall of this frame of reference, hold it out and drop it, it will appear to fall down, because once you let go of it, it's no longer part of the frame of reference. It's not bound to it in any way. And so it will appear to fall down as if under the influence of an external gravitational field. But of course, what's really happening is that the floor of the reference frame is being accelerated up toward the object, now freed from the bonds of the reference frame, at 9.81 meters per second squared. Perspective is everything. It's the relativity of whether you're falling in a gravitational field or whether the floor is rushing up toward you at the same rate. It's the ambiguity in those perspectives that lead to the key insights that blossom into the general theory of relativity. So, in order to help us to picture this, let's consider reference frames in the same way that we've done this in special relativity before. Let's imagine a frame that's we're going to always take to be exactly and absolutely at rest. We choose which frame that is, and then we define it as the rest frame. It's our choice to make. It doesn't matter which one we pick. I'm going to choose this one with x and y coordinates as the absolute rest frame. Now, the frame over here with our friendly observer in it, it's labeled as having its own axes, x prime and y prime, for instance. And I've exaggerated the x-axis here only because I'm going to need some room on this as I start to play around with it. But at first, at time 0 in our little thought experiment here, the rest frame and this frame are in the same state of motion. The velocity of what will become the moving frame is instantaneously 0 at time 0. And so it too, instantaneously at time 0, is a rest frame. But this frame, which I've labeled with prime notation, is actually experiencing a net constant acceleration a. And in the next instant of time, its velocity changes from 0 to something non-zero. In this case, it goes to being a teensy bit above 0, a little differential of velocity dv above 0 in the I hat or positive x prime direction. So it was at rest, same as the actual rest frame, and an instant later it is no longer instantaneously at rest. Instantaneously now it represents a moving frame, s prime, at velocity dv relative to what we consider the actual rest frame. But that acceleration continues to act. And so in the next instant of time, the velocity is increased again to twice dv. And so now, while at this instant of time, it's another inertial reference frame, albeit with a different velocity relative to the rest frame, it is the result of an acceleration that has been acting on the system the whole time, from time 0 to time 1 to time 2. At each instant in time, this frame is inertial because it has a well-defined velocity at that moment with respect to the rest frame. But overall, we can clearly see that this is a non-inertial reference frame, one that is experiencing a net acceleration, and a person in that frame would conclude overall that there must be some external force acting on the system, because they will see objects freed from their frame of reference to behave as if an external force is acting on them. Now, let's start to dig a little bit into some of the implications of the more general view of space and time, now that we've freed ourselves and allowed for the equivalence of a gravitational force to a frame that's non-inertial, experiencing an external acceleration by any means necessary. Now, using this imagery of frames that are instantaneously inertial, but overall non-inertial frames of reference, let's analyze an observation of light that has been emitted during this period of slight accelerations of the frame of reference S'. So let's consider a light source, this black dot here, that's pegged to the y-axis of frame S'. It's fixed in that frame. It's bolted to the wall. We can consider the y-axis to be a wall in the frame of reference. The x-axis is like the floor of the frame of reference. The person is firmly rooted on the frame of reference. And they're experiencing only a slight acceleration. It doesn't totally knock them off their feet to be accelerated. It's a very gentle acceleration. The speeds that we will consider always in these examples will be very much less than the speed of light. This will help us to get at the implications of general relativity without having to dig into the full general mathematics of relativity, which is much harder. So this is our situation. At time 0, we have our happy observer. They're looking at this light source on the wall that could emit a pulse of light at any time. And in fact, at time 0, we're going to allow the light source to send out a wave of light. So at that moment, t equals 0, it emits a wavefront. But at the same time, the frame is accelerating. It's been accelerating, and instantaneously at time 0, its velocity happened to be 0. So it was in our rest frame, as we've defined it. But at that moment, time 0, the light source pulses, emits a wavefront, and that wavefront, of course, being light, is going to travel at a velocity of exactly c from the perspective of any observer in any frame of reference. And it will travel from the left to the right, from the above the origin of the S' coordinate system, where the light source is pegged, toward the observer over here at some other coordinate along the horizontal axis in frame S'. So we have a light wave, a wave front, traveling at c, released from its prison in the light source at time 0. Now, at some time later, the light wave will cross the gap between the light source and the light observer, and the light observer will see it. But what will the observer see? Because in that time that it took the light wave to cross the gap, the frame has changed its state of motion from 0 to some velocity dv. Will the observer see the light wave as it was emitted from the source, or will they see something else? Let's take stock of the key elements of this question from the picture that I showed you on the previous slide. First, the light was emitted originally from a source that was considered to be at rest. That light was emitted with frequency f at the source, f source, and wavelength lambda, also defined at the rest frame of the source. Now, the light source and observer remain a fixed distance apart the entire time in this question because they both accelerate together. The system is experiencing only gentle accelerations, not enough to knock the observer away from their spot on the x-axis. So they remain planted at their position, the light source is bolted to the wall, the whole thing is accelerating together at the same rate. So their state of motion is changing instantaneously in the same way at every moment of time. And so there is no change in the distance, call it capital L, between the source of the light and the observer of the light. Light travels at c, 2.998 times 10 to the 8th meters per second, no matter the frame of reference in which it was observed. It was emitted in a frame that was at rest. It will be observed in a frame that is moving, but no matter the state of motion or the change of the state of motion of that frame of reference, the observer, if they were measuring the speed of this wave, is always going to say it moved at c. The light will take a finite, non-zero time to travel to the observer from its source. It has to cross a gap. That's going to take some time. and by the time the light reaches the observer, they will have entered a state of non-zero velocity. From the cartoon on the previous page, they went from 0 to 0 plus a little bit due to their acceleration, and I've called that little bit a differential of velocity, dv. Therefore, the light wave in the end will be observed in a frame of reference that is now moving with respect to the frame of the source, which had been a rest frame. What does this sound like? This sounds an awful lot like a Doppler shift problem. Light being viewed in a frame that's moving with respect to the original frame of emission. This basic insight then guides the math within the framework of special relativity that we can do to calculate just what the observer will see. So let's do some very basic calculations with this, building on top of all of the stuff that we've been looking at over the previous lectures and time in our course. I have emphasized this before. I'm going to codify it now. I want us to assume that we are in an instantaneously inertial reference frame. That is, at any moment in time, we have a definite velocity that's well defined, albeit changing from moment to moment to moment to moment. We want the velocity of that frame to be greatly less than c, not even close to the speed of light, less than 1% the speed of light, or even smaller. And that's so that we can have v over c, which we've previously defined as this nice number beta, to be much, much less than 1. This is going to come in handy very quickly in this problem. Let's assume, again, as I pointed out before, that the distance from the light source to the observer, which is fixed this whole time, is some length L. Because the light source travels in the same frame as the observer, L remains constant the whole time. The light will take a time, which will denote delta t, t2 minus t1, t1 being the time of emission, t2 being the time of observation, and that's going to be given by L divided by c. Light has to travel across a gap of length L. It does so at a fixed speed c, the speed of light. The time that will take is L over c, full stop. Now in that time, delta t, the frame of the observer will have accelerated by an amount a, up from rest to a velocity v. And we can actually then analyze this using the very same equations of motion from introductory physics, which are still valid here for the conditions that we're looking at. There we could relate initial velocity to final velocity by considering the acceleration of a system and the time over which the acceleration acts. This equation will do nicely. The final velocity v will be equal to the initial velocity v subscript 0, or v naught, plus a term that's the acceleration times the time that is passed over which the acceleration has acted. Now we can plug in some specifics here for us. V will be equal to 0, the initial velocity of our instantaneously inertial reference frame, plus the acceleration times L over c, which is delta t, the time it takes for the light wave to get from the source to the observer. This then leads us to the conclusion that v is equal to a times L divided by c. And if we transform this into an expression for beta, we find that beta, which is v divided by c, is given by the acceleration times the distance divided by the speed of light squared. Now, let's take this information and let's put it into the context of the Doppler shift, the relativistic Doppler shift, specifically the special relativistic Doppler shift. So we're going to treat the case of small velocities relative to light. Beta is a small number. The Doppler shift of the light wave by the time the observer sees it will be given simply by what we did before. We take the frequency of the source, we multiply it because the observer is in a frame that becomes a frame that's moving away from where the source was. We have to multiply by the square root of the quantity 1 minus beta divided by 1 plus beta. This represents a lengthening, ultimately, of the wavelength of the light, a redshift. But we want to get acceleration of the frame, the distance between the light source and the observer, and the speed of light into this equation. We want to put these things from our picture into this equation. And the way we can do that is by doing some binomial expansions of the numerator, the square root of 1 minus beta, and the denominator, 1 over the square root of 1 plus beta. Well, if you do those two things and multiply them, do the binomial expansion of the square root of 1 minus beta of 1 over the square root of 1 plus beta, multiply those together, you find you get expansion products that look like this. 1 minus a half beta plus terms that are higher order in beta, and 1 minus a half beta. The same thing again, plus again higher order terms in beta, which I've just left out but indicated that they're supposed to be there from these three dots. The product of these things is multiplied by the frequency at the source of emission. Now, because we're working in the case that beta is a number much smaller than 1, because v is much smaller than c, we only have to keep the leading terms in all of this. And if we multiply out this product and then only keep the leading terms in beta, we wind up finding out that this product is approximately equal to just 1 minus beta, all times the frequency at the source of emission. Now, we have an expression for beta in terms of the acceleration of the frame, the distance between the source and the observer, and the speed of light. And if we plug that in, we get a final form of this approximate equation for the frequency that the observer should see. The observer, in the moment after the light has been transmitted, they accelerate, they get up to a velocity v relative to where the source had been, and then they observe the light. They will see the frequency shifted by an amount of 1 minus the quantity al over c squared. This represents a shortening of, this represents a decrease in the frequency relative to the source, or an increase in the wavelength of the light. You can play around with this yourself and convince yourself that that's the case. But we basically conclude that the observer, who now at the moment of observation has been put into a new frame that's not that in which the light source was at rest when that emission had originally occurred, will now observe the light to appear shifted from its source frequency, and in this case, it's a red shift. If the observer were in a frame accelerating in the opposite direction, in the direction from the observer toward the source, rather than from the direction of the source toward the observer, so A becomes minus A, then the light would instead appear blue shifted, shifted to smaller frequencies or shorter wavelengths. So let's think about light as viewed in an accelerating frame of reference. We've found by making this approximation that we have a frame of reference that's all accelerated at once, so that the light that was emitted at time 0 is observed by an observer in a frame that's no longer at rest with respect to where the source of emission had been, that the observer will see a frequency as they accelerate to the right in the direction from the source toward the observer. They'll observe a reduced frequency of the light, a lengthening of the wavelength. But let's dig back to the equivalence principle. The equivalence principle states that there is no difference between an entire frame of reference that's all experiencing an acceleration due to some external force and a frame of reference that is merely experiencing an external gravitational acceleration. As a result of the equivalence of these two things, one is forced to conclude that the shifting of light must also occur in a gravitational field of acceleration. In other words, if the source of that acceleration is gravity, for instance, A equals g times the mass of the Earth divided by the radius of the Earth squared, because you're standing on the surface of the Earth, that's just 9.81 meters per second squared, the old little g from introductory physics. And imagine instead we're viewing light from a source above us. We are downstream in the gravitational field, and there is a light source down on the ground below us, sort of upstream in the gravitational field. We would conclude that the light, as we observe it, emitted up from the ground toward our eye, must be shifted, in this case a redshift, in frequency. This phenomenon is real. It has been confirmed repeatedly by experiments over and over and over again, and we'll look at some of those through problem solving in the class. It's a real phenomenon. It must be taken into account when you are dealing with electromagnetic radiation and gravitational fields, and it's known as the gravitational redshift, or, depending on how the problem is set up, gravitational blue shift of light. In this example, if we were laying on the ground, looking up at a source that's above us, and looking at light that's emitted down toward us, because we are further upstream in the gravitational field of acceleration, we would see the light in that case as blue shifted. It's equivalent to switching around the acceleration sign. Now, this very same phenomenon, the red shifting or blue shifting of light merely because of its transmission in a field of gravitational acceleration, has other implications, including for the very nature of the passage of time in different parts of a gravitational field of acceleration. So by implication from this previous example, the Doppler shifting of light by a gravitational field, one can also predict that time itself will pass at different rates, at different heights, different locations, in a uniform gravitational field. We saw that the frequency of light in a gravitational field is altered depending on the degree of acceleration. If I increase the acceleration of a frame of reference, or equivalently, increase the amount of gravitational acceleration a system experiences, I will increase the Doppler shifting effect. Frequency, of course, looking back at the discussion of waves and the Doppler shift and other things related to waves, frequency is a measure of the rate at which events happen, the time between events, effectively. So consider observing time at a height 0 above the surface of the Earth. We'll call that person the lower observer, somebody right at ground level looking at time passing, say by looking at pulses of light or ticks of a clock or something like that. And instead, a person who's way higher up, more upstream in a gravitational field of acceleration, a higher observer, also looking at their clock or their light pulsing or ticking away. From our exploration of frequency and period, we know that the frequency of a wave is given simply by 1 over the period of the wave. You can think of that as the passage of time between regularly spaced events. So, the period is just a difference in time. It's a delta t. And so really, frequency is another way of saying that we're looking at 1 over a time difference between regularly spaced events. In other words, frequency is really probing time structure. Now, if we were to be looking at the time between regular events at our higher altitude in the gravitational field, this would be related to 1 over the frequency of events at that higher altitude. And we already know how to relate those through the Doppler shift to the frequency of events at the lower altitude. We just have to take this Doppler shifting equation again, do the binomial expansion, and we find out that we are just multiplying the time duration at the lower altitude by a quantity 1 minus beta. And because we are experiencing a gravitational acceleration here, a height h above the surface of the Earth, this is equivalent to 1 minus gh over c squared in this approximation. 1 minus, say, 9.81 meters per second squared times your height above the surface of the Earth divided by the speed of light squared. You take that quantity and you multiply it by the duration of time between regularly spaced events at lower altitude, and you get the time at higher altitude. And so as a consequence of this, we expect time to pass more slowly for observers who are lower down in a gravitational field. If you were to take this to some extreme, imagine a person deep down in a gravitational field, they might experience an hour. But a person higher up in the gravitational field might observe that days, weeks, or months pass, depending on the degree of difference of location in the gravitational field. Time that passes higher up in a gravitational field is always multiplied by a number whose value is less than or equal to 1, meaning that less time passes lower down in the field. This is a real effect, and this effect has been confirmed experimentally over and over and over again. And it plays a major role in the operation of key systems to modern existence, such as the Global Positioning Satellite, or GPS system. All modern navigation typically relies on a system of about 24 satellites, each satellite orbits the Earth twice per day. So it's moving very fast around the Earth as a result of that. These are not so-called geosynchronous or geostationary satellites that always sit above the same point on the surface of the Earth. Rather, the GPS satellites orbit, and they make about 2 rotations around the Earth per day. 3 satellites at any time are required to make a triangulation measurement on the surface of the Earth, and they do this using very precise clocks that they carry along with them that have been synchronized to clocks on the ground. And this system allows you to make position measurements on the surface of the Earth. But the problem is, first of all, that those satellites are traveling actually very fast relative to the surface of the Earth. So they experience a special relativistic time dilation. Observers on the ground would claim that their clocks are running a bit more slowly than an equivalent clock on the ground because they're moving and people on the ground argue that they're at rest. So there's a special relativistic time dilation effect. But in addition, because humans who are down on the ground making these observations are lower in a gravitational field, an observer on the GPS satellite would argue that, well, okay, that's true, there's a special relativistic effect, but there's also a gravitational effect, a general relativistic effect, because the clocks on the Earth that we're supposed to be synchronized to are lower down in a gravitational field than the clocks in orbit around the Earth. And so for those clocks, there's a general gravitational slowing of time. And these 2 factors must be taken into account in the modern GPS system. And in fact, any guideline document that you look at for engineering systems for the GPS network will warn you about these corrections, spell them out for you, and tell you how to do them so that you can properly synchronize clocks, taking into account all of these time effects between the ground and in orbit around the Earth. These are real effects with real consequences on things like basic day-to-day navigation, and without the general and special theory of relativity, we would never have understood these. Had we launched a GPS system before understanding space and time at this level, we would have failed to construct a working GPS system. Now, one other implication of general relativity, and this can be relatively kind of quickly looked at in a cartoonish way by referring to our accelerated frame of reference, our sealed vessel. This other effect that we'll take a look at here is the deflection of light by a gravitational field. Now, this might seem novel to you, but in reality, the deflection of light by a gravitational field, the falling of light near the surface of the Earth, was not a new idea in the time of Albert Einstein. It was actually quickly realized, within certainly decades or a century, after the work of Isaac Newton had established the laws of mechanics and gravitation, that since all objects, regardless of their mass, fall at the same rate in a uniform gravitational field. Think of dropping a wadded-up ball of paper and a bowling ball at the same time from a few feet above the ground. If you drop them so that their bottoms are starting at the same height, they'll hit the ground at the same time. The mass of the paper and the mass of the bowling ball seem to play no role in the rate at which their velocity changes as they head toward the surface of the Earth. Well, if mass doesn't matter for gravitational acceleration, then even, one might argue, a massless phenomenon like light should fall in a gravitational field. Now, the specific reason why this would happen was put on much firmer footing thanks to the equivalence principle, and I'll walk through an example of that argument here. So, consider the cartoon at the right. We have our sealed vessel, it's sound and vibration proof, no windows, no doors, no way of knowing whether you're on Earth or far out in space, away from all planets and stars. Now, in reality, this system is being accelerated upward by a rocket you can neither hear nor feel nor see, and it's doing so at 9.81 meters per second squared constantly. So you're in this sealed room, there's a light source on one wall, and you can push a button and fire a wavefront, a pulse of light across the room so that it strikes the wall on the other side. Now, at the moment that the pulse is emitted, and that's illustrated here on the left, the line connecting its location of emission points straight across the room to a point on the other side of the wall. But By the time that the wave reaches the other wall, and that's illustrated here on the right, the wave, freed from its connection to this frame of reference that in the meantime has changed its state of motion, the light wave will travel on that absolute straight line. But from the perspective of a person inside the vessel looking at where the light wave strikes the wall, if they had very precise equipment, or if the speed of light were much slower than it actually is, then they would actually observe that the light wave strikes the wall at a point that's lower than where it was emitted from. So in an external frame of reference, that light traveled on a real straight line. But the frame moved up in the time during which it crossed the room. From a perspective of an observer inside the frame who doesn't know that any of this is going on, they see the light wave strike the wall at a lower point, some vertical displacement below where it was expected to strike, that is, at the level of the emission source. So the light wave reaches the wall, but it does so, in this case, at a lower point. Now, by the equivalence principle, there is absolutely no difference between this frame of reference being accelerated by a rocket or a similar sealed room that's sitting on a planet experiencing a gravitational acceleration downward of 9.81 meters per second. And so, because of the equivalence of an accelerated frame of reference and a frame that's merely experiencing a gravitational acceleration, light must also fall in a gravitational field, because there's no distinction between these two cases. It turns out that this is actually generalizable to any body with mass bending the path of light. And this is actually the key insight that Albert Einstein's general theory of space and time, the general theory of relativity, had, that helped to distinguish it from Isaac Newton's original theory of acceleration and gravitation. In Newton's theory, the deflection of, say, starlight around a massive body like another star is smaller than the deflection predicted in general relativity, which is supposed to be the more correct description of space and time and the way that energy and matter respond to space and time. So in the general theory of relativity, the degree of deflection of light around a massive object by falling in a gravitational field, if you will, is twice as big as predicted in Newton's original mechanical theory combined with his law of gravitation. That's a key distinction between the two ideas, the general theory of relativity and the old theory of mechanics married to the law of gravitation. It was that prediction that was tested in the late 19-teens and led to the confirmation that Einstein's work was probably the correct description of space and time and energy and matter. And this catapulted Einstein into global fame. It also led to a host of other predictions for other interesting phenomena.
Because light can be deflected by large masses, we could imagine being able to see objects that shouldn't be visible to us. Using large arrays of telescopes and looking out into the distant sky, we can look for cases where we see a background object whose light has been bent around a foreground object, allowing it to reach our telescope. This so-called gravitational lensing allows astronomers not only to see objects that would otherwise be obscured behind other foreground objects, things that sit between us and the thing we want to look at, but because the general theory of relativity gives very specific relationships between the amount of mass and the degree of the deflection of light, one can use the deflection of light itself to measure the mass of objects with which you can never hope to have physical contact. Gravitational lensing is one of the many tools that general relativity gives to us as human beings to better understand the universe, even parts of the universe that are very old, very distant, or both.
So as you can see, the general theory of relativity has some fairly impressive large-scale implications. If you remember something back from your calculus, The second derivative of something with respect to something else tells you about the curvature of the system that you're studying with the derivative. Now, we've considered the fact that space and time are really part of a singular structure. They really should be thought of as part of one four-dimensional framework, which is called space-time. In special relativity, we see that space measurements in one frame can turn into time measurements in another. Space and time are constantly getting traded for one another or tangled up in one another in calculations of motion from one inertial frame of reference to another. There's a link between space and time, and that link comes from the fact that they're really part of one interchangeable four-dimensional framework, space-time. And it's in this framework that matter and energy can be described to move and change. So general relativity is really a theory of space-time, a general broad theory of space and time. And ultimately, it concludes that what we call the force of gravity is really due to the fact that mass and energy cause space and time to curve, or in more colloquial language, bend or warp. The second derivative is a sign of curvature, and so it should have been a clue that since there's no distinction between accelerating a frame of reference or subjecting that same frame of reference to an external gravitational field, there must be no difference between curvature and gravity. And in fact, that's one of the broad conclusions of the general theory of relativity. Energy and matter curve space and time, and so other bits of matter, or even light, that travel past that object that's bending space-time will follow the curvature of space-time. And the result of this is that from our perspective in 3 dimensions, they appear to accelerate. What is a ball doing when you hold it out at shoulder height and drop it? It's not being pulled down by the mass of the Earth. Rather, it's following a path in space-time that's curved due to the presence of the mass energy of the Earth bending that space and time. That is what gravity is. That is what Einstein was able to achieve, the very thing that Isaac Newton could not grasp, the nature of gravity, curvature of space and time. Space and time tell energy and matter how to move. Energy and matter tell space and time how to bend or curve or warp. This elegant summary, paraphrased from its author, is a beautiful way of remembering the implications of the general theory of relativity writ large, and it comes from the mind of luminary theoretical physicist John Archibald Wheeler. The universe is observed to expand in all directions at once, and the more distant an object you view in the universe, the faster it appears to be moving away from us. This tells us that overall, space-time is curved. Now, on the grandest scales, the largest distances that we can reasonably observe in the universe's space itself appears to be very flat and smooth. But just because space is flat and smooth overall doesn't mean that space-time is. And the expansion of the universe is evidence that space-time itself is curved. The curvature of space-time leads us to conclusions about the origin and the fate of the entirety of the universe. And it tells us that the universe as we know it now, space and time and energy and matter, was born 13.78 billion years ago in an event we have yet to fully understand, but which is described by the phrase, the Big Bang. Let's review what we have learned in this lecture. We've looked at the transition in thinking from the special to the general theory of relativity. We've looked at some implications of the general theory of relativity on physical phenomena. Specifically, we've considered what it means for light to travel in a gravitational field from a higher to a lower vantage point in that field. We've concluded that light should Doppler shift, either redshift or blue shift, depending on the direction in the field that you observe it. we've also concluded that light should be bent in its path of travel in a gravitational field, and we've drawn all of these conclusions by using the equivalence principle to map behavior in an accelerated frame of reference onto a frame that's experiencing an external gravitational acceleration. We've then looked at some of the large-scale implications for space and time. The bending of distant starlight around massive objects that intervene between us in the universe. The use of the warping of space and time and the bending of light to infer the mass of objects that we can never hope to weigh by putting them on a scale. And the overall implications for the nature of space-time as a framework in which energy and matter play out, the fact that energy and matter tell space and time how to curve, and the curvature of space and time tells energy and matter how to move, and how the overall curvature of space-time indicates to us the origin and possible fate of the entire universe itself. These grand themes all stem from the elegant thinking of a brilliant physicist who accepted observational evidence from experiment about the nature of light, thought deeply about the world around him, learned the math necessary to describe the universe, and in that elegant language spoke a volume about the cosmos that we are still reeling from today. In this lecture, we will learn the following things. We'll learn about the concept of temperature of a material body. We'll learn how to establish a scale and measure of temperature, about the response of material bodies to changes in temperature, and finally, about heat energy as the underlying agent connected to changes in temperature. There are many things that are left unsaid in the first 2 semesters of introductory physics. We're only able to cover a prescribed range of topics, and that range can be described as follows: motion, force, the laws of motion, relating force and acceleration to changes in state of motion, energy, momentum, the conservation of energy and momentum, non-conservative forces, oscillatory motion, and rotational motion. That's typically what we get covered in the first course in physics. In the second course in physics, we're able to cover electric charge, electric force, electric fields, electric potential, and electric currents, and the combination of all those things into electric circuits. And then we explore magnetic field and force, and the basic behaviors of light, such as geometric optics or interference and diffraction. Now, as a result of this in introductory physics, there is essentially no time to discuss the laws of heat energy, also known as thermodynamics. But nonetheless, thermodynamics is an essential foundation of modern physics. It ultimately was a branch of physics that helped to lead the way to quantum mechanics, the theory of the very small. And that is the next subject of this course. So in this part of the course, we will establish the second half of the foundations of modern physics, the concept of temperature, the concept of heat energy, and some of the behaviors of heat energy. We all have a fairly solid familiarity with the various concepts associated with thermodynamics. If you go outside on a day when it's cold, you feel like something is being pulled from your body en masse, as if the world around you is hungry to take something away from you and keep it for itself. And this feeling, this sensation of the loss of something from our bodies, where we have to trap it to keep it in, is often what we call cold, or the concept of a cold temperature. Of course, the flip side of cold is hot. There are environments, there are situations where instead we feel like something is being put into our body and we want to get rid of it. We might shed some clothing in order to help achieve this, to help regulate our own sensation of temperature. When the world around us is hotter than us, we feel that penetrating into our skin in a way that can be uncomfortable. It causes us to sweat and so forth as a mechanism to try to maintain our own state of body temperature. So cold and hot, these ideas are familiar to us, even if we cannot articulate the physical reasons why these situations exist. Now, connected to these two things is also the concept of establishing a numerical measure of the degree of hotness or coldness of an environment. So, for example, the average human being, and this can vary by age and gender and a number of other factors, is typically comfortable, especially for intellectual work, office work, something like that, in a temperature range between 70 to 75 degrees Fahrenheit. Now, a human being experiencing an environment where the temperature is observed to be less than that number will often express a feeling of being cold, chilly, chilled, needing to bundle up more to maintain their body warmth. On the other hand, a person who's subjected to an environment above that range, maybe 85 degrees Fahrenheit instead of 74 degrees Fahrenheit, will complain about sweating too much, feeling too hot, wanting to cool off in some way, maybe by drinking an iced beverage of some kind, or maybe taking off a jacket if you're in a work environment, something like that. We have a concept of being able to measure the degree of heat or cold in the world around us, including the heat of our own body. Taking our temperature to see if we have a fever is another concept that is pretty familiar in the human world. Now, connected to these sensations, these experiences, we have to come up with a series of critical issues and a plan in order for us to be able to quantitatively describe these scenarios of hot or cold. We have a conception of hot and cold. We have a conception that we can measure these things somehow. But we need to establish the basis for actually having that quantitative measure, that quantitative description of these concepts. How do you know something is hot? How do you know something is cold? How do you measure that? And how do you allow other people independently to establish the same scale of measure? Let us begin by establishing that scale on which we can quantify those ideas, like a room is too hot or a room is too cold. Let us then look at the origins of hot and cold, and how the underlying concept is really tied to a fundamental concept called heat energy. We will close with a relationship between heat energy of a body and its ability to radiate energy away. But in this particular lecture, we're going to focus on temperature, heat energy, and the effects of heat energy not only on the temperature of a body, but the structure of a material body. Let's begin by establishing a measure of hot and cold. Now, consider the world around you. There are some phenomena in nature that appear to occur at very specific so-called thermal conditions. That is to say, if you could reproduce the environmental conditions under which a particular phenomenon occurs, that phenomenon would occur repeatably, reproducibly, reliably. So, for example, the freezing or boiling of a body of water. The only substance on Earth that can exist in solid, liquid, and gaseous states under Earth conditions is water. It's essential to life as we know it, and because it's able to coexist under a very narrow range of conditions, as either a liquid, a solid, or a gas, it makes an attractive phenomenon on which to establish a range of behaviors that can be used to delineate a scale of temperature measure. Now, that said, of course there are materials other than water, and they also change in response to temperature. For example, in the opening lecture video for this series, I showed you the result of heating a bimetallic strip. Now, I'll return to heating or cooling metals later, but we've observed already that two metals bonded into contact with each other will bend, curve, when exposed to a heat source, and that's because
In this lecture, we will learn the following things. We'll learn about the connection between temperature and the constituents of a material body. We'll learn about the precise nature and cause of heat energy. And finally, we'll learn about the radiation of energy from a material body. Now, matter is ultimately made from building blocks. For example, a liquid may be made of a large number of atoms or molecules. The atomic theory would not really be accepted as a reliable description of nature until about 1905. But once one adapts the atomic theory as the correct description of material bodies, one is then forced to conclude that the large-scale macroscopic properties of a material object are somehow connected to the microscopic behaviors of the building blocks from which that material is constructed. Now, the number of things that are used to construct a material body in the human world, the macroscopic world, is vast. For example, there's the concept of the mole. 1 mole is the number of atoms in a 12-gram sample of carbon-12. Now, experimentally, you can work it out, and you'll find that 1 mole's worth of things, anything at all, grains of sand, planets, stars, atoms, anything, is given by a special number known as Avogadro's number. And that number is 6.02 times 10 to the 23 of anything per unit mole. 1 mole, therefore, is 6.02 times 10 to the 23 things. Heat energy must have a connection to the behavior of the building blocks of matter. After all, if one is depositing a form of energy into a material body, that energy must go somewhere, and we must look to the constituents of the material body to figure out where energy might be going. This helps answer the questions, what is heat energy, and where does heat energy go exactly, or where does it come from? Let's look at an ideal gas as a laboratory for the connection of macroscopic concepts such as the volume of a material or the temperature of a material and the pressure exerted by a material on its environment to microscopic concepts like the position and velocity of an atom or molecule. Now, we're going to focus on ideal gases. I'm going to start with a very simple simulation of an ideal gas. This simulation is provided by the PhET demonstration toolkit that's available on the web. And this is a simulator of an ideal gas system. Now, to start, I'm going to put one heavy particle of a gas, just one atom or molecule of an ideal gas, into the system. Where do the properties of gases like pressure and temperature come from? Well, pressure is force per unit area. And so the pressure exerted by an ideal gas on its container, and in this case the container is represented by this box outlined here, that pressure comes from the force of the collision of the ideal gas particle with the walls of the container. So for example, we've injected one massive gas particle into the system, and we see that it's bouncing around the inside of the container. It collides with the walls of the container, and because this is an idealized system, we treat it as having perfectly elastic collisions with the walls, and the walls do not move. And because of this, this forces the momentum of the particle, the component that's perpendicular to the wall it collides with, to reverse upon collision. So for instance, the particle strikes the bottom wall, and we see that its vertical component reverses. It strikes the right wall, and its right moving component reverses to the left. We see also that because momentum is conserved in this closed and isolated system, that the total speed of the particle remains fixed, even if its direction changes, and that momentum changes are conserved independently in every direction. A collision with a wall to the left or to the right does not change the speed component that is vertical or parallel to that wall. So, the origin of the pressure of the gas is the force it exerts due to its momentum change on the walls of the container. I could now instead inject more particles into the system. So now let's start by injecting 50 gas particles into this system. We'll give them a moment to spread out in the container. And we see that while they all come in together as a clump, because they didn't all quite have the same velocity, they start not only colliding with the walls of the container, but with each other. Now, an ideal gas will have elastic collisions with the walls of the container and with itself. And we see that very quickly the gas particles have spread out fairly uniformly throughout the container, and they continue to collide. Collisions will exchange momentum between colliding particles, but on average we can see here that the particles are all moving with about the same speed. Some are moving a little faster, some are moving a little slower, but collisions level that out. And we stare at this for a moment and see that these gas particles all appear to have some average amount of speed and a distribution of velocities that's sort of spread around that average. So slow-moving particles can get struck and become fast-moving particles can get struck and become slow-moving particles, but on average it seems like there's a pretty typical consistent average speed. On average, we don't see these particles getting much faster or much slower as a group. While an ideal gas is truly an idealization, there are many gases that are nearly ideal in nature. For instance, all of the noble gases, for example helium or argon, they behave very much like ideal gases under many common conditions. There are even many other substances that, under a range of conditions, can behave according to the idea of an ideal gas. Careful experimentation on systems that behave in this sort of ideal manner have revealed that there is an empirical law that relates the macroscopic properties of a gas, the number of moles of gas constituents, given by the lowercase letter n, the volume of the gas, given by the capital letter V, the temperature of the gas, given by the capital letter T, and the pressure exerted by that gas on its containing volume, for instance, the walls of the container that hold it, and that's denoted by the letter capital P. This equation is known as the ideal gas law. Most students learn this in a chemistry course in either high school or college. PV equals nRT, the product of the pressure exerted by a gas and the volume of that gas, is equal to the number of moles of that gas times a constant times the temperature of the gas. Now here, this constant is denoted capital R. It is known as the ideal gas constant, and its value is 8.314 joules per Kelvin per mole. It's named in honor of the French chemist Henri Regnault, therefore the letter R. But since a gas is made from small constituents, albeit a very large number of them, can we connect the microscopic properties of those constituents, their positions in space, the changes in those positions in space with time? Can we connect those to this macroscopic statement about the aggregate behavior of the gas? To connect the microscopic to the macroscopic, let's begin by doing what physicists and chemists in the 1800s did and turn to classical physics. After all, Newton's laws of motion were the only things that they knew to be reliable as describing nature, so why wouldn't you turn to the thing that had been working for a couple of hundred years already? Let's begin with the concept of mass in this ideal gas. Let's define the molar mass of a gas as capital M. This is simply the mass for every mole of this gas. It's given by adding up Avogadro's number of individual constituent masses, which we'll denote as little m. So if each atom or molecule that makes up an ideal gas each has an identical mass little m, then the molar mass is that little m times Avogadro's number. That gives us the mass per mole of this gas. What about the volume of the gas? Well, to keep things simple, let's consider a nice cubical space containing our ideal gas. It has a fixed size, it has sides all of length L, and that means that the area of any side of the cubical space, the box in which we're holding the gas, is given by capital A equals the square of the length of any side. And that also means that the volume is determined, capital V, by the cube of the length of any side. Now, pressure is a bit more difficult. Pressure is the sum total of the force, F total, per unit area exerted by all gas constituents on the walls of the container at any moment in time. An individual gas molecule will occasionally collide with a wall of the volume containing it. That collision will briefly exert a force. That force on that area is the pressure. Now, of course, a gas is made from many constituents, and so it's the sum total of the average number of collisions per some unit of time that cause the pressure on the walls of a vessel. How might we describe this using concepts of motion, Newton's laws, and conservation laws, all from classical physics? Well, let's begin by thinking about a single constituent. Each constituent has a velocity vector at any moment in time with three components: an x component, a y component, and a z component. Now, since we're considering an ideal gas, we're talking about elastic collisions between a constituent of mass m and, for instance, the wall of the container along the x-axis. Let's only focus, for now, on the component of the motion of a gas molecule along the x-axis. Now, during these collisions, the wall doesn't move, and so its velocity before and after the collision is zero. And if you consider a single collision along the x-axis between a gas molecule and the wall that it strikes, and if you conserve kinetic energy and momentum, as would be true of an elastic collision, then you find that the initial momentum of the gas molecule must be given by its mass times its original velocity in the x direction. And after the collision, conserving momentum and kinetic energy, you're forced to conclude that it has the same speed along the x-axis, but it's reversed the direction of its motion. So the final momentum just after the collision with the wall will be negative m times its speed along the x-axis. Now, a collision results in a change in momentum for the gas molecule, and a change in momentum is what is known as an impulse in introductory physics. The impulse is just the difference between the final momentum and the initial momentum. And in this case, if you crunch the numbers, you find out that if we knew the mass of a gas molecule or atom, and we knew its velocity just before the collision along the x-axis, that the impulse that results from this change in momentum is negative 2mvx. Now, if we knew the time over which the impulse occurs, then we might compute the force that's exerted by just this one constituent on the wall, and we can do that by relating impulse, time, and force using Newton's second law, that the force is equal to the change in momentum divided by the change in time. What is the time between collisions in one dimension? Well, with a specific wall, the time between collisions in one dimension is just the time between when the constituent strikes the wall for the first time, bounces back horizontally across the box, strikes the opposite wall, then bounces back along the x-axis to the first wall, the one on whom we're considering the force. It's that time, the time between the collision with the wall, striking the opposite wall, and returning to the first wall. The time between collisions will be given simply as twice the length of a single wall along the x-axis divided by the speed along the x-axis of that constituent, 2L over Vx. Now the force of the gas constituent acting on the wall will be equal in magnitude, but opposite in direction, to the force that the wall exerts on the constituent. The pressure is the force that the gas exerts on the container. What we've computed is the force that the gas molecule has experienced by being acted on by the wall. We can use Newton's third law to relate what we have to what we want. We want the force exerted on the wall by this constituent. We have the force exerted on the constituent by the wall, and they're related in Newton's third law by a minus sign. And if we plug in the force that the constituent experiences because of the wall, the minus signs cancel out, and we're just left with 2 times m times Vx divided by the quantity 2L over Vx. And simplifying this, we find that the force experienced by the wall due to this one collision from this one gas molecule is mvx squared divided by L. That is, the mass of the gas molecule times its speed along the x direction squared, divided by the length of the wall along the x-axis. But that's just one gas molecule. Pressure is the sum of all such forces added up across all constituents in the ideal gas, and then dividing by the area of the wall in question. So what we really want is the total force exerted by all collisions by gas molecules on the wall in a given time. And we want to divide that by the area of the wall, which is just L squared. Well, the total force will be given by adding up the forces exerted by individual gas molecules with their individual velocities, the component along the x-axis. So for instance, there may be Avogadro's number worth of ideal gas constituents. And so we have to look at each one in a time window, delta t, during which these collisions should be considered. That time window is given by 2L over V. And we find that all we have to do is sum up mv1x squared over L cubed plus mv2x squared over L cubed plus mv3x squared over L cubed all the way up to the total number of molecules that make up this gas. Notice that every term in this sum has a common multiplicative factor of m, the mass of the constituent, divided by L cubed, effectively the volume of the container. So we can pull that out in front of the sum, and then we just have to sum over this velocity squared of all of the gas molecules along the x-axis. Well, the gas molecules are colliding with each other. We looked at this in a simulation. So they don't all have the exact same horizontal speed at any given time. But they do collide with each other, and they do on average have the same speed over some unit of time. So what we can do is we can approximate this sum by saying that we're going to consider the fact that all of the gas molecules have, on average, the same horizontal component of velocity, and that sum will just then be given by the total number of molecules, capital M, times the Vx squared average, the average of the square of the x component of their velocities. That number is one thing for all of the gas molecules, even if each of them has a slightly different horizontal component of speed because they've been colliding with each other and with the walls. Simplifying this one step further, we can replace big N, the total number of gas molecules, by Avogadro's number, Na, times the number of moles of the gas, little n. That appeared in the ideal gas equation, and that's why we're putting it in here. So the final equation we get is that the pressure exerted by the gas on the wall is just on average given by the mass of each molecule or atom divided by the volume of this cubic container times the number of moles of the gas times Avogadro's number, which tells you the number of things per mole, times the average of the square of the x component of the velocity. Well, let's see if we can relate that x component to the total speed of each gas molecule on average. On average, the x component of a constituent's squared speed will simply be 1/3 of its total squared speed. V squared, the speed of a single molecule will just be given using a variation of the Pythagorean theorem as the sum of the squares of the components, Vx squared plus Vy squared plus Vz squared. So on average, we would expect after any number of collisions that each of those components will be 1/3 of V squared. So if we plug that in, we take our pressure equation, which is just rewritten here, and we plug in the fact that Vx squared average is really just 1/3 of the average of its total speed squared. We finally arrive at a situation where we can begin to relate microscopic properties like the average speed squared of molecules and their masses to the large-scale properties of the whole gas. For instance, multiplying this equation by the volume cancels out the V in the denominator of the microscopic equation. We wind up with P times V is equal to the mass of each constituent times the number of moles of the constituents times Avogadro's number times the average speed squared divided by 3. Well, we can simplify this further by remembering that we defined molar mass, the mass per mole of the ideal gas. And that's just given by the mass of each constituent times Avogadro's number. So that replaces M and Na in the equation. And we wind up with the molar mass times the number of moles times the average of the speed squared of a molecule divided by 3. Well, by the ideal gas law, PV, which is equal to this thing, is also equal to nRT. Notice that the number of moles of gas appear on the right and left of this equation and cancel out. And we can actually finally solve for the average speed of a single molecule in an ideal gas by rearranging this equation to isolate V average. And when we do that, we find out that this microscopic property of an individual gas molecule, its average speed, is given by a combination of the macroscopic properties of the gas, the square root of 3 times the gas constant, which is just a number, times the temperature of the gas, divided by the molar mass of that gas. The microscopic has been connected to the macroscopic. We see here that classical physics can give you some insights into how the individual constituents of a material have relationships with the macroscopic properties of that material that are easier to measure on the human scale. We can take one final step, and instead of looking at just the speed, or average speed, of an individual gas molecule, we can consider the average kinetic energy of any single constituent of the gas system. Well, that's just going to be equal to 1/2 times the mass of a constituent times its average speed squared. That's the definition of the kinetic energy of a typical molecule in the gas. Now, from the ideal gas relationship between average speed, temperature, molar mass, and the gas constant, we learn the following: that the average kinetic energy of a single constituent in the gas, which is given by 1/2 m V average squared, can be instead related to the macroscopic properties of the gas, 1/2 times m times the quantity 3RT divided by the molar mass. Now this can be further simplified by replacing the molar mass instead with the mass per constituent times Avogadro's number, which is also just a constant. And we notice that the individual constituent masses vanish from this equation. And we are left with the following: that the average kinetic energy of a constituent of an ideal gas is given simply by a number, 3/2, times another number, the gas constant divided by Avogadro's number, times a single variable, the temperature of that gas. Now it turns out that R, the gas constant, divided by Avogadro's number, is actually related to another fundamental constant of nature, which is known as Boltzmann's constant. It's written as a lowercase k with a subscript b. And so in the end, we find out that the average kinetic energy of a single constituent of a gas, regardless of the masses of the constituents of that gas, is simply given by 3/2 times the Boltzmann constant times the temperature of that gas. This is a remarkable observation, a fantastic relationship, that something so tiny as the kinetic energy of a typical thing inside of a vast number of gas molecules is related to this singular macroscopic property, temperature, that we can control easily in the macroscopic realm. Now, Boltzmann's constant is given here as 1.381 times 10 to the negative 23 joules per Kelvin. It's a very tiny number, which makes sense because the average kinetic energy of a constituent of a large number of gas molecules ought to be a very tiny number, even for a standard temperature at room temperature, for instance. Now, when we measure the temperature of an ideal gas, what this tells us is that we are actually measuring, probing in a very direct way, the average kinetic energy of its individual constituents. And this tells us what heat energy is. Heat energy is determined by this thought process to be related to the average kinetic energy of constituents of a material body. That is to say, as one adds heat energy to a system, this raises the average kinetic energy of the constituents. Adding heat, Q, raises T, temperature, and this proportionally results in an increase in the average kinetic energy. Where is the heat going? The heat is going into the kinetic energy of the individual gas molecules. If you want to remove heat from a system, all you have to do is find a way to reduce the average kinetic energy of the constituents of that system. This also allows us to finally understand that a system with no kinetic energy, that is, constituents that are holding perfectly still, experiencing no collisions with the walls of their container or with each other because there's no motion at all, that is identified as being the lowest temperature that you can ever have. 0 average kinetic energy for your constituents is 0 Kelvin. We finally have a physical understanding at the most basic microscopic levels of a large system as to what it means to achieve 0 temperature. 0 temperature, a state of 0 heat energy, is also a state of 0 average kinetic energy for the constituents of that system. So this raises an interesting question then. How do you transfer heat energy either to or from a system? Well, there are many ways to do this, and I'm going to focus on 3 quite broad established mechanisms for transferring heat energy from a system, because ultimately I only really want to focus on one of them. So let's consider cooling. Heating will just be the reverse of any of the things that I say here. Let's begin with the mechanism of conduction. Conduction is when you place a second system, perhaps at a lower temperature if we wish to cool the first system, in physical contact with the first system. Think of 2 cubes of metal at different temperatures. We want to cool one of those blocks of metal. So we take another system that's even cooler and we press them together so that their 2 faces of the material are physically touching each other. At that interface, at that contact space between the 2 materials, collisions are going to begin occurring between the atoms or molecules of one system and the atoms or molecules of the other system. This creates an arena in which collisions occur, transferring kinetic energy from one system on average to the other. What you'll find is that higher kinetic energy constituents are going to typically lose some kinetic energy to the slower moving constituents at the interface of the other system. Of course, at the interface of the other system, those constituents will then start having more collisions with the things inside the system, and that's how heat energy is transferred by conduction through a system. It's all collisions. This decreases the temperature of the hot system and increases the temperature of the cold system until such time as the temperatures of the 2 systems reach a new equilibrium position, T1 equals T2. This will occur, typically, when the temperature of the hotter system is lowered down, and the temperature of the cooler system is raised up, and you finally reach a point where they both have the same temperature and they stop transferring heat energy. They, on average, have the same kinetic energy for all their constituents. No more transfer can occur. Then there is convection. In convection, you pass a fluid, like a gas or a liquid, across or around another system. So if we want to take a system and cool it, we might blow air over it, or push water across it in some kind of current. Collisions at the boundary of your system, between the constituents of your system and the constituents of the fluid, will transfer kinetic energy, on average, to the fluid. The fluid, if it's cooler, will have lower kinetic energy constituents, and collisions will tend to favor increasing the kinetic energy of the cooler system's constituents. And this ultimately cools your target system, system 1, by lowering the average kinetic energy of that system. And finally, there's radiation. Radiation is a process by which constituents lose energy by giving it up in the form of radiation of light. For instance, you might be familiar with the fact that you can stretch your hand out several centimeters, inches, maybe even up to a few feet away from a hot cooking pan on the stove. And even though you are not making physical contact with that, and even though the air is very still in the room around you, you feel something being transferred to your hand. You would say that you can feel from a distance that the pan is hot. Well, that's because it's radiating, typically at the infrared. And that infrared radiation, which you can't see with your eye, but which you can feel with your skin, will be absorbed by your skin. Radiation requires no physical contact between a system and the environment. In fact, if you took all the air out of the room and stuck your hand out in that environment, you would nonetheless feel heat being transferred to your hand by radiation. Electromagnetic radiation requires no medium to travel, and so even evacuating the room of air will still lead to a cooling of the pan, in this case, by the radiation of infrared light. Now, radiation has the effect of carrying kinetic energy away from a system and giving it to the environment writ large around it, even without physical contact. Radiation is what I'm going to focus on for the rest of this lecture. It's an interesting phenomenon because it is an interface between mechanics and electromagnetism. And you can already begin to see that since we got ourselves into trouble thinking about motion and the laws of electromagnetism and the laws of mechanics, that a place like this, heat energy and radiation, is another similar interface of classical mechanical view of the universe with the electromagnetic laws of nature, where inconsistencies may arise if you overly trust the mechanical laws of nature. There is a mathematical relationship that has been determined by experiment in the late 1800s and early 1900s between the energy that is emitted or absorbed by a heated material body and the temperature of that body. This was determined empirically by Joseph Stefan to be the following: that the power radiated or absorbed by a body, that is to say the change in heat energy per unit change in time, is given by the product of four numbers. Sigma, which is a constant of nature known as the Stefan-Boltzmann constant, whose value is 5.670 times 10 to the minus 8th watts per meter squared per Kelvin to the 4th. It's not a bad number to remember because it's got 5, 6, 7, 8 in it. I find that handy for remembering this number in a pinch. Now, the Stefan-Boltzmann constant is multiplied by another number, which is this curly lowercase Greek epsilon. Epsilon is the emissivity of the surface of a body, and it ranges between 0, no emission, and 1, perfect emission. You can see that a body with 0 emissivity will emit no power in the form of radiation, because the right side of this equation will always be 0. On the other hand, a body with perfect emission will maximally emit radiation given by the product of the other numbers, the Stefan-Boltzmann constant, the surface area, A, of the body, and the temperature of the body raised to the 4th power. Note that all material bodies above 0 Kelvin radiate energy in the form of electromagnetic radiation. You and I, sitting here right now at 98 degrees Fahrenheit, which is the typical human body temperature, are radiating light away from our bodies. We just can't see it. And we can play around and figure out what wavelength it is as an exercise in class. A perfect emitter with emissivity of 1 is also known as a blackbody. It's a very special kind of object. It is a system that absorbs all incident radiation, and it can subsequently re-emit its own radiation with perfect emissivity. Blackbodies are a special laboratory for testing the interface of the laws of mechanics, the movement of the constituents and the laws of motion that describe the allowed states of motion of that material at its smallest level, and electromagnetic radiation, the emission of light.
Now, before I show you an example of how classical physics, when applied to the question of radiation, got it wrong, I want to define for you a very useful concept, and that is the power emitted per unit wavelength in a radiation situation. This is known as the spectral radiance. Now, in a situation where an amount of energy, say delta Q, is radiated away by a body in some period of time, delta T, it is actually fairly typical to ask the following question, to really drill down into a question about the amount of energy within a certain range of wavelengths or frequencies of the emitted radiation. In other words, if I consider a range of the radiation with a minimum wavelength lambda and a maximum wavelength that's just a little bit higher than that, lambda plus delta lambda, where delta lambda could be a very tiny amount, how much energy per unit time is radiated by wavelengths in that range? And asking this question is answered by a special kind of function known as the spectral radiance. Now, it's often denoted by various letters. I'm going to use the capital letter B, and I'm going to make it a function of lambda, the wavelength, explicitly to emphasize the fact that it is answering a question per unit wavelength. This is the energy radiated per unit time, per unit wavelength. I could have also alternatively written B in terms of the frequency, f, because frequency and wavelength are related to the speed of light for electromagnetic radiation. But I'm going to use B as a function of lambda. If you want to know the power radiated around a specific wavelength, then you need to pick a small range around that wavelength and compute the product. So for instance, you might choose a specific lambda, and then because this is defined over a small range of lambda to lambda plus delta lambda, you need to multiply the spectral radiance, which is a function of lambda, times the window around which you are trying to compute the amount of power radiated, delta lambda, and that will return the power emitted around that wavelength. Now, that would be a sort of discrete way of thinking about it. If you have a well-defined continuous function, a function of lambda that varies continuously as lambda, representing this spectral radiance B, then you can just integrate. You can use integral calculus in a range to get the answer you desire. So for example, if I want to know how much power is emitted between two wavelengths, lambda 1 and lambda 2, I can simply take the product of B and D lambda and integrate that product from lambda 1 to lambda 2. And if B is a well-defined function, I can do the integral. It may not be pretty, but I can get a function that answers the question and gives me the power radiated in that range of wavelengths. Now, with that introduction in mind, let's take a look at a classical physics attempt to predict the amount of energy emitted per unit time about a given wavelength, lambda. This was worked out in the early 1900s and answers the question, how much power is emitted in, say, the ultraviolet range, around 240 nanometers, in some window around 240 nanometers? How much power is emitted in the range of red light, around, say, 740 nanometers, in some window around that? Answering that question in little steps through the electromagnetic spectrum will give you a picture of how power is distributed as a function of wavelength in the emitted radiation. Now, the classical version of this is known as the Rayleigh-Jeans law, and it's from 1905. And so again, you have to start from the spectral radiance function, the power per unit wavelength. That is this quantity here in the Rayleigh-Jeans law, 8 pi times a, the surface area of the object, times c, the speed of light, times the Boltzmann constant, times the temperature of the object, divided by lambda to the fourth. And if you check the units of that particular fraction, you'll see that it is joules per second per meter, so per unit wavelength. If you then want to know in a small window around the target wavelength, lambda, how much power is emitted, you need to multiply that by the size of the window, and that will then answer the question about how much power is emitted around that wavelength in a window about the wavelength lambda. So for example, this tells us that for, say, a spherical body that's heated to a certain temperature T, and that body has a certain surface area A, the shorter the wavelength of the radiation you consider being emitted from the body, the more and more power is radiated around that wavelength. If true, this would be a catastrophic feature of nature. So for example, consider a small sphere of metal or something like that. You make it out of a very good material, and it's got a surface area of just 1 meter squared, and it's got an emissivity of 1. If you heat that to 6,000 Kelvin, and just for reference, a very modest small propane torch can easily heat something to 3,000 Kelvin, you would emit about 10 to the 16 watts, that is joules per second, alone in dangerous ultraviolet radiation, for instance with a wavelength of 250 nanometers. That is easily lethal to a living organism. To give you a point of reference, you can buy easily on Amazon or at other online vendors a sanitizing wand. A sanitizing wand emits 4 watts of radiation power in the form of ultraviolet, specifically ultraviolet C, which has a wavelength which kills bacteria. Now, if it can kill bacteria, it can do significant damage to other kinds of living cells, including the cells of the human body. You should never expose your body to UVC if you can avoid it, because it causes damage to DNA, and this can lead to the formation of cancers. 10 to the 16th watts of UVC would be extremely dangerous, if not lethal. And all from a small heated sphere at 6,000 Kelvin? Well, that seems ludicrous. And it is ludicrous. If you actually go and measure the amount of power emitted at a given wavelength, it doesn't shoot off to infinity as lambda goes to 0. This is just not what is observed in reality. And yet, it is a byproduct of thinking of classical physics, the marriage of Newton's mechanics with electromagnetism. Let me show you a graph. I don't want you to worry too much about what the axes mean. I'm going to describe them in an oversimplified manner. The vertical axis tells you how much energy is emitted per unit time, per unit area, and per unit solid angle, so at some chunk of angle space, for a given frequency of radiation you're considering. So the frequencies are on the horizontal axis. High frequency corresponds with short wavelength. Ultraviolet radiation would have a shorter wavelength. X-rays would have a very short wavelength, and so forth. On the other hand, long wavelengths are down here at low frequencies. So infrared and red, they tend to have very small frequencies and correspondingly very large wavelengths. The blue curve, which not only comports with reality, but was predicted in a mathematical exercise by a physicist named Max Planck, that one is what nature should look like, and in fact is what nature does look like. If you heat a blackbody to 5800 Kelvin and look at the so-called spectrum of emitted power for a given frequency, the blue curve is what nature looks like. This yellow dotted curve is the prediction of the Rayleigh-Jeans law and comes nowhere near reality. It arguably maybe does an okay job for the very lowest frequencies, the very longest wavelengths of radiation from a body. Maybe a human body would be accurately described by the Rayleigh-Jeans law. But the sun, on the other hand, which has a temperature of about 5800 Kelvin, also behaves like a black body and is nowhere near described correctly by the Rayleigh-Jeans law. Now,
Another physicist named Wilhelm Wien figured out in 1896 his own version of this prediction, and that's the pink curve. And you'll notice that Wien's law, as it's known, does a pretty good job of describing the radiation at the highest frequencies, but does an abysmal job of describing radiation at low frequencies. Planck's law, however, nails it. Max Planck's law, as he derived it in the early 1900s, was the cornerstone of the correct description of the radiation from heated matter. So you can see here again a place where there's a breakdown between classical thinking, motivated by the things that we learn in introductory physics, the things that are from the familiar macroscopic world, applied to the world of the very small in this case, the individual constituents of a heated body of matter. There's a breakdown here, and a breakdown is an opportunity to make sense of the correct laws of nature. Max Planck figured it out, even where Wien and Rayleigh Jeans could not. So to review, in this lecture, we have learned the following things. We've learned about the connection between temperature and the constituents of a material body. We've explored the precise nature and cause of heat energy, the fact that heat energy is related to the average kinetic energy of the constituents of material, like an ideal gas, and that is directly related to the temperature of the macroscopic body of that gas. We've considered ways of transferring energy to and from objects, and we've looked specifically at the emanation of electromagnetic energy in the form of light from a heated body. We've looked at some of the laws that were either derived or determined to govern that kind of radiation of energy, and we've seen that in places where classical physics, mechanics, Newton's laws were combined with electromagnetism to predict the radiation from a heated body, a special kind of body, a blackbody, is a total breakdown compared to reality. In the next phase of the course, we're going to take this breakdown as a launching point for a deeper understanding of nature. We're going to transition from the very fast to the very small and begin to explore the origins of quantum physics. In this lecture, we will learn the following things. We will learn how the blackbody radiation spectrum was finally understood. We'll learn about the possibility that's implied by that solution that energy may come in discrete units. We'll learn about a phenomenon known as the photoelectric effect, and we'll learn how Albert Einstein resolved the puzzle of the photoelectric effect. In the last lecture, we saw how the Rayleigh-Jeans power spectrum prediction utterly failed to model nature correctly. Given a black body heated to a certain temperature T, the Rayleigh-Jeans model predicted that more and more energy should be emitted in shorter and shorter wavelengths, leading to some kind of natural catastrophe merely heating up a body to a few thousand degrees Kelvin. However, matter heated to a temperature T simply does not radiate according to that prediction, because if it did, the effects would be catastrophic. The shorter the wavelength and the more damaging the electromagnetic radiation, the more of it would have been emitted from such a body as predicted by the Rayleigh-Jeans model. It simply did not comport with reality. This mismatch between reality and the prediction of classical physics has been called the ultraviolet catastrophe. Correspondingly, the mismatch between reality and the prediction of Wien's model is known as the infrared catastrophe. Now, historically, this problem was not considered threatening or really so important that anyone truly panicked, although at least one individual did take this problem extremely seriously, and that's Max Planck. You got to admit, though, ultraviolet catastrophe is a lovely and exciting name. I should note that the term ultraviolet catastrophe actually doesn't date to the exact period when the Rayleigh-Jeans prediction or Planck and his work were established. but it actually appears to date to much later, about 1911, and seems to have been coined by the physicist Paul Ehrenfest. Now, in the last lecture, we saw that there was a model by a man named Planck, Max Planck, that did seem to have gotten the right answer. So what was it that Max Planck did? Well, he started from a mathematical model of a perfect blackbody, a simple model, a cavity fully enclosed on all sides, except for a tiny hole in the cavity. An ideal blackbody, to remind you, is one that absorbs all incident radiation on it, and then it re-emits its own radiation with some spectrum. It's got perfect emissivity, so it maximally radiates given its other physical properties. Now, once one hypothesizes that such a system exists, one then has to apply the laws of physics to predict or describe that emitted radiation spectrum, the amount of energy emitted, for instance, per unit solid angle, per unit time, per unit wavelength, and per unit area, per unit many things. But your bottom line is you're attempting to predict how much of each wavelength interval of radiation is present in the emitted bulk of radiation. Now, a cavity with a single small hole in it is actually a really good model for a perfect blackbody. If you shoot radiation at the hole, 100% of it, incident on the hole, will enter the cavity and be lost to the outside world. That radiation is absorbed by the cavity. Now, it then enters the cavity and it begins bouncing around inside the cavity, striking the walls and therefore hitting the bits of matter that make up the walls of the cavity. And fundamentally, as we've seen in physics 2, matter is made from electric charges. Now, as we also know, as these electric charges get struck by radiation, they're going to begin to gain kinetic energy, which will cause them to heat up the material surface of the cavity inside the cavity. A hotter object emits radiation in a different way than a cooler object. So again, the question we want to boil this down to is, what will that spectrum of emitted radiation due to the heating of the walls of the cavity from the incident radiation actually look like? Now, we can boil the black body problem down to just a very simple collection of phenomena that we can conceptualize of using information from physics 2. This is a very simple model of an electromagnetic wave, which would be what the radiation impinging on the surface of the cavity walls would look like. It's got an oscillating electric field, and perpendicular to it, it's got an oscillating magnetic field, and it's traveling perpendicular to both of those fields. This wave then strikes a charge in the wall of the cavity, so for instance an electron. The electron feels the electric and magnetic fields of the wave, and it will respond to those by accelerating. This is what we learned in physics 2. The wave, with its increasing and then decreasing electric field strength, for example, will cause an electron to accelerate more than less. It will oscillate. It will wave like a bit of matter in a rope that's wiggled, or in a chain that's shook, or in a string that's plucked. The electron will oscillate. So radiation enters the cavity with any number of possible frequencies or wavelengths that can compose that incident radiation, and all of it is taken in by the cavity through the hole. The electric charges that make up the matter in the walls of the cavity will either scatter, they'll be knocked off of their parent atoms, for instance, or maybe they'll wiggle in response to the electromagnetic wave that strikes them, and thus absorb some of the electromagnetic radiation as motion. Now, absorbing an electromagnetic wave causes the charges to oscillate, and an oscillating electric charge is a source of an electromagnetic wave. So these newly oscillating electric charges can emit their own electromagnetic radiation. This is the source of the emission spectrum from the blackbody. So what will that re-radiated energy look like when it escapes the cavity? That radiation too will bounce around inside the cavity, but some of it will make it out of the hole. What will it look like? And how much of each frequency is found in its power spectrum? Well, recall that the Rayleigh-Jeans model, using a purely classical model of all of this system, mechanics and electromagnetism via Maxwell's equations, determined that the spectrum should look something like this. that the energy emitted per unit time, taking into account the surface area and the whole viewing solid angle of the blackbody, will basically go as the temperature of that body over the wavelength to the fourth of a particular wavelength of light that we're considering as part of the outgoing spectrum. But as we can see, as you decrease the wavelength, that is, increase the frequency of the radiation, more and more and more power is emitted by the blackbody. Now, a key assumption that lay underneath the building of the Rayleigh-Jeans model was that all frequencies are possible for oscillating charges. A charge stuck in an atom in the wall of this cavity model can oscillate at any frequency it likes. All frequencies are possible. And that led to the Rayleigh-Jeans model. Let's make a very simple model of a system where we can cause oscillations to occur in electric charges, and then those oscillating electric charges in turn emit electromagnetic radiation, radio waves or light. That light then travels across a gap, striking another electric charge and setting it into oscillatory motion. To illustrate what I mean by this, imagine we have the ability to wiggle an electric charge over here at a transmitter site, and watch a sympathetic wiggle over here at a receiver site when an electromagnetic wave from the transmitter reaches the receiver. To illustrate this, let me start oscillating the electric charge on the left. What you're seeing here is the full electric field around that charge as it changes in time as the charge moves in space. The changing electric field propagates out at the speed of light and causes an oscillatory pattern in space. Some places have strong electric fields pointing in one direction, some places have weak electric fields, some places have electric fields that point in the opposite direction. We can better see this by looking at the amplitude of the electromagnetic wave as a function of position away from the oscillator, and we see the rising and falling in time of the wave as it travels to where the receiver is. The oscillator in this model is a charge that has been set in motion by radiation that was absorbed by the cavity walls. The absorption of the radiation causes the charge to oscillate, and the oscillating charge in turn emits its own electromagnetic radiation. So we're watching a charge that's been set into oscillatory motion by external radiation, emitting its own radiation here on the left, and then causing another charge to oscillate over on the right. That would in turn, of course, cause that secondary oscillation to generate its own radiation. And you can see how the blackbody problem is a very complex interplay, not only of mechanics, but electromagnetism. And getting the details of this right are essential to correctly predicting the radiation from a blackbody. Now, the fatal flaw that people like Rayleigh and Jeans made when constructing their prediction for the energy emitted per unit solid angle, per unit time, and per unit wavelength from, say, a blackbody, was that they assumed that any oscillatory frequency was possible for the charges. It seems a natural assumption. Electromagnetic waves originate on oscillating electric charges. If I change the frequency, and I can change it to anything I like in classical physics, I expect a different kind of electromagnetic wave with its own frequency to be emitted. And in classical physics, I can pick any frequency I want. Anyone at all. Because in classical physics, they're all possible. They're all allowed. And this was the fatal flaw, it turns out, in the Rayleigh-Jeans calculation of the blackbody spectrum. They assumed that those oscillating charges in the walls of the cavity could emit any frequency of radiation they wanted as they sympathetically begin to oscillate, having been struck by external radiation. It turns out that this leads to the Rayleigh-Jeans prediction of the power spectrum, which is utterly wrong. The Planck model, on the other hand, which arrived at the correct answer, results in a power spectrum that looks like this. It goes as 1 over lambda to a power, in this case lambda to the 5th. But there's an overall multiplicative factor, and that's where the temperature dependence shows up. It's also where a wavelength dependence shows up as well. And this extra piece has the effect of cutting off the power spectrum at high frequencies. In other words, as you go to higher frequencies, you actually see there's a turnover in the prediction of the model, and it drops off to 0. As you go to shorter and shorter wavelengths, higher and higher frequencies, you don't emit more energy, you wind up emitting less. Now, what was the difference between the Rayleigh-Jeans model and Planck's effort to model the blackbody spectrum? Well, one key assumption was that Planck did not allow all frequencies to be possible for oscillating charges. And I'll return to that assumption in a bit, looking at some of the historical context of Planck's own work. To give you a better sense of what atoms and molecules actually do when they are struck by electromagnetic radiation, let's look at this simulation incorporating the modern understanding of the interaction of radiation and matter. We have here a water molecule, 2 hydrogens bonded to 1 oxygen, and we can shoot radiation at it. Let's begin by shooting microwaves, long wavelength electromagnetic waves, somewhere between visible light and radio. If we start shooting microwaves at the water molecule, we see that many of the microwaves will pass through the water molecule, but some of them will be absorbed and cause rotational motion of the molecule, which then scatters the microwave. This is in fact how a microwave oven works. Microwaves at the right frequency will cause water molecules to rotate and collide with each other, and kinetic energy is added to the system, and as we know, kinetic energy is related to the temperature of material. If you add kinetic energy to the water molecules in a system, you will heat it up. Let's change the wavelength of the radiation to infrared. We are now shooting much shorter wavelength light at the water molecule. No longer are we able to make it rotate. Rather, we are able to make it oscillate. The hydrogen atoms that are bonded to the oxygen will occasionally be struck by an infrared photon that then causes them to jiggle around a little bit before scattering off the photon. If we shoot visible radiation, which has even shorter wavelengths, at our water molecule, we see that it is effectively transparent to the visible light. All the visible light radiation is passing through the water molecule as if it's not even there. And that shouldn't come as a surprise to us. Water is transparent to light. So it makes sense that visible light should be able to make it through a body of water, and we see that modeled here. If we shorten the wavelength of the radiation even more to ultraviolet, we see that this also tells us something about water, that water doesn't respond to this wavelength of radiation. Ultraviolet radiation passes through the water molecule essentially unscathed. This kind of little simulation incorporates our modern understanding of electric charge, chemicals, bonding, and the ways that energy can and cannot be absorbed and re-radiated by atoms and molecules. We see that not all radiation causes a water molecule, in this case, to do anything. Only certain light frequencies or wavelengths have an effect on the charges of the water molecule, and thus can cause them to vibrate, oscillate, or rotate in such a way that might result in subsequent, later, re-radiation of energy. Now, as I showed you in the last lecture video, this model accurately describes the shape of a blackbody spectrum, but it comes at one small cost. Planck's effort resulted in the need for a new physical constant, which he labeled h, and eventually came to be known as Planck's constant. It is related to the degree of the discretization of the oscillation of the charges in the cavity. In other words, not all frequencies of oscillation are allowed, and h tells us something about the gap between allowed frequencies. Things in between in the gaps are not allowed. This is known as the quantization of the oscillatory motion of charges in the cavity walls. Quantization coming from quantum, a Latin word for how much, implying not an unlimited set of values that are possible for a system, but rather a discrete, well-defined, and finite set of values that are allowed for a system, with no values in between the allowed ones. Now, the reason that the spectrum winds up cutting off at short wavelengths or high frequency is that electromagnetic radiation, as a consequence of Planck's model, requires a specific amount of energy to make a specific wavelength. In other words, if you want to make ultraviolet light, you've got to put in a minimum amount of energy to do that. If you want to make something with a shorter wavelength than ultraviolet light, like X-rays or gamma rays, you have to put in even more energy. And not all of those energies are possible inside the oscillating charges of the cavity walls. So if you don't have that energy, you can't make that wavelength, and the spectrum naturally cuts itself off. This implied also that the energy of the radiation is quantized and itself can come in units or packets. Now, this new constant, Planck's constant, h, ultimately had to be determined from experiment. It wasn't predicted by Planck's model. It was a parameter in the model that had to be determined. And it has units of joules times seconds, which, if you flip back to Physics 1 and play around with those units a little bit, you'll realize that they correspond to units of angular momentum. This actually has deep implications for the universe, but we're not going to get to them right now. Now, its value was originally determined by Max Planck. By simply changing the value of h around in his calculations until at a specific temperature for a blackbody, he had a value that yielded a shape for the blackbody spectrum that best described that particular heated blackbody. Now, that's how he did it, and in fact, by doing this, by fitting the parameter to the data and determining the value of the parameter itself, he came to within a few percent of the currently accepted value of Planck's constant, which is already a remarkable achievement. But in science, if you build a model by tuning it to existing experiment, the true test of a model is whether or not it correctly predicts new phenomena that have not yet been either explained or observed. So Planck's constant by itself being determined from the blackbody may just be tuning a mathematical model to the data to get the answer you wanted in the first place. That's the first step in describing nature. But if you want to see whether or not you've learned something deep about nature, you need to find the next thing that you can test by applying the same idea with the same constant and see if you get answers that are consistent with nature. Now, the currently accepted value of Planck's constant is 6.626 and a bunch of other decimal places times 10 to the negative 34 joule seconds. That is a number worth memorizing, on par with the speed of light, 2.998 times 10 to the 8th meters per second, or the mass of the electron, 9.11 times 10 to the minus 31 kilograms. Planck's constant is one of those fundamental numbers that, when committed to memory, can be busted out when you need it to do a quick calculation, and can be very handy when doing things like engineering new systems, like in electronics, for instance. Now, this constant is crucially important in the modern world. I can't understate its value any more than I can understate the value of the speed of light. Its value is now the basis of the Système International definition of the kilogram. The definition of the kilogram used to be based on the size and mass of a platinum iridium bar that was kept under glass in France. There are many flaws with that. For instance, if atoms of that bar flake off over time and you don't notice it, then over time your definition of the kilogram, using that as a reference, changes. Weights and measures are crucial to things like economies and standards and so forth. And so you don't want your definition of the kilogram drifting over time. Now, so far as we know, Planck's constant is stable over vast periods of time, certainly over many billions of years. And so it was wise to redefine the kilogram using something that itself can be determined independently and is stable. And it turned out that a particular way of measuring Planck's constant lends itself to defining the kilogram. And that change went into effect only in 2018. Planck's constant also plays a fundamental and key role in all electronic devices, certainly all modern microelectronics. Those devices rely on the exact properties of semiconducting materials, and semiconductors can be precisely engineered thanks to the quantization, the discretization of radiation and matter. And ultimately, all of this stems in its scale, size, and control from the value of Planck's constant. Now, as I've hinted before, Planck's work had a consequence built into it that, if true, would radically change our view of radiation, electromagnetic waves. He realized in his paper on the subject that as part of the only way he could find to describe the blackbody spectrum, he was forced to assume that radiation had to come in quantized units whose sizes were controlled by the constant h and proportional by that constant to the frequency of the electromagnetic waves. This equation relates the energy and the frequency of electromagnetic radiation. E equals h, Planck's constant, times f, the frequency of the radiation. And since frequency and wavelength are related by the speed of light, this also implies a relationship to the wavelength of that light. Let me give you some of the context of Max Planck and his work. He concluded this effort in 1900, after many desperate years of working on the problem. But he himself did not fully accept the implication of what his newly developed constant h implied, and the consequences of his solution to the blackbody spectrum problem. Basically, his solution implied, if correct, that matter and energy can be quantized into discrete units, and that units in between those are simply not realized in nature. They're forbidden by the system somehow, by the parameters of the system. Now, he assumed that this was all some kind of convenient math trick that he had played, that it wasn't really describing nature at a fundamental level, and that someone else would come along, really solve this problem using the correct description of nature, and one day explain why the trick worked. If you look at some things that Planck himself has said over the history of his own life, from the year in which he published his blackbody spectrum paper to decades later as he reflected on that period of his life, you can gain some insights into his psychology as a scientist at the time. And in the paper that he published in 1900, he states, "Moreover, it is necessary to interpret the total energy of a blackbody radiator not as a continuous, infinitely divisible quantity, but as a discrete quantity composed of an integral number of finite equal parts." You can see here in sort of the tone and writing of his sentence that he finds something necessary to do, but he doesn't necessarily take away from that it implies reality follows from this assumption. The assumption that the total energy of a blackbody radiator is discretized and not continuous may merely be a mathematical assumption, but nonetheless, he found it necessary to make this assumption in order to interpret the data. Now, many decades later, in a letter that he wrote to R.W. Wood, he reflected back on this period. And one famous quote from this letter is often repeated, wherein he said, "The whole procedure was an act of despair, because a theoretical interpretation had to be found at any price, no matter how high that may be." And you get a real taste of his professional desperation. Where others had failed to describe the blackbody spectrum, Planck was desperate to figure out what avenue would lead to the correct description. He didn't necessarily accept that the mathematical steps required to follow that avenue implied anything about nature, but it worked, and he published it, even if he didn't fully embrace the implications of his own work. Now, another famous quotation from Max Planck, whose source I simply couldn't track down, but it is attributed to him by many other sources, was that he was ready to sacrifice any of his previous convictions about physics in order to solve this problem. Now, this last quote, especially, was motivated by another thing that Planck had to do to solve this problem, and that was to employ a statistical description of matter and radiation. Many physicists found statistics distasteful because under the hood, statistics tells you that you can't know for sure the outcome of a particular system, but you can know the probabilities of all possible outcomes even if you don't know which one will be realized in the next experiment. Many physicists who believed that the universe was deterministic, that is, that if you know exactly the initial conditions, you can find the exact outcome of the system every time, found the use of statistics to describe nature distasteful. Distasteful doesn't necessarily mean wrong, and that's why the hard work of the scientist is to use observations of nature to assess the assumptions that we have made in trying to describe and predict nature. Now, as I said before, the burden in science of a new idea falls not on your ability to describe the things that came before, but to explain the things that come after, without changing any of the assumptions of the idea. A truly successful theory, a theory that is not only built on facts, but predicts the existence of new ones, is ultimately forged in the fire of experimental science, married with mathematical effort. This lands us on the subject of the photoelectric effect. Now, the photoelectric effect was known in the late 1800s, but could not be described using what was known in the late 1800s. It was observed by physicist Heinrich Hertz. Now, he was the first person to definitively demonstrate the existence of electromagnetic waves. These had been a phenomenon predicted by Maxwell's equations, and in that same prediction captured the essence of light, that light itself is an electromagnetic wave. Hertz realized that if you were going to test the prediction that electromagnetic waves are real, independent of light, you would need to demonstrate their existence by transmitting them from one place in a laboratory, receiving them at another, and showing that the wave induces an oscillating electric charge at the target location. So what he ultimately showed was that an oscillating charge at one place in a room, a laboratory, could induce an oscillating charge elsewhere in the room with no physical contact, and this established the reality of electromagnetic waves beyond light. In fact, you could think of this as the first radio transmission. Now, he was also the first person to demonstrate an intriguing physical phenomenon, the photoelectric effect. Light, which is an electromagnetic wave at heart, at least in the Maxwell view of nature, shone on a metal, can liberate electrons from the metal. So take a beam of light, shine it on the surface of a metal, look for an electric current, and under the right conditions, you will see an electric current develop in the metal. Now, Maxwell's equations predict that the intensity of a light beam, an electromagnetic wave, is proportional to the squared strength of its electric field. That is, E naught squared, if E naught is the base maximal electric field value of a particular wave. Now, because of that prediction, attempts were made to describe and predict and explain the observed features of the photoelectric effect. So let me use an analogy combining mechanics and the laws of electromagnetism, Maxwell's equations, to attempt to predict the set of phenomena that you would expect to arise in the photoelectric effect. Think of the charges in a metal as a ball that's stuck in a pond in a patch of lily pads or weeds. What you want to do is liberate the ball. You would like to knock the ball out of the lily pads, free it so that it floats over to the shore and you can get it, because you don't want to step in all of these weeds. Who knows what's swimming around in this thing? Fine. So you and your friends devise a sort of classical photoelectric effect experiment. You get a bunch of empty buckets that you might have around to keep ice, keep your beverages cool while you're playing that day. You empty out the buckets and you carry them over to the shore of the pond. And one of you kneels down at the edge of the pond and starts using the bucket to push on the surface of the pond. Well, this generates water waves. So you're pushing on the surface of the pond, and the water waves are making the ball and the lily pads wiggle up and down, but it's not knocking the ball loose. No problem. You're at the limit of your strength, but you've got lots of friends. So your friends all also kneel down at the edge of the pond near you, and they start pushing on the surface of the pond. And you're not very coordinated, so these waves have different amplitudes at different times. But eventually, if you're patient enough, some waves will pass through the ball, they'll add up an amplitude constructively interfering, and they'll deliver enough energy to the ball to knock it out of the lily pads. So the photoelectric effect, in analogy to this ball stuck on a pond in a bunch of lily pads, should be behaving as follows. If you send in light waves, even feeble light waves that don't themselves have enough energy to liberate a charge from a metal, if you send in enough of those light waves at the metal, you will begin liberating charges. The light wave amplitude should add up. They go as the electric field squared of each wave, and if you wait long enough, you'll start knocking electrons out of the metal. That's what people expected from the classical theory of mechanics and electromagnetism. But what was actually observed in the close study of the photoelectric effect? Well, what was observed was that the intensity of the light you shine on the metal has no effect on initiating the effect itself. The photoelectric effect can't be induced by simply cranking up and up and up and up the intensity of light if that light doesn't already seem to have the ability to make a current flow in the metal. We can simulate the observed photoelectric effect using this PhET simulation that's available on the web. For example, I can start by trying to shine long wavelength light onto a metal. I've selected a copper plate, which is located on the left side of the apparatus. I have a representative light source at the top of the apparatus. And as you can see, I can control the intensity of the electromagnetic radiation, or light, that I can shine on the copper. I'm going to go ahead and crank this red light source up to 100% of its intensity. And as you can see, there is no observed current in the graph on the right. The graph shows on the y-axis the electric current that's observed in the system, and on the horizontal axis the intensity of the light, which is currently pegged at 100%. Even if you wait 1 minute, 10 minutes, 100 minutes, you think you're allowing the amplitude to build up and occasionally knock an electron out of the metal, but you see nothing. Now instead, if you change the wavelength or frequency of the light, you maybe can see what happens to the effect. Do you make an electric current flow? Well, if you start from a particular wavelength of light that doesn't cause the photoelectric effect, and then you change it gradually to a longer wavelength, say start with red light and then change it to microwaves or radio, you'll also notice moving the intensity of the light up and down doesn't cause the photoelectric effect to start. But if you shorten the wavelength from the ineffective wavelength to something shorter, higher frequency, shorter wavelength, at some point you'll suddenly notice that electrons will begin to flow through and off the metal. You can induce the effect as you shorten the wavelength. I'm going to begin to lower the wavelength of the light from red at about 750 nanometers, down to orange, down to yellow, and we still see that nothing is happening. I've definitely switched to a shorter wavelength of electromagnetic radiation, but we still see no current versus intensity on the graph. I'm going to continue to shorten the wavelength of the light. Now we're into the green, we're approaching light blue or blue. Now we're going to the more richer blues, and we're heading toward violet. Now, I'm definitely down at the shortest visible wavelength range of light, and yet the copper is doing nothing, and I'm blasting it with 100% intensity. But watch what happens when I push this simulation into the ultraviolet, very short wavelength radiation. Once I cross below a threshold wavelength or frequency for the radiation, suddenly electrons begin to get shot off the copper by the light. Now, over here you'll notice that the current has gone up a little bit on the vertical axis. I'm at 100% intensity, and I've moved up about 1 tick mark on this axis. Now, once you've set the photoelectric effect in motion, you might hypothesize that if you crank down the intensity of the light to some sufficiently low level, then the waves won't be able to add up enough anymore, and no more charge will flow, even before the intensity gets to zero. But what you find is that the electric current that you induce in the metal declines to zero as the intensity goes to zero, and the electric current only goes to exactly zero when the intensity is also zero. That is, you switch the light off. What I'm going to do now is I'm going to go ahead and lower the intensity of the light. Now you'll notice that, of course, the current is decreasing. As the intensity of the light decreases, I'm still knocking electrons off, but not as many. And of course, if I bring the intensity all the way down to zero, then the photoelectric effect switches off. There was no point in the intensity and current plot where the effect suddenly switched off before I got to zero intensity. In fact, if there's even a little bit of intensity, you'll notice that electrons start boiling off of the copper. Not many, but they come off, some very fast and some very slow. At a particular threshold wavelength and frequency, the photoelectric effect simply begins. Raising and lowering the intensity of the light seems to have no effect on the maximum kinetic energy of an ejected electron. Even very weak intense light, but with the correct wavelength or frequency, will rapidly eject an electron occasionally with a high kinetic energy, despite the fact that the intensity scales as the square of the electric field strength. And shouldn't more electric field produce more acceleration? That's what all of that stuff from Coulomb's law and physics 2 and Maxwell's equations says should be happening. I can lower the intensity down even more, down to just 1% of the source. And yet nonetheless, electrons will come shooting off of this thing with lots of kinetic energy. It's as if the kinetic energy of the ejected electrons from the copper have nothing to do with the intensity of the light, but only to do with the wavelength or frequency of that light. Now I can bring the radiation up in intensity a little bit so that we can see a few more electrons boiling off the metal. And what I'm going to do is I'm going to begin to increase the wavelength of the light, just very gradually, just a nudge at a time. At some point, we're going to cross a threshold where the light simply does not have sufficient wavelength to induce the photoelectric effect. And it seems that I've gotten to it at about 270 nanometers. Now I can go ahead and crank up the intensity to 100% now that I've moved just past the wavelength threshold to induce the photoelectric effect. And yet again, we see that intensity does not suddenly cause the photoelectric effect to switch on. Now you can see how frustrating this must have been for the physicists of the late 1800s. This set of observational facts defied explanation using all the battle-tested notions of classical waves and the laws of electromagnetism. Does this sound familiar? Does this sound like the moment that led to special relativity? Because if it does, you're on the right trail. You've found a place where the theory of motion and the theory of electricity and magnetism, which were largely developed on macroscopic things, then encounters a new microscopic phenomenon where it utterly fails to make accurate predictions. And that smacks of opportunity. So how was the photoelectric effect explained? Well, it was our old friend Albert Einstein who cracked the photoelectric effect in one of his 1905 so-called miracle year publications. This was the year that catapulted him into at least physics academic fame, and allowed him to finally secure a faculty position after years of toil at the patent office in Bern, Switzerland. Now, to explain the phenomenon, Einstein reached back to Planck's 1900 paper on the blackbody spectrum. Recall that a consequence of Planck's solution to the problem, desperate though the remedy may have been, was that light has an energy that's given not by the intensity of the electric field of the wave, but rather by the frequency or wavelength of the light. That is, E is equal to h, Planck's constant, times f, the frequency of the light. Now, since the speed of light is equal to the frequency times the wavelength, one can substitute into this to get the corresponding relationship with wavelength. Shorten the wavelength, increase the energy. Increase the frequency, increase the energy. Those are the relationships between frequency and wavelength and the energy of a light packet, a light quantum. So Einstein embraces the implication of Max Planck's work that radiation can be quantized into discrete units. And therefore, a single unit of light is hypothesized to carry, or cost to produce, h times f for light of a certain frequency, f. So even if one unit of light of a certain frequency strikes an electron, and therefore strikes it with a certain amount of energy given by h times f, the liberation of the electron is immediately possible, independent of the intensity of the light. More light quanta striking more electrons per second means more electric current. Fewer light quanta striking fewer electrons per second means less current. But if you have even one, you will liberate a charge. And that's consistent with the observations of the photoelectric effect, that once you make it happens all the way down to even very low intensity until you switch off the light source. So what are the equations describing the photoelectric effect that were worked up by Einstein in 1905? So he reasoned that it takes a certain minimum amount of energy to remove an electron from a metal. A metal isn't just going to give up its electrons without a fight. I mean, otherwise it would be really easy to just reach out and strip electrons off a metal, but it takes energy. So there's some minimum amount of energy that's required to liberate one charge from a metal, and this is called the work function, and it's denoted by the lowercase Greek letter phi. Now, if a quantum of light with a given energy strikes the electron and has energy that exceeds the work function, then it's possible to transfer energy to the electron and remove it from the metal. It can scatter the electron or even be fully absorbed by the electron. The maximum amount of energy that can be transferred to the electron by such an interaction of matter and light is given by the following equation, that the maximum energy that an electron can get when struck by a quantum of light is given by the energy of the quantum of light minus the work function. It takes some energy to remove the electron. If there's extra energy left over after that, it goes into the energy of the electron in motion. And finally, we arrive from Planck's hypothesis about the energy of these light quanta at the equation that the maximum energy you can transfer to an electron removing it from a metal is hf minus phi. Now, if hf is less than phi, the electron can't receive sufficient energy to be removed from the metal. hf must equal or exceed the work function in order to liberate an electron from a metal. And metals of different kinds take different amounts of energy to remove charges from them. Now, where does that energy go? Well, it goes into the kinetic energy of the electron. The electron will gain kinetic energy as a result of this interaction with a quantum of light. And so finally we arrive at the following equation, that the energy we're talking about here is really the maximum amount of kinetic energy that any given electron can receive in this collision process. And that's going to be equal to Planck's constant times the frequency of the light that struck the electron minus the work function of the metal, the minimum energy required to remove the electron from the metal. This ultimately leads to the birth of the concept of the photon, and implies that light has both particle-like and wave-like aspects that need to be taken into account. Now, the classical description of light from Maxwell's equations imagines that light is an electromagnetic wave with an electric field that oscillates in time and space, a magnetic field that oscillates perpendicular to the electric field in time and space, and that the wave travels perpendicular to both the electric and magnetic fields. Each wave will have an energy per unit area given by this equation. This is what I said before, that the intensity of the radiation is proportional to the electric field squared. This is all a wave description. But Einstein's special relativistic description of massless phenomena, which light seems to be, says that the energy of a massless phenomenon is equal to its momentum times the speed of light. Now recall that special relativity did not tell us where the momentum itself for light comes from. But that, thanks to Max Planck and Albert Einstein, Planck quantizing radiation and the oscillations of matter in order to explain the blackbody spectrum, and Einstein adopting the quantization of radiation in order to explain the photoelectric effect, and doing so perfectly, then leads to the following description of light interacting with matter, that the energy of a light quantum is equal to Planck's constant times the frequency, or Planck's constant times the speed of light, divided by the wavelength of the radiation. And we see that the energy of the light is related to the frequency, and that the momentum is also related to the frequency, or the wavelength. The origin of the numerical value of a light quantum's energy is wavelength and frequency. Those tune and control the energy and momentum of a light quantum. Now, the wave-like aspects of light, like diffraction and interference, oscillating charges making electromagnetic waves, and electromagnetic waves then also sympathetically causing charges to oscillate. These are all very wave-like things that had all been very well confirmed prior to the early 1900s. But the blackbody problem and the photoelectric effect couldn't be solved with those wave-like aspects. You needed particle-like aspects of light, and these phenomena began to hint that those were needed. Light energy comes in units. That energy is defined by frequency and wavelength. And light is a massless phenomenon. An electron is a massive particle-like thing that can travel through space. Light is a massless thing that travels through space. And we see from the resolution of the blackbody problem and the photoelectric effect that light has these quantum discrete behaviors in the same way that particulate matter has a quantum or discrete nature. Now, Einstein referred to these packets of light energy as light quanta, and again that comes from the Latin quantum, meaning how much. Now, in a letter in 1926, physical chemist Gilbert Lewis coined the more common term, the one we use today, photon, implying a quantum of light, from the Greek for light. Now, in science, it's not enough to describe a phenomenon. It's important that that description have testable consequences, and that there is a test that could falsify the explanation and show that it's wrong. Now, if your explanation survives a test, it lives another day and gets to make more predictions, and over time, if it keeps surviving, it gets adopted as an accurate description of nature, perhaps even as a law of nature. You can imagine that Einstein's explanation was not readily accepted, of course, and much as Planck had met his own work with serious scientific skepticism, Einstein's adoption of the quantum nature of radiation to explain the photoelectric effect with all of these interesting consequences was also met with serious scientific skepticism. The American physicist Robert Millikan, who was one of the sort of few well-known American physicists in this early part of the 1900s, and his famous, especially to high school chemistry students, for the oil drop experiment that established the fundamental unit of electric charge, although that experiment is a whole fascinating story in and of itself. Millikan did not take the claims of Einstein's explanation about the so-called, the maximum kinetic energy of an ejected electron and so forth very seriously. He wanted to test this claim to see if it was possible to refute Einstein's explanation of the photoelectric effect. Now, we're going to do a reproduction of this famous experiment by Millikan in our class. But I'll tease the conclusion of this, and it's the following. That Millikan in 1914, after careful experimentation, confirmed Einstein's description of the photoelectric effect, all stemming from the quantum hypothesis of radiation. In the end, the photoelectric effect paper that appeared in 1905 during this amazingly productive year of work from Albert Einstein won the day. And it's no accident, therefore, that Einstein went on to receive a Nobel Prize in Physics in 1921. Interestingly, it's for this work that Einstein received the Nobel Prize in Physics, not for special relativity, not for general relativity, but for this niche effect in experimental physics. Now, Einstein had extended Planck's work to an entirely separate space of experimental effort, not the blackbody spectrum where Planck determined the value of his constant and, while he made a satisfactory explanation of that spectrum, didn't accept the implications of his own explanation. Einstein embraced those implications and then predicted all the aspects of the photoelectric effect, not only correctly describing what was known of the phenomena, but then leading to the experiments of Millikan, who confirmed that description as accurate fully in its mathematical formulation. This set the stage for an entirely new other perspective on nature. Not the theory of space and time and the speed of light and gravity, the theory of the very fast, but the quantum view of matter and radiation, the correct theory of the very small. So to review, in this lecture we have learned the following things. We've learned how the blackbody radiation spectrum was finally understood, and about the possibility implied by this resolution that energy may come in discrete units. We've also learned about the photoelectric effect and how Einstein resolved the puzzle of the photoelectric effect by embracing the conclusion of Max Planck's work on the blackbody radiation spectrum, applying them to the photoelectric effect to make predictions about that phenomenon, which ultimately proved to be the correct description of nature. And that all of this has set the stage for a new view of radiation and matter. In this lecture, we will learn about the following things. We will learn about the nature of a kind of radiation called X-rays. We'll learn a little bit about the production of X-rays. And finally, we'll look at the scattering of X-rays by matter and the implications for the nature of electromagnetic radiation. Now, X-rays were discovered serendipitously in 1895 while Wilhelm Röntgen was experimenting with what are then known as cathode rays, and which we would now simply know as electrons. He was using a device that would boil electrons off a metal using a very strong electric field, and he observed some distance away from the apparatus that a special phosphorescent screen was glowing, even though there should be no radiation from the experiment actually reaching the screen. And so he became obsessed with trying to understand this phenomenon, and after careful experimentation, he decided that he had isolated a new kind of radiation that was heretofore unknown. And using the variable for an unknown quantity in math, which is usually x, he coined the term X-rays to describe these. Now, one of the things that he observed during his experiments was that if he allowed the X-rays to pass through his hand, it would cast a shadow on a screen behind the hand that showed only the bones of his hand. And in fact, this led to him attempting to make the first, what we would now call, medical X-ray in 1895. He used the hand of his then spouse, Anna Ludwig, and her hand, famously, is the first medical X-ray ever known to have been recorded in the history of science. You can see here the dark areas that look very much like the bones of the hand. The knuckles are up here. She's clearly wearing a ring or something around her finger here, and the tips of the fingers are up here. The thumb is off to the side. For public presentation, Röntgen made a much nicer version of this picture using a different hand and a different experimental apparatus. But essentially, this is the birth of medical imaging as we think of it now, non-invasive imaging using radiation or something else to see inside the body. Now, we now know that X-rays are a kind of electromagnetic radiation. They're a very short wavelength of light. You can't see them with your eyes, but if you have the right instrumentation, which Röntgen did when he serendipitously discovered them, you can induce a signal in something that can be seen with the eyes. They have wavelengths that range at their smallest between 0.01 nanometer all the way up to 10 nanometers. Now, as Röntgen discovered, they easily penetrate common low-density materials. Think cardboard, skin, muscle. Most X-rays will pass through those undeflected, unstopped. Now, if you use more dense material between you and the source of X-rays, then, of course, what he observed was that more of the X-rays are stopped. So the light regions here are places where X-rays easily made it through. The dark regions are places where many fewer X-rays penetrated through the hand in order to get to the imaging device on the other side, in this case, photographic film. So lead, bone, this is more dense than skin, muscle, paper, cardboard, and so it's more likely to stop or scatter X-rays. Now you can imagine that these are insanely useful, not just for practical applications, but for all kinds of interesting studies of the natural world. And they would themselves become a key object of study, and ultimately would lead the way toward understanding more about the particle-like aspects of light's behaviors. Now let's talk about Arthur Holly Compton and X-ray scattering experiments. As I mentioned in the previous lecture, in the late 1800s and early 1900s, there were not many notable physicists from the United States. Now, that's as compared to the then European powerhouse of both education and research that was long and well established across the Atlantic Ocean. Now, one of the physicists who became very well known in the early 1900s was Ohio-born Arthur Holly Compton. Interestingly, his PhD thesis was in part on the reflection of X-rays. After his PhD, he received National Research Council support and was then free to travel and do research abroad. And he selected to conduct work at the then famous Cavendish Laboratory in Cambridge, England. And he did this in 1919. Now, there he would experiment with very short wavelength light, including X-rays and gamma rays, laying the groundwork for his eventual discovery of what is now known as the Compton effect. He returned to the United States in the early 1920s and became faculty at Washington University in St. Louis. And it was there that he observed definitively and methodically now what we refer to as the Compton effect, that X-ray quanta scattered by free electrons experience a lengthening of their wavelength after the scattering, and that this lengthening is a strong function of the angle at which the light is scattered. So how to explain this? This is a very particle-like picture of an X-ray striking a free electron, causing the electron to scatter, and itself being scattered. Now, in classical electromagnetism, a wave would come in, it would start an electron oscillating. The electron would oscillate sympathetically, but this shouldn't result in a change in the wavelength of the radiation. Like waves on the surface of a pond, it'll make things on the surface start to bounce up and down, but the wave itself doesn't change wavelength when it scatters through these things. On the other hand, Compton could only explain this phenomenon by analyzing this scattering process from a more particle-like viewpoint, where the X-ray quanta have energy and momentum before and after the collision with the free electron, and that because the energy and momentum of the quantum is changed, the wavelength is changed. And he came up with a precise mathematical formula to relate all of these changes. So we can hypothesize, as Compton did based on Einstein's 1905 photoelectric effect work, which was itself based on Max Planck's blackbody spectrum work, that the X-ray incident on the electron, which I've labeled here I for the purposes of the coming notation, before scattering, carries a total momentum that's given by E equals Pc for the incident momentum and energy. This can be related through Planck's relationship to the frequency of the radiation, so h, Planck's constant, times Fi, the initial frequency of the radiation. And if we want to get wavelength into this to consider shifts in the wavelength of the scattered light, then we can convert this into hc over lambda I, where lambda I is the initial wavelength. Now, this allows us to write the momentum of the incident X-ray, as the initial momentum is Planck's constant divided by the wavelength. So E is most neatly equal to h times f, but p, the momentum of the quantum, is most neatly related to the wavelength by h divided by the wavelength, lambda. The scattering process then occurs, and the final scattered light quantum carries a different momentum, p final equals h over lambda final. Now, the initial electron state we could take as being at rest, and so it has no velocity in the initial state. But the final state, it involves an electron that's now been scattered at some angle, phi, that we'll write down later. Now it has a total speed u final, and thus it has a total momentum. Now, I'm going to be careful here. I'm not going to assume that this is necessarily a slow-moving electron, and in fact, in reality, in the Compton scattering experiments, these electrons come out with a whopping great amount of momentum, putting them very close to the speed of light, so close that it is obviously safe to use the relativistic definition of momentum. That is, the gamma factor that's a function of the speed of the ejected electron times the mass of the electron times its speed. Now, to analyze this as a scattering process involving the collision of a X-ray with a stationary electron, leading to a moving electron and a scattered light quantum, we need to only conserve total energy and then momentum in the x and y directions. So x is here clearly labeled as the horizontal direction, positive to the right. Y is the vertical direction, and it would be positive upward vertically. So let's go ahead and do this. Let's start from conservation of momentum in the horizontal or x direction. This is a closed and isolated system, so the initial momentum of the system, that includes the X-ray and the stationary electron, must be equal to the final momentum of the system. That now involves the scattered light quantum and the moving electron. So if we substitute in with the equations for the initial and final momentum of the light quantum, and we put in the component of the velocity of the electron along the horizontal axis, we wind up with this equation, which, removing the zero, because the electron in the initial state is not moving, simplifies to this equation here. Now, let me comment on a few things. First of all, the initial momentum of the X-ray is entirely along the x-axis, but only a part of its final momentum lies along the x-axis, and so that's given by hc over lambda f, its total final momentum, times the cosine of the scattering angle theta. Now, there's another angle in the problem. It's the angle between the horizontal and the electron that gets scattered, and that's denoted phi. And because of the picture up here, we're only considering the horizontal component of the electron's momentum, and that's given by gamma mu cosine phi. So far nothing exciting going on. It's just breaking down the kinematics of the X-ray and the final state light quantum and the scattered electron all along the x-axis. And that's about as far as we can go right now without knowing things like phi, the scattering angle of the electron. We need more equations. And so we're going to turn to conserving momentum in y. So let's go ahead and write down the vertical conservation of momentum for the same problem. I'll proceed through this relatively quickly. Again, the initial total momentum in the y direction must be equal to the final total momentum in the y direction. There is no initial momentum in the y direction. The X-ray is moving entirely along the x-axis. The unscattered electron has no velocity, so the initial state is all zeros. And the final state has two pieces, the positive vertical component of the scattered light quantum and the negative vertical component of the scattered electron. And so we can consolidate the zeros on the left-hand side, and we wind up with this equation here. Now we have sines instead of cosines for the two scattering angles in the problem. Now, we could use this to solve for phi, or at least sine of phi, where it's already looking a bit nasty. We can already see that this is going to be a bit of a lift in algebra. let's see if the conservation of total energy in the system holds any comfort for us in attempting to get at a singular equation that relates the initial wavelength, the final wavelength, and the scattering angle of the light quantum. Well, we're going to conserve total energy. Total initial energy must be equal to total final energy. We can plug in the total energy of the initial X-ray, hc over lambda I. Now, remember, the total energy of the unmoving electron is not zero. This is special relativity. Mass energy is internal energy and is therefore just energy. So we have to put in the rest mass energy of the electron. The final light quantum has an energy hc over lambda f, and the final scattered electron has a total energy given by gamma times the mass of the electron times c squared. This involves both kinetic and internal mass energy. Now, we can then just rewrite this equation without the conservation of energy stuff on the left, and we arrive at this equation here relating initial and final energies. Nothing's really simplified. So there's not a lot of comfort here. It's going to be an algebraic lift, but these are the pieces that Compton would have worked with, and in fact did work with, in order to try to understand his scattering experiments. From his experiment, he would have known three things: the incident X-ray wavelength, lambda I, the scattered light wavelength, lambda f, and the angle at which light is scattered, theta. So the question is, of course, can we use algebra, and possibly pages of it, in order to relate these things using this hypothesis of a particle-like scattering process between light quanta and an electron? And can we then make a prediction for the relationship between these three things? Well, the answer is yes, and I'm going to leave the lengthy algebra to the viewer or reader of all of this stuff here. But basically, we're going to eventually find, by working through all of this, what Compton found, and that is that the predicted relationship between the final and initial wavelength and the scattering angle is given by this very nice-looking equation here. In fact, what we find out is that from Compton's analysis of this process, it suggests that the difference in wavelengths after and before the scatter will depend only on the scattering angle of the light and some constants of nature, h, the mass of the electron, and the speed of light. Compton ultimately confirmed that this was a correct description of these experiments by doing his own experiments and testing this idea. Now, there are some implications from the Compton effect, which is described in this formula. An undeflected X-ray, that is an X-ray that goes straight through the system with an angle theta equals 0, will experience no shift in wavelength. The cosine of 0 is 1, 1 minus 1 is 0. There is no difference between the initial and final wavelength of the X-ray. That doesn't lead to a big surprise. But more interesting, perhaps, is that if you have a completely deflected X-ray, one whose scattering angle is 180 degrees, or pi radians, that is, a so-called backscatter, comes straight back at the source of the X-rays, it will experience the maximal possible shift in wavelength. And that corresponds, from an energy perspective, to the largest achievable kinetic energy for the electron. That's the most kinetic energy a scattered electron is ever going to get, is when you have a perfect backscatter of the X-rays as a result of losing energy to the electron and coming out at this 180-degree scattering angle. Now, Compton, in the course of doing his experiments, did observe scattered light at angles other than those expected from simply scattering off the electrons. And from this, he determined that some of the X-rays were scattering not off of just electrons in the atoms, but entire atoms themselves. That is, you could rework the algebra that would lead to the Compton scattering formula, not by putting in the mass of a scattered electron, but by putting in the mass of an entire scattered atomic nucleus or atom. And if you do that, you'll find that scattering at the same angle leads to a much smaller wavelength shift, because the mass of an atom is much bigger than the mass of an electron, and that causes the wavelength shift to get much, much, much smaller at the same angle. But nonetheless, you will see scattered light with an entirely different set of wavelengths, albeit at a lower rate, at that same angle, when sometimes the X-rays scatter off of whole atoms and not just electrons. What this also implied was that for light with wavelengths or frequencies at the level of X-rays, which does span a large space of wavelength ranges, scattering of the light behaves more like scattering particles off of other particles, like bouncing tennis balls off of bowling balls or something like that, rather than waves off of particles, where waves would cause sympathetic oscillations in the particles but wouldn't change the wavelength of the original wave. So this flies in the face again of the purely wave hypothesis of light. And it seems that under these conditions, a much better and more accurate description of the way that light behaves is as if it behaves as a large collection of quanta, more than as a collection of waves. Now, this all has deeper implications that stem from the Compton effect. Let's take everything from the last few lectures together into one coherent picture. All together, the blackbody problem, the photoelectric effect, and Compton scattering point toward a complex set of aspects of light behavior. Light isn't just a wave, and it's not just a unit or discrete thing like a particle. Under some conditions, light behaves exactly according to classical Maxwell equation theory. Waves scattering off of or otherwise interacting with and causing oscillations in matter. That behavior was well established by the late 1800s. Electromagnetic waves really can behave like waves. But under different conditions, suddenly one can observe that light behaves more accurately according to a particle description, a quantum description, that light is discretized in some way, not continuous like a wave. So in that case, it's better described as a collection of quanta, the photon, so many photons all acting together. And that can be thought of as particles interacting with the particles that themselves compose matter, electrons, whole atoms, and so forth. So what ultimately resulted from all of this was that there are particle-like aspects of light's behavior that tend to correspond more often to when the wavelength of the light was very short, that is, very high frequency, whereas the wave-like aspects of light's behavior seemed to manifest or correspond more when the wavelength is very long, that is, the radiation has very low frequency. Somewhere in that space of wavelengths and frequencies, between very long and very short, there's a transition between these sets of behavior, wave-like and particle-like. But what defines short and long? That's a very arbitrary distinction. Something that's hot to one person may actually be kind of chilly to another. Think about the way that offices are heated or air-conditioned. Some people find the temperature in a typical office setting perfectly fine and acceptable. Some people have to put a blanket over themselves to stay warm because they view it as chilly. Okay, but how do we define short and long to understand when the wave and when the particle-like phenomena are applicable? Well, it turns out that the answer has to do with the dimension, d, or size, or scale, of the system with which the light interacts. So the longness or shortness of wavelength, or the highness or lowness of frequency, is when compared to the size of the system with which the light interacts. If the wavelength of the light is much, much greater than the dimensions of the system, think long wavelengths that are far in excess of the size of atoms, for instance, then it turns out that wave-like behavior rules. The atom experiences light like a wave. If the wavelength is much, much smaller than the dimensions of the system, then the system experiences light more like being crashed into by a particle, where all the momentum and energy is transferred at once. Particle-like behavior rules. Now, in the middle, as the wavelength becomes comparable to the size of the system, things get very complicated, and you have to be extremely careful and have an accurate theory in order to actually predict what's going to happen in that case. So there are some extreme cases. The wavelength is much smaller than the dimensions of the system. The wavelength is much longer than the dimensions of the system. Those are easy to handle when absolutely particle-like behavior or absolutely wave-like behavior manifests. In the middle, things get dicey. And in order to describe systems which have comparable sizes to the wavelength of light, for instance, you need the right theory. We don't quite have it yet. Now, let's talk about the sizes of things as a primer for what's to come in our thinking about the interactions of light and matter. To probe the scales of things with sizes larger than a virus, and we can see from this chart over here that a virus has a size scale that's roughly 100 nanometers. Okay? You can find that it's sufficient to use visible light. Bacteria have sizes of about 1 micron, 1,000 nanometers in size. Red blood cells, 10,000 nanometers, or about 10 microns in size. Hairs about 100 microns, or 100,000 nanometers in size. Ants are 10 to the 6 nanometers. Baseballs are about 10 to the 8th nanometers. We're in the realm of the macroscopic. Macroscopic here meaning larger than the wavelength of visible light. So this helps us to understand a little bit about why it is that we didn't get ourselves into trouble with large-scale descriptions of motion and radiation, a la Newton's laws and Maxwell's equations, when we were dealing with things that had sizes that were much smaller than the wavelengths of light that we were using to interact with them. Looking at a bacterium or a red blood cell or a hair follicle with a microscope is straightforward because the wavelength of visible light is much smaller than all of those things, and so it simply scatters off of them, and we can resolve the sizes of those structures quite easily. When you have a wavelength that's smaller than the structure you're looking at, you can resolve the features of that structure. But to probe viruses and DNA or hemoglobin or macromolecules, like glucose, for instance, you need X-rays. You need to get down to sizes that are about the level of 1 to 5 to 10 nanometers or so. In those cases, you're going to need something like X-rays if you want to resolve the structure of glucose, hemoglobin, DNA, which are obviously essential to understanding modern biological functioning. So X-rays are your friend when you want to probe structures that are smaller than bacteria. X-rays will allow you to see, if you have the right instrumentation to reveal them to the eye, these sorts of distance scales. But if you want to probe atoms and molecules, you need to really push your X-rays. You need to go down to the shortest X-ray lengths, about 0.01 nanometer or so. The scale of atoms is at the level of 0.1 nanometers, or 10 to the minus 10 meters. So X-rays can be comparable to, or smaller than, but not by much, the size of an atom. And so the particle-like aspects of light begin to emerge naturally at this scale. It's no surprise that the behavior of X-rays, which is an electromagnetic radiation, became very particle-like when we started looking at them interacting with atomic systems like the atoms in metal and the electrons in those atoms. Those things turn out to have scales that are roughly comparable in size or a little bit bigger than the kinds of X-rays that were scattering off of them. And so that's when we got ourselves into trouble when it came to the theory of light and how it's supposed to behave when it interacts with matter. It's when the size of the light got to be smaller than the size of the thing that we were smashing the light into, and suddenly we needed a slightly different description of light in order to understand all that. Now, just to tease things, if you wanted to probe the nucleus of an atom, there we're talking about sizes at the level of 10 to the negative 15 meter, or 1 femtometer. And for that, X-rays are just too big. You're not going to resolve things of the size of a nucleus of an atom using X-rays. Instead, you need something with a wavelength that's really short, like gamma ray radiation. Or even other things that, as we'll learn, turn out to have even smaller wavelengths than gamma rays. Let's revisit the phenomenon of the interference of light. We've looked at this in class in the context of the Michelson-Morley experiment. What we saw in an in-class demonstration was that light that is forced to pass through a very narrow opening will diffract, you'll get a pattern on a screen some distance away from the slit that the light passes through that shows light and dark spots. The bright spots are where the waves have constructively interfered and their amplitudes have added up. The dark spots are where the waves have been out of phase with each other and destructively interfere. Black areas are places where the waves completely cancel each other out. This computer simulation imagines sending in light waves toward a barrier that has two slits in it. The light can diffract through either slit. The resulting wavefronts that come out on the far side of the barrier then interfere with each other. And if we put a screen up here on the right side, we could imagine imaging this and seeing bright spots and dark spots and bright spots and dark spots and then fainter bright spots and so forth. The pattern can be controlled by changing the geometry of this setup. So for instance, if I increase the separation between the slits and wait a few moments for the light pattern to catch up, we'll notice that as we take more data with the screen on the right, the number of bright fringes has increased. We now see that what was once faint on the outside is much brighter. But nonetheless, we have bright, dark, and so forth. This is a wave behavior. How can we reconcile the particle nature of light and the wave nature of light in a phenomenon like this, two-slit light diffraction? Instead of imagining waves of light coming into a system with two slits in the barrier, let's instead set up a situation where we can fire, say, photons that correspond to green light at a barrier with two slits in it, one at a time. If we do this, we imagine sending in one photon. That photon has to go through either the barrier on the left or the barrier on the right. We don't know which barrier it's going to go through, but we can look at the screen on the other side to see where it lands. And slowly, one photon at a time, as we look at the observing screen on the far side, we see green dots. The green dots indicate where the photon that we fired ultimately wound up on the screen. One photon at a time, we're building up an image on the far side of the screen. Now, this is rather tedious. We'd like to see if a pattern emerges in all of this. So I'm going to speed this up, and then when sufficient information has been received by the viewing screen on the other side, I'll comment on the pattern. Sufficient time has passed that we can begin to comment on the pattern we observe on the detector screen. There are places where photons have clearly clumped after passing through the two-slit process. There are places where we find few or no photons on the detecting screen. For instance, those darker regions flank the bright region in the middle. This is akin to the interference pattern that we saw when we were thinking about light as a wave traveling through this system and interfering with itself. Now, single photon by single photon, we're building up a similar intensity pattern on the screen on the far side. There are bright bands, dark bands, bright bands, dark bands, and so forth. The same alternating pattern of high intensity and low intensity that we saw from the wave behavior. Indeed, it seems that the wave behavior is recovered in the limit of a large number of photons passing through the system. This reconciles the wave and particle behavior aspects of light in a single experiment. And in fact, this famous Young's two-slit experiment is one of the many ways that one can reconcile and understand these dual aspects of the existence of the phenomenon we call light. In fact, what seems to be true for the single photon experiment is that we're unable to predict with certainty where any single photon will wind up striking the screen on the other side. But the probability that a photon will strike in the middle is much higher than the probability that it will strike just to the right or just to the left of center. And from that, we can begin to build an understanding that the probability of where a photon goes on the screen seems to be somehow related to the intensity, the amplitude squared, of the light wave description of nature. Now, in this lecture, let's review what we have learned. We've learned about the nature of X-rays, and we've seen a little bit about how to produce them by experimenting with cathode rays, electrons smashing into a target. We then looked at the scattering of X-rays by matter, and following Arthur Compton's explanation of his scattering experiments, have come to understand something about the nature of radiation with very short wavelengths. From this, we've seen the implications not only for the nature of electromagnetic radiation, as having both particle-like and wave-like aspects under different conditions, but something about the conditions themselves that trigger these different aspects of the behavior to be observed. When the wavelength of the radiation is much smaller than the scale of the thing that it's scattering off of, then we see the particle-like aspects of light's behavior emerge. When the wavelength is much greater than the size of the thing off of which the radiation is scattering, then we see the wave-like aspects of the radiation emerge. And in between, there's a transition, a place where we lack a theory so far to actually understand how to calculate. These are the foundations for what will happen next, as we depart the comfortable world of radiation with its wave-like behavior and now its newly understood particle-like behavior, and turn our eye from radiation to matter itself. In this lecture, we will learn the following things. We'll learn about the structure of the atom as it was known in the late 1800s and very early 1900s. We'll learn about how matter itself can have wave aspects to its behavior. We'll learn about Louis de Broglie's experimentally verified conjectures about the wave properties of matter. And we'll learn about how to conduct experiments that reveal the wave aspects of matter's behavior. To review, let's take a look at the things that describe the wave aspects and the particle aspects of electromagnetic radiation. Recall that the wave description of light was really the first and most formally developed part of the description of its behavior set, and these are included in Maxwell's equations. Now, they describe a spatially and temporally distributed phenomenon. You can boil the wave equations in Maxwell's equations down to this set of equations describing space and time variations in electric and magnetic fields, and these variations propagate at the speed of light in the material under configuration. For simplicity, we can assume empty space, or simply the vacuum, and in that case, the solutions in empty space are the famous electromagnetic wave solutions, an oscillating electric and magnetic disturbance that travels at the speed of light perpendicular to the variations in electric and magnetic components. And then, of course, there's an energy per unit area of an electromagnetic wave in empty space. There's no one place where the energy is concentrated. There's more in some place and less in others, and one can think about the energy density or the energy per unit area of a traveling electromagnetic wave phenomenon. Now, the particle description of light, which emerged from evidence based on the blackbody radiation spectrum and the photoelectric effect, these are descriptions of something that has definite energy and definite momentum at a definite location in space and time. That's what a particle is. It's a localized phenomena at a very specific place in space-time, whereas a wave is a spread out and distributed phenomenon that isn't only in just one place in space-time. Now, from Albert Einstein's work on the photoelectric effect, which built upon Max Planck's work with the blackbody spectrum, we have sort of a combined description of the particle-like aspects of light's behavior set. So, for instance, in special relativity, we have massless phenomena whose energy and momentum are related by the speed of light, E equals p times c. But unfortunately in special relativity, we couldn't glimpse where the energy or the momentum of light came from. We got nonsense answers from pure special relativity. However, Max Planck's work with the blackbody spectrum revealed another relationship, that the energy of a quantum of light, a photon, is related to the frequency of the light, E equals hf, and the constant of proportionality is Planck's famous constant. We can plug in the relationship between wavelength and frequency for a light wave, c equals f lambda, and we can get a relationship, for instance, between energy and frequency, energy and wavelength, and more interestingly, between momentum and wavelength, which we get by combining the energy and momentum relationships between special relativity and the blackbody spectrum. So we find that for a quantum of light, a localized packet-like unit of light, energy is related to the wave properties of that same phenomenon by E equals hf, and momentum is related to the wave properties by p equals h over lambda.
Let's model a long wavelength interaction and a short wavelength interaction using a beaker sitting in a tank of water. This identical beaker is going to be smashed into by a wave under two different conditions. On the left, a long wavelength disturbance that's much larger than the size of the beaker, and on the right, a short wavelength disturbance whose size is comparable to that of the beaker. This will illustrate the difference between wave-like phenomena and particle-like phenomena. The motion on the left, as the wave develops in the tank, will be more gradual, with the beaker gently falling and then rising. Whereas on the right, when the short wave crashes into the beaker, it's almost as if it's been struck by something small and fast-moving. Look how violent the collision on the right is compared to the one on the left. We might argue the beaker on the right has been struck by something more particle-like, whereas the beaker on the left, which is bobbing around, has been struck by something more wave-like. This helps to illustrate why a wavelength phenomena short compared to the target will exhibit particle-like behavior, whereas a wavelength long compared to the target will exhibit wave-like behavior.
But what if? What's so special about electromagnetic radiation? Why does electromagnetic radiation get to have all the fun of having particle-like and wave-like aspects to its behavior set? What if matter, electrons, protons, neutrons, whole atoms, also could exhibit wave-like behaviors? They had been experienced primarily as particulate objects, definite things with locations in space and time. But maybe it was just because nobody had observed the wave aspects of the behavior up to a certain point, such as in the early 1900s. There were hints, of course, that something funny was going on with matter at the scale of the atomic size. So, for instance, it had been long known, since certainly the work of Anders Ångström in the early part of the 1800s, that the emission spectra of elements like hydrogen gas or helium gas, that they emitted only certain colors. White light comes in a full rainbow, and if you stare at white light closely enough, for instance from the sun, you'll see that there are missing lines of color in its spectrum, but they're hard to detect. If you take a pure gas and you excite it so that it emits light, it's much easier to see that it's only allowed to emit certain wavelengths, certain colors of light. Here I show you the hydrogen emission spectrum revealed using an optical disc, a DVD or a CD-ROM. The many scattering surfaces for light on the surface of the disc will spread any light that strikes it out like a prism into a rainbow. But we see an incomplete rainbow from hydrogen. There's a bright red line, there's a bright blue-green or cyan line, there's a blue line, and then there's a fainter purple line, which you can actually see part of down here reflected in the disk. Now, this is a more classical way of laying out the emission spectrum of a gas like hydrogen, flattening it all out on a plane.
Here's that red line, the blue-green line. It's very hard to see the faint dark blue line, and then there's a violet or purple line down here. These are the long wavelength emissions, these are the short wavelength emissions, but there are big gaps in between these things, and no two elements have the same spectral fingerprints. Excite helium, excite neon, excite argon, and you'll get a very different pattern of colored lines out of each of those. Why? Why are atoms only allowed to emit certain kinds of light? That was a source of curiosity in the 1800s that could not be resolved. Whole mathematical patterns were observed out of the relationships in wavelength or frequency between these colored lines, but nobody could make sense of why these relationships existed and where they came from. Now, to understand what's going on with matter at size scales like that of the atom, it's very valuable to dig back a little bit into the history of the discovery and description of the atom as a real phenomenon in nature. Now, of course, thousands of years ago, philosophers and mathematicians and perhaps what would now be considered proto-scientists and engineers thought deeply about matter, and they argued endlessly about whether it was continuously distributed, made of only a finite number of substances, or atomic in nature, that is, coming in small units that could be built up into the structures we experience in nature. But that was a lot of argument without a lot of evidence, and our modern understanding of how to understand the natural world and the scientific method reflects the reality that speculation is fine, but the final arbiter is observation of nature and the testing of your claims. The discovery of atoms as a real feature of nature, or at least a potentially real feature of nature, goes back to the early 1800s, when chemist John Dalton discerned that not only elements have weight, and that the weights are specific to each element, in proportion to, for instance, the weight of hydrogen, but also that when you react one element with another element, you'll only get products from the reaction that completely use up the reactants if you have the right proportions of reactants. For instance, you might try reacting two things 1-to-1, but have an incomplete reaction. React them in a ratio of 2-to-1, and you completely eliminate all of the original reactants that went into the process. That was something that Dalton characterized. And it was a strong hint that the elements come in units, and that those units have rules of combination that only allow certain proportions of them to completely react and disappear into other final products. Now, it wouldn't be until 1897, although speculation had preceded in the decades before this work, that Joseph John, or J.J. Thomson, would reveal the first component of what would come to be known as atoms. Atoms themselves were not completely firmly established as the correct description of nature in 1897, but Thomson found out by experimenting on a kind of radiation known as cathode rays in his day that they actually possess of mass, but they possess of a unit of mass that is about 1,000 times less than that of hydrogen. Now, this would imply that either there's a lighter element than hydrogen, or perhaps one had ripped something out of hydrogen and isolated it in the first place to be studied. He observes that these cathode rays, with their very tiny masses, also possess of electric charge and can be made to, for instance, accelerate in electric fields or bend in magnetic fields. In 1905, based on the idea that this electron, which composes the cathode rays, which is the identity of the cathode rays, is a piece of what we call atoms, he proposed a model of the atom. Imagine a central large positive charge with negative charges embedded in it. And this was known as the plum pudding model because it looked very much like a British dessert known as a plum pudding, where you have a whole bunch of raisins or other fruits embedded in sort of a uniform distribution of dough, which is cooked up into a dessert. So imagine that the raisins are the negative charges and the positive charge is the dough, and the negative charges are spread throughout the dough. This was Thomson's model of the atom. Now that may sound ludicrous and cartoonish, but the beauty of science is that that's a conjecture that can be tested. For instance, you might imagine trying to do experiments that
verify whether or not the negative charge and the positive charge are uniformly spread out in something of the volume of an atom. That's an experiment that couldn't necessarily be conducted at that moment in 1905, but it was certainly possible shortly thereafter. Now, cherry-picking my way through the story, I want to focus for a moment on Marie and Pierre Curie. Now, they, among many other people, came to understand that unstable elements, or radioactive elements that emit radiation when they decay away, results in a new kind of radiation that had not yet up till that point been understood. Now, they experimented on these radiations, and it was finally Ernest Rutherford who classified them into the modern way that we usually talk about emission of radiation from unstable atomic nuclei. And those three classes of radiation are alpha, beta, and gamma, for the first three letters of the Greek alphabet. Alpha radiation would eventually be revealed to be a whole hydrogen nucleus entirely ejected from a very heavy nucleus of a very heavy atom. So this would be 2 protons and 2 neutrons bound together in a very stable little unit, and it can be spat out of an unstable nucleus that spontaneously radioactively decays. Now, alpha radiation is highly electrically charged. It has +2 units of the elementary charge because of its 2 protons, and that means that it can't penetrate very far into material, but it can get into material, and it can dump a lot of energy along the way. As I mentioned, Ernest Rutherford came up with this classification scheme. He was another physicist who is considered to be one of the greatest experimentalists, if not of his day, perhaps even of all time. Working in conjunction with the physicists Hans Geiger and Ernest Marsden, he scattered alpha radiation off metallic targets, and he found out, by looking at the scattering process, that the plum pudding model of J.J. Thomson did not describe what happened when you scattered alpha particles off of atomic nuclei. The Thomson model would have postulated that because all the charge is very spatially spread out, the probability of striking any of the positive charge or any of the negative charge is extremely small. And so for the most part, you'd expect to find your alpha radiation traveling through the atom lightly scattered, but mostly coming out on the other side of the target. But when Rutherford asked Geiger and Marsden to look at what's called backscattered alpha particles, that is, look for alpha particles that strike the metallic target and then reflect almost exactly back at the original emitter of the alpha radiation, they were surprised to find out that there are a significant number of alpha particles that bounce back off of the metal target as if they're striking a huge target of positive charge concentrated somewhere in the center of every atom. And this, in fact, was a picture that Rutherford used to build his own model of the atom, modifying J.J. Thomson's model and concentrating all the positive charge in each atom at the center of the atom. This forms the first sort of planetary model of the atom, as electrons orbiting a central, tightly packed nucleus with a huge positive charge, of course depending on the element in question. But it was this picture that adequately described the backscattering process, with its higher rate than expected from the Thomson model, observed by Rutherford, Geiger, and Marsden. This is now known as the Rutherford model of the atom, and it would be further modified as more experiments were conducted on this system. Now, how do we know the sizes of atoms? Well, skipping ahead a little bit in the story of the atom, you can look at the scattering of X-rays. For instance, we looked at Compton scattering in a previous lecture. But imagine scattering X-rays with slightly longer wavelengths than we would have been talking about when talking about Compton scattering. Here, the X-ray is, it turns out, comparable in size to the atoms off of which it's scattering, with wavelengths of about 0.1 nanometer or so. Smashing these X-rays into crystalline solids like table salt, sodium chloride, it was observed that specific patterns will appear in the scattered X-rays. So, for instance, this image on the right is the very first X-ray diffractogram made by Max von Laue, Paul Knipping, and Walter Friedrich in 1912. Not long after Rutherford's experiments revealed that the atom was composed of electrons with a tightly packed positively charged nucleus.
Now, von Lau, Knipping, and Friedrich noticed that there were bright spots where the X-rays tended to accumulate and dark regions where no scattered X-rays tended to be observed. And this, interestingly enough, looked like a interference pattern that you would expect from light interfering and scattering in different ways off of a target. So using these interference patterns, and especially through the work of William Henry Bragg and William Lawrence Bragg, the only father and son team to ever win the Nobel Prize in Physics, they were able to explain the scattering of the X-rays as being off of small objects, albeit with comparable size to the X-rays in question, and separations in space that were similarly comparably sized. So William Henry Bragg and Lawrence Bragg did their own scattering experiments, and Lawrence Bragg in particular developed a model of the scattering process of scattering X-rays off of regular layers of atoms in a crystalline solid that beautifully explained these patterns of light and dark that were observed at first by von Lau, Knipping, and Friedrich in 1912. And this actually led to the ability to determine the approximate size of atoms using these X-ray diffraction patterns. Let's take a look at the model that Lawrence Bragg developed, because it will help us to understand how we can detect wave properties in general going forward.
Let's begin by modeling a crystal as a series of regularly arranged atoms layered in planes. We'll come back to the separation between the planes later, but they could be represented by some distance, d, which will appear later in this example. Let's then imagine that we draw an incoming X-ray that scatters off of one particular atom in a plane at the top of the system. Now, from the place where this ray has been emitted, the X-ray will strike an atom and scatter off of it. This will have a certain path length associated with it, the default length that this X-ray had to travel during the scattering process. We can imagine then that this X-ray came from the plane of emission shown here, which makes a 90-degree angle to the original X-ray. A second ray emitted from very close by from the plane of emission, which also makes an angle of 90 degrees with respect to that surface, strikes another atom nearby, missing the first one but hitting one in the layer below it. That ray also scatters and is detected at another point where the first X-ray is also detected, photographic film or a camera or some system like that. Now, because the second ray did not strike the same atom as the first X-ray, there's going to be an extra bit of distance that the second X-ray has to travel before coming back to the plane where the first X-ray is also detected. So we can imagine considering what that extra length is by drawing another line parallel to the line of emission, the plane of emission, that represents the extra distance that the X-ray would have to go. That's highlighted here in red. This is the extra length that the X-ray, the second one scattering off the second atom, has to travel before it returns to the same location where the first X-ray also strikes a detection system. On each side of the scatter off the second atom, we have an extra length, capital L, that the X-ray had to travel. And we can start doing some geometry to figure out how one relates that extra length L to the displacement d between atoms and the planes of the crystal. Notice that the angle between the black lines, which are parallel to the plane of emission, and the red lines here must also be 90 degrees. This is some geometry that you yourself could work through to verify. But that ray will always remain perpendicular to the plane of emission. Now, the scattered X-rays will make an angle, theta, with respect to the surface of the crystal. And if one works through the trigonometry and the geometry of the problem, you'll find that there is one interior angle inside the little triangle whose hypotenuse is d, and who each have a side of length L, and the similar angle is indicated here. Now we can relate the length L, this is half the extra length the ray has to travel, to the distance d and the angle theta of scattering by simply noting that in this triangle the sine of theta is equal to L, the opposite side, divided by d, the hypotenuse of the right triangle. Now, Let's think about what's going to happen if these two waves, one scattered off of one atom on the surface of the crystal and one scattered off of an atom in the next layer of the crystal, meet at the same place on the detection screen at the same time. One of these X-rays, the first one for instance, is a wave, and it's going to have crests and troughs just like any other electromagnetic wave. Now, its partner X-ray that arrives at the same time will interfere constructively or destructively depending on the alignment of the second ray with the first one. Let's imagine we want to figure out what the condition is for completely constructive interference, that is, where the peaks of X-ray 1 line up with the peaks of X-ray 2, and the condition for that is that they be shifted relative to each other by exactly an integer number of wavelengths. This is the condition for constructive interference. The waves can be shifted in distance by some distance 2L with respect to each other, but the condition is that that distance 2L has to be an integer multiple of the X-ray's wavelengths after scattering. So n times lambda, so that is an integer number n, times the wavelength of the X-ray, lambda, meets the condition for constructive interference when n is an exact integer multiple of lambda. As I said, the condition for constructive interference is that n times lambda is some distance d, and that's the extra distance that the second X-ray has to travel. And from our picture, that's twice L. Now we can relate this extra length L to the angle of scatter of the X-rays theta using the trigonometric relationship derived earlier. And that relationship was just that sine theta, the sine of the scattering angle, equals L, the side opposite that angle, divided by d, the hypotenuse of the triangle. This allows us to solve for L in terms of d and sine theta. L is equal to d times sine theta. Now plugging that into our constructive interference condition, we find the following: that if the second X-ray is shifted by an integer number of wavelengths with respect to the first, n times lambda, then this will simply equal to 2d sine theta, constrained by the scattering requirements in the system for constructive interference. And this condition, this mathematical condition in order to obtain constructive interference, is known as the Bragg condition, as derived by Lorentz Bragg originally in thinking about this X-ray scattering process. So all one has to do is look at angles where you see bright spots in the interference pattern, and this will tell you, given the wavelength of the X-rays, what is the space separation of the planes of atoms in the crystal.
Now, in the specific case of the sodium chloride X-ray scattering that I hinted at earlier, if you take regular crystals of sodium chloride and expose them to a beam of X-rays, you can look to see where in scattering angle, relative to the incident beam, the bright spots and dark spots appear. So, for instance, we have here an X-ray spectrometer. The vertical axis is the number of X-rays per second that are detected, and the horizontal axis is the angle with respect to the incident beam of X-rays. Now, theta here is the scattering angle with respect to, say, the surface of the material, but this can be related via 2 theta back to the original angle to the beam. You'll notice that there are, in fact, places where there are buildups of intensity of scattered X-rays. So, for instance, just before 30 degrees, around 28 degrees or so, and just around 32 degrees. And then there's another clump of peaks over here. There's a clump just around 60 or so degrees, and so forth. And then there's another clump over here. There's a very low bump and then a larger bump. And you'll notice that these bumps come with different intensities. Well, what's going on here is that a copper emitter is being used to generate the X-rays. And because of the properties of copper, it generates 2 kinds of X-rays in the beam, the so-called copper K-alpha line and the copper K-beta line. The K-alpha line has a wavelength of about 0.15 nanometer, and the K-beta line has a wavelength of about 0.14 nanometer. So they're not exactly the same wavelength, and that explains why the first bright fringe in the X-ray has 2 peaks, one from each of the K-alpha and K-beta lines. The second bright spot in the X-ray scatter has 2 peaks, again, one from the alpha and one from the beta line, and so forth. Now, if you take the Lorentz-Bragg scattering approach and you relate the locations in angle space of bright spots, constructive interference locations, back to the size of the scattering distance between scatterers in the crystal lattice, you can actually estimate the separation of the atoms or molecules that make up the crystal lattice. And you find out that this comes in at about 0.28 nanometers, regardless of which of these X-ray lines you consider. So we find out that the spacing of the scatterers inside a sodium chloride crystal is about the same scale as the X-ray wavelengths. It's only about a factor of 2 or so larger than the X-ray wavelengths. That's easy then for us to see the wave nature of the scattered X-rays emerge, because they are a little bit bigger then, but comparable in size to the things off of which they're scattering. It's no wonder we don't see strong Compton scattering here. The particle nature of the X-rays is not in effect the wave nature of the X-rays, because they're large compared to the size of the things they're scattering off of, is in effect. But this is nice because it tells us roughly the scale of the size of the scattering objects, and that comes in at about a fraction of a nanometer. So this roughly tells us that the size of atoms or atomic distance scales is at that level of about a fraction of a nanometer. Now, this tells us something about the sizes of atoms. Atoms come in at sizes around 10 to the minus 10 meters or so. This unit is not in the Système International, but it's known as the angstrom in honor of Anders Angstrom. The angstrom is about 10 to the minus 10 meters, and that roughly corresponds to the size of, say, a hydrogen atom or an atom that's slightly larger than that. Now, going back to atomic emission spectra, that is, heating or ionizing a gas, an elemental gas like hydrogen or helium or neon or something like that, we get these patterns of light that come out. It's as if only certain energies are permitted for the electrons in an atom. Well, why would that be? Well, in your mind, you might start modeling the electron in orbit around the central nucleus of its parent atom as a string on a guitar. A string on a guitar is confined at two ends. It's bolted down at two ends and tensioned. And once you set the tension of a guitar string, all the primary and secondary frequencies of its vibration are fixed. And that's how you can tune the tension of a guitar string and get a specific note. A note consists of a specific fundamental frequency and then a whole bunch of other frequencies layered on top of it with regular intervals. And what determines the frequency is the length of the string and the tension of the string. And that basically says how many of each kind of standing wave with a certain wavelength can actually be found on a guitar string. So perhaps, like guitar strings confined at two ends, electrons are wave-like and find themselves confined in a specific volume with only specific frequencies allowed. That would certainly help explain why these patterns of light are so specific to each atom. So we might draw in our mind a model of the atom as an electron confined to a volume, like a spherical volume with a radius that's about the size of an atom, 0.1 nanometer or so. Maybe it's there that these wave-like properties of electrons, which you couldn't really notice at larger scales, clearly emerge. And maybe that's why atomic spectra have the properties that they have with these regularly spaced and, in fact, mathematically related colored lines. This certainly would be consistent with observations of other phenomena like the blackbody cavity emitter, where only certain vibrational frequencies of the walls of the cavity appeared to be allowed, and that constrained the radiation that the cavity could emit. So this isn't totally alien. The blackbody spectrum and atomic emission spectra may be two aspects of the same behavior trying to tell us something about matter. So, if matter can be wave-like as well as particle-like, what is it that determines the wave properties of matter? Remember, for light, we had Maxwell's equations. They were built up from the careful study of the electric and magnetic forces and fields, and emerged as wave equations that, when solved in empty space, told us that light was an electromagnetic wave, an oscillatory phenomena with wave-like characteristics. We have no wave equation for matter. There is no first principles thing that we've experienced up through the end of the 1800s that tells us, oh, well, of course, there's a wave equation for matter too. So we don't have a starting point for the wave properties of matter, assuming they're even real at all. So in his 1924 PhD thesis, French physicist Louis de Broglie postulated in the same way that Einstein postulated that the speed of light was the same for all observers, that matter also has wave properties. And not only that, drawing from Planck's relationship between energy and frequency for light, and the relationship between momentum and wavelength that results from special relativity, de Broglie asserted the hypothesis that the very same facts would be true for matter if it had wave-like properties. So the energy of a piece of matter would be related to the frequency of the matter wave by E equals hf. That's a conjecture. That the momentum of a piece of matter would be related to the wavelength of the corresponding matter wave by h divided by the wavelength. That's a conjecture. So how would one prove this? Recall, Einstein made the conjecture based on the Michelson-Morley experiment that the speed of light was the same for all observers, regardless of the state of motion of the source of the light or the observer of the light. Relative motion did not change the speed of light. That could be tested by conducting experiments looking at the constancy of the speed of light with respect to motion. Now, that conjecture, along with the other postulate of relativity, had other predictive consequences for this description of space and time. And those consequences were verified. Think about time dilation and the lifetime of the muon. So how would one prove de Broglie's conjecture? Well, Bragg scattering offers the possibility to test this hypothesis. We could, for instance, compute the matter wave properties of electrons, and then we might try to find a system off of which we might scatter them and see if we can see the wave properties of electrons revealed by the scattering process. All we have to do is find a scattering system whose size scale is slightly smaller than or roughly comparable to whatever the corresponding matter wavelengths of an electron would be. So just as X-rays scattered from crystals allows the wave nature of X-rays to reveal to us the structure of the crystals, once we know the structure of crystals themselves, regular arrangements of atoms, we can then look at electron scattering and see if it reveals any wave properties of electrons. For instance, interference. Well, this is precisely what was done. So consider the electron with its mass of 9.11 times 10 to the minus 31 kilograms. Now, imagine accelerating it up to some momentum. Now, we're going to be fully relativistic here. We're going to use the correct definition of momentum because we might have to accelerate electrons to extremely high speeds to achieve the kinds of properties, the wave properties we would need in order to see if those wave properties exist. So we're going to use the fully relativistic momentum equation, the gamma factor of the electron times its mass times its velocity, which we can set by accelerating the electron. Now, by de Broglie's postulates, the momentum of an electron accelerated up to some speed u is going to be related to its matter wavelength by h over lambda e. So, what momentum would we need to accelerate an electron to probe the scale of a crystal, whose spacing is going to be somewhere around the level of 0.1 nanometers or so? Well, we would ideally want to achieve an acceleration that gets our wavelength down to something comparable to that, about 0.1 nanometer. Now notice that momentum, according to de Broglie's postulate, is inversely proportional to wavelength. So if we want to get the wavelength down to something the size of 0.1 nanometer, we've got to get the momentum up high to some target value. Now, if you crunch the numbers on this, this will require an electron momentum of about 7 times 10 to the negative 24 kilogram meter per second. That doesn't really tell us much. So, for instance, if we used an accelerating electric potential difference, a voltage, to get our electrons up to this momentum, what voltage would be needed to achieve that for an electron? Now, I'm going to leave the math to you if you would like to play around with this, but you need to make sure that you're careful and use special relativity to answer these questions. Remember the relationship between energy and the gamma factor, total energy and the gamma factor for an electron. That's written down here. And remember also from special relativity that that can be related to the momentum and the rest mass of the electron, okay, through this equation. And keep in mind also the special relativistic definition of kinetic energy. You're going to need to combine all of these things to get the answer to the question, what voltage would be needed to achieve this for an electron? But it turns out that this momentum corresponds to a gamma factor that's actually quite modest. It's only 1.0003. That's only a small fraction of the speed of light, and that shouldn't be hard to achieve for something as low mass as the electron. That corresponds to a kinetic energy of about 2 times 10 to the negative 17 joules. And if you remember your conversion of electron volts, an electron volt is roughly 10 to the negative 19 joules or so. This isn't many electron volts worth of kinetic energy. And so if you crunch the numbers and you relate the kinetic energy to the accelerating potential that would be required to achieve that for an electron with its 1 unit of elementary charge, you very quickly find out that this only requires about 150 volts. That is no problem at all. Certainly in the days when this experiment was done, and this experiment was done in 1927, achieving 150 volt electric potential difference for electrons was quite a trivial activity in that day. So that scattering experiment was famously done by 2 physicists, Lester Germer, shown on the right-hand side of the photo, and Clinton Davison, shown on the left. And this is, in fact, a piece of the equipment of their scattering experiment with the electron emitter and the nickel crystal that they used as a target in 1927 to do the scattering. And then they looked at the pattern of scattered electrons to see if any wave nature effects emerged. And what's the most obvious wave nature effects? Well, if you see an interference pattern in the scattered locations of the electrons, that is, if you see places where there are intense locations where electrons scatter to and other dark regions where they don't scatter to, then you would have some evidence for the wave nature of electrons. Matter wave properties could, in fact, be real. So, just as in X-ray scattering, if you scan over the scattering angle of the electrons from the crystal, and if wave properties manifest, then constructive and destructive wave interference should occur at different angles for a fixed wavelength, and thus a fixed momentum. All right, so this is an analogy to the X-ray scattering process, of course, that we looked at earlier with Bragg scattering. So what you could do, of course, is you could set your voltage to accelerate the electrons to something specific to achieve a specific momentum for the incoming beam. And then you could look at different angles of scattering relative to the beam to see if you see intense regions and less intense regions of scattering. In that case, the Bragg scattering formula just applies. If you want to see the nth bright fringe of constructive interference, the first, the second, the third, and so forth, then all you have to do, knowing the wavelength of the thing you're scattering, is look at a specific angle, knowing the size of the crystal, the spacing between the scatterers and the crystal D. And then the wavelength would simply be determined using de Broglie's hypothesis, using the momentum of the electron. But actually, instead of scanning over scattering angle, in fact, when you can control very easily the momentum of the electrons, then it's actually easier to simply vary the momentum of the electron beam and observe at a fixed angle theta. So don't move around where you're looking. Just observe at a fixed angle theta and scan through voltage, which changes the momentum of the beam and thus changes the degree of the wave properties of the beam as a function of voltage. And as you scan over the voltage, sometimes you'll make the electrons have just the right wavelength to interfere totally constructively when they scatter. And sometimes, as you keep tuning the voltage around, you'll make them interfere totally destructively with each other, and you'll see no scattered electrons at that same angle theta. And this is what Davison and Germer did, and here's what they saw. So this is the intensity of scattered electrons versus the square root of the voltage of their instrument. And what you notice is that there is a place, of course, where there's a bright intensity peak, and then it falls off to a minimum, and then there's another bright intensity peak at a different voltage, and then it falls off to a minimum, and so forth. And you see that there are these increases in electron intensity at a certain voltage, and then you crank the voltage up a little bit more, and the intensity decreases down to a minimum. You keep cranking it, and it goes up to a maximum again. We are seeing exactly what would have been predicted from Bragg scattering combined with the matter-wave hypothesis. This did not have to be this way, but it turns out that matter also has wave-like properties that can be revealed under the right conditions. Just to really drive this home, in 2 dimensions, now scanning over scattering angle rather than fixing the scattering angle and scanning over electron momentum, this is what an electron diffractogram looks like. You see this pattern of bright and dark spots separated by gaps here. We can very clearly see that electrons will intensely build up in the scattering process in some places and not at all in other places, with big gaps in between both vertically and horizontally. There are very clearly bright spots and dark spots, just like a laser beam that interferes with itself through passing through 2 slits, for instance. Only waves can interfere with each other in this manner. And in this case, it's because the crystalline solids, like nickel, for instance, off of which the electrons are scattered, have structures that can accommodate an easily tuned electron momentum that yields a wavelength comparable to the size of the scattering system, or a little bit larger. And that's easy to do with even modestly accelerated electrons on a metal target. So here's what scattering and interference tell us about the true nature of both matter and electromagnetic radiation. Electromagnetic radiation already has a wave equation that describes its wave nature. It comes from Maxwell's equations. So again, we come back to this question, well, if matter can be revealed through experiment and observation to have wave properties under certain conditions, then where's the wave equation? Where's the equivalent of the thing that comes from Maxwell's equations that describes the wave properties of electrons, protons, neutrons, whole atoms, etc.? Where is it? What is it? Electromagnetic fields and light propagating through empty space, these are the solutions to Maxwell's equations. If we had an equivalent matter-wave equation, what will the solutions to the matter-wave equation look like? And these are all excellent questions. And these are the questions that after these kinds of experiments had been done, physicists really began to struggle with in the 1920s and into the 1930s. Now, we're going to get to the answer to this question very soon, but we have some hints for ourselves already. The solutions to the matter-wave equation, whatever they are, whatever specific form they take for a very specific system, an electron scattering off of a nickel crystal, an electron confined in a hydrogen atom. Whatever the solutions to the matter-wave equation are going to be, they're going to be probabilistic in nature. And we can already see this revealed in the scattering intensity patterns from experiments like Bragg scattering, the Davis and Germer experiment, and so forth. The intensity of the scattering pattern seems to have everything to do with the probability of finding a particle at a certain location in space and time after the scattering process has occurred. And that probability is controlled in some way by the original wave nature of the thing that experienced, in this case, the scattering phenomenon. Probability. Whatever our wave equation describes, it's going to be probabilistic in nature. Waves are a spread out spatial and temporal phenomenon. There's no one place where a wave is and where it is not. There are many places where a wave can be. And probability and the wave equation, whatever it is, are going to play a fundamental and deep role with one another in describing matter and radiation. So let's review. In this lecture, we have learned the following things. We've learned about the structure of the atom as it was known in the late 1800s and very early 1900s, cherry-picking our way through just a few scenes in the great story of the atom. We've learned about how matter itself can have wave aspects to its behavior, first hinted at, although no one really understood this at the time, by the nature of atomic spectra and the blackbody spectrum. Now, it was Louis de Broglie who conjectured
that the same wave and momentum and energy descriptions that could be discerned from the blackbody spectrum and special relativity equally applied to matter, like electrons. That was a conjecture. And that was experimentally verified using scattering experiments of matter off of other matter. The target had size scales that were comparable to the matter wavelength we were trying to assess, and in fact, tuning the beam of electrons to the right momentum to get the desired wavelength, we actually see that the wave properties manifest in the scattering experiment. If electrons did not have wave-like aspects to their behavior, we would not have seen the diffractograms that can be discerned from scattering electrons off of crystalline targets. So that has also taught us how to conduct experiments, both with light and with matter, to reveal the wave aspects of matter's behavior. And Compton scattering offers us a glimpse of how to reveal the particle aspects of the behavior of radiation and matter. All we have to do is get the wavelength of the phenomenon to be much smaller than the size scale of the thing we're shooting it at, and the particle nature should manifest again. These ideas are going to play key roles going forward in everything we're going to do with matter and radiation.
In this lecture, we will learn the following things. We'll take a look at mechanical and electromagnetic wave equations to inspire our thinking about matter waves. We'll learn how to infer the nature of the wave equation for matter from an exercise involving the conservation of energy. We'll look at the meaning of the waves described by the matter wave equation, the so-called Schrödinger wave equation. And finally, we'll look at the limits of absolute knowledge that are imposed by the wave nature of matter. Let's take a peek at waves, beginning with classical mechanics. An introductory physics class would have taught you about oscillatory phenomena. And a wave is just another kind of oscillatory phenomenon that can be described by time and space-dependent functions. So in introductory physics, we learn that a time-varying oscillation along one dimension, for instance, a mass on the end of a spring that's bouncing back and forth on a frictionless surface or up and down in a gravitational field, can be described as simple harmonic in nature, and this allows us to write a mathematical function involving, for instance, the cosine of frequency and time and an offset from the amplitude being maximal at 0. This is a typical equation you might see in introductory physics to describe an oscillatory phenomenon. Now here, omega is a special kind of frequency. It's known as the angular frequency, and it's given in terms of the period of oscillation, which is a more familiar concept. The period of oscillation, often denoted by capital T, is simply the time required for one cycle of the phenomenon to conclude. The angular frequency is 2 pi divided by the period, and this essentially means that it's 2 pi times the frequency of oscillation of the phenomenon. Angular frequency is the rate of angular displacement if we were to model the repetitive behavior as going around a circle, completing one cycle of the circle, 2 pi radians, as completing one cycle of the phenomenon. Now, for all considerations here, let's set the phase angle, the degree by which we would need to offset the cosine function to get the amplitude to match the initial conditions of our oscillator. Let's set that phase angle to 0. Let's set phi to 0 to simplify this equation. If you then extend the phenomenon to 2 dimensions and imagine a long string, for instance, made from a bunch of tiny little masses, each tiny little mass bound to its neighbor as if by a little spring, and we pluck the string, that is, we displace part of the string vertically, then let it go, and it bounces up and down, the vibration of a string. Now we have a distortion in y that's traveling along x in time. And the solution to that problem looks something like this, that the displacement in y at any position x and at time t is given by some initial y times the cosine of a spatial part, k times x, I'll come back to k in a moment, minus a temporal part, omega t.
which we're already familiar with from the equation up here on a simple one-dimensional oscillatory phenomenon. Now, what is k? Well, k in this context is known as the wave number, and it's defined by 2 pi, the number of radians in a circle, divided by the wavelength of the phenomenon. So you can think of this as describing the number of cycles per unit distance in the phenomenon, whereas the angular frequency is the number of cycles per unit time. But these functions answer some question, and if they're the answers to a question, what is the question? Well, they are all solutions to a wave equation. That is, an equation that describes how changes in space relate to changes in time. Now, the one-dimensional mechanical wave equation, at least the one that tells you about vertical displacements and how they vary as a function of horizontal position in time, is simply given by the second derivative with respect to time of the vertical amplitude y, and that's equal to the a constant squared times the second derivative with respect to space of the vertical displacement y. And y, of course, is a function of x and t. So if you try applying this wave equation to the solution on the previous slide, you'll see the following. First of all, the left-hand side is the second derivative with respect to time of the vertical displacement y. Plugging in our function for the vertical displacement, we would get this equation now, the second derivative with respect to time of our description of the vertical displacement versus x and time. Taking one of the derivatives of this function results in us having to do the derivative twice, first of the cosine function and then of the argument of the cosine function. Well, the derivative of cosine is going to be the negative sine function, and the derivative of the argument is going to return a negative omega, a negative angular frequency multiplier. And so we'll be left with this, omega times the original amplitude y sub 0 times a sine function of the original argument. We have to take the time derivative of this one more time. If we do that, we wind up with an additional factor of negative omega out in front of the original cosine function. And so at the end of this, we wind up with an equation that's just negative omega squared times the original function y of x and t. Now let's handle the right-hand side of the wave equation. This is a constant term squared times the second derivative with respect to x position of the displacement y. We plug in our function for y again. Now, taking the first of the two spatial derivatives that we have here, we wind up with a function that looks like this. So the first derivative of cosine returns negative sine, and the derivative of the argument multiplied by that gives us a factor of k, and so we wind up with this. And we have to take the spatial derivative of this one more time. And at the end of this, we wind up with an equation that's negative the constant squared times the wave number squared times the original function y of x and t. Now, setting these two things equal to each other, as would be required by the wave equation, we find out that the function y of x and t drops out of both sides of the equation, leaving us with this simple relationship between the angular frequency squared, the constant squared, and the wave number squared. And if we take the square root of all of this, we see that we have c equals omega over k, and this is one of the velocities that's present in mechanical waves. The speed of the mechanical wave is given by the ratio of the angular frequency and the wave number. Now, this is a very quick tour of a solution to the wave equation and how you can see that it does solve the wave equation, and how when you plug it in, it returns a relationship between frequency squared, speed squared, and wave number, which is related to wavelength squared. A dedicated waves course would spend a lot more time on this, motivating the derivation of the wave equation itself from a simple model of a vibrating string or something like that, motivating how one sets up and solves that equation, and then showing you what relationships emerge from solutions under different conditions. Here, I am merely trying to motivate some thought process about wave equations and the resulting relationships that can be derived from the application of those wave equations to their solutions. So, sticking with mechanical waves for a moment, let's think a little bit about the energy that's contained in that wave. So again, our model here is a mechanical distortion of a physical medium. And that medium that I have in mind here might be a string made from many little bits of mass all hooked together as if by little springs, each with a spring constant and so forth. So if we model a string that way, we can think about the string as having a total mass, capital M, and a total length, capital L. And the little bits of mass it's made from are all equal in size and uniformly distributed along the length L. And so this string has a uniform linear mass density given by the Greek letter mu, which is mass divided by length, big M, divided by big L. No matter what chunk of the string we look at, every chunk will have the same mu because it's a uniform distribution of mass, and so we can always relate mu to the mass in that chunk and the length of that chunk. If we then vibrate the string such that a given part of it at some time t and location x will have a small mass m, and that mass will have a vertical velocity vy, that velocity will oscillate transverse to its length, just as the displacement oscillates transverse to its length. That tiny little chunk of the string will have a length dx, a differential of x, and a little mass m that can be related to the length dx by the linear mass density. So the little m divided by the little dx would be mu, because it's a uniform distribution of mass. So that means that m is equal to mu dx. And every place we see m, we can replace it with this product, and vice versa. The kinetic energy of that little chunk in a moment of its motion as the string vibrates will be defined by its mass and its velocity at a given moment in time t. So taking the classical definition of kinetic energy, we're thinking about a mechanical wave here, so let's think classically for a second. We have the little bit of kinetic energy possessed of by that little bit of mass is going to be 1/2 times its mass, which is mu dx, times its transverse velocity squared, vy squared. Well, vy is just the derivative of the displacement in the y direction with respect to time, dy dt, and we're going to square that. So we wind up, if you plug in that derivative and do that as we did on the previous page, we wind up with this equation for the little bit of kinetic energy possessed of by that little bit of mass that makes up the string. So this is the term for the little bit of kinetic energy possessed of by that little chunk of mass. Now, because it's hooked to its neighbors by springy things, each mass is linked to the next by, you could imagine, a little spring with a spring constant, the potential energy stored in that same chunk of mass will depend on the elasticity of the string, that is, the stiffness of the little springs that you could imagine hold one chunk of mass to the next. So thinking of the string this way, as concocted of a whole bunch of little masses m connected to their neighbors by little springs with spring constants kappa, then as in introductory mechanics for oscillatory phenomena, masses on a spring, you can relate the angular frequency squared to the ratio of the spring constant and the mass. That is to say, the spring constant is related to the mass times the angular frequency squared for an oscillating mass on the end of a spring with spring constant kappa. So the little bit of potential energy that's stored at that location at x in that little mass m is just 1/2 times the spring constant times the displacement from equilibrium squared. Well, that's just going to be a little chunk of potential energy held by that little bit of mass, 1/2 times kappa times the displacement squared. We go ahead and substitute for kappa with m omega squared, and we can substitute for m with mu dx. And then finally we can put in our equation for the displacement, and that now involves the cosine, and that whole thing is squared. So we have kinetic energy, we have potential energy. Let's look at the total energy possessed of by this little bit of mass m. So that little bit of mass m will have total energy dE, composed of kinetic and potential added together at any moment in time. We have the expressions for those two things, dk and du. And you'll notice that if you pull out all the multiplicative factors, you'll be left with the same coefficients multiplying a sine term squared and the same coefficients multiplying a cosine term squared. So you wind up being able to pull all those multiplicative factors, 1/2 and y naught and omega squared and mu and dx, out in front of a sum of a sine squared and a cosine squared. And there's a trigonometric identity that comes into play. Sine squared plus cosine squared is 1. And so the sine and cosine functions vanish from the total energy of this little chunk, and all that defines its little bit of energy that it possesses at any moment in time is that the total energy of that little chunk is constant. It may be divided differently between kinetic and potential, but the total energy of that chunk of mass that makes up that string that's vibrating is constant, and it's given by this number here. And again, it depends on angular frequency, linear mass density, the length of the element, the initial displacement of any element of the string, and so forth. This is just the energy stored in this little piece of mass m at a location x in space and t in time. Now note that the total energy depends on the square of the angular frequency. The presence of the omega squared multiplier tells us something about the number of time derivatives, or the product of the number of time derivatives, that had been present in the original equation for total energy. Remember, we had to square the time derivative of the wave function that solves this mechanical wave equation, and that yielded an omega squared term in all of this. So you can see that there are shades of the number of derivatives left over as sort of vestigial elements of the energy equation for this little bit of mass m. So here are the key takeaways from this look at mechanical waves. The mechanical wave equation relates the second derivative with respect to space and the second derivative with respect to time. You would derive its form in a dedicated class on waves, but we don't have time for that here. Nonetheless, I want you to take away the big lessons from this. Now, the solutions to the wave equation, when acted upon by the derivatives in the wave equation, yield squares of the angular frequency omega and the wave number k. Recall we had an equation relating omega squared, k squared, and the speed of the wave squared. The energy equation for the wave, or a part of the wave, is sensitive to the number of time or space derivatives in the underlying equation, and these manifest as multipliers like omega squared. And one might think about the presence of the squares of these quantities, like omega or k, as indicative of the underlying wave equation that you needed to have solved in order to get these solutions in the first place. Now let's take a quick look at waves and electromagnetism. This is the next classical wave equation that was discovered in the history of physics, and it's derived from Maxwell's equations for electric and magnetic fields. So the wave equation that results describes the propagation of oscillating electric and magnetic fields in empty space, for instance, although it's not limited to only empty space, and that wave equation can be written as follows: that the speed of light in empty space squared times a spatial derivative squared minus a time derivative squared, all of this acting on an electric field vector, is equal to 0. Well, again, notice that like the mechanical wave equation, we've got second derivatives in space and second derivatives in time, all acting on a solution, E vector, whose form we don't necessarily know beforehand. But if we solve the equation, we find out that the solutions to the oscillating electric field components look very similar to the mechanical waves, in that they have a vector amplitude instead of a scalar amplitude, a cosine function, a spatial piece, and a temporal piece of the argument of the cosine function. Now, I should note that yes, there is an identical equation for magnetic fields that can be derived from Maxwell's equations, but you can think of it as a bit redundant. It describes the action of the oscillating magnetic field, but can be related through the mathematics of the solution to the electric field. And so if you can remember the electric field wave equation, which I'm not asking you to do, but will come in handy in a dedicated course on electromagnetism later, you can very quickly work out what the form of the magnetic field wave equation is and relate the electric field to the magnetic field. Although they are in independent directions of one another, the field strengths are not independent of each other. This is an interesting problem in that electromagnetic waves are two-component waves. They have an oscillating electric component and an oscillating magnetic component. They have two kinds of information that are stored in the wave, and this is a theme that we'll return to later when we look at matter waves. Now, applying the wave equation written here to the solution written here similarly yields quadratic multipliers of k squared and omega squared. So for instance, we find that the speed of light squared will be equal to the angular frequency squared divided by the wave number squared. And this latter relationship turns out to be a direct consequence of the massless nature of light that we learn from Planck's relationship for energy and momentum and wavelength and so forth, and the special relativistic relationship between energy and momentum for massless particles. This allows its speed to be related directly to its frequency and wavelength with no other multiplicative or additive factors involved. So let's revisit that. The relationship between frequency and wavelength for a wave can be directly related to the energy present in the radiation quantum, the photon. The photon is the particle-like aspect of light's behavior, and the electromagnetic wave is the full wave description of light's behavior. So for example, from above, and from our previous look at electromagnetic waves, we know that the speed of light can be related to the wavelength and the frequency of light as follows. Wavelength lambda times frequency f. Now, to get angular quantities shoehorned into this equation, like omega and k, what we can do is we can multiply lambda f by a clever number 1. So I'm going to multiply by 2 pi divided by 2 pi. If I group the 2 pi in the numerator with f, I get omega, the angular frequency, 2 pi f. If I group the 2 pi in the denominator with lambda, I get k. K is just 2 pi over lambda. So I wind up with the equation that the speed of light is omega divided by k, the angular frequency divided by the wave number. Now, recalling that Planck's relationship for the energy and frequency of light related by Planck's constant is E equals hf, we can play that same game and shoehorn angular quantities in here by multiplying hf by a clever number 1, 2 pi, divided by 2 pi. Grouping the 2 pi in the numerator with f, the frequency in the numerator, and taking h and dividing it by the remaining 2 pi in the denominator, we wind up with this compact equation for the energy as related to the angular frequency. H bar is to denote h over 2 pi, and it is known as the reduced Planck's constant. Remember that Planck's constant has a value of 6.626 times 10 to the minus 34. So all you do is take that, divide by 2 pi. 2 pi is approximately 6, and so you wind up with a number that's about 1 times 10 to the minus 34. It's very convenient for all of these angular wave concepts to carry h bar around rather than h and 2 pi. So it's very nice to define this reduced Planck's constant notationally as an h with a line through the vertical part of the h. Now, the momentum of the quantum is given by p equals h over lambda. And again, if you insert a clever 1 in that, you'll find that this is equal to h bar times k, the wave number. What's nice about this is it kind of puts E and P for an electromagnetic wave on equal footing. E is h bar omega, P is h bar k. These are a little easier to remember than the h over lambda and h times f thing. At least I find them more convenient once you feel more comfortable with angular frequency and wave number as angular concepts of oscillatory motion. Recalling that the speed of light for our electromagnetic waves is given by omega over k, that is the angular frequency divided by the wave number, if we substitute in for those two quantities with their energy and momentum expressions, we recover the special relativistic relationship for light as a massless phenomenon. E equals p times the speed of light. So we've exactly recovered the Einstein energy relation for light, a massless phenomenon. So let's take an overview of the wave equations in classical mechanics and electromagnetism. They involve second derivatives of both space and time. So you see both d squared dx squared and d squared dt squared in these wave equations. Now we could have inferred that from the results of the wave equations, as their application results in squares of time and spatial frequencies. So for instance, omega squareds and k squareds appear in equations that result from the application of the wave equations. The energy equations tell us the proportionality of frequency to wavelength, as well as other useful information like that. And all of this kind of leaves you wondering, if we have a mechanical wave equation and an electromagnetic wave equation, where's the matter wave equation? Where's the evidence for that from the history of science up to the early 1900s? That's the problem, since its presence could not be inferred directly from previous measurements in the same way that Maxwell's equations were inferred from Coulomb's law, Gauss's law, and other things like that, Ampere's law, and ultimately, when composed together in the form of Maxwell's equations, led to the wave equation for light. And in the same sense that considering a string as a bunch of masses bound by springs that are tugged up and down and then caused to vibrate by being stretched will lead you to the wave equation, where's the exercise that leads to the wave equation for matter? And that didn't really exist up through the 1920s, the early 1920s. So the question I would put to you is it possible, given other equations, that we could infer from what we know its form? So if we know things about particles and waves, like wavelength and frequency and energy and momentum, and we know the relationships between those things, can we figure out the wave equation using all the information we have from atomic spectra, the blackbody radiation spectrum, the photoelectric effect, Compton scattering, and all that other stuff? Can we figure that out? So one can glimpse the hints of the underlying but unseen matter-wave equation, sort of like seeing a shadow cast on a wall by a complex object that's out of your line of sight, but whose shadow is projected onto a wall, giving you hints about the real shape of the thing you can't see. And we can get that glimpse of the shadow of the matter wave equation by considering the conservation of energy for a particle that's acted upon by an external force. Now, such a particle, in classical physics, would have, of course, a kinetic and a potential energy with specific forms depending on the force involved in the problem. Now, conservation of energy would require, no matter what, that the total energy of that particle is going to be the sum of its kinetic and potential pieces. Now, sticking to classical physics for a moment, because employing special relativity to derive the rules of matter waves involves a whole skill set of mathematics that really can't be expected of you at this stage of a university career, we're going to stick with purely classical low-velocity matter. Even small matter, like electrons, we're going to have to consider moving at relatively low velocities, not very close to the speed of light. Now, obviously that doesn't cover the full domain of phenomena of small particles like that, but it'll get us going and it will allow us to solve a great number of problems that are actually within our grasp once we figure out the matter-wave equation. So, using classical physics, we can write the kinetic energy as 1/2 mv squared, and we're going to leave the potential energy unspecified. I'm not going to worry about what the force is that's acting on this. Let's just say it has a potential energy u for now and leave it at that. Now, we have relationships for matter waves between total energy and frequency and total momentum and wavelength. But we don't have momentum in this equation. So let's get momentum into this equation. And the way we do that is we multiply yet again by a clever number 1. So if we insert a number 1 in the kinetic energy equation, that is just m divided by m, then we get an m squared v squared in the numerator. And mv is just momentum. So we wind up with momentum, classical momentum, squared in the numerator, divided by twice the mass of the particle, plus its potential energy u. So we have our kinetic term, now expressed in terms of momentum, and we still have our potential energy term, and they're summed together to get the total energy E. So let us now inject de Broglie's postulates into this equation. That is, E equals hf, which is equal to h bar omega, and P equals h over lambda, which is just equal to h bar k, again employing all these nice angular quantities. And if we do this, we now obtain the shadow cast on the wall by the matter-wave equation. And that is h bar omega equals h bar squared k squared over 2m plus u. You see it? The single power of omega on the left side indicates to us that a shadow is cast here by a single time derivative that's acted on some solution to the underlying wave equation. We don't see the solution and we don't see the wave equation, but we see the result of applying those two things, and that is a single power of omega on the left side. The k squared on the right-hand side implies that there's a second derivative with respect to space in the wave equation acting on the solutions to that equation, whatever they may be. So we have a single time derivative and a second space derivative that result in k squared and omega. So let's go ahead and take that equation with our hypotheses, our hunches, about what the underlying wave equation's form might look like, and let's try inserting those hunches into this equation above, assuming that an appropriate derivative has acted on an unknown solution to yield a single omega, or a k squared. So if we do that, if we take our hypothesis about the number of derivatives acting on some unknown function that solves the wave equation, yielding this relationship, we wind up with the following equation. On the left, h bar times the first time derivative of an unknown solution, which I'm denoting with the Greek letter psi, and it's a function of space and time. We're only considering motion in one dimension right now. On the right-hand side, we have h bar squared over 2m times the second derivative with respect to space of that same function, psi of x and t. And of course, we have the potential energy of the matter wave still tacked on to the right-hand side over here, and I'll return to that a little bit more later. So this looks promising. It has all the hallmarks of a wave equation, but it's different from Maxwell's equations or a mechanical wave equation in one key way. It has a second derivative in space, but only a single or first derivative in time. This will have implications for the kinds of functions that can solve such equations. And the solutions to this, as I've said, are denoted by the capital Greek letter psi as a function of x and t in one dimension. So let's explore solutions to this equation. And as we do this, we'll find that we are missing at least one key piece of the underlying equation. We've guessed at the form of the object casting the shadow on the wall, and we may have guessed incorrectly. So let's begin by guessing the form of the solutions to our equation, and then plug them in and see if we recover our energy conservation statement. So to simplify matters, let's consider for now free particles, that is, particles free from external forces, and that is most simply expressed by setting u to 0. The particle has no potential energy associated with it. We're only considering motion at a constant velocity, so that's a fixed kinetic energy, which then relates to the total energy of the particle. Okay, well, to solve our wave equation, we need a kind of function that, when acted on by a derivative, transmutes into another version of itself. So for instance, in the old wave equations, the mechanical wave equation, the electromagnetic wave equation, we had second derivatives acting on the solutions. Sines and cosines were great for that because after two derivatives, they return to their original selves. So that's what we did for traditional waves. We used sines and cosines. So let's take a guess. Let's guess that psi of x and t is just one of our mechanical wave solutions, a cosine of kx minus omega t. So we're not doing anything original here, we're just taking mechanical waves, getting inspired by them, and blindly applying that idea here. So let's write down our wave equation that we've guessed. H bar times the first derivative of our solution with respect to time. H bar squared over 2m times the second space derivative of our solution. Let's go ahead and plug our guess at the solution in. Alright, so we plugged our function in on both sides now, and then go ahead and work out the derivatives, and you should find the following conclusion. That we wind up with a positive sine function on the left, now multiplied by omega. We get a minus sign from the derivative of the cosine, but we also get a minus sign from the derivative of its argument with respect to time. So this winds up being net positive on the left side. But over here, the two derivatives of the cosine yield an overall minus sign. So we have a positive sine function and a negative cosine function. We can't cancel out the sines and cosines on either side. It doesn't recover our original energy conservation expression. It doesn't work to solve the equation. The left side and right sides don't give us what we would have expected based on where we had derived this from, which was the conservation of energy. And if you try just a sine function, it will similarly fail. So what if instead we combine sine and cosine functions? What if we add together sines and cosines? Because when you take the first derivative of something that's a sine plus a cosine, you'll wind up with a sine and a cosine in the result. And similarly with the second derivative. Maybe a superposition, an addition of sine and cosine, will do the trick. Alright, let's go ahead and try that. Now I'm trying the barest, simplest superposition. I'm assuming that they have the same multiplicative coefficient out in front, a, whatever that is. And otherwise, it's a cosine of the same argument and a sine of the same argument all added together. When you're playing around with solving equations whose solutions are not known to you a priori, that is, with prior knowledge beforehand, Guesses like this will get you through the process, and you should always try to start with the simplest guess and work your way up in complexity. So for instance, it may be these coefficients aren't supposed to be the same, but don't start by assuming that. Try assuming them and then work your way up to a more general set of solutions as you get more comfortable with solving the problem. So we write down our guess at the wave equation again, we plug in our new choice of the solution, we work through the derivatives, and we'll get the following equations. Now, what I want to do is I want to reshuffle the term order on the left side. I want to get the cosine first and then the sine second, so I'm just going to move these terms around without changing anything about the equation. And this is the final form of the equation I get. I get a negative cosine and a positive sine, and I get a negative cosine and a negative sine over here. I can't cancel these functions out. I can't recover the energy conservation expression we started from. It's a lot closer than we were with just cosine, but it's still no good. We've got problems with the plus and minus signs and all of this. It's a mess. And what's the real problem we keep running into here? Well, we keep generating stray minus signs from the single derivative of only the cosine on the left side. The derivative of the sine gives us something positive, but the derivative of the cosine gives us negative sine function. And that's what's really hurting us here. Our goal at this point is, if we're going to figure this out, we've got to find a way to get rid of this minus sign we keep picking up. And at this point, it helps to remember that there are other kinds of numbers than real numbers in the world. So everything I have done up till now is predicated on the assumption that these solutions, and perhaps even the wave equation itself, can only be composed from real valued numbers. You know, like 1.1 or 2.3 or pi or negative 75.6. Those are all numbers that can manifest in the real world. If somebody says, look, I'm going to give you negative $76, it means that they're going to take $76 away from you, right? That has real consequences. Negative numbers are real things in the world around us. But there are other kinds of numbers that don't have physical meaning in the world around us. And it's important to remember that. And they fall under at least one class of these numbers, is a category known as imaginary numbers. And in particular, it's helpful at this point to remember some of the behavior set of the archetypal imaginary number I, which effectively serves the role of being the number 1 in the imaginary number set. So let's pause for a moment and revisit imaginary numbers, which presumably you have seen in some context prior to this course. Let's recall that the imaginary number I is a special kind of number 1, but with no physical interpretation. So I is defined by the question, what squared equals negative 1? And the answer to that is I. And I's value would be the square root of negative 1, which is nonsensical. If somebody told you, give me $, you would not know what to do with that because you don't know how to calculate the square root of a negative number and then turn that into a real dollar value that you then hand that person. Now, this number can exist in a mathematical universe where it has plenty of self-consistent rules that don't violate any of the axioms of mathematics that you're playing with. And in fact, I doesn't violate any axioms of mathematics at all. So it's perfectly mathematically tenable, even if it's not physically realizable around us in the world. Its existence mathematically has consequences, though. So, for example, going back to the question that leads to I, you can take I and multiply it by itself. That's just I squared. If we plug in for I squared, we have the square root of negative 1 times the square root of negative 1, and by definition, that has to yield negative 1. And so I squared equals negative 1. I is the answer to that question. The square of what number gives me negative 1. But you'll notice that I squared has the ability to add a stray minus sign where none would have been present before. And I is the number 1 in the imaginary number world. It is the unit on which you can build all other numbers, integers for instance, in imaginary space. So the presence of extraneous minus signs when trying to solve equations using functions, as we've been doing with our guess at the matter-wave equation, could actually be an indicator of something. That we are trying to use real valued numbers and solutions only. But maybe the problem we're trying to solve is too complicated to only admit real numbers, that it requires the ability to store additional information that real numbers alone cannot accommodate. Those can be accommodated by complex numbers. These are numbers that contain both real and imaginary components. So for instance, the complex number z is made from two real numbers, x and y, but y is multiplied by the number I. And so iy is imaginary, x is real. This is a combination of a real and an imaginary part. This is what is known as a complex number. And it stores twice as much information as a single real number because it's got this extra component over here. And if this is reminding you a lot of vectors, like a vector z being equal to a component along the x-axis x and the y component y, that's good because a lot of the basic ideas of vectors translate into complex numbers and give us some confidence about how we can get useful information out of complex numbers. So let's explore complex solutions to this equation. So let's start by trying a guess at a complex solution. It's got a real valued part, a cosine, and it's got an imaginary part, ai sine. So all I've done is I've added the number I to the sine part of my solution. So again, here's my guess at the wave equation. I plug in my solution. I take my derivatives and I get the following results. Now again, I've got sine and cosine out of order on the left side. So if I shuffle them around to get cosine first and sine second and try to map that onto the right, I see that I still have a problem. I've got negative I cosine and negative cosine here. I've got a sine and I've got negative a I sine over here. I can't just naively cancel these things out. That doesn't really work. So I have a problem. I still can't get this to work out. If I were to try to move an I or a negative I from the left side to the right side, I'd still wind up with a stray I where I don't want one. And that isn't going to work for this problem. So it's ridiculously close to working out. We're so temptingly close to solving this problem right now, but something is still missing. Some salt is missing from our soup here that we used to try to mimic the recipe for the matter wave equation. So let's see if we can get one more opportunity to think about our assumptions by moving some minus signs around to see if we can find a clue that will resolve this little puzzle. So I'm starting with the last equation from the previous slide here. I haven't done anything to it yet, but what I'm going to do is I'm going to pull the minus signs on the right-hand side out as an overall multiplier, and then multiply both sides by -1. So I'm basically moving the minus sign here to the left side of the equation. So this is the net effect of doing it. Notice all the terms over here on the right are now positive. The minus sign that would have been on the right is now moved to the left and overall multiplies these terms. And if I go ahead and do that, if I multiply it through, I see that I now have I cosine here and negative sine here, and I have cosine here and I sine here. And that has a kind of weird rhythm to it. And that's the clue. The difference between the function on the left-hand side and the function on the right-hand side boils down simply to a missing factor of negative I on the left. If we had originally guessed that the wave equation was negative I h bar times a time derivative of the wave function, all of this would work out. We would actually get the left-hand side being equal to the right-hand side. So if we had just done this at the beginning, if we traded our original guess at the left-hand side of the wave equation, which was all predicated on our bias for real numbers, h bar times the first time derivative, if we traded that for negative I h bar times the first time derivative, then we'd solve our problem. And let me show you that. So to wit, let's revisit our guess at the form of the wave equation. I'm leaving the solution completely intact. That's still the same as what I had a moment ago. And what I've done is I've changed the left-hand side of our guess at the wave equation to be negative I h bar times the first time derivative of psi. I've done nothing to the right-hand side. Plug in the solutions, do the derivatives, play the game again where we shuffle the terms on the left-hand side to get cosine first and sine second, move the minus sign on the right over to the left, okay, and distribute that into these terms. Now multiply the negative I into the function. The negative I multiplied by this I gives me negative times negative 1, which is 1, positive cosine. The negative I multiplied by the sine function cancels out the minus sign here and leaves me with positive I times sine. Cosine, I sine. Cosine, I sine. The left and the right sides level out, and the function is now the same on both sides and can be canceled out mutually on both sides of the equation. So, bazinga, as a famous TV character might say at a moment of revelation. We've done it. We've cracked the underlying form of the matter-wave equation. Let's prove that by seeing if it returns to us the energy conservation relation that we started from. We've only shown here that we have a wave equation that, when acting on our guess at the solution to a free particle wave, returns the solution with a bunch of multiplying coefficients, and so we can cancel a function out of both sides. But we don't know that we've recovered the conservation of energy equation we started from. So let's see if this all works out. Let's review what we did. Starting from the total energy of a free particle, which is h bar omega equals h bar squared k squared over 2m, we constructed a wave equation that had the right time and space derivatives in it to return these factors of omega and k squared. We played with oscillatory solutions, and we learned that only complex functions will satisfy an equation like this. And from this, we inferred a missing imaginary number from our original guess at the equation. We should have had a negative I lurking on the guess of the left side of our equation the whole time in order for this thing to have viable solutions for the free particle that work out. The solution guesses that we made for free particles are of this form. They're complex. They have a real part and an imaginary part. And plugging them into the wave equation yields this relationship. H bar omega equals h bar squared k squared over 2m, which was precisely the energy conservation equation for a free particle that we began with. So it's entirely a self-consistent exercise. And that should be deeply mathematically satisfying, even if you're not completely comfortable with the process by which we arrived at that. But I promise you that this is not the first time, assuming this is the first time you've ever seen this kind of strategy done for solving an unknown equation with unknown solutions. This is not the first time you'll bust out this trick in your life if you ever have to solve hard problems. So this trick is actually useful, even if it feels a little clunky at first. And I hope it conveys to you the sort of incredible exercise that must have been required originally to derive this wave equation in the 1920s. We're doing this with the benefit of a century of hindsight, but our predecessors did not have the benefit of this much hindsight. So while I am able to look at resources and come up with ways of explaining the wave equation's form to you at this level of a physics course, the people that were involved in trying to write down the matter-wave equation in the 1920s did not have the benefit of this much hindsight, and so they were struggling with immense difficulty in a different mathematical landscape than we are in now. So, putting back the potential energy piece of this is the full, one-dimensional, what is known as Schrödinger wave equation. We have another function that we can tack on to the right-hand side here, v of x and t, which is known as the potential term. That function acting on the wave function, psi, would return the potential energy of the matter wave, in this case, u. And this is one of the most important equations in history, where I've added back the potential energy term to complete the equation for a particle in one dimension. The one-dimensional Schrödinger wave equation is one of the most revolutionary insights into the universe in the history of our species, named after Erwin Schrödinger, the first person in 1926 to fully determine the form of the matter-wave equation. Now, he was doing this using a whole different set of mathematical, algebraic, and calculus constraints. This is not how he derived this equation, but this is sufficient at this level to motivate where an equation like this might come from. He was using mathematical guidelines to infer the nature of the equation that we simply don't have the mathematical foundation for at this stage of a physics course to do. Now, you might look at this equation and think, well, this is horrible. I hate time derivatives, I hate space derivatives, and there's two space derivatives and one time derivatives, and these functions are awful, and there's imaginary numbers, and blah. Okay, that might seem daunting to you, and perhaps it is. But there's actually a much more difficult part to this equation, and that is that the hard part of the Schrodinger wave equation is the solving of the equation to specific situations. The real challenge of this equation is not this equation itself, although it doesn't look very pleasant, I know, but rather in the finding of solutions, the size of x and t, to this equation given different potentials, v, and so forth. Now, we've effectively solved the free particle case, and we'll explore the solutions to that for the rest of this lecture. But if a potential energy term is present, so in other words, if there are forces in a problem and you can't ignore them and you have to include them, and those result in potential energy or changes in potential energy for a particle in a problem, you have to completely rework this equation and find the correct solutions that satisfy the equation with the correct potential term added on. And that is much more difficult, and that is effectively what we'll spend the rest of this course learning how to do for different situations that map onto the physical world. Now, I should say that solving this equation for different situations is what has allowed us to understand semiconductors. It is part of what allowed the revolution in microelectronics to happen in the first place. Solving this equation for atomic system leads to an understanding of where chemistry comes from, and specifically, doing this on a grand scale is the heart of physical chemistry. Solving this equation for information systems is what results in quantum computing and quantum information, which is a hot subject these days and is one of the many technological frontiers of our species. I cannot understate how important the Schrodinger wave equation is for all the foundations of the world we live in today, but also all the potential for the great discoveries of tomorrow. In this lecture, we will learn the following things. We'll learn about a classical model of the atom, synthesizing 2 semesters of introductory physics with some of the concepts that we've been exploring in this course. We'll learn about how to impose specifically the matter-wave hypothesis on the atom and see if we can make some useful predictions about atoms using this structure, the so-called Bohr model of the atom. Let's briefly revisit the key observational features of the hydrogen atom at a macroscopic level. Atoms in general, when excited by an ionizing electric potential, emit not a continuous rainbow of colors, but rather a discrete set of colors, the so-called atomic emission spectrum. Shown here is the atomic emission spectrum for the hydrogen atom. It has a characteristically bright red line, which can be seen in the image over here on the right. It's got a blue-green or cyan line, which can also be clearly seen in the image over here on the right. It's got a darker blue line and a violet line, and those are a little bit harder to see. You can more easily see the dark blue and the violet line in this part of the image on the right. Now, while the atomic emission spectrum can be readily revealed by ionizing a gas in a sealed tube and then passing the light through a system that will spread it out, revealing the rainbow of colors that makes up any kind of light, the mystery of the atomic spectrum goes deep. Each atom has a characteristic spectrum. It's unique to each atom that we know of in nature. Hydrogen is different from helium. Helium is different from lithium. Each of them has this pattern that's their own. We do not understand the origin of this using classical notions of energy and momentum and matter, but at last we are ready to confront this last mystery left over from the 1800s using not only what was developed in the first 2 semesters of physics, but what we've been learning in this course. Now, let's be more numerical about the hydrogen emission spectrum. We have a red line, a blue-green or cyan line, a dark blue line, and a violet line. These have associated wavelengths for the photons that carry each of these colors of light to our eye. The red line, for instance, has a wavelength of 656 nanometers. The cyan or blue-green line has a wavelength of 486 nanometers. The dark blue line has a wavelength of 434 nanometers, and the violet line has a wavelength of 410 nanometers. For something we'll do later in this lecture, it's worth noting these numbers down on a piece of paper. Go ahead and pause the video, write these 4 numbers down, noting the colors that go with each of them, and let's save that information for a little bit later. Now, it was Johann Balmer who worked out the mathematical relationship between these lines in 1885. These are the lines of light from the atomic emission spectrum of hydrogen that are visible to the unaided human eye. There are, of course, ultraviolet and infrared radiations from ionized hydrogen. We won't talk about those here, but they're represented in other spectra. The Balmer spectrum is the one that spans the range of light wavelengths that are visible to the human eye. Now, Balmer noted that the wavelength of each of these lines is given by a simple formula, a constant b times this ratio, an integer n squared, divided by that same integer n squared minus 2 squared, or 4. Plugging in n equals 3, 4, 5, 6, etc., Balmer was able to show that there is a clear mathematical relationship between these colored lines here. The constant b was determined to be 364.5 nanometers. And all one has to do to calculate the Balmer spectrum is know this number and this formula, and use the integers greater than 2, and you can reproduce the wavelengths present in this picture. But why? Why is there a clear mathematical relationship between these colored lines emitted from hydrogen? And why are there similar mathematical relationships between the colored lines emitted from other atoms when ionized? These are deep questions, mysteries left over from the 1800s that physics in its day could not explain. Now let's recall the earlier models of the atom that we explored in a previous lecture. Joseph John, or J.J. Thomson, after discovering that cathode rays were really just electrons and had masses that were far smaller than the lightest known element at the time, hydrogen, constructed his Thomson model of the atom, imagining that the electrons with their negative electric charges were embedded in a larger swath of positive charge spread out in space. And if one were to fire particles through such atoms, they would mostly miss the electrons, which are very tiny, and pass almost cleanly and undeflected through this diffuse positive electric charge. Ernest Rutherford and his colleagues, however, revealed by scattering alpha particles off of thin metal foils that in fact sometimes the alpha particles would bounce almost directly back at the apparatus that had fired them at the metal in the first place. And this implied that there was some kind of densely packed small core of positive charge at the heart of each atom, surrounded by orbiting electrons, as if planets going around a sun. This model helped explain why, while many of the alpha particles would pass through the thin foil relatively undeflected, occasionally one of them would suffer a collision with this densely packed, positively charged nucleus of the atom, and suffer an immensely disruptive collision, some of which could send the alpha particles coming almost straight back at the source from which they had been emitted. Now, all of this was happening in the very late 1800s with Thomson's work and the very early 1900s with Rutherford's work. And as you'll see, as we learned more about the atom, as people thought more deeply about the implication of Max Planck's adoption of the quantization of energy to explain the blackbody problem, and Albert Einstein's adoption of that same notion to explain the photoelectric effect, models of the atom changed rapidly in response to these ideas. And this then led to the ability to conduct calculations, making new predictions about the behavior of atoms, but also new tests of how atoms should behave themselves. This was a dynamic period in physics, transitioning from the classical era of the previous 3 centuries into now the modern era that we would still be living in the after effects of today. Now, let's consider the Rutherford atom, but let's simplify the calculations and only think about an electron going around a single proton, so a hydrogen-like atom, but only in 2 dimensions. The electron is bound to the proton in a circular orbit by the Coulomb force, in the same way that the Earth would be bound to the Sun by the gravitational force in our solar system. So the electron would be orbiting the proton. The proton would be the central force emitter in this problem. The electron would be responding to that force, the electric force, the Coulomb force in this case. So that force would be given here by this formula. The Coulomb force exerted on the electron by the proton would be given by a constant, 1 over 4 pi times epsilon naught, and I'll come back to that in a bit. But basically, this is the permittivity of free space, epsilon naught. It has something to do with how electric fields can propagate through empty space. The product of the charges of the electron, which is negative, the fundamental electric charge, and the proton, which is positive, the fundamental electric charge, and that divided by the distance squared between the electron and the proton. Now this r would be the orbital radius of this circular orbit. Now I want to note here that this unit vector r hat carries all the directional information of this force. Now by convention, r hat points from the source of the force, the proton, to the recipient of the force, the electron. It is the sign of the electron's negative electric charge that ultimately flips the direction of that vector and has the force pointing back toward the proton, that is, making it an attractive force. Now, according to Newton's second law, digging back to our first semester introductory physics, the sum of all forces on the electron will be simply summarized by its mass times its net acceleration. Well, what acceleration is this electron experiencing as it orbits the proton? The answer is a centripetal acceleration. This ultimately is a center-seeking force, which results in a center-seeking acceleration, changing constantly the direction of the electron's velocity vector. So that means that the acceleration, the net acceleration of this electron, has a well-defined form. It's given by v squared over r in magnitude, and its direction, center-seeking, will point to the center of the circular motion, which again is in the direction of negative r hat, that is, from the electron to the proton, whereas r hat is defined as being from the proton to the electron. So we have all the pieces we need to build a Rutherford model of the atom in 2 dimensions, using these ideas of a centrally compact, positive charged nucleus and orbiting electrons. So let's go ahead and do that. We can set the sum of the forces, which is just the Coulomb force, equal to the mass times the centripetal acceleration. Now note that there is a negative r hat on the left side, negative r hat on the right side. Negative r hat drops out of this entire equation, and we're left with just this equation. 1 over 4 pi epsilon naught times e squared over r is equal to the mass of the electron times the velocity of the electron all squared. Now I'm leaving it in this funny form because this almost instantly lets us write down the classical kinetic energy of this electron, that is 1/2 mv squared. If I just multiply this equation by 1/2, I immediately get the kinetic energy of this electron going in orbit around the central proton. 1/2 times 1 over 4 pi epsilon naught times e squared over r. Now, I'm going to leave this equation unsimplified. I'm going to leave this 1/2 sitting out in front to ease the next step, and that is computing the total energy of this electron. You can go ahead and multiply this out if you want to, but it's convenient for what's going to happen next to just leave it out that way to remind us that doing math with this thing is going to be relatively straightforward. So let me rewrite the kinetic energy of the electron here at the top of the slide. Now the total energy is the sum of its potential and kinetic energies for that electron at a given orbital radius r. That is to say, the total energy of the electron is just its kinetic energy plus its potential energy. Well, the only force present is the Coulomb force, and so that means it has an electric potential energy. And that electric potential energy for the electron, UE, will be given by its charge, negative E, times the electric potential of the proton, V with a subscript P. Well, the electric potential of the proton is just going to be given by 1 over 4 pi epsilon naught times the charge of the proton divided by the distance between them. So we wind up with this equation for the electric potential energy of the electron, 1 over 4 pi epsilon naught times negative E squared over r. And that allows us to then write the total energy, E, as follows. It's just our kinetic energy plus the potential energy, which is a negative number. And you see why I left the 1/2 here. It was convenient because I have 1/2 times a common multiplicative thing here, and just subtracting off that common multiplicative thing here. And so ultimately, at the end of the day, I get a negative number for the total energy of the electron, and that's okay. It just means that the potential energy of this particular electron outmatches its kinetic energy for this particular orbital radius, r. So this is the final expression that I get for the total classical energy of a 2D Rutherford atom. That is, just considering the electron going around a stationary proton in the center. Let's write that equation down. We're going to pull it up later. We're going to need it again for something that happens later in this lecture. But this is about as far as I'm going to go with this for the time being. Now, how do we get modern concepts like the fact that the electron is actually a wave and not a point-like particle into this thing? Well, we see the problem already with the Rutherford model. It's not going to explain the hydrogen emission spectrum, right? Because in the Rutherford model, any orbital radius r is allowed. You can put any r in there and you'll get an E out. Now, because any total energy is allowed for the electron, this cannot explain the discrete energy spectrum of electrons in a hydrogen atom. We already have a sense that quantization of some sort must be present in the atom, right? This is the atomic emission spectrum. It bears the fingerprints of a constrained system with only specifically allowed energies determined by those constraints. Now, the de Broglie postulates enter to provide the crucial missing thing, the clue, that will help us to understand this whole problem. This is the key step that ultimately leads to quantization. So, for example, we know that the momentum of an electron matter wave is given by Planck's constant divided by the wavelength of that matter wave. We can relate the particle-like properties, momentum, to the wave-like properties, wavelength, using the de Broglie postulates. Now, classically, and because we're doing things at low velocity, we'll revisit this as a consequence of these choices later, but we're going to start off thinking classically. We can write the momentum in terms of its speed. And that's just going to be the mass of the electron times its velocity, or in this case, the magnitude of its velocity at speed, thinking purely classically. So the question we want to answer is every wavelength of the electron possible for our electron? If it is, then every momentum is allowed in the atom. And we're right back where we started again. If every momentum is allowed, every speed is allowed. And if every speed is allowed, every radius is allowed. This has consequences in a system where there are relationships between things like speed and orbital radius, speed and momentum and wavelength. But maybe that's the flaw. Maybe the problem here is that not every wavelength for a matter wave for our electron orbiting this central proton is actually allowed. We had a discussion in class about the Schroedinger wave equation. And in that discussion, I drew the real part of free particle wave functions or other kinds of wave functions up on the board. And I invited you, the class, to discuss whether or not those wave functions made physical sense. I mean, it's possible to write things down mathematically that don't make sense physically. And let's revisit that discussion. I will review the salient points here as I go through some examples. And let's apply that discussion to the electron in orbit around the proton and see what conclusions we might draw. Now, let's start by thinking about a circular orbit. A circular orbit is quite simply one that, after one period, repeats again. And that means if we're thinking about the electron as a wave at a moment in time, sort of frozen in space at a moment in time, remember, it's not only going to be at one place. Its wave function is spread out over space, and the space over which it's spread out is the circumference of its orbit. That's its one dimension that it's traveling along in this problem. So whatever the wave function of this electron is, it had better at least obey the basic mathematical principle that when it gets back to itself at the starting point of its orbital circumference, it starts all over again from exactly where it began. So let's imagine the real part of the electron matter wave, and we're just going to make one up. And it might describe the electron traveling along such a circumference of an orbit of radius r at a specific time 0. So we're going to freeze this wave function, which of course itself is not physical, but we're going to imagine it being frozen in time at a given moment. And it might look something like this. If we pick a 0 point on the orbital circumference, which I've marked here in one dimension, it might be that its wave is at a local maximum. The real part of its wave function might be at a local maximum there. And then as we move along the circumference, the wave function declines and then goes negative, and then it comes back and it goes to 0, declining to 0 again, and then it goes positive. Now, at one circumference, that is at 2 pi r, we see that the function I've chosen here nicely comes back to where it started. This seems to behave itself in the sense that the wave is one continuous wave that repeats nicely in space, because again, we froze in time. It's possible that this wave might be waving in time, but we froze in time, and so in space, this thing had better meet itself when it gets back to its starting point, and I'll explain physically why that needs to be in a moment. So this one seems to be a reasonable candidate wave function for describing our electron in orbit around a central proton. It nicely repeats itself when it reaches 2 pi r, that is the 0 point again on its circumference. Its behavior is very smooth and continuous at the boundary where the orbit then repeats, where that is 2 pi, which cycles back to 0 again on a circle. Now let's take a look at a wave function that's also plausible mathematically, but has some undesirable physical properties. So what about this matter wave for the same electron at the same radius r? We've frozen it in time. It's a perfectly reasonable wave function, right? It's got one wavelength here. It looks wavy. Is this a good physical wave function for describing the electron? Well, if we look at 2 pi r, we see that where the wave function ends up when it gets back to its beginning again is not where it started. Now, that doesn't per se have any mathematical negative consequences. I mean, this is a perfectly allowed function. I can write it down. It has something called a jump discontinuity. When it gets back to its start, it jumps from this value right before 2 pi r back to its starting value at 2 pi r. But this has physical consequences. So because it has this jump discontinuity at 2 pi and does not cycle back to where it started, the jump discontinuity results in a first derivative at that point that is infinite. That is, the derivative of this wave function with respect to space, d dx, at that point, 0 or 2 pi r, has an infinite slope. Now, because the first derivative with respect to space in the Schrödinger wave equation plays the role of the thing that tells you the momentum of the particle, the jump discontinuity means that we have an infinite momentum point in the wave function. And a place of infinite momentum is physically forbidden. It just doesn't make any physical sense. If this were the case, the universe would have ended long ago if things like this were possible, because there would be a particle which would contain more energy than every other particle in the universe, and that would have all kinds of terrible physical consequences. So this kind of wave function is physically forbidden. It may be mathematically allowed, but it violates physical notions of naturalness in the world around us, because the jump discontinuity has a physical consequence, that is, infinite momentum. What about this wave function? What about this matter wave for the same electron again, at the same radius r? Does this look to you like a good wave function? Go ahead and pause the video and stare at it for a moment. If you drew the conclusion that, yeah, it's a pretty good wave function, you're on the right track. I mean, it's got twice the number of wavelengths in 2 pi r that the first one did, but it comes back to where it started at 2 pi r. In fact, it differs exactly by a factor of 2 in wavelength from the first one. And in fact, all waves that satisfy the relationship that their wavelength is an integer multiple of the shortest continuous and complete wave you can write down, the so-called fundamental, if you will. All harmonics of the fundamental wave of this electron will satisfy this condition that there's no infinite momentum point anywhere along the physical space, the circumference where it would occupy in space. And in fact, none in between those integer multiples will work. They'll all have the same problem that the previous example had. There'll be a jump discontinuity when you get to 2 pi r. This results in a place of infinite momentum. It's unphysical. So, whatever the wave function that describes the electron in orbit around the proton, it must satisfy this condition in order to have physical meaning. An integer number, n, times some fundamental wavelength lambda, is going to be equal to 2 pi r. The only lambdas that will work will be those that satisfy this constraint, that is 2 pi r over n equals lambda. Now, if we utilize the de Broglie postulate relating momentum and wavelength, then we wind up with nh over p, substituting in for lambda, equals 2 pi r. And classically, remembering that p is equal to mv, this puts a constraint between the radius and the speed, and the integer multiple in question here. nh over mv equals 2 pi r. Now, you'll notice that I can move the 2 pi over to the left side, and then I'll have h over 2 pi, and that allows us then to substitute with the reduced Planck's constant h bar. Remember that h bar is just h divided by 2 pi. You get this a lot when you start switching to the angular quantities, angular frequency, and wave number and things like that. The h bar is very convenient in those contexts. So let's go ahead and just absorb the 2 pi into the definition of h bar, and we'll arrive at the following equation for the speed of the electron and its relation to the radius of the orbit. That is m times v times r equals nh bar. That can be rewritten to solve for the speed of the electron, ve, which is nh bar over mr. And in preparation for relating this back to energy concepts, I'm going to go ahead and square VE, so I get VE squared, which is just this thing on the right-hand side here. So from the matter wave hypothesis, I have a relationship between V, an integer multiple of the fundamental wavelength, and the radius of the orbit that determined that wavelength in the first place. Now, V and R also appear in things like kinetic energy. So you can already see that we have a new constraint to throw into energy equations that will lead us to perhaps some final understanding of why it is that the atomic spectrum is discretized. Now, before we do that, I want to talk a little bit about Niels Bohr's actual postulate. It's worth noting that the way that Bohr attacked this problem was to postulate that there was a quantization of angular momentum in the atom. That is, the electron was quantized in its orbit around the proton. Now, he did this in 1913, and this was about 11 years prior to de Broglie's work, which was in 1924. So Bohr asserted, having, I guess, seen that quantization worked in other problems to explain things that had previously gone unexplained, he asserted that since h and h bar, the reduced Planck's constant, have units of angular momentum, that is, joules times seconds, it might be in an atom that the angular momentum L is a multiple, an integer multiple of h bar, that those would be the only kinds of angular momenta that would be allowed in an orbital system like a 2D Rutherford atom. So the angular momentum of the electron can only come in multiples of h bar, and for a circular orbit we can relate the constraint and h bar directly to the angular momentum of a particle going in a circle, and that's just p times r, which classically is mvr. And so this leads to the equation mvr equals nh bar from Bohr's assertion. Now, later on, de Broglie would explain the reason why this works, and that's based on what we just saw on the previous slide. That is, if there's a constraint on the structure of the electron wave function, requiring that the radius, the circumference of the orbit be related to integer multiples of a fundamental wavelength of the electron, then if you go back to the previous slides, or go back in the lecture video, you'll see that this exact same condition resulted from the matter wave consideration. So this points to the fact that in 1913, when Bohr made this assertion, this is quite a bold assertion, really born out of the success of the ideas of quantization in the previous decade or so, based on Planck's work and Einstein's work and so forth. This was Bohr being very intellectually bold, and it paid off because, as you'll see, this model works extremely well. So finally, we can take the kinetic energy equation, and we can eliminate the speed of the electron in that equation in favor of the quantization condition from the matter-wave hypothesis. So that is, here's our kinetic energy for the electron in orbit around a proton. That can be related to the generic kinetic energy, 1/2 mv squared. But we have an expression for v squared from the quantization condition from the matter-wave hypothesis, and that was determined earlier to be this. So if we substitute that into the equation, we find out that the kinetic energy from Coulomb's law is equal to this kinetic energy expression, taking into account the quantization of the wave function of the electron, that only certain wave shapes will be allowed for a given orbital radius r. And some algebra will finally lead you to this expression for the allowed radii of an atom. It's actually quite remarkable. The allowed orbital radius in this 2D model is simply given by the product of an integer, 1, 2, 3, 4, etc., squared, that's n, times a product of a bunch of fundamental constants of nature. Notice there are no variables left. You have the numbers 4 and pi. You have the constant of nature, the permittivity of free space, epsilon naught, whose value is given here, 8.85 times 10 to the minus 12 farads per meter. You have the fundamental constant, Planck's constant, the reduced version, squared. And a reminder that h bar is 1.05 times 10 to the minus 34 joules seconds. You have the mass of the electron, 9.11 times 10 to the minus 31 kilograms, and the fundamental electric charge, 1.602 times 10 to the negative 19 coulombs. The only thing that can vary in here is n, and n is fixed to be an integer, 1, 2, 3, 4, 5, etc. So the radius of the orbit in our hydrogen-like atom is simply given by an integer squared times a number. So what is that number? Well, if we stick in n equals 1 and solve, we arrive at what is known as the Bohr radius. It's the smallest orbit allowed in the hydrogen atom because of the imposition of the matter-wave hypothesis, or Bohr's angular momentum quantization condition, which turn out to be equivalent. The Bohr radius is just this thing here. And if you calculate it out, it's about half an angstrom, 5.3 times 10 to the minus 11 meters. Which is to say that the smallest a hydrogen atom can ever be with its one electron and its one proton is about 1 angstrom across. And as we saw from earlier discussions in the lectures in this course, an angstrom is roughly the size scale of an atom. And that's no accident. It's imposed by the matter wave nature of the electron. So we find in this model of the hydrogen atom, based on a classical definition of kinetic energy and momentum, but with matter wave quantization imposed, we suddenly find that only a fundamental orbit and its harmonics, multiples of that orbit, are allowed. And this begins to look a lot more like the atom that gives rise to a quantized atomic spectrum. But the question is, can we see that spectrum arise from this model? Well, to answer this question, let's again consider the total classical energy of an electron orbiting a proton at radius r, but again impose the condition that n times lambda, the matter wavelength of the electron, equals 2 pi r. That led to our writing of the Bohr radius and then all the allowed radii of our hydrogen atom, n squared times the Bohr radius. So we have the total classical energy of this electron. I'm just repeating the expression we wrote earlier. And then I'm plugging in with the expression for r, n squared a naught, and putting in the full definition of a naught here, the Bohr radius. So you wind up, if you play around with it a little bit, getting an equation that looks like this. You get negative a bunch of numbers and constants times 1 over n squared. That factor in front of 1 over n squared is negative 2.19 times 10 to the negative 18 joules, if you go ahead and punch in all the numbers here and calculate it. In electron volts, this is a much more familiar number. This is the famous negative 13.6 electron volts. That is the energy of the electron in the hydrogen atom in its lowest orbit. And of course, this also turns out to be the energy required to fully ionize an electron out of its parent hydrogen atom. If you want to free that electron completely, get it away from its proton, from hydrogen, and put it out at infinity, you have to put in 13.6 electron volts to liberate it. So the energy of an allowed orbit of integer n, corresponding to radius r equals n squared times the Bohr radius, is given by this simple equation, that the energy of that orbit, that specific orbit, is negative 13.6 eV times 1 over n squared, where n is 1, 2, 3, 4, etc., any integer. This is a remarkable fact. Just by imposing the matter-wave hypothesis on this and requiring that the wave functions be well behaved when thinking about the wave function spread over the circumference of a circular orbit, we've immediately arrived at a quantization condition for our model of the hydrogen atom. But how good is this model?
In order to understand how the Bohr model of the atom will give us the kinds of quantized energy spectra that would result in specific wavelengths of light being emitted by an excited atom, let's step back and take a look at the Bohr model for a moment schematically. The picture on the left illustrates the classical drawing of what the Bohr model of the atom would look like. It's very similar to the picture that I sketched earlier with a single electron orbiting a single proton. Here, the smallest gray circle corresponds to the n equals 1 orbit, the smallest orbit that an electron can have around the proton at the center of the hydrogen atom. And that corresponds to the Bohr radius. The n equals 2 orbit is a multiple of 2 squared, or 4, times the Bohr radius. And similarly, the n equals 3 orbit is going to be a multiple of 3 squared, or 9, times the Bohr radius. Electrons can only orbit at these allowed radii, going in a circle around the central single proton. That means that if an electron is struck by, for instance, electromagnetic radiation, a photon, it could be caused to jump into a larger orbit if the electron possesses of sufficient energy to give the energy to the electron needed to transition from one orbit to the next. So for instance, we might imagine that the electron started in the n equals 1 orbit of the hydrogen atom, was struck by a photon of sufficient energy, and was able to transition to the n equals 2 orbit of the atom. Maybe this resulted in a complete loss, a total absorption of the photon that struck it, or maybe the photon was scattered, losing energy and changing its wavelength, gaining a wavelength in the process, becoming longer in wavelength. Now, the image here shows the opposite of that process. An electron starts in, for instance, the n equals 3 orbit, and then spontaneously falls down to the n equals 2 orbit. But because conservation of energy has to hold, the energy difference between the n equals 3 orbit and the n equals 2 orbit must go someplace, and in this case it would result in the emission of a photon. So because the atom conserves energy, in order to go to a wider orbit, it must absorb the energy from someplace. A photon with the right frequency and wavelength can do that. To drop down to a lower orbit, that is one characterized by a smaller integer n, it must release energy, and emitting a photon of a specific wavelength and frequency will do that too. So let's consider a transition that releases a photon, emits a photon in the process, from an orbit that's marked by an integer n greater than m, the orbit into which it falls. So n is some integer, m is some integer, and n is greater than m. The change in energy, delta E, is going to be given by the final energy, the energy of the state marked by the number m, minus the energy of the initial state, the orbit marked by the integer n. Well, if we plug in the formulae for the energy of any specific orbit in a hydrogen atom, that's going to give us an overall multiplicative factor of negative 13.6 electron volts. And that's going to be multiplied by the difference between two fractions, 1 over m squared minus 1 over n squared. So, for example, for the transition from the n equals 2 orbit to the n equals 1 orbit, or n equals 2, m equals 1, we find that delta E is E1 minus E2, and that's going to be given by 10.2 electron volts. Go ahead and work that out yourself for practice, but you should find that that energy is 10.2 electron volts. But this energy must go somewhere, and so this lost energy from the electron would go into the creation of a photon that then is emitted during the process. And that photon will have an energy given by h bar omega, the product of the reduced Planck's constant and its angular frequency. So let's think about the photon wavelengths from electron transitions in hydrogen. Using this energy conservation idea, and combined with the relationship between the frequency, wavelength, and energy of a photon, we can then calculate the expected wavelengths of photons
emitted from an ionized Bohr atom. So an atom where, for instance, an electron starts out at infinity and comes down into one of the low orbits, or maybe starts just above and drops down to a slightly lower orbit. Now recall that the Balmer series, the visible wavelengths of light emitted in the atomic emission spectrum of hydrogen, involved an empirical relationship between wavelengths of emitted light from hydrogen given by the following formula, where the integer n ranges between 3, 4, 5, 6, and up. And this integer here is fixed at 2. Well, this looks a lot like the kind of relationship you might derive from the Bohr model of the atom in the transition between, say, n equals 3 and n equals 2 state. So just to see if we're at all matching reality, let's tabulate the energy of photons and the corresponding wavelengths of the photons that would result from transitions from the 3 to 2 state, the 4 to 2 state, the 5 to 2 state, and so forth. And if you do that, you find the following remarkable things. That the wavelength of the photon emitted when the electron goes from the n equals 3 orbit to the n equals 2 orbit is 656 nanometers. And if that sounds familiar, it should sound exactly like the red line in the Balmer series, which has this wavelength. If the electron instead started in the n equals 4 orbit and dropped to the n equals 2 orbit, that results in a photon of wavelength 484 nanometers, which is blue-green and is weirdly close to the blue-green line in the Balmer series. Similarly, 5 to 2 results in a 432 nanometer wavelength photon, that's blue. And 6 to 2 results in a 409 nanometer photon, that's a violet. And these are, in fact, to good accuracy, the Balmer series lines. Now, they differ a little bit from the numbers before, and I'll comment on that in a moment. But overall, the pattern is very well explained by the quantization of orbits in the atom due to the matter-wave nature of the electron, and thus the resulting quantization of angular momentum, a la Niels Bohr's conjecture in 1913. This is a remarkable fact. The fact that just using a classical model of the atom, combined with matter-wave nature of the electron, one can immediately reproduce a pattern in the world around you. In this case, the Balmer series of atomic emission spectrum lines. This is incredible. Now that said, it is wise to revisit our model and compare that to what we might actually expect from a more realistic model of atoms. After all, atoms are not two-dimensional things. They're three-dimensional things at the very minimum. And we haven't included an extra dimension in our model. We've only made a very good approximation to what we would expect real atoms to need to be more accurately described by. But you have to admit, it's a pretty good model for what we were trying to accomplish. It almost exactly reproduces the Balmer spectrum, which no previous model could do. So the so-called Bohr-Rutherford model of the atom, which is what we constructed here, has a few assumptions built into it. One of them is obvious. It's two-dimensional. We said that outright. A little bit less obvious, although I hinted at it throughout this discussion, is that we've modeled this atom as if the electron is free to move, but the proton, or substituting the proton with a whole nucleus with Z protons instead, so 2, 3, 4, 5, 6, 7, 8 protons, whatever you like. We have the proton pinned and unmoving at the center of the atom. But, think about planets orbiting stars, or planets orbiting other planets, things of comparable size and mass orbiting each other. One isn't fixed while the other one goes around it. Rather, they co-orbit a common center, and that center is the center of mass of the system. So a more accurate model would take into account the fact that the proton can also wobble in response to being tugged on by the electron via the Coulomb force. Now, we've also obtained this model by combining a very classical picture of a planetary atom with very classical notions of momentum, kinetic energy, and so forth, with the matter-wave idea. That's how we stitched quantum physics into this, through the matter-wave idea. A more realistic model of the atom, of course, would be fully three-dimensional from the start,
It would allow for the motion of both the electron and the proton, and in fact, if one puts that into this model, one much more accurately captures the Balmer spectrum wavelengths. They're a little off from what's predicted in this model, but they're almost exactly predicted by using a model where the proton can also wobble a little bit in it as it's orbited by the electron. And of course, in reality, we wouldn't start from a fully classical picture. We would try to exactly solve Schrodinger's wave equation in 3 dimensions, using as our potential acting on the wave function the Coulomb potential, written here, in full 3-dimensional glory. So there's a R vector hidden in here that has x and y and z in it. The truth is we are simply not ready at this stage to commit to more realism in describing the atom. This was already a bit of an exhaustive exercise at the level of, say, coming out of introductory physics. But I promise you that through the rest of this course, we are going to build up a toolkit that would allow you to attack this problem in a later semester, starting from the principles outlined in this course. So let's review. In this lecture, we have learned the following things. We've learned about a way to develop a classical model of the atom from classical energy and force considerations. We've done so in 2 dimensions. We've then imposed quantum physics on this by sticking the matter-wave hypothesis into the atom via the electron, thinking about what wavelengths would be allowed for an orbit of a given radius r, and then imposing that condition on the energy conservation that is derived from the classical model built in the first step. This has allowed us to make predictions about the behavior of a hydrogen-like atom in this model, and we found that it matches remarkably well with observational evidence. This is certainly a far more accurate description of nature than anything that has come before. And this is the Bohr model of the atom, which is a building block to a much larger picture of quantum physics, the physics of the smallest things in the universe. So let's see what we have learned already from this most basic scenario, a particle moving at constant speed free from external forces. There is a wave equation, which means that the solutions will not have definite localization. Okay, these are waves. They describe a phenomenon that's not specifiable to any one location in space, and that means they're spread out. And as a result of that, and because they describe something that is oscillating, we're led to questions like, what is it that's oscillating? What are the implications for measuring things like position or momentum of particles when fundamentally they're waves and they're not localizable to any one definite location in space at any one time? I may not be able to know everything that I thought I could know about particles from matter waves, which are really what matter is. Electromagnetic waves are variations in the strength of electric and magnetic fields, and mechanical waves are variations in, say, the density of a medium or the displacement of a medium. What's oscillating in a matter wave? We'll come back to that. Now, to better understand these solutions, we need to confront the mathematics of these complex functions a bit more closely. And I don't want you to be daunted by the presence of either complex numbers or complex functions. They're basically just a representation of information that becomes necessary when a problem has too much information to be described by only one class of number, say real numbers. It's okay. It just means that matter waves contain more information than real numbers alone can capture, and there's nothing scary about that. All we have to do is become more comfortable with the language of complex numbers and how to get real values out of them, because after all, real numbers are the only things that are realized in the physical world.
It may be true that phenomena can be described by complex numbers and complex functions, but when we make measurements of the natural world, we don't get the answer I back from it. We get numbers like 5 or negative 52 or 73.771 back from measurements. Those are all real valued. And so, regardless of the fact that the wave equation may be complex and its solutions may be complex, somehow we've got to get real numbers and only real numbers out of these things. And to really understand that, we need to take a look at complex numbers and a little bit of the algebra related to complex numbers. But basically, complex numbers just double the available amount of information you can store in a single number. That's all they do. So our working solution to the free particle wave equation is of this form. We've seen it a bunch of times now. And it looks weirdly similar to that representative complex number z I showed you earlier, x plus iy. It's a complex structure with a real part, which we could represent by x, and an imaginary part, which you could represent by y. It looks very similar to a simple complex number. But as I've said, observations of the natural world are conventionally described by real numbers, not imaginary ones. Now, that's okay. I mean, we've already kind of hinted at the fact that complex numbers look a lot like vectors, and we're used to dealing with vectors, with an x component and a y component. And from those, we're comfortable summarizing the information content of a vector using the concept of its length or its magnitude, a single real number. For instance, you might have a three-dimensional velocity with a vx, a vy, and a vz component, and that's all very complicated, but you're very comfortable going, look, the speed of the particle is v, where v is the square root of vx squared plus vy squared plus vz squared, a single valued real number that summarizes the overall thrust of the velocity vector. So that's not scary at all. That's something you've been doing since beginning introductory physics. The question here is, how does one get a single real number out of a complex one? How do we get the measurable out of the complex function or number? Well, you might just try, your old friend, the square, right? Square the complex number and see if that gives you a real value. But unfortunately, it gives you a complex polynomial. You wind up with a real number x squared and a real number negative y squared, but a complex piece 2i xy. That's the sum of the cross terms of this square. If only we could get rid of that cross term, we'd be home free. We would actually recover something that looks weirdly like the Pythagorean theorem with an x squared and a y squared term. This is almost a hypotenuse squared, but it's not real valued. So this may be the hypotenuse in some space, but it's not the hypotenuse in the real number space of measurement. Okay, so that won't work. Now instead, to get a real number, you need to do something like this, and this is part of what defines the algebra of complex numbers. You're going to take z, and you're going to multiply it by a special version of itself, known as z star. This is just x plus iy, the original complex number, times x minus iy. And you'll notice that when you do that distributed multiplication out and add all the terms together, you wind up with x squared plus y squared and no cross terms. Well, this looks weirdly like the Pythagorean theorem. You've got an x component squared, you've got a y component squared, and this is somehow related to a sort of square of the complex number, although this funny thing z star is required. So, while that yields something more consistent with, for instance, your experience with the Pythagorean theorem about the length of a vector, but it does it with a complex number with real and imaginary components, what is this thing z star that we've employed to get away with this? And the answer is that z star is what is known as the complex conjugate of the complex number. All you do to take the complex conjugate of a complex number is take all numbers I inside the number and replace them with negative I. That's it. You're going to send I to minus I. You're going to flip the sign of all the i's, and that is all z star represents. Now, to keep this kind of consistent with our instincts about vectors and lengths and magnitudes and things like that, we have a shorthand notation for z times z star, z times its own complex conjugate, to indicate that it is the square of the real length, the thing we would really measure as a consequence in nature if we described a problem using complex numbers. And that is denoted by the magnitude or absolute value bars of z all squared. So the magnitude of z squared is defined as zz star. So if you see this notation, absolute value or magnitude of z squared, in complex space, that denotes the product of z with its complex conjugate z star. That's how you get the real valued length of a complex number or a complex function. Now, another interesting thing about the free particle solutions is that one can simplify the notation that we've been using to carry around these free particle solutions. And that is the language of sines and cosines and exponential functions. So, for instance, it's really clunky to have to keep writing out these sines and cosines in our free particle wave function solution to the wave equation. It would be nice if we could compactify this notation somehow. And mathematics does offer us a more compact representation of the same information, and will also give us some practice with imaginary numbers like I. Ultimately, we will be able to summarize the free particle solutions as a single exponential function, rather than a sum of sines and cosines. To get there, let's consider a Taylor expansion of the sine function, sine of x. So the sine of x, Taylor expanded into a series of terms, becomes x minus x cubed over 3 factorial, plus x to the 5th over 5 factorial, etc. Similarly, the cosine function can be Taylor expanded into the following: 1 minus x squared over 2 factorial, plus x to the 4th over 4 factorial, etc. Notice that the sine involves only the odd powers of x, and the cosine involves only the even powers of x. So x to the 0 is 1, x squared, x fourth, and so forth. And the sums all have alternating pluses and minuses that are used to combine the terms together. Now, recall that the Taylor expansion of the exponential function e to the x looks like the following. If you Taylor expand e to the x, you wind up with 1 plus x squared over 2 factorial, etc. So if you stare at these three things for a second, you're dangerously close to being able to find some combination of sine and cosine that, when added together, yields e to the x. But it's not going to be real valued, because the sine and cosine expansions have alternating plus and minus signs in front of their terms, whereas the e to the x expansion is all sums. And so we see a problem here. We would like to use e to the x to represent some combination of sine and cosine of x, but we can't do that because we have these stray minus signs on alternating terms that complicate our ability to use only real numbers to do this trick, to make sine and cosine combine to get e to the x. Well, again, leaving that expansion of e to the x up here, let's go back and revisit a little bit the use of the imaginary number I and the implications it might have for combining sine and cosine. So note that while the expansion of e to the x involves the sum of a bunch of power of x, and the sine and cosine expansions have alternating sums and subtractions, we might use this rule that when you see stray minus signs, that they might be indicative of products of the imaginary number I. We can crack the puzzle. So let's think creatively for a moment, and let's recall that I squared equals -1, and that allows us to then rewrite terms like negative x squared, which appears in the expansion of the cosine function, as I squared x squared, or in other words, ix all squared. So it's as if we replaced the argument of the cosine function with I times the argument that we started with. Now, in the sine expansion, we have odd-numbered powers of x, like negative x cubed, for instance, and that could be rewritten as I squared x cubed, but that's not very satisfying. We have different powers of I and x in this. But let's keep in mind that if we have a term that looks instead like negative I x cubed, that can be rewritten, and you can practice this for yourself, as I cubed x cubed, which is just ix all cubed. So with those things in mind, let's recall our free particle solutions are of the form a times the cosine of an argument x plus I times the sine of an argument x. Well, if we stare at that for a second and we plug in the Taylor expansions of cosine and sine, we would get this, that we have a times, for instance, just keeping the first two terms in the Taylor expansion, 1 minus x squared over 2 factorial. And we're going to add to that ia times this expansion of sine, keeping only the first two terms, x minus x cubed over 3 factorial. Now, if we distribute the imaginary number I into the parentheses on the right-hand side of this sum, we can start employing the identities and relationships that I wrote up here. So for instance, negative ix cubed is just ix all cubed, and negative x squared is just ix all squared. So for instance, I wind up with terms like this. I have ix here, which is fine, we can leave that alone. I have negative ix cubed, and that can be replaced with positive ix all cubed. And that's done here. Now for the cosine, I have 1 minus x squared over 2 factorial. Well, negative x squared can be replaced with ix all squared. And you'll notice what's happening. We're eating up the minus signs in algebra involving the number I. So we wind up with a positive sum of these terms. 1 plus ix all squared over 2 factorial plus ix all cubed over 3 factorial, etc. if we were keeping more terms in the Taylor expansion. This thing here can simply be rewritten as a times e to the ix. The argument of the cosine and sine was x, but combining them in this way with a multiplicative I in front of the sine term, we get to rewrite that sum as a e to the I times x, the original argument of the sine and cosine function. So we've traded a real valued function for a complex function, but it's a much more compact notation than what we had before. And this allows us to rewrite the free particle solutions in this more compact form as a times e to the I times the quantity kx minus omega t. And this is a little bit easier to carry around on a piece of paper than the sums of sines and cosines with the imaginary number I in only one of the two terms. Now, what is the magnitude of our free particle solution? And let's keep in mind that we don't know if the constant out in front of the function a is real or complex. So let's try to calculate the magnitude squared of the wave function of the free particle. Let's do that. So we're trying to calculate the absolute value of psi squared. And remember, in a complex space of functions or numbers, that's defined as psi times its complex conjugate, psi star. Well, what is that? Well, psi is just a times e to the I, kx minus omega t. The complex conjugate of psi would involve changing I to negative I everywhere we see it. But we don't know if there's an I hiding inside of the prefactor a that multiplies the exponential function. So to be very careful about this, in case the a is also a complex number, we're going to replace a with a star and I with negative I up here. And that's about as far as we can go with this. If we now group terms together in the multiplication, we have a times a star, we have e, I, kx minus omega t, and grouping the exponents together, we have then negative I times kx omega t. These exponents completely cancel each other out to 0, and we're left with a term that's just e to the 0. E to the 0 is 1. So this then simplifies to a times a star, or just the magnitude of a squared. So the measure of the wave particle function for a free particle is just a real number, the magnitude of a squared. But what is it that we've just evaluated? What is this function that solves the wave equation, and what is the meaning of its length? These are the questions that really racked people's brains in the 1920s and 1930s. This was a real intellectual struggle in confronting the wave nature of matter. So one is forced to interpret these functions and their meaning. There is no easy answer from first principles in nature about what the wave function is because it's a complex function. You don't actually have any physical meaning to its real and imaginary parts. It's only the magnitude of the wave function squared that has any physical meaning. And so you have to lay an interpretation down as to what you think the underlying wave function is and what is waving. It's not energy because energy is a real thing. It's something else. And I have to tell you that in the history of physics, and you may have seen this in popular videos on quantum mechanics, which often are rife with misunderstandings of the underlying math and subject material, it's this contest of intellectual ideas that has caused the most hand-rubbing and consternation and some of the most bitter disagreements and strong opinions in the history of science. And it's all been over a function whose direct value has no physical meaning, because it's based in part on imaginary numbers, which themselves have no physical interpretation. It's only the real valued magnitude of the complex function or the complex numbers that have any physical meaning. It's not those numbers themselves. It's only the measure of their overall information content that has meaning in the physical world. Now, the most practical interpretation, one which has also been met with the most experimental success since Erwin Schrödinger first published his wave equation, is that of a probabilistic meaning to the square of the wave function. That is to say, this thing, the magnitude of psi squared, this amplitude squared of the wave function, is interpreted as representing a probability per unit distance, per unit time in one dimension. In 2 dimensions, it's per unit area, and in 3, it's per unit volume. Now, to obtain raw probabilities, one has to specify the exact conditions under which the free particle has been prepared. For instance, where was it starting from exactly, and what was its momentum, and things like that. And then you can answer questions such as, given that this is a matter wave, and it's not localized once it's released to any one place in space, what's the probability of finding this particle between, say, 1 centimeter and 2 centimeter from the point of origin? Or, what's the probability of finding the particle a distance of 3 centimeters from the point of origin 1 second after it starts its journey? These are questions you can try to answer in the framework of the matter wave equation, the Schrödinger wave equation, and all the math that goes along with it. And we don't have that framework available. We're going to develop that framework going forward and try to get answers to questions like this. All right, so that's our goal. We're going to conclude our discussion of the implications of the wave nature of matter in this lecture, and later lectures we'll begin to think about specific problem statements and then how we use the Schrödinger wave equation to attack those problem statements and interrogate the solutions to get answers that can be measured in a laboratory experiment. The wave function itself is not directly accessible, but its amplitude squared in different situations has physical consequences for measurement. Now that said, because we're mathematical beings that can imagine things that are not physically realizable in the world around us, we can use some math and computer aids to try to visualize the wave function of our matter particle that's free from external forces. But to do this, we have to concoct a space of the imaginary value of the wave function and the real value of the wave function. Now, these are not physical axes in space. They don't have physical extent. Remember that this is an oscillating probability. Probability itself is not physical, but the probabilities of outcomes are physical. And so you have to be very careful to separate your visualization of the wave function from physical meaning, which is only derivable from the square of the wave function, the complex conjugate times the original wave function. Nonetheless, because we are mathematical beings and we can think abstractly, let's attempt to visualize what the wave function of a free particle would look like without specifying how it was prepared. In that case, then, it's the solution that we've written down already. And we can imagine thinking about the amplitude of the wave function along its imaginary axis and along its real axis. So along its imaginary axis, it's a sine function whose amplitude starts out at 0, goes to a maximum, plunges to a minimum, and returns to 0 after one cycle. And along the real valued axis of the wave function, it starts off at maximum amplitude, eventually goes through 0 to a minimum, back through 0 to a maximum after one cycle of the matter wave. And note that the maximum of the matter wave in the real value part of the wave function is achieved at the same location as the 0 point of the imaginary part of the wave function, which is what you would expect from a cosine and a sine function combined together. Now, of course, if we construct this in 3D space with our imaginary axis, our real axis, and then the spatial location and physical space of the particle, we wind up with a helical structure, a helical surface that winds through imaginary and real space. Keeping in mind that we're talking about the imaginary and real components of the wave function. But at all points in space, as we've seen, the amplitude squared of this is a constant valued number that doesn't depend on space and time. And so whatever wave function is doing, varying in its real and imaginary parts, in physical space, it represents a constant probability density everywhere in space in time. So there's nothing waving in physical space. In the space of the wave function, you have oscillation, and that oscillation is related to the probability of finding the particle at that point in space at that moment in time. But in physical space, all you have is the magnitude squared of the wave function. That's the only physical thing that manifests in the measurable world. Now, to close out this lecture, let's take a look at what it means to try to measure both the position and the momentum of a matter-wave representation of a particle. So here's a real valued part of the wave function of a matter wave. It's the cosine. It starts at 1, goes to -1, returns to 1 after one cycle. And you see I've got two wavelengths represented in this picture. I've ignored the complex part, but it's also waving at the same time. We're looking now just at the physical position of the particle versus the value of the real component of the wave function. The imaginary component of this wave also has an important role in what happens with the physical reality of the particle, but it's not shown here. I just want to concentrate your energy now on thinking about what it means to measure momentum and position for a wave, or at least a particle described as a wave. Now, measuring the position of a free particle boils down to determining where it is along the x-axis. So for instance, I might do that by zooming in more and more on this wave and saying, okay, I'm localizing the particle more and more and more by spotting the little chunk of its wave function in the real valued component located at that point in space. But measuring the momentum of the same particle boils down to a different observation. Measuring the momentum of the particle is related to determining the second derivative of this wave with respect to space. That is, determining the curvature of this wave. That's what the second derivative with respect to space tells you. It tells you about the spatial curvature of the real part, or the imaginary part, of the wave function. And it's that curvature, the degree to which the wave bends to move toward the next part of its cycle, that determines momentum. Now, it's very easy to determine the momentum in this picture. We clearly have two wavelengths. We could sit down and easily determine from the information on this page what the wavelength of this wave is. All right? But we might be a little less certain about where it is because there's a couple of cycles of its real valued part of its wave function here. So maybe it's here, or maybe it's here, or maybe it's here. All right, so knowing the momentum really well might preclude knowing the position really well. But what if we really localize this particle to one specific place in position space? All right, so what we want to do is try to locate the particle more and more precisely by zooming in on the wave function to really localize the phenomenon to one narrow region of space. And this is equivalent to identifying where it is in a range x and x plus delta x, and then sending delta x more and more towards 0 to zoom way, 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 way in on a narrow slice of the wave. All right? But as we'll see, it's going to become harder and harder to establish the curvature of the wave as we do this, and thus the momentum of the wave is going to slip from our grasp. Now, to help you with this exercise, what I want you to do is really stare at the wave in this region right here where I'm indicating with the mouse cursor. Okay? So really stare at the wave here. Right now, you can clearly see that there's well-defined curvature. You could easily and readily determine the wavelength of this phenomenon. How about now? Can you easily determine the wavelength of this phenomenon? I've zoomed in, localizing more in space where I want to see where the particle is, but in doing so, I've traded a lot of the curvature away in order to do that. It's getting harder to determine the wavelength of this wave, but you could still maybe do it. You've got a peak over here, and you can see how it's declining. There's lots of curvature to determine the momentum of this wave, but how about now? I've zoomed in even more. Stare at that. Are you confident you could determine the curvature of that wave? And you may be remembering the old wave, but as you continue to stare, can you determine the curvature of the wave? Well, I messed with you a little bit. While you were staring at the wave, while I was daring you to think about the curvature of that line, I did one more change to the wave. I'm still zoomed way in on it, but I changed the wavelength by 10%. Did you notice? Did you notice that the wavelength changed from the previous zoom in to the zoom in you're looking at now? An astute observer might have noticed while they were staring at it that the grid behind here changed when I did that. And that corresponds to a change in where I was zoomed in on the wave. But the starting value and the ending value of the wave in this picture didn't change. The heights of the waves where they enter the picture and exit the picture were concocted identically, giving you the impression that you were confident that the wavelength was the same as the wave from before. But it's not. I changed the wavelength by 10%, but presented you with a similar zoomed-in region. And this is meant to confuse you on purpose, to show you that the more you close in on the wave function, the harder and harder and harder it's going to be to determine the curvature of the wave. Is this line straight? Is it bending gently? How much is it bending? You don't have infinite resolution available to you in the universe. You're going to hit a limit at some point, and it's going to get extremely hard to determine if this is a straight line or not a straight line. And if it's not a straight line, you're going to struggle with determining exactly what its radius of curvature is. And that struggle is reflected in a loss of control over your knowledge of the momentum of the particle. Knowing the position too well comes at the cost of knowing the momentum. So let me repeat that statement one more time. When you're dealing with matter waves, knowing the position very well comes at the cost of knowing the momentum with any precision. Knowing the momentum very well comes at the cost of knowing the position with any precision. That I reflected in my earlier statement about being zoomed out looking at many cycles of the wave. You're very confident when you're zoomed out that you know the wavelength of this phenomenon. But because there are many places where the particle is likely to be and less likely to be represented by the changing amplitude of the wave in real space, you're getting kind of confused about where it might actually be. Is it more at one of the maxima, or more at the other maximum, or more at the third maximum, or the fourth maximum, or the fifth maximum? Gaining confidence in momentum comes at the cost of confidence in precision. And it was the physicist Werner Heisenberg who worked out the mathematics of this particular issue in 1927. Now, the real way to do this, of course, is to take the wave equation and to work through the Fourier transform, which tells you something about the information content of the wave in position and frequency or momentum space. That's a little above the ability of a course like this to work out, although you are welcome to look into it on your own if you're comfortable with integrals and derivatives at a high level, at least at the level of, say, Calc 2 and Calc 3. Heisenberg codified the relationship between the certainty or uncertainty of our knowledge in momentum and the uncertainty of our knowledge in position in what is known as the Heisenberg uncertainty principle. And it's a very definitive statement, albeit an inequality. It says that the uncertainty in the knowledge of momentum, delta p, times the uncertainty in the knowledge of position, delta x, must always be greater than or equal to h bar, the reduced Planck's constant, divided by 2. Why is it that we don't worry about knowing how fast our car is moving while also knowing its position on the road? We don't freak out about that. Like, if we're going to stare at the speedometer for a moment, we're suddenly going to look up and realize we're in New York City, whereas we were in Dallas at the beginning of our glance down at the speedometer. That doesn't happen in the real world. You don't increase your confidence in your current velocity, and thus your current momentum, and then suddenly look up and realize you're on the moon. I mean, this is essentially what we're talking about here with tiny matter waves, right? Is that once you become very confident you know where the particle is, you suddenly lose all confidence about its momentum, and vice versa. Well, it's no wonder we didn't notice it. H bar over 2 is a number that is approximately 10 to the minus 35 joule seconds. That's an insanely small number. It's no wonder we didn't notice this before, and that it would only manifest at the scale of things tiny, like atoms, or electrons, or the nucleus of the atom, or things like that. But this statement holds for matter waves, no matter what situation you're in. You cannot know the position and the momentum at the same time with infinite precision. And you can see that if you did try to know one of them with infinite precision, that is delta x exactly equal to 0. So you want to know exactly the position of a matter wave. So you specify an experiment that lets you get infinite precision, no uncertainty on the position. You completely lose control of the momentum. The uncertainty on the momentum blows up to infinity in order to hold this as a constant. That's the only way to satisfy this inequality, is if delta p blows up to infinity as delta x goes to 0. This is a limit imposed by the wave nature of matter. It's unavoidable. You cannot know this pair of variables, x and p, with any simultaneously perfect precision. Now, of course, the why of this is buried deeply in things like the Fourier transform and in the algebra of matrices, that is, collections of numbers in multiple dimensions, which is another form of language that can be used to derive quantum mechanics, which is where we are essentially at now. That's above the pay grade of this particular class, but I just want to say that because you are going to encounter quantum mechanics again in a dedicated higher level course than this one. And I want you to understand that I'm having to wave my hands quite a bit at this level in order to motivate this. Nonetheless, you will have a second crack at this where you'll begin to see the whys of all of this. Where is this coming from? Why h bar over 2? Why this particular product of momentum and position? Are there other products of things that similarly in pairs are uncertain? When you know one, you don't know the other, and vice versa. These are excellent questions, and I don't expect you to be satisfied with this right now, but this is where we can get in a course at this level after 2 semesters of introductory physics. So let's review what we have learned in this lecture. We've learned about mechanical and electromagnetic wave equations, and from that we've learned how to infer the nature of the wave equation for matter. And this has given us some ability to get at the meaning of the waves described by the matter-wave equation, albeit by interpreting what's going on based on our experience with the natural world. The wave equation involves complex numbers, and the solutions to the wave equations involve complex functions. We have to get real numbers out of this thing if we want to map it onto the real world. And the only way to do this is, for instance, to calculate the amplitude squared of the wave function. In doing that, however, we lose any ability to understand or map the physicality of the wave function itself onto the real world. It's only the amplitude of the wave function that has implications for the real world. So the wave function describes oscillating probabilities, and it's the amplitude squared that tells us the probability per unit distance per unit time for something to be true in the Schrödinger wave equation, describing a matter wave involving either no forces or some forces. But the wave nature of matter ultimately imposes a limit of absolute knowledge on our ability to understand the world around us. What we learn from exploring the wave part of the wave function of the matter waves is that there's a limit to our knowledge. If we know the position of this wave very well, we lose control over its momentum. If we get control over its momentum at a high degree, we lose our confidence in information about the position of the particle any longer. These pair of variables are related to each other in their uncertainty by the Heisenberg uncertainty principle, and fundamentally this imposes a limit of absolute knowledge on what we can know about a system of particles at any given moment in time by making measurements. These are the foundations of quantum mechanics that we will build on going forward, and we will spend the rest of this course essentially applying quantum mechanics and special relativity to problems involving the very small things in the universe, like atoms and individual subatomic particles, to make predictions about the natural world and understand phenomena like atoms and the behavior of particles trapped in systems like you would find, for instance, in semiconductors. These are all basic applications that are at our fingertips now that we have a foundational equation that we can solve in order to understand the outcomes of these particular situations. In this lecture, we will learn the following things. We will learn about the postulates of quantum mechanics, the inviolable tenets that are the foundations of this branch of physics. We'll also learn about some guidelines that you can employ for wave functions so that you can learn to solve the Schrödinger wave equation. We'll learn about classical analogs of quantum systems that we might want to model, building on what we know already about a classical system, but employing that in the Schrödinger wave equation. And finally, we'll learn about a specific archetypal model, a quantum model of a bound particle, known as the particle in a box, or infinite square well model, and we will solve it using the Schrödinger wave equation. Let me remind you first about the one-dimensional Schrödinger wave equation, which I will represent using a shorthand going forward, SWE. Much easier to carry that around than Schrödinger wave equation. The Schrödinger wave equation has a time-dependent statement on the left, and on the right it has a spatially dependent statement about the wave function, and finally it has a portion here that describes the action of an external force on the particle or system represented by the wave function. The above is the one-dimensional Schrödinger wave equation, and generally speaking it allows for solutions that vary in space and time, and it also allows for forces represented by the underlying potential that gives rise to the force that varies in space and time. This is very complex, so to utilize this equation we will need to do the following. First, we will represent physical situations with a model, and what that usually boils down to, because the time piece on the left and the space piece in the middle are essentially fixed by the form of the equation, is varying the form of the potential, V. This describes how the system constrains particles described by the wave function. Now, this effort may involve simplifying assumptions in the aid of creating a simple model of the force or forces that can act on the particle. And these choices, these simplifying assumptions, have consequences that I'll talk about later. We will define the basic rules of quantum mechanics. What are the inviolable tenets of problem solving in quantum mechanics that, if untrue, mean the fundamental dissolution of quantum mechanics? We'll also define some guidelines for how to write down wave functions that will work to solve the Schrödinger wave equation, for instance in a specific situation. Now, these guidelines may be violable depending on how you approximate physical situations, but don't represent a fundamental failure of quantum mechanics if violated. In other words, poor assumptions on the part of the problem solver, the physicist, are not to be held against the fundamental framework of quantum mechanics. So, what are the inviolable tenets of quantum mechanics? Well, these are known as the postulates of quantum mechanics. And I'm going to warn you at the beginning that I am glossing over some of the elegance of these postulates in favor of a bit more wordiness, because we don't have the mathematical foundations quite yet in order to take advantage of the more elegant and direct way of stating these postulates. So, what are the postulates of quantum mechanics? Well, the first one is that at each specific time, the state of a system, that is, for instance, a particle or collection of particles, can be entirely represented by a space of functions that are related to the wave function psi. Now, while psi depends on a finite number of things, like spatial position along the horizontal space axis and time, the space of functions that can be related to the wave function and can fully represent the possible state of a system can be infinite in dimension. Now, for our purposes, we will concentrate just on the wave function rather than on this larger notion of a space of functions that can describe a system. A more advanced course will concentrate rather on that space of functions, which has all kinds of properties and rules associated with it. It's called a Hilbert space, and it's named after mathematical physicist David Hilbert. The second postulate is that every observable quantity of a system, for instance, a measurement of momentum or energy, will be represented mathematically by the action of an operator on the state of the system. Now, I'll elaborate more on this a little bit later, but think back to how I waved my hands and derived the Schrödinger wave equation. For example, the total energy is measured in that equation by a time derivative acting on the wave function. And as you'll see, other actions of other derivatives effectively represent operators that measure quantities of the system. These would be the outcomes of doing experiments. And finally, the only possible results of a measurement of an observable are related to characteristic numbers, known as eigenvalues, of those